Hello and welcome back to the course on artificial intelligence. Today we're going to discuss the plan of attack for this section. We're talking about Q-learning and we've got quite a few tutorials, so I think it's a good idea for us to quickly go through them to understand what to expect in the upcoming videos. So here we go. All right, what we will learn in this section. First things first, we will talk about what reinforcement learning actually is and what the philosophy behind reinforcement learning is and how reinforcement learning actually can be seen in real life and how it relates to things that we observe in real life or actually things that we do ourselves. Then we'll talk about the Bellman equation, a very fundamental concept underpinning everything or a lot of things that are happening in reinforcement learning, especially in the space of Q-learning and what we're going to be discussing in this section of the course and in the following sections. Then we'll talk about the plan and the plan that an artificial intelligence comes up with in order to navigate inside an environment, and we'll see what how that comes together. A very quick but quite interesting tutorial. Then we'll talk about market decision processes, a new concept. We're going to introduce a very new concept which will slowly even add an extra layer of sophistication to our Bellman equation, to our whole reinforcement learning, to our Q-learning concepts. And that's the way this section is structured, that we introduce the Bellman equation in a very simplistic form, and then slowly throughout the tutorials we add layers of sophistication to it in order to get to the final version that is our designated destination in terms of Q-learning. But we'll get there slowly in order for us to have enough time to process all of the information and let it settle in. And market decision processes is an extra layer of sophistication on top of what we've already discussed or what we will have already discussed by then. Then we'll talk about policies versus plans. Another interesting tutorial. They're all interesting. Just another quick tutorial on how policies differ from plans and what the differences there are. And these are terms that you will probably hear or read in other literature if you're going to be delving into it to get additional information on reinforcement learning. Then we'll talk about adding a living penalty to our environments. And that's kind of another way of adding complexity into the environments that our agents are going to be operating in. Then we'll talk about the intuition behind Q-learning. So up until that tutorial, we're going to be talking values of states, and then finally we're going to switch to talking about values of actions or Q values. And then we're going to introduce the temporal difference. So this is the tutorial where everything that we've learned is going to come together to explain how exactly do agents or how does artificial intelligence learn? How does it update its values throughout the iterative process that it's going through? And then finally, we're going to look at a visualization of Q-learning. So we're going to take everything we learned and we're going to look at it happen in front of our eyes and watch an artificial intelligence actually perform Q-learning and do all of the things that we're going to discuss on an intuitive level is going to actually do in practice. And that will help us even further grasp that knowledge that we're going to be covering off in this section. So hopefully you're very excited about these upcoming tutorials. I definitely am. And there's some very interesting slides coming up. And more importantly, the concepts themselves are very, very interesting. And I'm sure you're going to enjoy them quite a lot. And I look forward to seeing you next time. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. I hope you're excited about today's tutorial because we are taking our very first step into the world of AI, and today we're talking about reinforcement learning. It's a very important tutorial because it will underpin everything else that's going to be happening in this course. So let's get started. Here we've got a little maze, and this maze is our representation of an environment, and that's what we're going to be dealing with. In this course, we're going to be dealing with certain environments in which our artificial intelligence is going to be performing, is going to be taking actions, is going to be looking to beat these environments, going to be looking to win in these environments. And here we've got an agent. The agent is our artificial intelligence. That's the person or that's the mind that's going to be navigating these environments and learning from the feedback that the environments are going to be giving it in order to perform certain actions. And so the way it works is the agent performs certain actions in this environment, and as a result, the state in which it is in will change. So it might be further or closer or more to the left, more to the right. It might have a certain other parameters that describe its state. And those parameters are going to change. So the state is going to change because of the action it takes. And it will also get rewards based on the action. So every time it takes an action, the state will change and it'll get a reward. Now, bear in mind, sometimes it might happen that it won't change the state. The action won't change the state, or there won't be a reward for taking that action in that certain state it was in. But nevertheless, the agent is going to keep doing that. It's going to be taking actions, changing the state, getting rewards, taking actions, changing the state, and getting rewards. And by doing that process, it's going to be learning about the environment. It's going to be exploring the environment, understanding what actions lead to good rewards and favorable states, and what actions lead to bad rewards and unfavorable states. And this is a very simplistic representation of a very global problem. So if you think about it, environments actually don't have to be just mazes. It's not just about getting out of a maze or finding a treasure in a maze. An environment can be pretty much anything in life. So imagine you waking up in the morning and cooking an omelet. So in order to make that omelet, you need to go through certain steps. You need to get the salt, get the eggs, get the frying pan, switch the fire on, and so on. And it does sound like a routine, mundane thing, but it's become routine because you've done it so many times. But in reality, it's an environment where you're performing certain actions. You're putting the fire on, you're putting the frying pan on the fire, you're putting all the eggs into the frying pan, and you're putting some salt on the eggs, and you're turning them over, and so on. So as you can see, there are certain actions which you're taking in certain states, and those actions lead to certain other states and sometimes rewards. So for instance, when you put the fire on and you wait, you're taking the action of wait too long, and then you put the eggs into the frying pan, the reward is going to be very negative. It's all going to burn. On the other hand, if you do all the correct actions in the correct times, so it's also very important to understand that actions should be taken at the correct points in time. So for instance, putting the salt in the frying pan before you put the eggs in might not be the best idea. You might want to take that action of putting the salt into the frying pan after the eggs are in there, so in a different state. So it's important to remember that. And at the same time, so if you take all the correct actions in the correct order, in the correct states, your final reward could be that you get an omelet which you can eat. And so that's a very basic activity in your life, but if you think about it, it is actually an environment, and you are the agent going through this environment and performing tasks. You don't really need to learn anything because you already know it pretty well, but at the same time you could learn. Maybe you could learn how to make a better omelet, or especially if it's your first omelet that you're making, you're probably going to screw it up, but you will learn from that because you will understand what actions lead towards states and rewards. And anything else in life, for instance, even trading on the stock market and buying and selling and getting certain feedback from the market in the sense of return, positive or negative returns, that's also an environment, and that's you participating in that environment as an agent. Driving a car is also an environment where you can turn the steering wheel, you can accelerate, you can brake, and so on, and you're getting feedback from the environment. And one of those feedbacks is a policeman giving you a speeding fine if you're going above the acceptable or allowed speed limit on that highway. And therefore, from there, you learn that, okay, that's not something that should be done because it leads to a negative reward. So rewards don't have to be just at the very end of the process. They can be throughout the journey, throughout the process. So those are a couple of examples. And in terms of AI, the simplest way to think of reinforcement learning is like training a dog. When you train a dog, you give it certain commands, and if it obeys those commands, then you give it a treat. You give it like a biscuit or something. If it doesn't obey those commands, you tell it that it's a bad dog, or you just don't give it a treat. And through that process, it learns what certain commands or what it needs to do, what action it needs to take in certain states. And the states are the commands that you're giving it. And based on that, it will get certain rewards. Of course, in the world of AI, it's not that complex. You don't have to give the AI treats. You don't have to have like a bag of biscuits with you every time. You just give it a +1 or a -1. So it's a huge advantage that in the world of AI, we've created these AIs ourselves. So the rewards that we're giving them, if you think about it, this is really cool. If the rewards you're giving them, they don't actually exist. They're just a plus or a -1 or a one or a zero, something like that. So it's all non-existent, it's all imaginary stuff, but at the same time, it leads to great results. We can create these amazing things, these amazing artificial intelligences by just providing rewards which don't really exist, the plus and minus one. It doesn't cost us anything, but at the same time, it leads to results. So very similar to real world and that example of dogs, but here the rewards are digital and just numbers. And with that in mind, we can talk about a little bit about robo-dogs. I love this example. So this is just a random picture. It's not necessarily that exact robo-dog, that is trained through reinforcement learning. Some robo-dogs, especially the older ones, you'd have an algorithm in there. And this is actually a good example of the difference between pre-programmed agents and reinforcement learning agents. So you could have a robo-dog which is pre-programmed to how to walk. It will say, so in the algorithm behind the dog, in the software, it'll say, okay, so in order to walk, you need to move your left leg forward, left front leg forward, then your back right leg forward, then your front right leg forward, then your back left leg forward, and repeat that action. And that's a definition of walking. It's a function inside this dog. And then it might have, how to sit, how to stand, and things like that. Whereas in a robot dog that is trained through reinforcement learning, what happens is you don't pre-program it. This is the key concept to everything here, that you don't have any algorithm inside that is hard-coded into the dog. Instead, you have what we'll be discussing in the future. You have this reinforcement learning algorithm, which is told that, okay, so the goal is to get from where you are now, not knowing anything, to the end of the room, for example. And here are the certain actions you can take. You can move your right foot, you can move your left foot, you can move your right back foot, left back foot. So here are all the degrees of freedom that you can do. You can move them like this, you can move them like that. So like a list of actions you can take. And your rewards are every time you take a step forward, you get a +1. Every time you fall over, you get a -1. And that's all there is to it. And then they just leave the dog and let it figure it out on its own. So the dog tries to stand up, it falls, and it realizes that, okay, I shouldn't do that action that led to me falling, because every time I fall, I get a -1, which is not good for me. Then, so it does the other action that helped it stand up. And then it figures out, it just experiments, tries things randomly, and then figures out that it can make a step forward by moving its right front foot. And it gets a +1, and it realizes, I should do more of that. Okay, cool. So it now learns that it should do more of this and less of that. And through this learning process, it very quickly understands how it can walk. And those dogs that figure it out on their own can actually sometimes walk better than dogs that are pre-programmed. Because when we pre-program things, we look at the real live dogs or we use our own imagination how to do it. Whereas a reinforcement learning dog can optimize things on its own, and because it's an AI, sometimes it can get even better results. And that's how they can train these same robot dogs to play soccer. You can't train a normal dog to play soccer because simply the whole approach is different, and it's not something that probably a normal dog has been trained to do or has ever done in its process of its evolution. Whereas reinforcement learning robot dogs can very easily understand how to play soccer as long as you tell them what the rewards are, what the goals are, what the possible actions they can take are. So that is how reinforcement learning works in general. That's a quick overview of reinforcement learning. I hope that got you very excited about what's going to come next, because it's a completely different world compared to pre-programmed solutions or hard-coded solutions where you have the if-else conditions. This is very different, and we're going to be talking more about that. In the meantime, we've got some additional reading for you. So if you'd like to have some supporting materials, here's a great article which you can look into. It's called Simple Reinforcement Learning with TensorFlow. It's got 10 parts. The link is here, and you'll find the clickable link in the course resources. It's by Arthur Giuliani. It's a 2016 article. And you can follow along this course and also get additional information from that article. But bear in mind that article is with TensorFlow, whereas in this course we are using PyTorch. So different implementations, but at the same time, you might pick up a few things here and there that might supplement your learning that we're going to be doing in this course. So great article to follow, even if you're not considering following it for sure. Just in case, check out that first part and see if you like it. See if you would like to read it a bit more. And then we've got specific to this tutorial about reinforcement learning. There's a paper by Richard Sutton, which is called Reinforcement Learning 1 Introduction. It's a 1998 paper, so quite old, but it's at the same time, you can learn a bit about reinforcement learning, some of the examples like that omelet example and other examples of where reinforcement learning can be applied, and just a general overview of reinforcement learning if you are looking for some additional reading. And on that note, we're going to wrap up this tutorial. Can't wait to see you next time, and until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're going to talk about the Bellman equation. It's quite a complex topic, and we're going to introduce it in a step-by-step manner throughout this whole section of the course. So we're not going to just jump straight into the most complex version of the Bellman equation right away, but instead we're going to introduce it slowly in order to gradually understand how it works. And I hope you're cool with that approach. If you are, let's get straight into it. So we're going to have a couple of key concepts that we're going to be operating with. And these concepts are: S stands for state, so the state in which our agent is, or any other possible state in which it can be. A represents an action that an agent can take. So an agent can have access to a certain list of actions, and actions are very important when they're looked at in a state combination. So when you're in a certain state and then you look at actions, then it starts to make sense what's going to be the result of those actions. Because if you look at an action by itself without a state, it doesn't really make sense because you don't know where you are and where you can possibly end up in. Then we'll have R, which stands for reward, and that's the reward the agent gets for entering into a certain state. And gamma is the discount factor, and we'll talk about the discount factor in a second. It'll all make sense just now, but let's just take a note, make a mental note that we are going to have this letter gamma that we'll be operating with later on. So the person behind the Bellman equation is Richard Ernest Bellman. He was a applied mathematician and came up with the concept of dynamic programming, which we now call reinforcement learning, or which we call the Bellman equation now that's what we call it now. And in 1953, he came up with that concept, and that's when the Bellman equation came to be. So let's have a look at how this all works. There's our lovely agent in the bottom left corner, and he is in a maze. And this is quite a classical maze where you've got some blocks. The white blocks are blocks in which the agent can step into. The gray block is the one that is just not accessible, so that's like a wall in this maze. The green is where the agent should be aiming to end up in. That's where we want the agent to go. That's the finish. And the red is a fire pit. So if the agent falls into the fire pit, he will lose the game. So in the fire pit, the reward, which is R, is -1. So that's our way of telling the agent that's not something we want you to do. Like, remember an example of when we're training dogs, we want to tell them like bad dog if it's not doing the right thing that we want it to do. Same thing here. We want to tell the agent that this is not something you should be doing. It shouldn't be ending up in the square. So every time it does end up in the square, it'll get a -1 reward. So it will be punished with a -1 reward. On the other hand, if it ends up in the green square, it'll get a +1 reward, meaning that that is what we want it to do. So those are the two rewards that the agent can possibly get. And how does it learn how to operate in this maze? Just like in that example of the robot dogs that learn to walk, we're just going to let it know. We'll just tell it that here are the actions you can do. You can go up, right, left, or down. Those are the 4 possible actions that you can take. And that's it. Have a play around with that. See what you can come up with. So the agent might go to the right. Then they might go more to the right. They might go back to the left. They're just randomly pressing these buttons and they're trying to see what happens. Then they go back here, they go up, go down, go up, go right. So for now, they haven't learned anything. So far, nothing's happened. They go right, and then bam, they end up in the green square. So they realize, wow, I just got a +1 reward. So as soon as they stepped into the green square, they got a +1 reward. And that triggers the algorithm to say, okay, that's really cool. I am rewarded for ending up in this square. So I want to end up in this square. So what does that mean for the agent? That means it starts to ask the question, how did I get to this square? What was the preceding state I was in, and what action did I take to get into the square? And then it looks back and says, okay, so the preceding state was this one. It turns out to be valuable in that state, the one that's marked with the red arrow, because from that state, I'm just one step away from getting the maximum reward I can possibly dream of +1, like a biscuit for a dog. From as soon as I know if I ever am in that state, that square marked with the red arrow, all I'll have to do is press right. So how do I tell myself, how do I remember that that state is valuable? Well, to me, there's no difference actually. As the agent, there's no difference in whether I am in the green square or in the white square, right? In the green square, I get the reward of 1. So I'm going to mark for myself that the white square for me, it has the value of 1 because it leads exactly to reward 1. So as soon as I'm in the white square, I know I'll just take one more action, I'll be in the green square, and I'll get a reward of 1. So that's why I'm going to say that the value of this square is equal to 1, because it leads directly without any sort of subtractions. As soon as I'm in here, I know my reward will be 1. So I'm going to mark this square as v equal to 1. That's the value, that's the perceived value of being in this state. Next, the agent's going to be like, okay, so how did I get into this square? And, he might walk around again and so on, end up in this square again and be like, okay, how did I get into this square before that? And the way I got into this square was from this square. Interesting. Okay, so as soon as I get into this square, I know that all I have to do is go right, and then from here I already know that I'm going to win. I know exactly how everything's going to unravel from here, and I know the value of being in this state is equal to 1, and since there's nothing is stopping me from going from here to here, the value in this is going to, the perceived value, I'm going to value being in here as v equal to 1 as well, because as soon as I'm in here, I know I'll be here, and I'll be here pretty quickly, so I'm going to win. And then how do I get into this square before that? Well, I got into this square from this square. So the value, a similar approach, the value of being here is also equal to 1. And so on. So the value of being here is equal to 1, and the value of being here is equal to 1, because each one of them leads to the next one and leads to the finish line. So that's all like pretty logical at this stage. This is us pretty much designing the Bellman equation right now. So we could possibly think about designing an equation that helps an agent go through the maze. So look at the reward, then the preceding state, give it a value of equal to reward, the preceding state, and so on. So it kind of like creates this pathway. It's all great and well, but the problem here is, okay, what happens if our agent, for some reason, starts in this state? Instead of starting here and taking these actions, but it actually starts in this state. How does it know? How does it remember which action to take? Should it go right or should it go down? Or should it maybe go left or should it go up? How does it remember which is the next continuation from here? If the only values it has is these values of equal to 1. So it cannot see what's further away. It can only see, all right, what I have here and what I have here. How does it know which way to go? Well, at this stage, it doesn't. It's pretty identical for the agent which way to go. And so that's why this approach doesn't really work. It's a very simplistic explanation. Of course, there's much more to it, but in an intuitive way, that's why we kind of just carry on this value backwards like that, because one of the reasons is once the agent is in between these two values, where is it going to go? It can get confused like that. And so how do we solve this problem? What are we going to do here? And this is where we're going to start introducing the Bellman equation in its actual form slowly, step by step. So the Bellman equation looks something like this. So we've already talked about V, the value of being in a certain state. S is your current state or any given state. And there is S as well. And S prime is the state, the following state, the state that you will end up in after this state, and by taking a certain action. But we know that there's many actions that an agent can take, and that's why we've got this max over here. So by taking an action, what will happen to an agent? So let's say we're in state S. By taking an action in state S, and we take action A, what will happen is we'll instantly get a reward by getting into a new state. And remember that reward can be 1 or +1 or -1 if it's at the end of the game, or it can be a 0 if it's throughout the game. In this case, our reward throughout the game is 0. So that's the reward. Plus, we will get into a new state which has value of S prime. So that's the value of the new state. And gamma. We'll talk about gamma in a second. But the point I'm trying to raise here, or the point I'm raising here is that we've got many different actions that we can take, and that's why we've got the maximum. So by taking action, we get a reward, plus we end up in a new state. And so for every in our case, we have 4 possible actions. For every one of the possible 4 actions, we're going to have a equation like this. So this is going to have a value they will have a different value for every one of the 4 actions. And we're going to look at only the maximum because, of course, the agent wants to take the optimal state. So if he's in state S, he's going to look at these values. He's going to find the maximum based on the action and going to take that action that leads to the maximum of these values. So hopefully that makes sense why we're taking the maximum here. Then once we've got the reward and the value of the state, why do we have this gamma parameter here? Well, it's there exactly to solve that problem of where the agent doesn't know which way to go because it cannot, it's comparing the values of 2 states on both sides and they're the same. That's why the gamma is called the discounting factor. So we're going to have a look at that in practice now to better understand it. So let's take our formula. We'll put it here on the top right. And now we will analyze what the values of the different states are. And every state here is a square now made. So any one of these white squares is a state, and we were going to calculate the value of being in that state. So let's start with this square. What is the value of being in this state? Well, we need to take the maximum of this value across all actions. And we know that this value is maximized as we get closer to the finish line. That's how it's constructed. And by looking at it, you can see, because here it's got the reward and here it's got a discounting factor multiplied by the value of the next state. And it just makes sense that that's how we would construct that equation. So it makes sense that from here, the maximum of this value will be if we move to the right. So that's how we calculate the value of the state. This value of this state is equals the maximum, or equals to this value if we move to the right, if we take an action of moving to the right. So what will this value be? Well, the reward of moving to the right is equal to 1. And regardless of what gamma is, we don't have a value in the state because we are already in the best state possible. So this is the final state. It won't have a value. We just get a reward here, and that's the end of the game. So the value will be of this maximum will be equal to 1. And that's why value of state S here is equal to 1. Now, things get interesting when we move to the left, when we move backwards a bit. So now let's calculate the value of being in this state. And for that, we're going to need gamma. So let's say our discounting factor is a 0.9. And it'll make sense what a discounting factor is once we calculate this. So from here, just based on our intuition and because we know how this maze works, we know that the best possible action is go to the right, because from here we go here. So that means the maximum will be achieved when in this state you go to the right. And so let's see what happens if we plug it in here. So if you go from here to here, you don't get any reward. It will still be a 0. But then you'll get gamma, so you get 0.9 times the value of the new state, which is 1. So in this case, the whole result of this is 1 times 0.9 times 1 equals 0.9. So that's our value, 0.9. So if we calculate this now, you'll see that from here, we know, just by looking at the maze, we know, because as humans, because we're understanding how this equation works. Of course, an AI, the agent, would have to experiment with these things. But because we have like a crystal ball, we can see this whole maze. We have like the bird's eye view right now. We know that the best action is to go to the right. So if we plug it all in here, it'll be 0, no reward, plus 0.9 times the value in this state, 0.9 is 0.81. And so on. So here it'll be 0.73, and here it'll be 0.66. So you can see that the way the discounted factor works is it discounts the value of the state as you are further away. So if you're familiar with finance theory, then it's something similar to time value of money. Like, what would you think about it this way? What would you prefer, to have $5 today or $5 in 10 days from now? Just if somebody was to give you a choice, I will give you $5 today, or I'll give you $5 10 days from now. Well, of course, you would choose $5 today. Why is that? Well, because you can take those $5 and you can invest them at a certain interest rate, which is very similar to gamma, and your $5 in 10 days will actually grow into maybe $5.73 or something like that. And that's how time value of money works, and very similar concept here. And the important thing to understand here, this is just a theory, a way that reinforcement learning works. So Richard Bellman came up with this equation, and from then, now that's how we use it. So you could go ahead and come up with a different equation. It doesn't have to have gamma. It might have some other factor, might not even have a factor. But this approach works, and that's why we're using it. And This is what it visually looks like. So the further away you are, the less value of this being in this state. And in terms of time value of money, if I could say to you, where would you rather be? Would you rather be here? Would you rather be here? You'd say I would rather be here. So we're creating that same phenomenon as in time value of money. We're artificially creating it through gamma, so that in order to incentivize agents or inspire agents to be closer to the finish line. So if an agent were to be asked, would you rather be here or here? Because of the way this equation works, it would choose to be here. There's nothing more to that, nothing less. It's not something that the world works this way. No, it's just something that we're artificially creating in order for our agents to understand that this is good, this is good, this is good. They're all good, but this one is better than this one, and this one is better than this one, and this one is better than this one. And that way you can see the agent can see in which direction it needs to go. So it can see that if I'm standing here, remember that problem that we had, or was he standing here? Yeah, so if he's standing here, do I go down, or like if I'm standing here, do I go up or do I go down? Well, now it's not a problem anymore, because you can see that it's actually better to go up because the value is bigger here. And then from here it's better to go right because the value is bigger here than here. And then from here it's better to go right because the value here is bigger than here and then here. And then from here, he already knows that he needs to go right because he'll get a reward here of 1. So that's how this whole approach works. Now let's have a quick look at the rest of the square. So how do we calculate the value in this square? Well, here is where things get a bit tricky. So from here, you might not actually go left, right? You might actually go right. So we can't just keep going like that, because it might actually be shorter to go this way. So what we're going to do is we're going to calculate the value in this square first. And because obviously from here, the best way is to go is up. Again, that's because we have the crystal ball, we can see things. And you'll see further down in this section, you'll see how the agent actually explores this, understands this on their, like through experimentation. But for us, we know that it's better to go this way. So we're going to calculate the value here. And that's why we're going to calculate the value in this square first. So here we have 3 possible actions. In reality, we actually have 4. We can also go left. The agent could hypothetically press left and bump into the wall and stay here. But for simplicity's sake, we're just going to show the actions that we, knowing what we know and having the crystal ball, we know which actions are the ones actually to lead to something other than the same state again. And so here, from here, we know that again, just because we have a crystal ball, we know that the best way to go is this way. An agent, of course, would have to experiment and find the best way. And you will see how that happens further down in the section. You'll see actually how an agent walks around and how you would experiment trying to find these values. But for us, we know it's that way. So here, if we plug everything in, 1, so the maximum, the best output is when you go up. Here's a 1, 0.9, 0. So you plug that in, you get 0.9. Okay, so we calculate that one. Let's calculate this one. Same approach. This is, you have 3 ways you can go. Actually 4 for the agent, but for us, we can see it's only 3. So 0.81. From here, you have 0.73. And it actually ties in nicely with this value, because then if you discount again, you get 0.66. And here you have 0.73 because this is the optimal route. So there you go. That is the values of all of these states. And now you can see that because we've created this equation, and we've created synthetically this whole concept of the closer you are to the finish line, the more valuable that state is. Now, because we've created that, now it's pretty obvious for the agent which way it should go. And we'll talk more about that in the coming tutorials. I hope you enjoyed today's session. And I know it might sound a bit very basic at this stage, but as we go through this section, we will add a bit more complexity to it. At the same time, if you cannot wait, if you want to jump into it, then there's a paper which you can look at, and it is the original paper by Richard Bellman. It's called The Theory of Dynamic Programming from 1954, and you can find it at this link. And there you go. So you can jump straight into it and read from the author of the Bellman equation. But just bear in mind that this is quite a mathematically heavy paper. And on that note, I look forward to seeing you next time. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. So we've talked about the Bellman equation and we've analyzed our little maze. Let's have a look at the plan. What is the plan? Well, here is our maze analysis, and we know that we can see actually the states, the values of each state. We can see what the value of being in every single state is, and therefore the AI can, or the agent can navigate this maze. So what is the plan? Well, the plan is simply like a treasure map for the artificial intelligence. Instead of looking at these values, let's just replace them with arrows, which indicate in which direction the agent should go because it knows those values. So an ideal scenario, after it's explored this environment, it knows the values of being in each state, and therefore it can come up with this map. So let's have a look again. We know that here value is 1. So if you are here, out of the 2, the better one is this one. So you go right. From here, out of the 2, this one's a better one, this one's a better one, this one's a better one. Or actually from here, you have 2 options, right? So here's kind of like a tie, so you just pick one at random. Doesn't matter which one, because the value in either case is the same, and more so, even if we look through, it'll take the same number of steps to get to the end. From here, you've got 3 options, but this one is the better value. From here, this one is a better value. From here, obviously, this one's a better value because here you just get a -1 reward right away. And here, from here, you have like 3 actually. So, but this one is the best one out of them, best value of the state. And so, therefore, if we replace them with arrows, it makes sense that this is how the agent would go. If it starts here, or if for some reason it ends up in this square, it knows how to get out of here. And it starts in this square, it knows how to get out of here, and so on. So that is what a plan is. And don't confuse plan with policy, because we're going to be talking about policies further on. Policies are very similar to plans, but they have a little trick to them because the environment is going to be a bit different. It's going to be stochastic. And that's what we're going to talk about in the next tutorial. So I can't wait to see you on the next one. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. And today we're talking about Markov decision processes, or MDPs. Let's have a look what we've got today. So last time we stopped on the concept of a map. So because we've calculated the values based on the Bellman equation, we can derive this map for our agent of this maze. And basically what that means is wherever the agent starts, so let's say it starts over there, it knows exactly which steps to take in order to get to the finish line. So it just goes up, right, and done. And so the question here is that it? Is it really that simple? Is reinforcement learning really that, for the lack of a better word, boring? Once you have the map, that's it. All you have to do is you're done. You just follow the map. Well, the reality is that it's not actually that all simple. And that's a good thing, because it makes this course more interesting for us, and we can actually solve much more complex problems. So this is where Markov processes come in. But first, we're going to talk about 2 things. We're going to talk about deterministic search versus non-deterministic search. So let's talk about the concept of deterministic search. This is our agent in the maze, and deterministic search means that if the agent decides to go up, then what will happen is, with 100% probability, it will go up. That's exactly what will happen. There's no other options. Once it says go up or clicks the up arrow, it will go up. There's no other options. Now, on the other hand, non-deterministic search is when our agent says it wants to go up. There are actually a couple of options. For example, there could be 3 options. And we're going to be looking at an example where there are 3 options, but it doesn't have to be limited to 3. It could be 4. It could be, depends on the problem. The randomness could be different. But in our case, it could be 3 options. With an 80% chance, he does go up. But then with a 10% chance, when he wants to go up, he'll actually go to the left. Just because that's how the environment works. That's the world that he lives in. And with another 10% chance, he'll actually go right. And in this case, he'll fall into the fire pit. So that is how it all works. That's an example of a non-deterministic search, a stochastic process. And what the point of this is to make a more realistic model of what could actually happen in a real world, in a real world type of problem. Because very rarely do you get situations like this when you do something and it happens exactly that way. And even if you think about it in terms of games, let's say you've got an agent playing Pac-Man, well, not always is it the case that if he's standing in this square, he goes up, he will get the same exact result every time. He will indeed go up, but it may be in one case he won't get eaten by a ghost, in another case he will get eaten by a ghost. So as you can see, there's some randomness to it because it depends on how the ghosts are moving, and they don't always move the same way. They don't always start in the same locations. So it's very logical. It's very is fair that there is some randomness. There's something that is not under the control of the agent. And this is just a way for us to represent that in order for us to learn how we can deal with it and how that affects the Bellman equation, how it affects the whole reinforcement learning process. But at the same time, the randomness is of course not limited to if you go up, there's a 10% chance you'll go right, or 10% chance you'll go left. Or if you go down, there's a 10% chance you'll go right or left. Or if you go right, there's a 10% chance you'll go up or down. It's not limited to where you're going to end up. Sometimes you might have a problem that is exactly like this. Sometimes the probabilities might be different. Sometimes the randomness might boil down to something else. It might be boiled down, like in that example of Pac-Man, of the ghosts eating you or not eating you, or it might boil down to something different. For instance, like there's like if the agent is playing Doom, and then there's something like a monster which is going to shoot him in one case, in another case there's a probability with which it will get shot and with which it won't get shot, and so on. So something that is out of the control of the agent, something that it cannot predict. That's what we're modeling here in non-deterministic search. And this is where we have directly approached two new concepts: Markov processes a Markov process and a Markov decision process. So let's have a look at these. And you know how much I don't like to put definitions and lots of text on the slides, but in this case, it is necessary for us to go through them. So let's have a look. A stochastic process has a Markov property if the conditional probability distribution of future states of the process, conditional on both past and present states, depends only upon the present state, not on the sequence of events that preceded it. A process with this property is called a Markov process. Very complex definition, and it kind of like even a little bit, not contradicts itself, but it feels like it contradicts itself. So here it says conditional both on past and the present states, depends only upon, but at the same time, it only depends upon the present state. So don't get too bogged down in that. I'll break it down in simple terms. So a Markov property is when your future states, so not just your choice, but the whole thing, your choice and the environment, it will only, like the results of the action you take in that environment will only depend on where you are now. It will not depend on how you got there. And that's it. So that's a Markov property, and a process which has this property is called a Markov process. So to put it into an example, so if your agent is here, and if he decides to go up, in our case, in our non-deterministic search example, he actually might go left and right, or right. That's because we have that stochasticity inside our environment. We have that randomness inside our environment. So any one of these three might happen. But the key here is that this is a Markov process because we don't care how he got here. He could have come from the top, ended up here. He could have come from the left, ended up here. He could have come from the bottom, ended up here. He could have moved around here like 100,000 times and then got here. It does not matter what happened before. Only what matters is which state is he in now. And so the probabilities of going left or right or up, they will always be the same if he's in this state now. And so that's basically just saying, it doesn't matter what happened before, we're here now, this is the state you're in. And don't forget that state doesn't just mean where he's standing. The state is the state of the agent in the environment. So is there like monsters on the right, or are there monsters on the left, or is the ghost coming from the top or the bottom? Whatever state you're in now, doesn't matter how you got there, doesn't matter how it all came to be that you're there in that state now. What will happen in the future is only determined by the state you're in now, plus the actions you will take. Then plus, of course, the randomness that is overlaid on top of that. So that's a Markov process. And a Markov decision process, or an MDP, or Markov decision processes, provide a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under control of a decision maker. So important to understand that Markov decision processes are different. A different whole concept to a Markov process. They're kind of like a mathematical framework. So, but at the same time, I thought it was important for us to understand what a Markov process is, because I think it still helps in the understanding of a Markov decision process. So a Markov decision process is exactly what we've been discussing up till now. So that the agent lives in this environment where it has control. Like, remember previously it had full control of what's going on, but now it has a little bit less control. It can decide to go up, but it actually knows, okay, so if I go up, there's an 80% chance I'll go up, there's a 10% chance I'll go left, 10% chance I'll go right. So not everything is fully under its control. There is some randomness in this environment. That's exactly what a Markov decision process is. A Markov decision process is the framework that the agent will use in order to understand what to do in this environment. So we've got an environment with some stochasticity, some randomness, and now the agent has to choose, for instance, should it go up, down, left, or right. It has to make that decision. It doesn't know what to do. And in order to make that decision, it's going to apply a framework. It's going to be using a Markov decision process in order to make that decision, what's going to happen, where it's going to go. And so basically this environment that poses this problem, it is referred to as the Markov decision process. So it's the framework that agent using. At the same time, the environment is referred to that the agent is operating in a Markov decision process environment. And so basically here we've got two concepts. We've got the Markov process is the way this environment is designed, that what happens from where you are now doesn't depend on the past. And at the same time, we've got the Markov decision process is the framework that the agent is going to be using in order to solve this environment. And the good news is that the Markov decision process, or that framework that we're talking about, is actually just an add-on to our Bellman equation. Is the Bellman equation, but just a bit more sophisticated. So let's have a look at that. This is our Bellman equation so far. It's the maximum of all possible actions. So the value of being in a state is the maximum of all possible actions that you can take from that state. The maximum is taken from the reward that you would get by taking that action in that state, plus a discount factor times the value of the next state, which is S prime. So that's what we've had so far. And now, because we have some randomness in our whole process, this part will change because we don't actually know which state we'll end up in. We don't know what S prime will be. Will it be, if we're going up, will it be up, or will it be left, or will it be right? So we actually have to place this with the expected value of the next state. So here we're going to replace this. So there's three possible states we can end up in. And so we're going to replace that with that's a value. That state has a value of S1 prime. That state has a V of S prime 2, S2 prime. And this state has a value of V of S3 prime. So now we're going to multiply the state that we actually are intending to go into by 80%, because that's our probability of getting into that state, plus the probability of getting into this state, 10% plus probability of getting in this state. So this is just our expected value. So if from statistics, if we take the expected value of getting into of the state that we'll get into, so kind of like the average. What's the average of what we'll get? And then we replace that over here. Then we get this equation. Now, it jumps very quickly just because this equation is bigger, but if you look at it carefully, you'll see it's exactly the same thing. So you've got max here, you've got max here. Then you've got R of S and A, you've got R of S and A. Here you've got gamma, you've got gamma. And then finally, here you've got V. So you knew exactly it was a deterministic search. You knew which state you'll get into. Now you don't know which state you'll get into. So instead of taking V, you're taking the expected value of the state you'll get into, or of the future state, or just in simpler terms, you're just taking the average of what you'll get into. So, you know, if like it was like if it was a 33% chance, then it'll be like this plus this plus this divided by 3, basically. But in this case, it's not exactly like average. It's a weighted average because of your probabilities here. So here you've got the probability of when you're in this state, you take this action of getting into state S prime times the value of S prime and summed across all S primes that you could possibly get into over here. So exactly what we had 3 here, 1, 2, 3, add them up, multiply by probabilities, add them up. Same here, 1, 2, 3, multiply them by probabilities and add them up. And that is your new Bellman equation. Congratulations. This is what we're going to be working with going forward. And that is the framework that is used in Markov decision processes. So that is the framework that solves this, that agents use to solve this whole stochastic, non-deterministic search problem where there's random events that are happening that they cannot control. So it's much more complex, but as you can see, because we built up slowly to it, now we already know about this, we already know about this, we already know about this, we know about this, we know about this. So all we did is we just introduced this part over here because there are probabilities involved in the action, or the consequences of your action are non-deterministic. They are based on certain probabilities. And so there we go. That's how a Markov decision process works and the underlying equation behind it. Once again, it is something that is more that more closely resembles real world problems, real world scenarios, or even game scenarios, because not everything is straightforward. There is some randomness involved, and not always will taking an action in a certain state will always not always will it lead to the same outcome. And so this is what we're going to be dealing with going forward, and that's going to make things way more interesting. So hopefully you're excited for that and excited to see what's going to come next. And in the meantime, I found a really cool paper for you to have a look at. This time it's a very applied paper. So this one's actually really interesting to read through. It's called A Survey of Applications of Markov Decision Processes, and it was written by White in 1993. There's the link, and it'll show you examples of where Markov decision processes actually are used to model real life scenarios. I think I was very excited by this. I was impressed by some examples. So population harvesting, for instance. So let's say you have some fish, and you know what the population of the fish is. You need to decide how many fish can we fish out this year, and so that's your current state, that's the action that you're taking, how many can we fish out this year, so that what are the possible outcomes of that, how many fish will we have next year, how many fish will we have the year after, and the year after, and so on. And it's not deterministic, because it's not like if you take out, I don't know, 90% of the population, then next year you will have, you know, back to 100%. It's not exactly deterministic. There are certain random factors involved which are out of our control, and therefore we have to understand what's going to happen. We have to model what's going to happen. That's where a Markov decision process is used. Agriculture, there's an example, like same thing, like harvesting crops. How much crops do we harvest? How much do we not harvest? Another one which I looked at, finance and investment. Like an insurance company needs to decide how much of its funds it will invest in any given, I think, day or year or some period of time. And there are certain factors that are out of its control. For instance, you know, the market movements, it doesn't know what can happen. So it needs to actually model that somehow, and a Markov decision process is used for that. So here you can see lots and lots of examples, and this is the number of examples given, I think, for each one. And so, yeah, even sports, 2 examples for sports and epidemics and motor insurance claims, inspections and maintenance and repair, and so on. So very interesting. Have a look at that, just to give you an understanding of, hey, this is not just all made up stuff, hypothetical, the Matrix type of thing. This is actually a real world scenario. So it'll give you a better understanding. And this is what we talked about in the promotional video for this course, that or the description of the course, that we're going to inspire you and your intuition to give you ideas for how to use AI in real life. This is your opportunity. Look at this paper to understand, okay, so we're going to be dealing with Markov decision processes going forward. That's really cool. What do they look like in real life? And this possibly could trigger some ideas for you how you could apply AI in the future to make the world a better place. And we'd be super happy about that. We'd be super happy if you could use what you learn in this course to make the world a better place with AI. How fantastic would that be? So on that note, I hope you enjoyed today's tutorial. I look forward to seeing you next time. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Previously, we had quite a strenuous and long tutorial on Markov decision processes, and hopefully you got along well with that, and hopefully I could explain things in a approachable and engaging way. And today we're going to talk about policies versus plans. It's going to be a quick and fun tutorial, because now we're entering into a new world. We're entering into a world of stochastic search, non-deterministic search. It's not just about getting through the maze, but also accounting for random factors that might just hit you in the head when you're going through this maze, and you need to be prepared for them. That's the world our agent is living in, and it's more fun, but it's also more dangerous. It's less predictable. So how is our agent going to behave? Let's have a look. There's our Markov decision process framework, which is once again our favorite Bellman equation. However, the more advanced version of the Bellman equation we were working with. So from now on, we're just going to call this the Bellman equation. And here we've got our maximum across all actions. So the value of a state, any state S, is the maximum across all actions that an agent can possibly perform in that state. And the maximum was taken from the reward that the agent will get by performing action A in state S plus a discount factor multiplied by the expected value of the new state it will be in. And the expected value is taken here because it doesn't know exactly what state it'll end up in. There are some random effects that are present in the environment that might alter the state, and not he might not end up in the desired state. He might end up in a different state. That's why we're taking the expected value over here, this sum over here. So let's have a look at this as our example, or in our example of the maze. So this is what we had previously. So previously we were dealing with deterministic search. So we knew that, all right, so if I'm here, I definitely need to go here. If I'm here, I definitely need to go here. If I'm here, I definitely need to go here. If I'm here, I'm here. So it was all pretty straightforward. Once you have this map, and remember we called it a plan. Once you have the plan, it's pretty straightforward what you need to do. There are our arrows. So that's the plan with the arrows. And from here it was very straightforward, where these are the routes that the agent would take. Wherever you start on this blue line, that's exactly the way you would go. However, now we don't have a plan anymore. We can't have a plan because, whatever we plan might not happen. It's not under our control. A plan is when you know exactly what you need to do next. You know the steps. So you have a starting point, you have a goal, and you know every single step, so you can plan them out. You're like, I'll do this one, I'll do this one, I'll do this one, like in life, like a plan. But at the same time, there's so much now randomness going on. You can't have a plan, because what if you get here and then you click to the right and actually takes you down? So that's not part of your plan. So that's why it's not called a plan anymore. And here we're going to calculate the values, or we're actually going to just look at the calculated values for this same problem, but given that we have this randomness inside. So these are the new values. And so why are these values different? So let's just compare it to what we had previously. This is what we had previously. These are the new values. So once again, we had previously, you can see 1, 0.9, 0.81, 73, 66, and this is what we have now. 86, so less than 1, 74, 71, 63, and so on. And by the way, these are not exactly the correct values. These are off the top of my head, but if we were to run an agent, some values would be something similar to this. And the values could change because depending on the gamma that we choose, 0.9 or other value. But nevertheless, for argument's sake, these are the values that we're dealing with now. And they're approximate. They convey the whole notion in the correct way. So let's have a look at them. Why have they changed? Well, why is here, let's start with this one. Here the value was 1. Why is it all of a sudden 0.86? Why is it less than 1? Can't we just go from here? Well, we actually can't, because from here, if we go right, which is our intention, if we go right, we would actually, with a 10% chance, we'd end up here. So we'd hit the wall and we'd be back in this state. And remember, we have a gamma, so the value would be discounted. Or with a 10% chance, we would end up here in this state. So it's not 100% probability I would get here. So therefore, this value can no longer be a 1. It's something less. And let's say it's 0.86. So that's an example of why it's like this. And you could get the exact value if you calculated the Bellman equation, the full Bellman equation that we have now. The only problem is that there'd be some recursion, because you would need to know the value for this, and then you would need to know the value for this. It's quite complex, and that's why we're not doing the calculations manually here. That's why but the AI can do them as it's going through all of this. It's like nothing too complex for the AI to calculate these things. So that's our value here, but now let's take a look at a different one. So here it used to be 0.9, just because of the discounting factor, remember, from here to here. Again, now from here, we can't just jump from here to here, simply because even if we go like this, we might end up back here, right? There's 20% chance that we'll still stay in the square because we'll hit a wall. And again, and so on. So the value of being here is 0.71. Again, the discounting factor, this might look odd to you, that this is, even with the discounting factor, this is too high. Maybe the discounting factor in this example is not 0.9, maybe it's 0.99 or something like that. So don't worry about that. Just kind of like focus on that the values have indeed changed, that the values are now less, mostly because it's not 100% probability to get to the state that you want to get. And what you will find an interesting one is here, that here it used to be 0.9, and it actually has dropped very much. It's dropped substantially. Why is that? Well, because if you go from here up, which is our intention, there's a 10% chance of hitting the wall, but there's a 10% chance of actually ending up in the fire pit and losing -1 to your reward. And basically that means for the agent, that's end of the game. And so this is a very bad state to be in. So all of a sudden, remember, we had 0.9 here, 0.9. So they were equivalent. It doesn't matter you here or here. They're pretty much equal in terms of value of being in each of these states. But now all of a sudden, bam, this state is like nearly twice as good as this one, simply just because here, if you go straight to, you go right where you want to go, the consequences of the randomness occurring is you just stay here. Here, one of the consequences, the 10% chance, is you end up in the pit. So as you can see, this is no longer such a good state anymore, simply because of something, that fluctuation that could happen. As you can see, this one is also very bad because it's as bad as this one in terms of, there's only a 10% chance of ending up in the pit and 10% chance of ending up in the wall. But at the same time, there's the discounting factor. So first of all, the discounting factor. And also, after this one, you'd have to go here. And even if you hypothetically went here, you could end up in the pit again. So that chance would also be taken into account. Because remember, this value is derived from this value, and this value is derived from this value, right? And therefore, it's smaller. But in reality, actually, that what I said there was wrong. This value is not derived from this value. So if you just have a look now, you will notice that this value, V over here, is actually greater than this one. You will notice that for the agent, it's better to go around this way than this way. And it makes sense, right? Because this way, it doesn't lose. There's no chance of getting in the pit. Yes, it's a bit longer, and therefore the discounting factor has a bigger effect. But at the same time, simply because there's a chance of getting in the pit here, if it goes straight, there's a chance of it jumping in the pit. So it'd rather take its time, and it'll just like go around, because that way there's a much lesser chance of it getting a pit. There still is. So if from here it goes there, if from here it goes there, it could potentially get into the pit because it could end up there and then it could end up in the pit. But nevertheless, it's a lesser chance, so it would just go around like that. So very interesting to see how the route changed. Remember, previously from here you would go like that, from here you'd go like that, and from here you'd go like that. And now all of a sudden you can see it's changed. So let's draw the arrows and see what it looks like now. And oh, voila, you see even a more random thing, right? So yes, this is true, but look at what happened here. Look at this one, and look at this one. Were you expecting that? That's something definitely, like when I saw this for the first time, I was very impressed. I was not surprised. I was surprised, and I was not expecting this at all. And this is an example of, when AI can outsmart a human. It's like something you can't even predict, but the AI, through reinforcement learning, remember that example of the dogs that can actually sometimes walk better than normal real life dogs, or pre-programmed robot dogs, or can play soccer, simply because they come up with these ideas that even we can't see. And so that's a great example, right? So you probably weren't expecting that as well, that the agent, instead of going up, it's like, why would if I go up, then there's a 10% chance I'll jump into the pit. But what does it achieve by going into the wall? Well, 80% of the time it'll bump back and stay in this state, but 10% of the time it'll go here, and 10% of the time it'll go here. So all of a sudden you can see that now it's actually, in this new approach of jumping into the wall, there is a 0% chance it will go into the fire pit from this spot. So, and it's like, it really doesn't want to go into the fire pit, so it rather bounce into the wall a couple of times, and then it will go either right or left at some point, because that randomness is going to happen. And so it learned that through experimentation. It learned that, okay, when I go forward, the results are not as good as when I go to the wall. And if you think about it, it's like this robot. If you think about it, like there's a fire pit, this square is like a very tiny ledge, and then this is like a mountain, like a cliff, and this robot is just hugging the cliff and just like trying to waiting until it like pushes it right or left. Because, well, as a human, you'd probably do the same. You wouldn't be standing facing that way or that way. You'd be hugging the cliff, right, or something like that. And hopefully, you never end up in a situation like that. But just visually, if you think about it, same thing here. And so that's pretty intense, right? So that the AI came up with this idea, and same here, that instead of going left and risking getting a fire pit, I'm just going to try bounce off the wall, hug the wall, try to jump into the wall, and at some point, I know that, just there's a probability, there's a 10% chance every time I do that, I'll go here, and sometimes it will happen, and I'll end up here, and I'll be safe, and then I'll just keep going like that. So very, very interesting approach that the AI took here. And as you can see, the routes are like this. So from here, it might go right, and then it'll go right to the exit, or here it'll go left like that. and here it will, at some point, it will go left and it'll go like that. Again, this is important to understand. It's not a policy. So even when it jumps from here, it will go here, maybe, and then from here it might actually, instead of going straight, it might actually go back to the right, and then from here it might go to the left, it might go to the right. So there's lots of different options for it to go. So it might not follow exactly this arrow, it might go the other way. This is just the desired routes that it's designed for itself, but the way it'll work out is actually could be different. It depends on the real world. So there we go. That's the world of artificial intelligence. That's what a policy versus a plan is. And hopefully you're slowly getting excited by what the AI can do, especially given what we saw over here. These are some very virtuoso type of decisions that the AI is coming up with. And as you can see, when you apply AI, even from this small example, you can see that even when you apply AI in the real world, maybe you'll come up with ideas and decisions that even sometimes humans can't come up with. And that's exactly kind of like what happened in those games where the Google AlphaGo was playing versus Lee Sedol, the champion of Go in Korea, back in the world champion of Go, and they were playing in Korea back in 2016. I think it was March 2016. It came up with some moves that humans had never played in 3,000 years, or humans were not used to playing. And this is exactly an example of that. So once again, hope you're getting excited and pumped about this course and about what we're going to create. And I look forward to seeing you next time. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're talking about the living penalty. All right, so here we've got our Bellman equation, and as we've been going through this course, we've been slowly making it more and more complex. So far we've already added these probabilities in here, and also we've added the discounting factor. Now we're going to look in more detail at this side of the equation where we have the reward. Now remember previously when we talked about how reinforcement learning works, we said we have an agent and it performs actions in the environment, and in exchange, or as a result of that, it gets a new state in which it's now in and a reward for that action. Well, so far in our example, we've only been getting rewards at the very end, either if we get to the finish line, or if the agent ends up in the fire pit, he gets a +1 or a -1 reward. But that is a very simplistic approach to reinforcement learning, and in more realistic scenarios, you will likely have rewards throughout the journey, not just at the very end. You might have rewards throughout the journey. For instance, if it's an AI playing a game, and if, for example, it's like shooting somebody in Doom, it might get points for killing that enemy. Or it might be in a different other game, if it overtakes another car or something like that, just because of the rules of the game, not because of its way of analyzing the game, but actually the game is structured in a way that it's reinforcing, it's giving points for doing certain actions even before the game is over. So scenarios like that are very common, not just in games and also in real life. And that's why we're going to introduce something similar into our example, a simplified version of that, but nevertheless a reward that is continuously given to the agent throughout the game, not just at the end. And the way we're going to do it is by looking at the other tiles. So right now we only have reward +1 at the final tile and reward -1 at the other final tile, the fire pit. But now we're going to add rewards in every single tile. We'll add a very small reward. It'll be -0.04. And as you can see, it's negative. So every time the agent moves, he'll get a negative reward. And that's why it's called a living penalty, because no matter where he goes, he will always get this negative reward, except for these final tiles, because that's the end of the game. And so here you can see the reward even on this tile is -0.04, but that doesn't mean that he starts with that reward. He only gets this reward, and this is important to remember, he only gets this reward when he enters a tile. So whenever he performs an action, he goes here, then he will get this reward -0.04. And then if he comes back to this tile, he'll get another -0.04 reward. And so the longer he walks around, the more he accumulates this negative reward. And therefore, it is an incentive for him to finish the game earlier, as quickly as possible. And so now let's have a look at how our policy, or how the agent's policy, is going to change depending on what value we set for this reward. So here are 4 environments, and in each one we're going to explore a different reward. Now we're not going to do the calculations. We're just going to project the results, and you will see that intuitively they make total sense. So here we've got a reward for any step, or for getting into any state, is equal to 0, just as what we've seen before. Here the reward is going to be minus 0.04, what we just introduced now. Here the reward will be minus 0.5, or the living penalty will be minus 0.5, so much higher, you can see, than here, more than 10 times greater. And here the living penalty will be minus 2, so even more than the reward you get for jumping, or even less than the reward that you or the agent gets for ending up in the fire pit. So let's have a look at how the actions, or the optimal policy for passing this environment will change depending on this reward. So this is our original policy. And as you can remember, we had these two very interesting and even a little bit weird decisions by the agent, but which totally makes sense if he can live for as long as he likes, if he can just travel around for as long as he wants without being penalized for staying alive very long. Why not? Why wouldn't he just go into the corner here, into the wall, and just keep doing that until it so happens that he goes this way, and then he will walk around. And same thing here. It's much safer for him to jump into the wall, hoping that one of these will come up eventually, and then he'll go to the finish line anyway. Because by choosing these two actions, he doesn't risk getting into the fire pit. Now let's see what happens if we add a reward, a negative reward for just being alive, for making a step, for making a move. So here you can see that instantly these two changed. Now the agent doesn't want to jump into the wall. He is more likely to risk getting to the fire pit, having a 10% chance of jumping in here, but he will go forward. Because every time he jumps into the wall here, if he was going to be doing it here as well, every time he jumps into a wall, he performs an action, he ends up in this state with an 80% chance, and that means with an 80% chance he will get a minus 0.04 reward, meaning that a lot of the time he's going to be getting this, accumulating this negative reward. Same thing here. If he jumps into the wall, waiting for that moment when he will actually be randomly moved to the right, if he keeps doing that, he will accumulate this negative reward, and that the result of that, if you perform the calculations, you'll see that the result of that, the expected value of that approach, jumping to the wall, is worse than taking the risk of going forward and actually ending up in the fire pit. So he changes his decisions in these two blocks to instead move forward, and here move to the left, even though there's a risk of jumping in the fire pit, simply because now the longer he's alive, the longer he will accumulate this living penalty. In the next environment, now we're increasing the living penalty to even a greater number, minus 0.5, and let's see what changes here. So now you can see that compared to this environment, the only thing that changed here is that this arrow is pointing to the right. And what that means is that now it's no longer a good option for the agent. Oh, actually also this arrow was pointing to the left, and now it's pointing to the upwards. So now it's no longer a good idea for the agent to go around from here, go around all the way, because if he goes around all the way, yes, he's safer. There's no chance of getting into the fire pit. But at the same time, or there's a less chance of getting to the fire pit, but at the same time, he will accumulate quite a substantial negative reward as he walks around. So the path is too long. So that forces him, even whether he's here or here, to take the shorter route to get here, even though he has a much higher risk of getting into the fire pit, because as soon as he ends up in the square, there's a 10% chance of getting into the fire pit. According to his calculations, it's just the expected value of this approach is better than the expected value of going around, simply because we've increased this living penalty. And finally, we're getting to the example with the living penalty of minus 2.0. So here, I would encourage you to pause the video now that you've seen how the policy has changed as we increase the living penalty. I encourage you to pause the video and to think for yourself, what will happen in this scenario? What do you think the optimal policy will be, given that the living penalty is so high? So I'll let you pause the video if you'd like to. And now I'm going to jump into showing you the solution. So in this case, if you increase the penalty to minus 2.0, it's so high. Remember that the penalty here is only minus 1.0. It's so high that the agent just wants to get out of the game in any way possible. Even if it's just by jumping into the fire pit, he will do it. He will be like, every time I make a step, every time I end up in a new state, or every time I make an action, I end up getting a -2 reward. So what's the point of trying to get to the finish line if from here it'll take me 2 extra steps? I'm just going to go here and then straight into the fire pit, because that way my reward is going to be less. The negative reward is not going to be as bad as in the case of just making additional steps. So you can see that adding this living reward, and depending on the value of the living reward that we're adding, the results are going to be different, and the agent is going to select different policies. And that's basically how the reward value is incorporated by the Bellman equation, even when it's not just at the finish line or at the end of the game, but even throughout the game. And once again, it doesn't have to be on every single in every single state. Depending on the environment itself, it might be given to the agent at certain specific states, not at every state. But in our simplistic example, we're just using rewards at every given state to illustrate this concept. So I hope you enjoyed today's tutorial. And as you can see, we've already made our Bellman equation quite sophisticated, and now it can be applied to many different scenarios. And I can't wait to see you in the next tutorial. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we are finally talking about Q-learning. All right, so we've already got this equation, the Bellman equation, which we've added lots of components to. We've got the reward here, which can be not just at the very end, but it can be at any given step. We've got the discount factor. We've got the probability, because now we're looking at Markov decision processes, and here we've got the probability of ending up in different states regardless of what action we take, or actually given the action we take, they can be multiple states that we can end up in, and then we've got the value of the next state. So you can see it's kind of like a recursive function and so on. But you probably still have one question. The question is, where in all of this is the letter Q? Why is it all called Q learning? So where's the Q? And that's the question that we're going to be answering today. So far, we've been dealing with values, the value of being in a certain state. And now we're going to look at how Q fits into all of that as well. So here we've got two examples. On the left is what we've been doing so far. Our agent has been analyzing, okay, I'm over here. This is a Markov decision process, so it doesn't matter how I got here. The rest of the environment doesn't care of the steps that it took me to get here. From now on, I have to make the optimal decision where to go, here, here, or here, based on the current state and all the future states that come from here, but not from the past. And so he can see that there's three options. There's state 1, state 2, state 3. And based on his experience, he has calculated the values in these states. And now he's going to, using the Bellman equation, so even that though this is a stochastic process, so he knows that he'll go here, but there's a chance that he'll go left or right, and so on. So based on these values, he's going to make a decision. That's what we've been doing so far, and that is totally the legitimate approach here. But now we're going to modify it a little bit. We're going to take the same exact concept, same exact problem, but here, instead of looking at the values of each state that he can end up in, we're going to look at the values or the value of each action. So we're not going to use the letter V anymore, because V is for the value of the state. We're going to use Q. And you might have a question, why the letter Q? Well, Q, some people speculate that Q, well, I read this, I think, on Quora. Somebody mentioned that Q is because of quality. But at the same time, I couldn't find any other references to that. So it might not be because of that. It might be just because that's the letter that was used at the time. And now it became super popular because it's all called Q learning because of that. So no exact reason why it's called Q, but nevertheless, at least it helps us distinguish between V and Q. So Q here represents, rather than the value of the state, it represents, let's go with quality. It represents the quality of the action. Represents, okay, so I've got 4 actions. What are the different qualities of these actions? What is the, or the value of the action, or the quality of the action? Which action is more lucrative? So I need a metric telling me, all right, how do I quantify this action? And then I can compare them. And that is exactly what Q is. And so here he's got 4 possible actions. As always, go up, right, left, or down. And based on the action, there's going to be a formula which tells us the quantifiable value of that action, which we're calling the Q value of that action. So let's have a look at how we're going to derive this formula for Q. How does it actually relate to V? Because as you can imagine, because actions lead to states, there has to be some sort of link between the two, right? We've already determined how to calculate this, and we're pretty good at it. We know how to use the Bellman equation in very different environments with lots of different complications. Well, let's leverage that knowledge to understand how we can now calculate Q in order to make the same predictions. Because as you can imagine, the environment doesn't change depending on what approach we use. The environment is going to be the same regardless. So therefore, this approach and this approach should always give the same result. And therefore, that's another reason why these two should be linked. So let's have a look. So here's our V approach, where we're just going to look at the value of any given state, this state, any other state. And here we're just using the letter S here because that's the current state. And so therefore the terminology will be the same in both equations. And here we're using QSA. Q is of the state S and the action A, because action is up, but in which state did we perform that action? We performed that action in state S. Okay, so now we're going to write out the Bellman equation for the first approach. As you can see here, we've got V of S, so the value of any given state S is the maximum of the reward that you get. So maximum based on the actions, so you have three, in this case you actually have 4 actions. So maximum out of all the possible actions, and then of this part, which we've already discussed many times. So this is our reward that we get from performing that action in that state, plus a discounted factor multiplied by the expected value of the new state that we're going to be in. An expected value, because it is a stochastic process, we don't know exactly for sure that we're going to end up over here. We might end up on the left or the right with a certain probability. That's why these probabilities are in here. All right, so that's our value. And now let's look at Q. So Q is going to be defined, we're going to use this to define Q. So let's say the agent from this location, from this state, performed the action up. What is the Q value going to be equal to? Well, first of all, let's see what he'll get in return. For performing this action up, first thing that he'll get is a reward, right? That's no doubt about it. There's going to be some sort of reward. It might be 0, but we know that the way this reinforcement learning process works is that sometimes for performing certain actions from a given state, there's a reward. So we're going to add that in here. And then we're going to add, what are we going to add? Well, let's think about it. What is the next thing that happens after he's gotten the reward? Well, the next thing that happens is that now the agent is in a certain state. He could end up here with a 80% probability or some probability, but actually he could end up here or here. But wherever he ends up, now we already have a quantified metric for that state he's in, and that is actually the V value of that state. But because he can end up in many different states, in 3 of the possible different states, we have to look at the expected value of the state that he'll be in. And so we're going to add that in. We're going to add, of course, the discounted factor as we previously had, because that is somewhere in the future. And then we're going to add the sum of across all possible states that he could end up in by taking this action times the probability. So what we're saying here is that, okay, so by performing an action, you're going to get a reward plus, which is a quantified metric, plus you end up in a state. We don't know which one. It could be here, it could be here, it could be here. But here is the expected value of the state that you're going to end up in. And now we're going to multiply it by discounting factor because that is 1 move away. So that is our Q value for performing this action. And what you will notice here right away is that the Q value is actually exactly identical to what's inside these brackets over here. And why is that? Well, if you think about it, here we're taking the maximum of the result we will get, the maximum across all possible actions. So we've got 4 actions, and we're taking the maximum across all possible actions of the result that we'll get by taking each of those actions. And in Q, we're defining, interesting, what will we get by taking a certain action? So if you think about it, it makes sense that the value of a state, so for instance, this state, is the maximum of all of the possible Q values, right? So here in this state, by being in the state, the agent has 1 Q value, 2 Q value, 3 Q value, 4 Q value. So he has 4 possible Q values. Well, the value of the state, it makes sense that the value of the state is the maximum of all of those 4 Q values. And that is exactly what we can see here. That's a good confirmation of this new formula that we derived. If that wasn't the case, if that didn't match up, then we would have questions. We'd be like, so why doesn't it match? Why doesn't it match up if Q value is a quantified metric of performing an action and V depends on is the maximum of the possible results of the 4 actions that he can perform. Hopefully that makes sense, and that confirms the formula that we've just derived. And now we're going to make it even more interesting. We're going to get rid of the V entirely, because you can see here you got V is a recursive function of V. So, and then we got V, and then V, and then V, and then V, and so on. So you can express this V through all of the following V's, the most optimal V's that will come up. Here, we're expressing Q as a recursive function of V, or as a function of the next V. And then we'd have to plug in this V, and then we'd get back to the V. So what we're going to do is we're actually going to take this V and we're going to replace it with Q, right? So let's have a look at that. We're going to take this V of the next state, and we're going to plug this into that formula over here. And as you can see now, so this part doesn't change, this probability doesn't change. But as we just discussed, V of S is the maximum by all actions of Q of S and A, right, over here. So that's what we're going to replace in here. So we're going to say a maximum of course, it's the new action, the action that we're going to take, because here we've got V of S prime. So here now we've got the maximum across all A primes, so the actions that we're going to take from this state or from whichever other state we end up in. But the action that we're going to take from there, and a maximum across all those, and the maximum is of all of the Q values that are available to us in that new state S prime, comma A prime, and that's the action. So there's going to be another 4 Q values there. So now, as you can see, let's go through that again. So as from what we derived, as from what we discussed, just through logic and intuition, so that we can see that V and S are actually, V of S and Q of S and A are linked. V of S is the maximum across all actions of Q of S and A. You can see it right here. So this part is identical to this part. And then we're going to leverage that, and we're going to replace this bit with V at S from here, but not this exact formula. We're going to take this internal part, and we're going to replace it with Q of an S and A. So we're going to plug that in here, and this part is going to be Q of S prime A prime. So maximum of Q across all A primes of Q S prime A prime. And now we have our formula. So now we have a recursive formula for the Q value. So now the agent can think, what's the value of this action? What's the quality of this action? What's the Q value of this action? Well, it depends on the reward I get in the immediate step after that. Plus, it depends on the discounted factor times the maximum of all the possible Q actions in that state. But I don't know if I'm going to get there. So I need to also look at that state. And that's why we have this expected value over here. So we have this sum, probability times the maximum, and that's our expected value. So very similar formula, as you can see, but this time we're expressing things through the Q values. And that's why this whole algorithm is called Q learning, because this is what is looked at. This is what the agents actually use. They don't look at the states, they look at their possible actions, and then based on the actions, on the Q values of the actions, they will decide which action to take. So they'll just look at the maximum Q value in this given state. It has 4 actions. What is the best action to take? So it can compare, instead of comparing the different states it can end up in, it's going to compare the possible actions that it currently has. Then by finding the optimal one, it's going to take that action, and then it's going to repeat that process, and so on. So now you can see how all of this comes together, how the reward, the discounting factor, the stochastic Markov decision processes, and the V values and the Q values all come together in order to give us this one super powerful Bellman equation for Q values, which we can now apply and let our agents learn how to beat the environment. And so that is an intuitive explanation of what's going on. I know we went through the formulas, but it is necessary because this is like our formula that we've been going through this whole chapter, and I think it's a good transition from V to Q, and it illustrates how they're linked between each other. And if you'd like to get a bit more of a rigorous approach, mathematical approach, and like you see the mathematics behind it and learn a bit more about Q values and how they work, then we've got some additional reading for you. This paper is called Markov Decision Processes, Concepts and Algorithms by Martin van Otterlo, 2009. So you've got the link here as always. And here you can read in a bit more detail to understand all the nitty-gritty behind Q values and so on. And now that we've discussed all of these things relating to the Bellman equation, now we are ready to look at something more complex such as this paper in order, if we want to get some additional information on this, in order to kind of get a deeper understanding. But even if you don't read through this paper already, you should have a good working knowledge of what Q learning is all about and how agents come up with the actions that they need to take in a certain environment. So I hope you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're talking about the temporal difference. Now, it's a very important tutorial because temporal difference is the heart and soul of the Q learning algorithm. This is actually how everything we've learned so far comes together into play inside Q learning. So let's have a look. Remember the time when we talked about deterministic versus non-deterministic search? And remember how we said in this case, it's when the agent wants to go up, he definitely goes up. And when in this case he wants to go up, there's a 10% chance he'll go left, 10% chance he'll go right, and an 80% chance he'll go right, go straight up. Well, these numbers are, of course, arbitrary and can be different. And this whole concept is could be different in different problems. So it doesn't have to concern which way he's moving, just that there's some randomness, something that's out of the control of the agent happening inside this environment. And what effect that had is, as you remember, was that in the deterministic example, it was very easy to calculate the V values. Well, not necessarily always very easy, but in our case, we could just simply calculate them by using the Bellman equation, and we had the exact values. And then, as you remember, I very carefully mentioned that these values for the non-deterministic search example are off the top of my head. They're not calculated. At that time I said we're just not going to calculate them because it's very complex, but the computer could do it. And we just went along with these values that are just values that I made up, but they did get the job done. They helped us understand the concepts. Well, now we're going to return to that a little bit and understand what exactly is going on here. Why is it so much harder to calculate these values in the non-deterministic example? Or generally speaking, in these problems, in these environments and the agent going through them, why can it be so hard to calculate these values? Well, when you think about it, because when the agent moves, for instance, from here to the right, he doesn't necessarily always move that way. Sometimes there's a chance that he'll go when instead of going straight. So let's call these northeast, southwest. So instead of going west, the agent might sometimes go south. And for instance, from here, instead of going north, he might sometimes go east. So here, instead of going east, he might sometimes go south. And here, instead of going north, he might sometimes go east or west. And here, instead of going north, he might sometimes go east or west, and so on. And therefore, in order to calculate this value, you would need to know what this value is. But the interesting thing is that in order to calculate this value, you need to know what this value is. So there's a lot of recursion happening here, and therefore you cannot just define what these values are. And on top of that, this recursion is not deterministic. It is sometimes it happens this way, sometimes instead of going up, he'll go right, sometimes instead of going up, he'll go left, sometimes when he wants to go up, he will go up. So it is subject to chance. And so maybe many times the agent will go through this path and he'll go up, and he'll think that from here he always kind of goes up, and so the value of the state will be good, and then all of a sudden he'll drop into the pit and this value will go down. And so therefore you can see how there is some stochasticity or randomness to this whole calculation of these values because they're all interlinked. Plus, on top, you've got that randomness that's inherent in the environment because there's a Markov decision process. So that's where all of this comes together, and that's where we're going to introduce the concept of the temporal difference, which will allow the agent to calculate these values. And here we were dealing with V values, and since then we've already moved on to Q values. So that's what we're going to be working with. We're going to be looking at Q values. So as you recall, this is our Bellman equation for Q values. So a Q value or the value of performing a certain action A in state S is equal to the reward that you get after performing that action, so immediately after performing that action, plus you get the maximum, you get the gamma of the sum of all the possible, so you kind of get the expected value of the state that you will end up in. So as you recall, that was our formula for the Bellman equation. And now, just for simplicity's sake, we're going to rewrite it in the old-fashioned way, in the way that we used to talk about the Bellman equation before we knew about the stochasticity. So, as you remember, this was our Bellman equation in the sense of a deterministic search example, because here you don't have that expected value, you don't have the sum across all probabilities, you just have that as if it's determined where you're going to end up, what state you're going to end up, and then you're taking the max in that one state. And the reason we're rewriting it is simply, the only reason is because it is just easier to write it and it'll be easier to us to follow along with the formula. So we're going to just remember that we replaced this part with this part, and also you'll find this notation in a lot of literature, so it'll be easier for you to follow along with other sources if you're studying those. But do remember that, in fact, what we mean is this probabilistic approach here instead of this notation. It's just easier for us to operate this and understand what's going on and just kind of like look at the equations so that they're not too cluttered. But once again, just remember that, in fact, what we mean is this probabilistic approach over here. And so we're actually nearly done. So let's have a look at what's going on. So here is our blank state of the maze. We don't have any Q values. Let's see, or we may, but let's just keep it blank for now. Let's just look at one of the states, so at one of the cells, this one specifically. And here we have, for instance, for the action of going up, we have a Q value that we've calculated. So it's not that we don't have any Q values yet. We do, but we're just not illustrating anything. We're just keeping it blank for simplicity's sake. But we have the agent has been walking around for some time, and let's say hypothetically somehow he's calculated this Q value of going up or north from this state, from this specific cell, and the value is Q, S, and A. And so now what we have, so he is currently where this blue arrow is pointing. The agent is sitting in this cell. And now he needs to make a choice. Where is he going to go? And he knows the value of the action going north, and that is Q, S, and A. And here I'm saying before. And the reason for that is because that is before he takes the action. He hasn't taken the action yet, so he's still in this cell. And before he's taken the action, the value here is Q and S and A. And now he actually takes the action. So let's say he decides this is the best one, he takes the action, and he moves up to this cell. Well, now what happens is, now comes after. So after he's taken action, we can measure what is this value. Let's just calculate this value. The value of the reward for taking that action plus gamma times the maximum of this new state that he's just gotten into, S prime. And so the maximum across all possible actions in S prime. And so what we have here is the value before of that action, and then we've calculated this metric afterwards. But as you can recall from the previous formula, so if we go back very quickly, from the previous formula, what we just calculated is indeed the value. That is how Q of S and A is calculated. So this right part, we've just calculated it separately, but after we've taken the action. So as once again, before we knew a Q of an S and A value, something that we've calculated through our iterations previously. So a value that's stored in our memory, so just like a number that we know. And now after the actions being performed, we know what reward he actually got, what reward the agent actually got and we can calculate this new value. So in essence, we're kind of recalculating this value, but now with new information. The new information is the reward that we got. And plus what state we ended up in and what the maximum across that state, for what this new value is for that specific state that we're looking at. So what the value of that being in that state is. So basically the Q of an SNA, but given new information. And now the temporal difference is defined as TD of A and S of these two, of the difference between these two. So here, the first element is your after value. So the kind of like Q of S and A, but calculated afterwards. And the previous Q of an S and A, which you had stored in your memory. And so the question is, are they different? So ideally, they should be the same. Ideally, this should be the same as this, simply because this is the formula for calculating this. But the thing is that this is not something we calculate. This is something that we have from empirical evidence, something that we have from just going through the maze many times and calculating. So this is something we've come up with so far. It's not related to the current iteration. It's something that we came up with previously, not a long time ago, but in one of our previous iterations going through the maze. Whereas this is something we've calculated just now. And there's no guarantee that they're going to be the same because of the randomness that exists in the maze. Because this could have been calculated and some certain random events were triggered, and this can be calculated. Different random events were triggered. And so now let's rewrite that over here. Let's just move it up there. So how do we use this? The question is, okay, so we have this temporal difference. How do we use this? And why is it called a temporal difference? Well, the reason it's called a temporal difference is because you're basically calculating the same thing. You're calculating Q of S and A. So the Q value of that action, you're calculating here and you're calculating it here. But the difference is time. This is your Q of S and A previously. This is your Q of S and A now, your new Q of S and A. And the question is, has there been a difference? Have there been a shift between them in time? And how can we use this to our advantage if there is indeed has been a shift in time? Well, one thing we could do is we could say, okay, well, our Q of S and A this new value doesn't equal the old, so we're going to get rid of the old. We'll forget about the old, and we'll just use this as our new value. But that would not be smart. And the reason for that is that in our environment, random events can sometimes happen. And what if our old QS of S and A was something that, consistently happens like 80% of the time, and then like was represented by what happens 80% of the time, and then this new one just what happened due to randomness. In that case, we're going to throw away the one that is responsible for the bulk of the situation, and we're going to replace it with something that happens only 10 or 20% of the time. That wouldn't be the best approach to go. And that's exactly why we don't want to completely change our Q values. We want to change them step by step, a little bit by little bit. And that's why we're going to use this temporal difference in a specific way. So we're going to say, here's a formula. We're going to take our Q of S and A, and we're going to update it in such a way. We're going to take the old value of Q, S, and A, and we are going to add alpha times the temporal difference. So alpha is going to be our learning rate. That's a new parameter that we're introducing. That's how quickly is the algorithm learning. So basically, we're taking this difference, and whatever it is, we're adding it on to our previous Q of S and A. Now, this formula probably doesn't make any sense, or just by looking, it doesn't make any sense because you've got Q of S and A here and Q of S and A here. It's the same thing, so it probably should negate each other. But we're going to rewrite this in a bit of a different way. So I'm just going to show you again. So I'm just adding time to these formulas. So here is QT minus 1, the previous. Here's QT minus 1, the previous. Here's QT, the new. There should be a circle here, a red circle here as well, but never mind. And here we've got alpha temporal difference, the current temporal difference. So you can see what we're doing. We're saying, okay, let's take our current Q is going to be equal to our previous Q plus whatever temporal difference we found times alpha. This formula over here is the heart and soul of the Q learning algorithm. This is how the Q values are updated. And it's good that we've already learned what Q values are, what gamma is, what R is, and what all of this stuff is. And now all we need to see is that you have a previous Q value Yes, that's good. And then what can happen is that when you actually do take the action, when the agent takes action, he'll get a reward and he'll end up in a state. And so based on that, he can calculate, okay, so what should have been the Q value of that move that I made? And now that is this part of the equation. Subtract the old Q value, gets you temporal difference. And now you need to take a alpha times temporal difference. And that's how you're going to adjust your Q value. That's what you're going to adjust your Q value by. And now just to finish off, this is kind of like, this is sufficient to understand what's going on. But just to clarify things even more, or perhaps maybe confuse things even more, what we're going to do is we're going to take this temporal difference, or this temporal difference over here, and we're going to plug it into this formula. So we're going to take all of this part and plug it into this formula and end up with a huge equation. So here we go. There's our equation. So this is the full equation with the temporal difference written out completely. And the reason I wrote this out is, well, first of all, you'll probably find this in other literature if you study it. And the second thing is that it makes some things a bit more complex. Yes, the formula is longer, but also makes some things a bit clearer. So for instance, you can see here the role alpha plays. You can see it better because look at this. Here you've got qt minus 1, and here you got qt minus 1 with a negative sign. So if you plug in alpha equals to 1, if you put a 1 in here, then this will negate with this. So they'll destroy each other. And all you'll have left is this part. And what that means is exactly that situation where we said, all right, so we've got a new value, which it should have been. Let's update our Q value with the new value and forget about whatever we had previously. And as we discussed, that's not the best approach because there are random events here and we want to update things step by step. And on the other hand, if you set alpha equal to 0, what happens then is that you completely forget about this whole part and your QT, the new one or the current one, is going to be always equal to the previous one. So you're not going to be learning anything. And that means whatever is happening in the maze doesn't matter because you've decided on your QT value a long time ago and you're just going to keep it. And so that's why alpha shouldn't be 0 or shouldn't be 1. It should be somewhere in between, and it's going to allow you to learn slowly, step by step. It's going to allow you to, the agent, as it goes through the maze, is going to get this temporal difference, and slowly and surely this value is going to get updated and updated and updated. And what will happen eventually is that at some point, hopefully, the algorithm will converge. And what that means is that this temporal difference will start becoming closer and closer to 0, and eventually will be just, well, very close to 0, or even 0, 0, 0, 0. And what that means is that every single time your new QT value, or your new calculated value, what it should have been, so not this one, but what it hypothetically should have been after you take the step, will be just equal to your previous QT value. And then it's 0, and that means when your temporal difference is 0, it means your algorithm has converged, and it's not really necessary to continue updating what's going on. It's not necessary to continue updating your Q values. The caveat here is that the only time, probably one of the only times when you would still want to continue performing this whole, updating of your Q values, if the environment is constantly changing. If not just, it's not that it just has some random stochastic events in it, but the environment itself is modifying, is morphing, is changing with time. So you continuously need to learn because it's not possible for you to learn everything and come up with the optimal policy because the optimal policy is also changing with the environment all the time. In that case, you will need to continue calculating temporal difference and calculating the Q values. But other than that, that's kind of like an extra complication. Other than that, this is how Q values are updated. So this is the main formula of the Q learning algorithm. And this is kind of like the expanded version of that. And now it should all come together and make sense why we have the Bellman equation, and not only what it represents, the Q values, but also how the agent goes about updating its Q values and finding exactly what is going on in that environment so it can come up with the optimal policy. So I know this is quite a lot to take in, but hopefully you enjoyed today's tutorial and hopefully you were able to take away the underlying concepts and intuition behind Q values and what the whole notion of temporal difference is, and why it's important, why it helps us slowly train our agents and get them to understand their environments that they're operating in. And if you'd like to learn a bit more about temporal differences, then a very popular paper is Learning to Predict by the Methods of Temporal Differences by Richard Sutton of 1988. We've already had a reference by Richard Sutton as well, but this is another one, and actually he has a book. So if you get into his writing style and his style of communication, then check out his book as well. It's kind of like a more expanded version of all of these things. I haven't read the book, but that's what I'm imagining. At the same time, this is the link to the paper, and you can learn a bit more about, or probably a lot more about, temporal differences there. And I hope you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's section, we're tackling the topic of deep Q learning. So let's see how we're going to attack this. In this section, we will learn a deep Q learning intuition, the learning side of things. So we're going to separate deep Q learning, the intuition behind it, into two parts, the learning and the acting. And we're going to have two tutorials on that. So first we'll understand how the neural networks actually learn and how they update their weights based on what we are feeding them in, and how the whole concept of Q learning works. So how we're going to take the temporal difference concepts that we discuss in simple Q learning, we're going to apply them into deep Q learning. And then we're going to talk about how deep Q learning algorithms actually decide what action to take in what states. Then we're going to talk about experience replay, a very important addition on top of deep Q learning, which actually enables deep Q learning to work properly, and you'll see why it's important from that tutorial. And then we're going to talk about action selection policies. We're going to talk about how deep Q learning agents are able to combine exploration with exploitation. So once they found something, a good approach, they can use that approach, but also they need to explore so that they don't get stuck in a local maximum. And one more thing I wanted to mention about this section is it is highly beneficial if you have a look at Annex number 1, artificial neural networks. So if you go and explore all those topics, we've got some very powerful intuition tutorials prepared for you there. If you haven't done the deep learning course, if you've done the deep learning course, then you already know all of these things and you can proceed with the section. But if you want to get that additional knowledge about neural networks before you proceed with this part of the course, this is highly advisable because it will help you understand exactly how neural networks work and why they're so powerful, why we're leveraging them in this deep Q learning algorithm. And once you've refreshed your knowledge or gained that knowledge on neural networks from that annex, then come back here and we will proceed with the deep Q learning. If you're pretty comfortable with neural networks, then let's get straight into it. Let's start talking about deep Q learning intuition. And I look forward to seeing you on the first tutorial. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. And finally, we're on to the fun stuff. We're on to deep Q learning. All right, so let's have a look. Previously, we spoke about Q learning and what it's all about. And we learned about the agent, the environment, and how the agent will look at the state he or she is in, take an action, get a reward, enter into a new state, and based on that feedback loop, they will continue taking actions, and they'll learn from that, understand what are the better actions to take. And so we looked at this basic example of a maze. We understood that as the agent explores the environment, it understands what the values of the states are. Then we moved on from dealing with the values of the states to dealing with the values of the actions, or the Q values. And then based on that, we understood how plans in non-stochastic environments work and how policies work in stochastic environments. And this is an example of a policy. So that's a quick recap of everything we discussed in the basic Q learning. And now let's have a look at how this can be taken to the next level through deep learning, through adding deep learning. Okay, so this is our environment. And what we're going to do now is we're going to add, instead of just doing basic calculations in this matrix that we have, which is pretty simple, what we're going to do is we're going to add two axes. We're going to add an X and Y axis, or we'll call them X1 and X2, just to make things even more general. And here we've got we'll number the columns 1, 2, 3, 4. Here we'll number the rows 1, 2, 3. And so now every single state can be described by a pair of two values, x1 and x2. So any one of these squares in which the agent can possibly be in can be described by x1, x2. So for instance, right now he's in the square with x1 equal to 1 and x2 equal to 2. And therefore, that's in that same way, we can describe any square, meaning we can describe any state. And of course, this is a very simplified version of an environment of describing states, but nevertheless, it works in this case. And that means that now we can feed these states into a neural network. And by the way, here, I would just like to mention that at the end of the course, we've got annexes. We've got annex number 1 and annex number 2. In order to proceed successfully with this section, it's highly advisable that you check out annex number 1, which is on artificial neural networks, so you understand how they work, so that we don't have to delve into that here, and we can just use the benefits of the knowledge of how artificial neural networks work. And so we feed in this information on the state into a neural network, and then it will process this information, so x1 and x2. Depending on the structure of the neural network, it might have multiple hidden layers and so on. So that's something that you'll figure out in the practical tutorials. But at the end, we will structure in such a way that it spits out 4 values. And these 4 values are actually going to be our Q values. So the values which dictate which action we need to take. And further down in this tutorial, we'll see exactly how these Q values are used to decide which action is taken. But the main point here is that we no longer look at just this maze from a Q-learning perspective. We're now taking the states of the maze and we're feeding them into a deep neural network in order to get these Q values. And at the end of the day, we're still going to come up with an action. We're still going to understand what action we need to take, and we'll discuss all this in more detail. But the question right now is why? Why are we doing all of this? Why are we making things so much more complicated when that initial approach of Q-learning was working already? Well, the reason for that is the Q-learning was working in this very simplistic environment. And we're continuing to deal for now with this very simplistic environment in order to better understand the concepts. But at the same time, that simple Q-learning will no longer work in more complex environments. And we're talking about, for instance, the self-driving cars, which you'll be creating, or playing Doom, when the artificial intelligence is playing Doom, or other Atari games like Breakout, or even self-driving cars and more advanced reinforcement learning things such as like robots walking around and performing actions. In all those cases, basic Q-learning is insufficient, is not strong, is not powerful enough to be able to master those challenges. And just like we've seen in the deep learning course, if you've been in our deep learning course, or if you've done the annex sections, annex number 1 and annex 2, you will already know that deep learning is by far superior to any type of machine learning, let alone simple Q-learning. And that's why we're leveraging the power of deep learning here. So we're feeding in the information about the environment as a vector of values, so in this case just 2 values, into a deep neural network, and then we're using that to perform the actions that we want to decide which actions the agent's going to take. So that's kind of like a high-level overview of why we're doing this. And now let's have a look at, in a bit more detail, at what happens to the concepts of Q-learning when we make this transition from simple Q-learning into deep Q-learning. So as you saw in the previous intuition tutorials, we had a slide like this, which is the foundation of temporal difference learning. This is the formula for temporal difference. And basically, so let's go through this. So basically, we had an agent who was in this state over here, which is indicated by blue arrow. And we were understanding how temporal difference works for this Q value of, for instance, going up. And so what we saw here was before, this is in the simple Q-learning, not the deep Q-learning, this is in the simple Q-learning. What we saw was before, the agent had a certain Q value that he had learned about this action of going up. And so then he decides to take this action to go up. And right after he takes this action, he gets a reward for taking this action in this state. And that is that reward. Plus, now he can evaluate the value of the current state he's in, which is the maximum of all of the new Q values of all of the Q values of the new actions he can take, A prime, in the new state S prime. And we multiply it by the decay factor of gamma. So that is essentially the new Q value, or kind of like the empirical Q value that he has just received for taking that action. And ideally, these two should be the same. So the Q value that he had in his memory about this action in this state, it should equate to the actual reward plus the gamma times the value of the state that he ended up in. And therefore, that's how we calculate the temporal difference. We take what he got after minus what he had in mind, what he was expecting. You subtract one from the other, and that's your temporal difference. And then you use your learning rate alpha to adjust your Q value, your new Q value by the temporal difference, but with a coefficient of alpha. So that is the essence of the simple Q learning. Now let's have a look at how it changes in deep Q learning. And so we're still going to work with this slide, but we're going to just see exactly what's happening. So in deep Q learning, the neural network will predict 4 values. As we saw in the previous slide, and as we'll see further down in this tutorial, the neural network will predict 4 values, or it might predict more values if there's more possible actions in a given state. But in this case, we know that there's only 4 actions: up, right, left, or down. And so the neural network will predict 4 of these values. So there will be no, in a deep Q learning situation, it's important to understand there's no before or after. And this is how we'll get to know this a bit better. So the neural network will predict 4 of these values. And it will compare not to what will happen after, but the neural network will compare to this exact value, but it was this value which was calculated in the previous step. So in the previous time when the agent was in this exact square, so let's say, I don't know, some time ago, the agent was in this exact square as well, and it calculated this value previously. So in the previous time, a long time ago, the agent calculated this value. Then the agent stored this value for the future. And now the future has come. So now he's in the square again. And now he's got these Q values, which is predicted. And one of them is for going up. So now what he's going to do is going to compare the predicted value of Q to this value which he had recorded from the previous time. And we'll understand exactly why this is important right now. So just important to understand here is there's no before and after in this specific square, this specific time. We're taking the Q value that he's predicted using the neural network this time, and we're comparing it to this value, which he had from the previous time. From the previous time he was in this square, assessing all of the situation. And, the previous time he actually performed this action. So there we go. Now let's have a look at how this all works out in the neural network and why is it like that. I know it sounds a bit complicated right now, but we'll break it down into simple terms right just in a second. So this is our neural network. We're feeding in the states of the environment into the neural network. It's going through the hidden layers. Then it's coming out with these outputs, Q1, Q2, Q3, Q4. In that specific state, these are the Q values that the neural network is predicting for the possible actions. Those are the Q values. So then we're comparing to target. And these targets is exactly, so if we go back here, this is the target. So this is the value that was predicted. And then, but also we know that we have a target from the last time we were in the square. We have a target for this same action, which is up, for instance. So here we've got a target and we're going to compare. So we're comparing Q1 versus that target. We're comparing Q2 versus that target, the target that we had from previously. Q3 versus the target, Q4 versus the target. And so this is the part where the neural network or the agent is now learning through deep learning how to better go through this maze. And the key point here is that we're still applying Q learning, but the concepts in simple Q learning, you learn through temporal differences, which are pretty straightforward, which we've already discussed and we know quite well by now. But at the same time, in deep learning, how do neural networks learn? Well, neural networks learn through adjusting their weights. So we have to adapt the concepts of the concepts of simple Q learning to the way neural networks actually work, and that is through updating their weights. And so this is what we're trying to figure out here. How do we adapt that concept of temporal difference to a neural network so that we can leverage the full power of neural networks. And so far we've gotten this. So we enter our environment state here as a vector, goes through a neural network, we get predictions of Q values, and then from the previous time the agent was in that state, we have these Q target 1, 2, 3, and 4 for each of these respective actions. And so now we're up to, okay, let's compare each one with each one. And from here, it becomes pretty straightforward if you're up to speed with neural networks. Once again, that's all in annex number 1. We're going to calculate a loss, which is L here, and we're going to be Q target, this one, minus Q, minus this one. We're going to square that, so the square difference of each one of these, and we're going to sum them. So we're going to take the sum of the squared differences of these Q values and their targets, and we're going to sum them up, and that's going to be our loss. And so ideally, just as we had in the temporal difference learning, so if we go back for a second, remember we said, ideally, we want this to be equal to this. So we want the temporal difference to be 0. So that means basically the agent is predicting exactly correctly what, the Q values that the agent is predicting are exactly, or that he has in memory, are exactly descriptive of the environment. And therefore, the agent can navigate the environment pretty well, right? There's no surprises. There's no, as long as this temporal difference is highly positive or highly negative, then we've got some surprises. But if the temporal difference is 0, then he knows the environment so well that he can predict what's going on, and therefore his policy is going to be very good, and he's going to be able to navigate it. So here, same thing. So we want this loss to be as close to 0 as possible, as small as possible, and that's why now this is the part where we are going to leverage the real true power of neural networks. So we're going to take this loss and we're going to use backpropagation or stochastic gradient descent to take this loss and pass it through the network. Pass it back or backpropagate it through a network, and through stochastic gradient descent, update the weights of these synapses in the network. So that next time we go through this network, the weights are already a bit better descriptive of the environment. And that's exactly how it works. So here you have, if we go back, this is calculated, loss is calculated, and it gets propagated for the network. The weights are updated. Then the next time we get here, this happens again. And we get here, this happens again, and so on. And it keeps happening, and that's how this agent learns, or basically now it's a neural network, which is the brain of the agent, is learning, is becoming more and more descriptive of the environment, and therefore the agent is able to navigate the environment better. When we say descriptive environment, basically means that when we put in the states of the environment that the agent is in, we are more likely to get closer and closer to the actual Q values. And that happens because the Q values that we want and find the right action. And that happens because these Q targets are actually empirically derived. So how does he find these Q targets? That's actually this. So he actually observes, okay, so once I do take this step, what's the reward I get? And then what's the value of this state? So same thing as we saw previously in Q learning, in the simple Q learning intuition. So he learns this through trial and error, and then he constructs his network or updates the weights of his network in such a way that the predicted Q values are closer and closer approximating the target Q values. So very similar to the concept we discussed here in the simple temporal difference learning of the simple Q learning algorithm. So there we go. That's how the agent learns. So we're up to here. That's the learning part. Hello and welcome back to the course on AI. In the previous part, we talked about the deep learning, Q learning intuition. We started there, and in fact, we actually got all the way to this part, and where we talked about learning. And now we're going to move on to the actual acting part. So there's two distinct parts that we have to remember. So that's the learning part, but now he's done all of this. That's beautiful. Now he actually has to take an action. He has to decide what is he going to do. He's going to do action 1, 2, 3, or 4. And so how does he do that? Well, the way he does it is now, given those same Q values, so the Q values don't change. After we have these Q values, we've compared them, we've calculated the loss, we've backpropagated the error, we've updated the weights, but the Q values don't change in that whole process. So after we've got the Q values, they're fixed. We know what they are, so all of this happens, the network's updated, and now using those same Q values that we had, what we're going to do is we're going to pass them through a softmax function, And again, softmax is described in, I think, in Annex 2. And we'll talk a bit more about softmax further down or we'll talk about this action selection policy further down in the rest of this section. So just in a few tutorials. But for now, we're just going to say we're passing it through the softmax function. And basically what it does is it helps select the best one. It selects the best action possible. There's a small caveat to that. It's not just the best one possible. We'll talk about that in the action selection policy tutorial. But for now, let's just say it selects the best action from here. It says, okay, so Q1, the likelihood, basically we know the Q values. So it's predicted the Q values. So it can look at them and say, okay, so the highest Q value out of these, just as we did in the simple Q learning algorithm, it'll just look at all these four, say the highest Q value is this one, and I'm going to select that action. I'm not going to take those. And that's pretty much it. That's how it chooses which action to take, takes the action, and then all of this process happens again for the next state the agent ends up in our case, in the next square of the maze. But generally speaking, it's the next state. So there we go. That's how we feed in a reinforcement learning problem into a neural network through a vector describing the state that we're in. And once we feed it in, there's two parts of the process that happen. Part one is the learning. So remember that part where we compare each of the Q values with the targets, and then we backpropagate the loss through the network to update the weights so that our network is learning as we go through this maze or through this environment. And also the second part is, of course, we have to act. We have to select an action. And that is where we pass the Q values through the softmax function or basically an action selection policy, which we'll talk about further down. And then we simply select the action that we want to take and we perform that action. And then this whole process starts again. And then maybe the agent gets to the end. Maybe the agent doesn't pass the game. In any case, the game ends. And then once again, the whole process repeats. The agent plays the whole game again, and then that stops. So basically, that's another epoch. Every time the agent, every time the game ends, whether favorably or unfavorably, that's the end of an epoch, and then he starts again, and then he starts again, and then he starts again, and so on. So that happens, and this process happens for every single time the agent is in a new state. So the state is encoded here. So that's important. So not just for every single game that he plays, but for every single state. So he's in a state, it goes through this process, updates, and so on, and happens every single time. And so the learning happens, and then the acting happens as well. So that is deep Q learning or the intuition behind deep Q learning. We've got lots more to cover off. And then, of course, we've got the practical. And in the meantime, if you'd like to get some additional information on deep Q learning, we've got a recommended reading. So we've already spoken about Arthur Giuliani's series of blog posts. If you look at simple reinforcement learning with TensorFlow part 4, you will find the part that's relevant to what we discussed today. Note that here he talks about convolutions. We are not covering convolutions in this section. We're going to be talking about them in the next section of the course. So the difference here is that, so just kind of skip the convolutions part for now, and we'll talk about them in the next part of the course. But the difference is in convolutions, you're like your agent is looking at the image, and therefore he has to process an image, so an additional complication. For now, we're slowly, gradually building up to that. For now, we're encoding our environment through, so if you look here, we're encoding our environment, or maybe like look at this one probably, encoding our environment or encoding a state the agent is in as a vector. So in our case, there's a very simple vector of two values. Sometimes people, even in that simple maze, sometimes, or as you'll see from this blog post, sometimes people prefer the one hot encoded version of that state. So basically where every single box of the maze has so you have like a vector of, in our case, it would be 12 values, 3 by 4. So it's like either 1 or a 0, depending on which element, in which box you're in the environment. So in whichever way you decide to encode your environment and the state of your environment, that's how we're encoding it. So it's basically a vector. The key here is that it's not a convolution. So it's not like an image and there's no convolution involved. So this part will come later. For us, it starts over here. And that just simplifies the process for us to gradually understand better. And of course, don't forget that this blog post is written in TensorFlow and we're using PyTorch in our tutorials. So hopefully you enjoyed this quick intro into deep convolutional not convolutional yet, deep Q learning. And on that note, I look forward to seeing you next time. And until then, enjoy artificial intelligence. Hello and welcome back to the course on artificial intelligence. All right, so I hope you're enjoying the tutorial so far. We're nearly done with the intuition. You'll very soon get to the practical side of things. We've just got a few little things that we need to cover off. All right, so previously we talked about how we add neural networks into this whole equation of Q learning and take Q learning to the next step and turn it into deep Q learning. And today we're going to add an extra important feature which you will be coding in the practical side of things. So Hadlan and I decided that it's important for us to cover it off in the intuition side of things so that you're more prepared for it when it comes in the coding side of things. So as we discussed, we've got the network there. There's two parts that happen. First of all, it's the learning. So the network actually learns with every new state. It slowly updates its weights to get better and better and better at dealing with this environment. And then there is the acting inside the state. So after the Q values have been counted in the state, then one Q value is selected. So today we're still going to talk about the learning part. We're going to come up with a interesting feature that's going to, well, we're not going to come up with this feature ourselves, but we'll talk about a feature that is very important for deep Q learning, and that feature is called experience replay. All right, so here is our network. So we've just copied it over here. We've got that a loss that is calculated at the bottom is backpropagated through a network. And let's have a look at an example of what happens to understand the problem that we're dealing with a bit better. So here is an example actually from this course. This is a screenshot shot exactly from this course. This is what you'll be programming. This is a self-driving car that is driving through this along this road, and it has to learn how to navigate this road. And so what is, as we discussed previously, what is this in this state? And of course, the state is not just going to be x1 and x2. Adlan will describe a bit in a lot more detail what the state is. It is going to be a couple of parameters which relate to the angle of the car and some relative parameters, what the sensors are reading, and so on. So there's going to be more parameters than that to describe the state, but nevertheless, it's going to be a vector of values. It's going to go through a neural network, and then on the output, you're going to have some Q values. Again, there will be a different, depending on this environment, there can be a different number of actions, possible actions, but we're just going to, for simplicity's sake, leave it at 4, just for us to be able to understand a bit better what's going on here. So in this case, the question is so far, what is this input into this neural network? Or more specifically, how often do we trigger this neural network? How often does this neural network go through? Well, every time the car ends up in a new state. So the car makes a move, it ends up in a new state, and then all that data, all that information from about the state goes through the network. Q values are calculated. This error is calculated based on what we discussed in previous tutorials. This error is backpropagated through the network, weights are updated, then the car selects which action it wants to take, makes that move, ends up in a new state. In the new state, everything starts over again. And so basically this happens every time the car is in a new state. Well, have a look at this example. I specifically took this screenshot because it's very well illustrates the problem that is addressed through experience replay. And experience replay is not just something that we use in this course or in this specific problem. It is something that you will see used throughout, like on and over again in artificial intelligence algorithms, because it is so powerful and it's so important. So look at this car. This car in this problem or in this environment, its goal is to go from here to here and back. Its goal is to navigate its way here without crossing these walls which are made of sand. And so the car started over here, it went down, and its reward is based on how close it is to its target. So the car went from here, it went down, and kept going like this, along this wall. And what it's going to do next is going to turn, and it's going to keep going. Well, what we want it to do is keep going here. But let's think about it for a second. Once it got to this wall, every single time it moves forward, 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 and so on. It moves forward. So there might be like, depending on the structure environment, it could be like 100 moves here or 50 moves here. It just keeps moving forward, 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 forward. And nothing changes. Nothing really changes. Yes, it gets further away from this target, closer to this target. That's lovely. But in terms of the surrounding environment, not many things are changing. It's still that same wall. If you're sitting in the car, you've probably seen this situation when you're driving, and the whatever you're seeing is like the environment is so monotonous that you're just seeing kind of the same thing is just passing by. But imagine you're driving through a desert and you're just seeing the same thing. It's the same sand. It's the same sand. Nothing is happening. Nothing is changing. And so but every single time we're putting that state, that new state, into here. Yes, of course, something might be changing. For instance, you're driving the car and your GPS is showing you're closer to your destination. So one of these inputs is changing. But a lot of these other inputs, the sensors, for instance, which are on the car, they're not changing. And therefore, as you're driving, so in this state, you input the inputs into your neural network here, 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 and here, and here. All the time, the inputs are pretty much the same. And so if you keep inputting the same inputs, the same values, the same vector, or very similar vectors into your network, because there is no variety, the car will learn very well one thing. It'll learn very well how to drive along this wall, which is on its right. And so that's how the network will update, and it will get rewarded. It will slowly start getting rewarded for driving so well. It will be like, oh, okay, so up from here, it'll start learning. Oh, I'm doing so good. I'm doing even better. I'm doing it better. It will have this false perception that it's actually doing very well, even though it only learned how to drive along this wall. And so the neural network will become very adapted to driving along this wall, and then all of a sudden there's this curve and the car doesn't know what to do. And it completely doesn't fit in with this neural network. And even if it does adjust somehow, let's hypothetically say it passes this part and then it ends up on this wall, same thing is going to happen. It's going to drive from here, here, here. Okay, now the neural network is restructuring itself to adapt to this wall. And then bam, this thing happens. And then even if somehow it gets past that, it'll drive past this thing. And then same thing along these lines. So basically, it's like a very vivid example of a problem that what we have is that because the way we're using the neural network, updating it with every single state, once we have lots of consecutive states, they don't even have to be the same, but there is in environments, it's normal that consecutive states are somehow correlated or somehow interdependent. And we don't want that interdependency to bias our network. We don't want the car to just learn how to drive along like a straight line or along a curved line or like anything that you think that you can think of in life where an agent would be navigating an environment, wherever you can think of correlated or interdependent states that come after another, that can really mess up your neural network if you're just going to let the agent learn from that. And that's where experience replay comes in. What happens in experience replay is these experiences, so these states that it's in, 1, 2, 3, however many, 50 states here in a row, they don't get put through the network right away. They're actually saved into memory of the agent. And so, for instance, it saves all these, and at some point, once it reaches a certain threshold, which you'll be able to code, and Adlan will show you how to do that. Once it reaches a certain threshold, then the agent decides for itself, okay, it's time to learn. I have this batch of experiences that I have, and now I'm going to learn from that batch. And so it randomly selects a uniformly distributed, and uniformly is important here because that's something we'll talk about on the next slide. We'll mention that, but it takes a uniformly distributed sample. So basically all experiences are considered to be equal. It takes a uniformly distributed sample from that batch of experiences that it has, and then it goes through them and it learns from them. So it doesn't take all the experiences, it just takes a uniformly distributed sample. So it might take a couple from here, a couple from here, a couple from here, and each experience is characterized by the state it was in, the action that it took, the state it ended up in, and the reward it it achieved through that action in that specific state. So 4 elements in each experience: state 1, action, state 2, and reward. And so it takes all those experiences and then it passes them through the network and it learns. And that way it breaks the pattern of that bias which comes from the sequential nature of the experiences if you were to put them through the network one after the other. So that's the main focus of experience replay. That's what the problem it addresses. And another benefit of experience replay is that sometimes in an environment like this, you might have very valuable, rare experiences. So, for instance, I don't know, let's look at this corner, right? This is a right corner, right? And a very sharp one. How many sharp, so it'll be coming from here, assuming it's going to be hugging this corner. So how many sharp right corners do we have in this whole environment? We only have one right corner here and one right corner here, right? So when it's coming this way, that's a right corner. And then when it's going back, it's a sharp right corner here. So, and this one's not sharp, this one is sharp. So there's only one opportunity in the whole environment to learn from a sharp right corner. And that's an important experience because it might get really good at driving along straight lines, get really good at doing like soft corners like that, and then it will keep messing up this sharp right corner simply because it doesn't have that much opportunity to learn from it, and so therefore it will learn everything else pretty quickly, but it'll take a long time to learn this right corner. It's a very simplified example. It's a very simplified explanation, but it illustrates the concept that sometimes there are rare experiences which can be valuable. And if you're just doing a simple neural network where you're putting in your values here and they're going through, and like even if we forget about that problem of the sequential nature of experiences and how they can be interdependent or correlated, even if we forget about that for a second, what happens is once you put an experience in, it goes through, the network's updated, then you instantly forget about that experience. You move on to the next one. That's just how the neural network works. Then you move on to the next state, the next state, the next state, the next experience, next experience, next experience, and so on. So this right corner, as soon as it goes through the network, it's gone, and you don't have any memory of that valuable experience. Whereas with experience replay, because you're putting these experiences into batches, you can organize your batch as a rolling window. So for instance, you could have like 100 batches, so 100 experiences in your batch. So when it's coming back from here, it's as soon as it has this recorded this experience in its batch, then like at some point it takes a uniform distribution from its batch of experiences, and then there's a rolling window. So it forgets these experiences, but then it keeps these experiences. And then again, it learns from, once it's here, it learns from this batch. And then once it's here, it forgets all the way up to here, but then it has a batch of experiences like that. So therefore, now it learns from these experiences. And that way, what you're getting is that this right-hand corner, it might come up several times in its learning process because it was in that batch when the batch was like this, around there, then it was in the batch here, in the batch here. So it came up in several batches because a batch might be updated as a rolling window of experiences. So the older experiences get kicked out, the newer experiences are added, and then again, older experiences get kicked out. So an experience it stays in the batch for quite some time, and the car or agent can learn from that experience several times. So that's another advantage of experience replay. And of course, the final advantage is experience replay gives you an opportunity to learn from more experiences than if you're just learning from one at a time, because you have that batch, and therefore, and it's a rolling window, and therefore, even if your environment is limited to experience, your experience replay approach can help you learn faster. And instead of just redoing the environment many times, you can learn faster because you don't have to redo it. You have those experiences saved. So those are the main advantages of experience replay. Let's recap on them. We've got we're breaking the pattern of independence and correlation of sequential experiences. We save rare experiences which might be important, and therefore we can learn from them more often. And we can learn in environments. We can learn faster in environments which are experience, which have a shortage of experiences, or which don't have that many experiences that the agent goes through, and still we can be able to learn them. So that is what experience replay is all about. If you'd like to read a bit more, then there's an interesting article published by DeepMind in 2016. It's called Prioritized Experience Replay, and it talks about why are we using a uniform distribution to select our experiences from the experience batch? Why don't we find a better way to select our experiences and prioritize some of the experiences which we feel that are important? And so it's quite an interesting thing. So in this case, you will be able to not only reinforce your knowledge on experience replay, but you'll actually be able to move with the cutting edge of technology. So this is 2016 and published by DeepMind. So it's a very recent, very powerful paper. So you'll be able to actually explore the limits, or explore even further this algorithm and take it to the next level. So I'll leave it up to you to find out why and how we can change the uniform distribution to a different approach to experience replay from this paper if you'd like. And I hope you enjoyed today's tutorial, and now we know what experience replay is, and we can confidently use it in our practical tutorials. And I look forward to seeing you next time. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. I hope you're enjoying the course so far, and today we're talking about action selection policies. All right, let's dive straight into it. Previously, we talked about adding a neural network to our simple Q learning, and so far we're getting quite into deep Q learning. We've talked about the learning part quite a bit, including adding some elements to it, and today we're talking about this part. We're talking about the acting. So let's have a look. So here we've got what we discussed about the acting, that once you input the values, the parameters or the vector describing the state the agent is currently in that environment, then that is after all the learning is done, or even before the learning is done, basically we get all the Q values. So we're not interested in the learning right now, we're interested in the acting. So once we have these Q values, how do we understand which one we need to use? Well, if you think about it, Q values are simply, these are the predictions for the Q values. So as we did in the simple Q learning algorithm, what did we do? We just selected the one with the highest Q value. Once we have the one with the highest Q value, we just take that action because it just brings us the highest Q value, and that we know that Q value is calculated as the immediate reward that we expect to receive plus the decay factor times the value of the next state, and it's a recursive calculation. So why not? Why wouldn't you take the best Q value, and that's kind of the end of it? But as you can see here, it's not as simple. Here we're using a softmax function, and this is where we're going to talk about action selection policies. So here, in reality, we don't have to have just a softmax function. We can have different action selection policies. For example, we've got epsilon greedy, epsilon soft, and we've got the softmax. And those are kind of like the most commonly used action selection policies. Of course, there are others. For instance, the most basic one is, here's a very simple action selection policy. Just select the best, the one with the highest Q value. But why doesn't that action policy fly? And why do we have different types of action selection policies? Well, it all boils down to exploration versus exploitation. And that is the core of reinforcement learning, because we've already talked about this a little bit, that your agent, when it's operating in an environment, it might predict certain Q values, which might be good, and it might not turn out great. It might turn out that those Q values are bad, and it'll be forced to explore. So if we, for instance, in this case, predict that Q2 is the best one, and then it takes Q2, takes action 2, and so from here it takes action 2, and then it gets a very negative reward. Then the environment is forcing the agent to go and explore, because now it's going to learn that, oh, actually, I thought Q2 is going to be very good, but it turned out very bad. So the result turned out very bad. So the network is going to update itself. So next time he's in this state, he might still choose Q2 if it was, if it was very, very favorable. So you might think that's like, he might need a couple of penalties, punishments in order to learn that Q2 is a bad action. But maybe he'll already soon learn that, okay, I'm going to take a different action. I'm going to take this action because now it has the best Q value. So sometimes the environment forces the agent to take to explore different actions. But sometimes the agent might find itself stuck in a local maximum. It might find that it found, like through its initial exploration, it found that, oh, this is a pretty cool action. Like, I'm going to go right here. And that's a pretty cool action. But the problem is that it thinks it's the best action simply because it hasn't explored. It's explored going up, it's explored going left, It's explored going right, but it hasn't explored going down from that specific state that it's in. And now that it's kind of like biased towards this action, it thinks it's a good action, it's going to keep taking, it's going to keep getting, it's going to keep taking this action, it's going to keep getting a good reward. But what if this action would have been even better? If this action would have been so much better that if it knew about this action, it would actually switch to this action. But because it got stuck in a local maximum and it's getting these good rewards, it's just going to be reinforced. It's just going to keep reinforcing itself that, or the environment is going to reinforce it that this is a good action to take, keep doing that. But the reality is that there's this other action that it hasn't found yet, or hasn't even explored, that would have been much better. And so what we want to do is we want to come up with an action selection policy that allows our agent not to get stuck in a local maximum. Yes, it's important to keep doing the good actions. That's the exploitation part. We want to exploit what we've found, but at the same time, we still want to explore. We never want to stop exploring. It's like in life, you never want to stop learning. You stop learning, you die. There's a saying like that when you're not growing, you're dying, or something like that. So you want to keep learning, and your agent wants to keep learning, and that's where these action selection policies come in. So we've got 3 listed here. So the first one is epsilon greedy. It's a very simple one. It sounds pretty complex in the sense that like it's got a cool name, and usually things with such cool names are complex. It's actually not. So basically what it does is it will select the one with the best Q value. And epsilon greedy, you might hear it in other places. It's just like a selection policy. So in this case, we're using it to select our out of our Q values out of our action. So you'll select the one with the highest Q value all the time, except for epsilon % of the time. So for instance, if you set epsilon to 10%, then you're going to, or 0.1, then 10% of the time, the action is going to be selected at random. So 90% of the time, you're still going to be selecting the best action based on the highest Q value, but 10% of the time is going to be selecting a random action. Uniformly, just going to be absolutely randomly taking an action. Or if you set epsilon to 0.5 or 0.05, that means that 95% of the time, the agent is going to be taking the action with the highest Q value, but 5% of the time, it's still going to be selecting a random action. So it's going to be going out there and exploring. So epsilon soft is very similar. Oh, by the way, that's kind of like why it's called epsilon greedy, because you're greedily selecting the action, the good action, except for that little epsilon % of the time. So the lower the epsilon, the more greedily you're selecting that kind of the action that is the optimal action, and the less you're leaving, less chances you're leaving for exploration. Epsilon soft is the opposite. So basically, you're selecting at random, you're selecting 1 minus epsilon % of the time. So if your epsilon is like 0.1, so 10%, then only 10% of the time you're taking this action, and 90% of the time you're selecting a random action. So very, very simple, just inverted algorithms. And softmax is kind of like the next step from, or it's a more advanced version, I would say, of the epsilon greedy algorithm. Although they both have merit and they both have place, we're going to be using softmax in our coding, in our practical side of things. So that's why we're going to talk in a bit more detail about softmax. So let's have a look. So let's move on to softmax. Hopefully it's pretty clear about epsilon greedy. It's a pretty straightforward algorithm. Select this one most of the time, except for sometimes go and explore. And now we also see why it's important to do that exploration, so that we don't end up in local maximums in our optimization process. So now we're going to talk a bit more about softmax. There's a tutorial on softmax at the end of the course. I think it's in annex number 2, where we talk about the concept behind softmax. I'm just going to refresh a little bit here. So there we're talking about convolutional neural networks. And by the way, we aren't going to be covering we're not covering convolutional neural networks in this section of the course. In this section, we're still using a vector. But in the next section of the course, when we're creating an AI to play Doom, we are going to be using convolutional neural networks. So it could be beneficial for you to look at convolutional neural networks and then take the softmax function, or you can learn a bit more about softmax after you take the convolutional neural networks annex of the course later on. But here's a quick refresher. So here we've got a convolutional neural network which decides whether it's a dog or a cat. So here we've got the voting process between these neurons, and this one says that it's got the features, the fluffy ears, the pointed face type of thing, and the kind of like the features, the types of eyes, the way the eyes look, all these features that belong to a dog. So it's a 95% chance that it's a dog and a 5% chance that it's a cat. But the question is, how did we get, and in that tutorial, we're talking about how did we get these values to add up to 1? Well, whatever the convolutional, or our whole neural network, so the convolutional neural network plus the fully connected layers, whatever it's spat out, whatever the values it spat out, we applied a softmax function over here. And this is where we introduced the formula for the softmax function. This is what it looks like. And then we got these values. And so basically that's a quick refresher. This is the formula for the softmax. What it does is it takes however many outputs you have, doesn't matter. It will take them and it will squash them all into values between 0 and 1, regardless of how big they are. Just by looking at this formula, you can see that there's a total sum at the bottom. So these values are going to be between 0 and 1. And also all these values are going to add up to 1 always. And so that's very beneficial for us because when we're using the softmax function, what happens is we get these Q values. We select this best Q value, but in reality, what happens is these Q values that we get, they're actual numbers, right? So there's some kind of numbers. They don't have to all add up to 1. They don't have to be between 0 and 1. Just some numbers. But when we apply softmax, we don't just select the best one. We actually get numbers like that. So we get numbers in the range between 0 and 1. And that also add up to 1. And so what other thing do we know that adds up to 1? Well, probabilities. We know that probabilities always have to add up to 1. So that is why we can say here we've got Q values, but here all of a sudden we've got we've got probabilities. So we can say that the likelihood of this being the best action is 90%. This being the best action is 5%, 2%, 3%, because we know the higher your Q value, the better the action. And so if we squash them to 0 to 1, then these become probabilities and we can deal with them as such. And therefore, now is when the action is selected, and that's how we come up with Q2. But if you look at it closely, this isn't a strict 100%, and these are not strict 0%. So this is a 5%, 2%, 3%. So the most natural way to apply the softmax in order to preserve exploration in the algorithm is to use these exact probabilities as how often we're going to be taking that action. So these probabilities actually represent the distribution of these actions that we're taking. So basically, softmax makes it very easy for us to come up with a way to combine exploitation and exploration. So the best action will always have the highest probability because it has the highest Q value, and therefore here we're going to use these as our distribution, and we're going to say, okay, we're going to be taking Q2 90% of the time. But 5% of the time, we're still going to be taking Q1, and 2% of the time, we're going to be taking Q3, and 3% of the time, we're going to be taking Q4. And the beauty here is also that as these values update, as the agent goes through the network more and more and more, it becomes more familiar with the environment, and therefore these updates. So this value, for instance, might become like it might ascertain that this value is actually less or this actually is higher, and so these probabilities will also change as an agent goes through. So even though here we've got Q2, nobody is to say that sometimes 5% of the time, to be more precise, we'll be selecting Q1 as the action to take. And sometimes, or action 1 will be taking action 1. Sometimes we'll be taking action 3, 2% of the time, and action 4 will be taking about 3% of the time. So every action has a chance to play in this process as long as we have enough iterations and the agent goes through lots and lots of times through these states that they're in, and that's how any kind of deep learning algorithm works, that you want to do this many times so that you learn from experience. And therefore, as you can see here, it's a very natural transition to, we're not just randomly, like in the epsilon greedy algorithm, we're not just randomly selecting the actions, we're selecting them based on their softmax values, which makes it like has some logic behind it, not just at random 10% of the time we're selecting a random action, but there's some logic behind how we're doing it and based on the Q values that we've explored. And so that's the action selection policy that we're going to be using in this course. You're welcome to definitely check out the epsilon greedy action selection policy if you like, but we're going to be predominantly using the softmax action selection policy. And I've got an interesting reading for you. So this is called Adaptive Epsilon Greedy Exploration in Reinforcement Learning Based on Value Differences. It's a 2010 article, and it's interesting because Mike Michel, I'm not sure how to pronounce it, Michel or Mikel Tokic, introduces a different type of algorithm, so an adjusted epsilon greedy algorithm, and called the VDBE algorithm, or epsilon greedy VDBE algorithm. You can see it over here, and he actually compares it to the epsilon greedy and softmax, and it's an epsilon greedy algorithm, which basically the main idea behind it is to adjust the value of epsilon depending on the state the agent is in. So if the agent is very certain about the state they're in, then epsilon should be smaller, so there should be less exploration. If the agent is uncertain, epsilon should be higher, should be more exploration. So it is a 2010 article. I'm not sure if this new proposed algorithm is widely used or has been accepted in the community, or if artificial intelligence has moved kind of away from this suggestion. But nevertheless, it will definitely help you reinforce your knowledge about action selection policies, which we discussed. The epsilon greedy and the softmax will help you. It'll give you an opportunity to compare them side by side and also see in which direction people actually think when they want to improve artificial intelligence. So if you're ever planning on creating really interesting algorithms that are pushing the edge of artificial intelligence and pushing the envelope in this space, then this could be a good way for you to see in which direction people think sometimes when they're trying to improve the norms of artificial intelligence, or the norms that existed back then in 2010. So there we go. Hopefully you enjoyed today's tutorial about the action selection policies. We learned about epsilon greedy, epsilon soft, and the softmax. And now you're even more prepared for the practical side of things. And on that note, I look forward to seeing you next time. And until then, enjoy AI.
Hello my friends, and welcome to the practical activities of this Artificial Intelligence A to Z course. My name is Adlan de Ponteves. I'm the second instructor of this course who will be doing all the practical activities with you. And the reason I'm starting from this Gmail page is because I want to do everything from scratch so that you don't miss any step while setting up your AI environments. Alright, so as you can see, I literally just created this new email address, artificialintelligenceatoz@gmail.com. because indeed we will be building the different AIs of this course in Google Colab. And in order to implement code in Google Colab, well, you need a Gmail address. So that's why please make sure to at least have a Gmail address. I just created one. It took me a few minutes so that we can set up Google Colab. And now, why did I choose Google Colab to implement the AIs together? Well, that's for a very simple reason. It's just in order for us to not have to install any packages, because if we implement this, for example, in Jupyter Notebook or another IDE like Spider, we will have to install a lot of packages and this will be a lot of hassle. While if we implement the codes of our AI in Google Colab, well, you will see it's super easy, because in Google Colab Notebooks, you will see that most of the packages we'll use are already pre-installed. For example, PyTorch is already pre-installed, which is the framework with which we're going to build our AIs, and many other packages are already pre-installed. And even if we have to install some packages, well, this will be super easy. You will see you basically won't have any trouble getting the required packages to build our AIs. So that's really awesome. If you're a beginner in AI, trust me, we should totally do this in Google Colab. And speaking of Google Colab, well, right before this tutorial, I gave you a link. I actually just copied this link, so I'm gonna paste it right now with you so that I can start from scratch with you. So I'm gonna paste this link in a new tab. Here it is. I'm entering it, and this will take us to the folder containing all the codes of this AI A to Z course. And so it's divided in three parts. Part 1, Deep Q Learning, containing the Deep Q Learning code. Then part 2, deep convolutional Q-learning containing the code that implements the deep convolutional Q-learning model. And finally, part 3, containing the code that implements the A3C model. All right. And of course, right now we're going to start with part 1, deep Q-learning. And so if you go inside, you will see 2 notebooks, one with the complete code that implements the whole AI with all the results and everything, and one that contains the partial code, meaning the code not related to building the artificial intelligence. And that's actually going to be our starting point. We're going to open this notebook right now. Please open the notebook and you will see that inside I kept all the code cells that are not related to the core of the AI so that we don't have to re-implement them. Like, for example, installing Gymnasium, which I will introduce you right away. It is basically our playground for building the AIs. Then importing the libraries, right? We will not re-implement this together. This is not really essential. However, everything that has to do with building the AI or training the AI, well, we will implement all of this together so that you really understand how to build an artificial intelligence. All right. So that's what we will do. And then in part 3, as you can see, we visualize the results and that it's not really essential. We don't really have to implement this together. So I left the code in this partial code notebook. Okay. So we're going to have a lot of fun implementing these code cells, to create the architecture of the neural network of this first AI and then training it in these different steps. This will be super exciting. I can't wait to start the implementation. Now, before we finish this tutorial, I just want to introduce you to our playground, which is called Gymnasium. It's an amazing platform where you can build different AIs for different environments. I'm going to quickly introduce you to the essential one. So let's start with the basics. Classic control, that's where you can build an AI, for example, to do the cart pole or the mountain car or the pendulum. Okay, so we won't do that. This is too classic. I want to do something more exciting and advanced. And well, speaking of which, let's have a look at the Box 2D environment, which is what we're going to use for module 1 with the deep Q-learning model. Because indeed, with this whole popularity of SpaceX and building an AIs for space, well, I chose the first environment for our first AI to be Lunar Lander. And in this one, as you can see, we'll train an agent, which is this spaceship here, to land properly on the moon, between these 2 flags here. So this is going to be pretty fun. That's going to be for module 1. Then for module 2, we're going to have fun with the Atari environment. But first, let me quickly show you, the other environment. So you have toy text also, where you can, for example, train a taxi, like a self-driving car, to navigate in a map. Then you have the Mujoko environments, which are pretty cool, but which I covered in another course, so we won't use them for this course. But for example, you can train an ant to walk on a certain field, or a half cheetah to walk, or even a humanoid to walk. This is covered in other courses of ours, so we won't do that in this course. But what we'll do is even more fun, in my opinion. You'll tell me what you think. We're gonna train some agents to play the famous and popular Atari games. You remember when we were kids? We used to play those games, and well, that's exactly what we're going to redo today, but this time with an artificial intelligence. And so, for module 2, what is the game I chose? Well, let me show you. Let's click see more environments here. I chose for module 2. I'm sure you know this game. I'm sure you played it in your childhood or even still now, because personally I really like it and I would still play it today. I'm talking about, let's see where it is. I'm going to scroll down a bit more. I'm talking, of course, about Pac-Man. We're going to train an artificial intelligence to play Pac-Man in module 2. And then finally, what did I choose for the last AI we're going to build in this course, the A3C model in module 3? Well, I chose something that we probably all like. I don't know if you liked the Matrix movie with this famous quote of Neo saying, "I know Kung Fu." Well, in module 3, we're going to train an AI to be able to say, "I know Kung Fu." Because indeed, the environment that I chose for module 3 is exactly this one. Kung Fu Master. We're basically going to train an artificial intelligence to be able to fight Kung Fu against another agent. All right? I hope you're excited about all this. That marks the end of this introductory tutorial on all our practical activities we'll do in this course. And of course, at the end, we'll also have another practical activity for LLMs. This will be a lot of fun because this is the AI of today that you also need to know how to build and how to handle. So there you go. I look forward to now starting the implementation of our first AI for our first module, Deep Q-Learning for Lunar Landing. Hello my friends and welcome to this new tutorial of module 1 on Deep Q-Learning for Lunar Landing. So in the previous tutorial, we got access together to this partial code of our deep learning implementation. However, now we're going to start coding, we're going to start running the cells, and therefore it's very important to understand that this notebook here is a read-only notebook. Therefore, you can't make any modification, and that's for the obvious reason that you all have access to this notebook, and therefore no one should modify anything. However, now we will create your own copy of this notebook, which will be created inside your Google Drive folder. And that's exactly why I told you in the previous tutorial that you need a Gmail address in order to use Colab. Because indeed, in order to use Colab, you need to have a Google Drive, which you can only have with a Gmail address. All right. So let's create this copy now. To do so, we simply have to go to File here and then click Save a Copy in Drive, and this will indeed create a copy of this notebook inside your Google Drive folder. I'll show you right away exactly where it is. So actually, if you open a new tab here and then go to your Drive, well, you will see this new folder, Colab Notebooks, inside which you will find, well, this copy of our deep learning implementation that you just created in your Google Drive. All right. And this one, you can modify it. And so now what we're going to do is rename this. We're going to remove the copy here because it's anyway now in your own Google Drive. And now if you want, what you can do is create the same structure of the course, with those 3 folders. Feel free to do that if you want to. Or, you can just keep your different notebooks in this Colab Notebooks folder, just like that, okay? Feel free to do however you prefer. And so now we're going to go back to, well, this notebook copy we just created. If I refresh it, it will be renamed Deep Learning for Lunar Landing Partial Code. And now we can modify it because now it belongs to our Google Drive folder, and therefore we are the owner of this notebook copy. All right, and that's it. Setup done. We can now start the implementation. Not only that, we can also run the cells. And speaking of which, well, that's going to be our first step here. The first cell we have to run is to install Gymnasium, because as I told you in the previous tutorial, indeed, most of the packages are already pre-installed inside Colab, except some of them like Gymnasium. So here we're going to install Gymnasium. Then we're going to install the Atari environments from Gymnasium. And then same for the Box2D environments from Gymnasium. All right, so this will just install this. I'm going to show you right away that this will work with no issue at all. In order to run the cell, you simply need to click this play button to run the cell, and you will see that it will install Gymnasium and the environments here of Atari and Box2D with absolutely no issue. Let's check it out. Now, as you can see, it's downloading some, dependencies and packages, installing collected packages, Farama notifications, successfully installed Farama notifications. Now downloading another license, which is needed for Gymnasium and the different environments. It also downloaded Shimi, AutoROM, installing build dependencies. You see, you have nothing to worry about. Everything is getting installed successfully with absolutely no issue. Whether you are on a Linux or Mac or Windows, you don't have to worry about, opening a terminal or command prompt and installing the packages that we will use for this course. Here, nothing to do. Everything is fine. Now it's installing the Box2D environments for Python. And in a second, we will have everything, Gymnasium related installed properly for this notebook so that we can build and train our AI in the Gymnasium environments. Now it's almost done, should be done in a few seconds, and then we'll be good to go to run the next cell to import the different libraries. But let's just wait for this to finish. It's going to be finished imminently now. And there you go, successfully build Box2D PY, installing collected packages, Swig Box2D PY, and there you go, successfully installed the Box2D environments and the Atari ones. Alright, so you see, no problem at all. That's the beauty of Google Colab. We just have to run a cell and this installs everything without having to open any terminal or command prompt. Alright, now let's run the next cell, which is about importing the libraries. So let me quickly explain what the libraries will be used for. So this is for the operating system. This is because we will use some random parameters, random variable generators. This is NumPy in order to work with arrays and mathematics. This is of course the Torch library because we will build and train our AIs with PyTorch. Therefore, we import the torch library first, then we import the NN neural network module from the torch library, then the optim module for the optimizer when training the AI, again by the torch library, then functional because we will use some functions during the training, again this is from the neural network module by the torch library, autograd, same, another module by the torch library for the training again, more specifically stochastic gradient descent. Then variable in order to create some torch variables, we will see that later on in the course, and then finally these modules from the collections library, which will be used indeed during the training. Alright, so let's run the cell as well. In order to do so, we simply have to click this play button to run the cell, and this will import all the libraries. And by the way, as you can see, we didn't have to install any of these libraries. That's exactly what I was telling you in the previous tutorial. All these libraries are already pre-installed within Colab. So we don't even have to do those pip install, right, like we did for Gymnasium, for the torch libraries, right? That's the beauty of Colab. Here, everything is already pre-installed, so we only had to import them. All right, so that's it. That's it for the setup. Now we are ready to do our first implementation in part 1, building the AI, and more specifically, creating the architecture of the neural network. And well, that's exactly what we'll do in the next tutorial. So are you ready to get your hands on building an AI? If yes, well, join me in the next tutorial where we'll create the architecture of our first AI here, which will be trained later on to land properly on the moon. Hello my friends, and welcome to part 1, building the AI, where we're going to create the architecture of our neural network. Are you ready? Let's do this. So we're going to create a new code cell here, inside which we're going to create a class, which will therefore contain the whole architecture of our neural network, meaning the brain of the AI. So here we go. We start with class, then we're going to name this class network, or you could call it neural network or brain if you want, because it represents the brain of the AI. And then we're just going to use a feature of object-oriented programming, which is inheritance. I recommend to look online if you don't know what it is, which basically allows us to inherit from the tools of another class, which is the module class from the NN module, so that we can build a neural network. All right, so how does it work? Well, we call our NN neural network module, from which we're going to call another class, which is called the module class, which is the class from which we want to inherit all the features of this class. All right, so let's press enter, then let's add a colon, and then here we go. We're going to start, of course, with the init method. All right, just like in any class. And well, I just pressed enter. You see, that's the assistance of Google Colab. That's good. You probably got the same, so there we go. What do we have to input here in this first argument? Well, it's going to be the state size. What is the state size? That's simply the number of inputs in a state. And to exactly know where it is, well, we have to have a better look at our environment, which I remind for module 1 is lunar lander. We're going to train an AI to land properly on the moon between those two flags here. And well, here is a nice description of the lunar lander environment. What is the action space? Discrete 4. That means that our AI has 4 possible actions that it can play. And then for the input, well, let's see a better description here of the observation space. As you can see, the input state is a state of an 8-dimensional vector, which are the coordinates of the lander in x and y, then its linear velocities in x and y, so that's for its speed vector basically, but we also have its angle, then its angular velocity, and 2 booleans that represent whether each leg is in contact with the ground or not. Alright, so that's the whole observation space, an 8-dimensional vector describing at each time step, well, the state of the AI, the agent. All right. And then we can also see a better description of the action space. I remind that there are 4 actions. The first one is 0, do nothing. The second one is 1, fire left orientation engine, basically move to the left. Then second action of index 2 is fire main engine, basically continue in the same direction. And then finally, last action of index 3, fire right orientation engine, meaning move towards the right. All right. So you see better how the action space and the observation space is described. Then we'll have a look at the rewards when we do the training. But for now, we will only need those information of the action space and the observation space. So here we go. Let's go back to our implementation. And therefore, here, as we perfectly understood, well, the state size is going to be 8. But we don't have to specify 8 yet. We will do when we call the network class later on in the training. All right, then this argument is going to be for the action size, which I remind is, as we just saw, 4, right? 4 actions. And then we're just going to add a default seed of 42, just to fix a seed for the randomness. And we'll see if we use 42 in the future. Then here, that means that nothing will be returned. And actually, you can either choose to keep it or delete it. And then here, next row, well, the purpose of that row is to activate the inheritance. Here, we don't have to specify anything in the init function. However, in super, we're going to enter as argument network and self. And that's just in order to activate the inheritance. All right, and now that's where things get interesting. That's where we're going to start building the architecture of the neural network. But first, we're just going to activate the seed super quickly with self.seed equal, and then we're going to use a function by the torch library, which is going to be manual seed. We're going to find it here. There we go, manual seed. And then, of course, in parentheses, we're going to enter the seed argument that is right here in our arguments. So that's just to generate some random factors. And now, there we go. We start with the architecture of the neural network. All right, so let's do this. Let's start from the first full connection between the input layer and the first fully connected layer. And therefore, the first variable I'm creating here is going to be FC1, representing the first full connection between the input layer and the first fully connected layer. All right, and so how do we create that? Well, we call our NN neural network module, from which we're going to call the linear class, which we can get thanks to the inheritance from NN module. And what do we input in this linear class? Well, first, the first argument is the number of neurons in the input layer, basically the state size. And then the second argument is going to be, of course, the number of neurons in the first fully connected layer. All right, so for the first argument, there we go. We enter the state size. Perfect. And then, now, big question is, what is going to be the number of neurons in the first fully connected layer? Well, there is no rule of thumbs to immediately tell what is the optimal number of neurons in the first fully connected layer. I'm just telling you that there was a lot of experimentation to build a performance AI that manages to land properly on the moon. And the optimal number of neurons that was found for this first fully connected layer is actually 64. All right, but of course, there was a lot of trial and error before finding that optimal number of 64. Okay, and that's it. That's it for the first full connection, FC1, going from the input layer to the first fully connected layer. So now I'm going to copy this. I'm going to paste it just below in order to create the second full connection. There we go, FC2. And so now, according to you, what is going to be the first argument here? Well, that's obviously going to be the number of neurons in the first fully connected layer, therefore 64. And then, what is going to be this number here in the next fully connected layer? Well, that depends if we want to have just one fully connected layer or another one. If we want to have just one fully connected layer, then the number here would be the number of neurons in the output layer, meaning the number of actions, meaning 4. Or if we want to have another fully connected layer, well, we would have to specify the number of neurons in this new fully connected layer. And well, actually, again, through a lot of experimentation, trial and error, we realized that the best architecture contains a second fully connected layer, which actually contains, again, 64 neurons. So we actually keep it like that. That's our second full connection between the first fully connected layer and the second fully connected layer. And so now, finally, I'm going to copy this line again and paste it right below. I'm going to call this third full connection, of course, FC3. It is going to have as a first argument the number of neurons in the previous fully connected layer, therefore 64. And however here, what is going to be the new number of neurons? Well, again, the question is, do we want another fully connected layer? And this time, no. Actually, the best architecture contains two intermediate fully connected layers between the input layer and the output layer. So there we go, we stop here. We can directly finish with the output layer containing the action size. And well, therefore, the argument here is going to be action size, which I remind for our lunar landing environment is going to be 4. All right, but for now we say action size. All right, and that's it. That's it for the architecture of our neural network. Congratulations, you just built a powerful neural network, which is actually the brain of our AI, which then will return some action to try to land on the moon. So that's going to be it for this tutorial. In the next tutorial, we will make another function to forward propagate the signal from the input layer to the output layer. I can't wait to do that with you in the next tutorial, and until then, enjoy AI. Hello my friends, and welcome to this hands-on tutorial where this time we're going to build the forward method inside this network class, which will forward propagate the signal from the input layer to the output layer through our two fully connected layers. Alright, let's do this. So we're going to call this function forward, which is going to take as input, well, first self, and then, according to you, what is the main argument that this forward function will call as input? Well, that's of course going to be the state, because it's going to propagate the signal from the state to the output layer in order to play a certain action at a certain time step. All right, so here we go. First, we're going to propagate the signal from the input layer to the first fully connected layer. And how we're going to do that? Well, we're going to use our FC1 object, right? Because this is an instance of the linear class, therefore returning the first fully connected layer. And so right here, I'm going to take this self.fc1, the first full connection. I'm going to paste that here. And of course, it takes as input the state, the current state at a certain time step in the environment. And since fc1 state actually returns the first fully connected layer, well, we're going to create a new variable here, which will contain exactly what is returned by self.fc1 state. Then we're going to have to activate this signal thanks to a rectifier activation function. And to do so, we're going to update the value of x by calling first the f shortcut that we actually imported before when we imported the libraries. It is right here. It is actually the functional module from the NN module by the Torch library, which we shortcut as f. Okay, so that's just in order to call the functional module. And so from this functional module, we're going to call one of its functions, which is the relu function, representing, of course, the rectifier activation function, which takes as input x. And that, meaning these two lines of code, actually propagate the signal from the input layer to the first fully connected layer with a rectifier activation function. And so now we're going to copy this because we're going to do exactly the same for the second part of the forward propagation, meaning from the first fully connected layer to the second fully connected layer. And so I'm copying this, and here of course we just have to replace fc1 by fc2, and then of course state by x, because the second full connection fc2 takes as input the signal from the first fully connected layer and will return the signal in the second fully connected layer. And then of course we keep this, we're going to still activate our neurons in the second fully connected layer with a rectifier activation function. Alright, perfect. And now let's take care of the final part of this forward propagation, which is to finally return the final signal in the output layer containing our actions. And to do so, well, we can finish with a return, and then we call our third full connection fc3, which takes as input, of course, x, which is now fully activated with our rectifier activation function through the first fully connected layer first, and then the second fully connected layer. And there we go. That forward propagates the signal from the input layer containing the state to the output layer containing our actions, and we're done basically creating the architecture of our neural network. Alright, so you see the beauty of PyTorch? We created this architecture super efficiently. We now have our brain, we now have the brain of the AI, which therefore is able to be trained in part 2, training the AI. So whenever you're ready, let's do this. Now we're not going to forget to run our cell, right? This beautiful cell we just implemented together. So here we go, we just have to click this play button here to run the cell, and perfect, the cell was executed successfully. Alright, so join me in part 2 to train the AI whenever you're ready, get some energy, and I'll see you super soon to start this training implementation. And until then, enjoy AI. Hello my friends, and welcome to part 2 of this implementation, training the AI. We have just built the brain of the AI in part 1, building the AI with the architecture of the neural network composed of two fully connected layers between the input layer and the output layer. And now we're gonna train this brain to land properly on the moon. And our first step here will be to set up the environment. That will be a very simple step. So here we go. Let's do this one in this tutorial. So we're gonna create a new code cell. And the first thing we're gonna do, of course, in order to set up the environment, first we have to import Gymnasium, which contains all the environments that I introduced to you in the first tutorial of this module. So here we go. We're gonna import Gymnasium, and we can give it a shortcut like gym. All right. Then now that we have Gymnasium, well, we can import the environment in which our AI will be trained, meaning the Lunar Lander V2 environment, exactly this one here. So let's go back to our implementation and let's create a new variable which will be exactly this environment. And to get it, well, we first call our library Gymnasium, from which we're going to call a function called make, in which we're going to input exactly the name of that environment. So it's not exactly called Lunar Lander, it is called exactly Lunar Lander V2. That's exactly the name of the environment that you have to enter, by the way, in this make function that you can also see here. You see, you have all the documentation here that can help you if you want to practice, for example, implement this yourself before you watch the tutorial with me. All right, so let's go back to the implementation. Let's paste that inside, and there we go. Now we have our environment. The next step, we're going to get some parameters that we'll need later on in the training, like for example, the state shape, the state size, the number of actions, right? Remember when we build the architecture of our neural network, well, we see that it's going to be the arguments of the network class, right? The state size, the action size. So that's actually what we're going to get right now while setting up this environment. So we're going to start with the state shape, which is of course this vector of 8 inputs that we saw 2 tutorials ago when I explained to you the observation space and the action space. So here we go, state shape, and to get it, well, we're going to call our environment, the variable env, from which we're going to call this following attribute observation space, from which we're going to get the parameter shape. And that will give us exactly the state shape. And now we have the state shape, that's good, but we also need the state size. So I'm creating a new variable which I'm going to call state size, and which will be exactly, well, the number of elements in this input state, meaning the 8 parameters describing at each time step the state of the environment. Remember the coordinates of the lander, then the coordinates of the velocity vector, etc. Right? We saw that together 2 tutorials ago, and it's also, of course, in this Lunar Lander Gymnasium documentation. So state size, to get it, well, let's be efficient. Let's take this, because actually the state size is going to be the first index of this env observation space.shape. And so the first index is going to be 0, because indexes in Python start from 0. All right? So we're going to do some prints at the end to see that we have the right parameters. Then, after the state size, well, naturally, we're going to get the number of actions. So let's call this number actions. And then, how we're going to get that? Well, it's not going to be with observation space, but of course with another attribute called action space. So we're going to take our environment again, env, from which we're going to call this time the action space. Here it is, action space. And then we just need to add a dot and n to get exactly that number of actions. All right, we'll do another print later on to show the number of actions, which is of course 4. Remember, do nothing, move left, move right, or keep the same direction while slowing down the descent. And so here we go. That's the parameters I wanted to get for now, which we will use later. And now let's do some final prints to make sure we have the right parameter values. So let's start with the state shape, which I'm first going to enter in quote, state shape. Let's see exactly what it is. And so here I'm separating the string with a comma. And then after the comma, I put the value of state shape, which is of course given by our variable state shape, which we just created. All right, this one, yes. Now let's copy this to do the 2 other prints. First for the state size, which is of course given by our variable state, well, size. And then finally, let's print the number of actions. So here I'm going to replace that string by number of actions. And of course here, the variable is going to be number actions. All right, we should be good. Let's run the cell to see what happens. We should get 3 prints. Well, before we run the cell, let's actually expect what we're going to get. For this, the state shape, well, we're expecting a vector of 8 elements. Therefore, it's going to be 8, nothing in parentheses. Then the state size, we understood that it is 8, right? The position coordinates, the velocity coordinates, 8 in total. And then the number of actions, well, we perfectly understood that it is 4. All right, so that's what we expect. Now let's run this to see if we're right. And there we go. State shape, a vector of 8 elements. State size 8. 8 input values in each state of the environment at each time step. And then number of actions 4. Perfect. So we're good to go for the next step of this training implementation, initializing the hyperparameters. I look forward to seeing you in that next tutorial. And until then, enjoy AI. Hello my friends and welcome to the second step of the training implementation, initializing the hyperparameters. So now what we're about to do is simply to create some new variables while at the same time initializing them with a certain value. Alright, so I'll show you. Let's create a new code cell. The first variable we're going to create and initialize is the learning rate. Alright, so that's the name I choose for the variable. And then we're going to initialize its value to 5 times 10 at the power of minus 4. Alright, 0.0005. Okay, now the question is, why do we choose such a value for the learning rate? Well, again, that's after a lot of experimentation, trial and error, to get the best performance at the end when training the AI to land on the moon. Okay, so no rule of thumbs again. This is the best value after experimentation. Next, the next variable is going to be mini batch size, which refers, of course, to the number of observations used in one step of the training to update the model parameters. And so now, is there an optimal value? Well, not really this time. The usual value we choose based on common practice is actually 100. That's a good size of mini batch for deep Q learning. All right? Then, next hyperparameter, the discount factor, also called gamma. So I'm going to call it discount factor just for educational purposes, just to make it super clear for everyone. But if you're used to gamma, you can of course call it gamma. And what are we going to initialize it to? Well, first, let's remind that the discount factor represents the present value of future rewards. So, for example, if we have a low discount factor close to 0, well, that will make the agent short-sighted by only considering the current rewards. However, if we have a discount factor close to 1, well, that will make the agent consider the future rewards in its accumulation of the total reward. And actually, we will get the best performance with a good consideration of the future rewards as opposed to being short-sighted. And therefore, we're going to choose our discount factor gamma to be 0.99. All right, close to 1. Then next parameter, well, that's going to have to do with our next step here, implementing experience replay. I'm talking, of course, about the replay buffer size. And what is that? Remember, that's the size, basically, of the memory of the AI, meaning how many experiences, including the state, the action, reward, next state, and whether done or not, in the memory of the agent. You know, the training to sample and break the correlations in the observation sequences. All right, and I remind that the purpose of that is to stabilize and improve the training process. And so now, what is a good replay buffer size? Well, we're going to choose to store 100,000 experiences in the memory. Let's actually note it like that. Int of 10 at the power of 5. All right, 100,000 experiences stored in the memory of the AI, which will stabilize and improve the training process. Perfect. And now we have one final parameter, which is the interpolation parameter used for the training. So that's the parameter that will be used in the sub-update of the target networks. A very important parameter, also called tau, but again, for the purpose of this training, I'm going to call it interpolation parameter. All right. But of course, if you're used to tau, you can call it tau. Great, so what is a good value of this parameter? Well, again, after experimentation, after testing several values of this hyperparameter, I can tell you already that the best value, the optimal value to train our AI to land on the moon is actually 0.001, right? Which we can know this way, 10 at the power of minus 3. Alright, and that's it. That's it for the initialization of the hyperparameters. We're now ready to move on to the next step, implementing experience replay. I can't wait to do that with you in the next tutorial, but please make sure to get some energy for it because we'll have 3 methods to implement inside the replay memory class. Alright, so now let's execute this cell and I'll see you in the next tutorial for this next step. And until then, enjoy AI. Hello my friends and welcome to this new step of the training implementation, implementing experience replay. So here we go, let's create a new code cell. We have a lot to do in this cell and we're going to start by creating a new class, which we're going to call replay memory class. That's the usual name we give to the class that basically implements experience replay. And then in parentheses, we're going to specify object, meaning that there's no inheritance this time that we're using, object, and then colon, and here we go. Let's start with the constructor method to initialize the replay memory object. All right, so that's of course the init method, which will take self, to refer to the object, and then another argument which will be capacity, the capacity of the memory. And here we go. So first, we're going to implement a line of code that will be useful if you want to execute this code outside of Colab, for example, on a Jupyter notebook with your machine, if you want to use a GPU. So we're just going to implement this self.device equals, then we call the torch library from which we're going to call the device function, and then in parentheses we're going to specify in quotes CUDA colon 0, meaning we're going to use the GPU if torch.cuda.is underscore available, there we go, is equal to true. Basically that means that if CUDA by torch is available, then we're going to use the GPU, and then else we're going to use the CPU. Okay, so that's just useful for if you want to execute this code and make the training faster and more performant using a GPU. All right, then we're going to take care of the capacity here. So we're going to call our object again self, from which we're going to create the capacity object variable, which we're going to initialize to the capacity argument here, which will be specified later on when we create an instance of the replay memory class. Okay, so we'll see what it is exactly later, but for now, that's how we're going to initialize the capacity variable of our object. All right, so here we go, capacity, which by the way is the maximum size of the memory buffer. Perfect. Then we're going to create a new object variable, which will be self.memory, which is of course the list that will store the experiences, each one containing the state, the action, the reward, the next state, and whether we are done or not. And we're going to initialize that to an empty list, all right, in square brackets. Okay, and that's it for the init method, the constructor method that initializes the replay memory object. And so now we're going to move on to the next method, which will be the push method that will add an experience event into the memory buffer. So let's take a little break here. We'll do that in the next tutorial. And until then, enjoy AI. Hello my friends and welcome to this new tutorial. In this one, we're going to implement a new method of the replay memory class, which will add an experience into the memory buffer. I remind that we chose our replay buffer size to have 100,000 experiences inside, and well, the method we're about to implement right now is the method that will add those experiences into this replay memory buffer while also checking that we don't exceed the capacity. Okay, so let's do this. Let's start by defining the method, which we're going to call push, and then in parentheses we're going to enter two arguments. The first one is self for the object, and the second one is going to be the experience or event, as you want. That's the same thing. It's what basically contains, the state, the action, the next state, the reward, and that boolean done saying whether we are done or not. All right. So push self event and then colon, and then here we go. Let's implement that method. So first, remember that self.memory is initialized as an empty list. So the first thing we're going to do naturally is to append an event into that memory. And so very simply here, we take our memory object variable that was defined in the constructor init method. There we go, memory, and then we add a dot, and then the append function that you all know, which is a function that can append, meaning add an element into a list. And what do we want to add into this memory list? Well, that's of course the event, right? State, action, reward, next state, and done. Okay, so that's the first step. But now we must make sure that the memory buffer does not exceed its capacity, after we appended that event. And so just below, we're going to add an if condition saying, if the length of our memory, the memory of the object, if this length is larger than the capacity, which is self.capacity, then what are we going to do? Well, according to you, which event should we remove from the memory? Should it be the most recent event or the oldest event? Well, it should rather be the oldest event, right? Because the oldest event is at this point less relevant than the newest event. Okay, so let's delete that oldest event. And to do so, we're going to delete what we want to delete, which is exactly, well, the first element of our memory, meaning the memory of the object. And how do we get that first element? Well, of course, we specify in square brackets the index of that first element, which is, of course, the index 0. All right, and that's it. That's all we need to do in order to implement this push method that adds successfully an experience event into the memory buffer while making sure that the memory buffer does not exceed its capacity by removing the oldest experience if necessary. Okay, so now we're good to go for this second method. So now we're going to implement the third one, which is going to be the sample method that will randomly select a batch of experiences from the memory buffer. So if you want, practice yourself implementing this before we do the tutorial together. And well, whenever you're ready, I look forward to seeing you in that next tutorial to implement this. And until then, enjoy AI. Hello my friends, welcome to this new tutorial, and here we go implementing the last method of this replay memory class, which will be the sample method. Well, we choose to call it sample, which will randomly select a batch of experiences from the memory buffer. Alright, so here we go. Let's define this new method called sample, which will take as input, well, first self for the object, and then batch size, which will be the number of experiences that are going to be sampled in the batch. Okay, so then colon, and then here we go. So first we're going to create a new local variable which we're going to call experiences, and which will contain the experiences sampled in the batch. Alright, and so how are we going to get them? Well, we're going to use the random library from which we're going to call the sample function, which takes as input what, according to you? Well, of course, where do we want to sample the experiences from? Well, that's of course from the memory, self.memory, the memory of our object. Okay, then second argument, what is it going to be? Well, it's going to be the number of experiences we want to have in this batch, and that's of course the batch size. I'm adding k here because that's this expected argument that we see here of the sample function, and that's the batch size. All right, perfect. So first step done. And now we're going to extract one by one the different elements of each sampled experience. Meaning that, remember, an experience contains the state, the action, the reward, the next state, and the boolean done. And so we're going to extract and stack those elements one by one. Alright, so let's start with the first element of an experience, which are the states. And so how are we going to do this? Well, first, we're going to call numpy, from which we're going to call the vstack function that will stack the states and the sampled experiences together, right, by extracting them and then stacking them. And so since it's a function, I'm adding here parentheses, and then I'm going to do a one row for loop. You know this, right? That's like a for loop within a list. So you add a pair of square brackets here, and then I'm going to do this for e in experiences. We're going to stack the first elements in those experiences, and therefore that's of course e of index 0, right? The states have the index 0 in each experience because it's the first element of the experience composed of state, action, reward, next state, and done. Okay? So we're getting all the states for all the experiences that were sampled. However, we must just check that each experience in this for loop is existent. And the way we're going to check this is just with an extra if condition saying if e, the experience, is not none. Alright, and that's it. So at this point we have just stacked all the states together from the sampled experiences. Good, but that's not enough. Now what we also need to do is convert these stack of states into PyTorch tensors, because then, you know, we're going to work with PyTorch to do the training and especially the neural network when updating the model parameters through backpropagation, and therefore we need to convert these states here into PyTorch tensors. And so how are we going to do this? Well, we're going to do this with another function from the torch library. So I'm calling the torch library first, and then this function is very simply from underscore numpy. And that's exactly what will convert these numpy arrays, because now this is a numpy array, and so I'm closing the parentheses here. There we go. And so now with this torch.fromNumpy, well, this numpy array becomes a torch tensor, a PyTorch tensor. Okay, then almost done, but we also need to make sure that the data type of these states, now PyTorch tensors, is only float. And that's again in order to give a certain format expected then by the torch functions and classes that will perform the training. And so to make sure of that, we're just going to add a dot float and then just some parentheses. That will make sure the data type is set as float here. And then remember, because we have our device, whether we are using a CPU or a GPU, we're just going to add at the end dot to self.device, one of the variables of our object. And that's just in order to move this stack of states into the designated computing device, whether it is a CPU or a GPU. All right, and that's it. That's how we stack the states together by making sure they're torch tensors, the data type set as float, and moved to the designated computing device. Perfect. So now we're going to sample the next elements in the experience, meaning next the action. So what I'm going to do is I'm going to copy this line of code, then paste it right below, and then simply replace the states here by the actions, and of course the index here 0 by 1, because the action is the second element in the experience, therefore the element of index 1. And then, however, is or should it be set as a float? Well, no, because remember the actions can either be 0, 1, 2, or 3. There are 4 actions, and therefore it's better to set the data type here as a long integer. All right? So then we're good to go. Then next sample of elements, well, that's going to be the rewards, of course. That's the third element in the experience. So I'm replacing here again states by rewards, and then of course the index 0 by 2. The third element in the experience, therefore the element of index 2. And then for the type, is it going to be a float or a long integer? Well, that's going to be a float, of course. So all good here. Then next sample of elements, well, these are going to be the next state. So here I'm going to replace states by next states, and then the index 0 by 3. All right, the fourth element in the experience, therefore the element of index 3. And then, is it going to be a float? Yes, because you know we have angles, we have velocity values, coordinates, so it's definitely a float rather than a long integer. It's just like the states, basically. Okay, and then, finally, let's take care of the last elements in the experiences, meaning the dones. So first I'm going to replace the states here by dones, then the index here by, of course, 4, the last element in the experience, therefore the element of index 4. And then, however, here there's a little difficulty. For the type, it's not going to be directly float. In fact, we have to set the data type first as the Boolean type, which is uint8. And the way we're going to do this is just in between those two parentheses here, we're going to add a dot asType, which is a function that sets a type, a data type. And it is inside this asType function that we're going to specify the uint8 Boolean data type, which we're going to call with numpy. Therefore, I'm adding np here, then dot, and then there we go, uint8. And this, the np.uint8 data type, is used to represent Boolean values before converting them into float tensors. Alright, and for the rest, we're good to go. So now we can just finish this sample method by, of course, returning those samples of elements, starting with the sample of states. Then here there's a little trap. Naturally we want to say the sample of actions, but actually from what is expecting then in the training, we actually have to return the sample of next states. You will see why exactly later. Then the sample of actions, and then the sample of rewards, and finally the sample of dones. There we go, and we're done with the sample method from the replay memory class. So double congrats, not only you implemented that sample method, but also you implemented fully that replay memory class. So now let's execute this cell to make sure we did everything right, and that seems to be the case. Perfect. Congrats again, that was a big class to implement. So now we're ready for the next step, implementing DQN class. It's going to be an exciting one. We're approaching very soon that exciting training. I can't wait to show you this and show you the final results. And until then, enjoy AI. Hello my friends, and here we go with this new step of the training implementation, implementing the DQN class. And check this out, we're almost done with part 2 implementation, training the AI. After that we'll have part 3 visualizing the results, which I remind we won't implement together because this is not really essential to knowing how to build an AI. This is just a visualization code, so we won't re-implement this together, but that's great. I can't wait to show you the final results. We are on a very good way to build a powerful AI that is able to land on the moon. So here we go with that new step, implementing the DQN class. So let's do this. Let's create a new code cell. And our first step will be to create a new class, which we're going to call agent. Or you can call it AI, or you can call it body, you know, to oppose that to the brain we just made before in the network class. But let's keep the usual names that are commonly used in practice, which is agent. So here we go. Let's create this new class, which we're going to call agent. Nothing to specify in the parentheses, colon. And here we go with the constructor method to initialize the agent object. I'm talking, of course, about the init method. All right, so what is it going to take as argument? Well, first self to refer to the object. Then it's going to take the state size and then the action size, which I remind for our environment is 8 for the state size and 4 for the action size. All right, then let's add a colon and here we go. So first, the first object variable we're going to create is the same one as we created before, self.device, just to give us the choice if we want to use a CPU or a GPU. For example, if you want to use this implementation outside of Google Colab. So what we'll do to do this efficiently, and because we did it before, we're just going to take this line of code because it's going to be exactly the same, copy it, and then right here, we're going to paste it. Okay, no need to do it again. We understand how it works. Then, next object variable is going to be, of course, the state size. So remember, this is the argument, but we still need to create the object variable. Whenever we create a new instance of the agent class, well, we need to define those variables proper to the object. And the first one we're going to create now is self.stateSize. And then, of course, it will be initialized to the state size argument that will be entered later on in this class instance. All right. Then, next object variable is going to be self.of course action size. So that's the object variable, and then we'll initialize it to the argument action size, which will be entered later on when we create the object, meaning instance of this agent class. And by the way, remember that we already initialized the variable for the action size, which we called number actions, right? This is exactly the same one when we set up the environment. Number actions here is exactly action size, the size of the action space. So if you wanted, to make everything clear and the same names, you could also name the object variable number actions, okay? But it's good to work with several names. At least you know that action size is actually the size of the action space as opposed to the state space. So there we go. Self-action size equals action size. Now, according to you, what is the next object variable we have to create? Well, there we go. It's time to do a little bit of Q-learning here. We haven't introduced any Q-learning so far, so now is the time. And so how are we going to do this? Well, we're now going to create two Q networks, the local one and the target one. Remember, as in deep Q-learning. And how we're going to create them? Well, remember, we created our network class before, and so we can just simply create two instances of this network class, one that will be the local Q network and one that will be the target Q network. So here we go, let's do this. Let's start with the local Q network. So I'm going to call it local Q network. And as we said, it's going to be created as an instance of the network class which we created before, and which contains indeed those arguments, because remember, it inherits from the module class by the NN module. And actually, since we already provided a default value for the seed, we just need to enter those two arguments. So right here in the network class, I'm going to paste them, and that's it, because these are actually the arguments of the object. All right, perfect. And then remember, we need to add this, meaning two parentheses self.device, in order to move it to the designated device, GPU or CPU. Perfect, and now let's do the same for the target Q network. So I'm pasting the line above, and I'm going to replace local here by target. And it's going to be initialized exactly the same way. Okay, then next step. Now that we have our network, what do you think we should create as an object variable? Something very important for the training of our AI. Do you know what it is? Well, I'm talking, of course, about the optimizer. So the next object variable I'm creating here is self.optimizer. And we will create that object as an instance of the Adam class, which allows to build the Adam optimizer. All right. So the Adam class comes from the optim module. And there we go. From the optim module, I'm calling the Adam class, which will take as arguments first the local parameters, meaning the weight of our local Q network. So we're going to take our local Q network here, self.localQNetwork. We're going to paste that inside the Adam optimizer, and then we're going to call an attribute of this local Q network, which is parameters, and which are exactly the weights of the network, meaning what we will update step by step to predict better and better actions to play in order to land properly on the moon. So parameters, and then there is one more argument, very, very important for the training, and we can see it here very well highlighted. I'm talking, of course, about the learning rate. All right, so we add here LR equals, well, this will be equal to the learning rate variable we initialized before in this part 2. Learning rate, there we go. Then next step. Okay, so we took care of the local and target Q networks and the optimizer, and now according to you, what else do we need in order to implement that DQN class? Well, that's of course the memory of the AI, thanks to, of course, our replay memory class. And so I'm creating this new object variable self.memory, which will be initialized as an instance of the replay memory class, which will of course take as argument, remember, let's have a look again at our replay memory class. It takes as argument the capacity, when we create an object. And what is the capacity? That's something we also initialized before. Here it is. That's of course the replay buffer size, which has a capacity indeed of 100,000 experiences. So I'm copying this, and then inside that DQN class, I'm going to enter it as the argument of the replay memory class. All right, and now we have one final thing to do in this init constructor method. That's just a final object variable we need to define and initialize for the rest of the training, which is the time step. All right, the time step counter, for deciding when, in which moment we're going to learn and update the network parameters. So how do you want to call this? You can call it time step or t step. And of course, we will initialize it as 0. All right, and that's it. That's it for the constructor init method. Now we have all the object variables we need to implement that DQN algorithm. And that's exactly what we'll do in the next 4 tutorials. Indeed, we have 4 more methods to implement here for this DQN class. So we'll do 1 method per tutorial. So I can't wait to see you in the next tutorial for implementing that next method. And until then, enjoy AI. Hello my friends and welcome to this new tutorial. In this one we're going to implement a new method of that agent class, which will be the step method. And this is a method that will store experiences and decide when to learn from them. Alright, so let's do this. We're going to start with def to define this new method. Then we're going to call this new method step. And then this new method will take as argument, well, first self to refer to the object, but then, as you might guess, it will take the experience, right? Because first this method step stores experiences. However, we're not going to directly input here experience. We're going to decompose the experience into its different elements: state, action, reward, next state, and done. All right, so that's going to be the arguments of the step method. Then let's add a colon, and there we go. Let's implement it. So the first thing it's going to do is to store the experience in the replay memory. And therefore, since we already created our memory object with self.memory as an instance of the replay memory class, well, we're going to call our self.memory object. So I'm taking it here, and then I'm pasting it right here. And then remember, in the replay memory class, we also implemented the push method that stores an experience in the replay memory, and therefore, of course, we're going to add a dot here to call the push method from this self.memory object. Then we add some first parentheses because it's a method, a function, but then we're going to add another pair of parentheses because we have the experience decomposed like that. So in fact, in order to enter the experience here, well, we're going to enter the whole tuple of the state, action, reward, next state, and done. So I'm taking this, and just inside, I'm pasting it. All right? Perfect. Now, next step. So remember that this step method does 2 things. First, it stores the experience, so that's what we've just done. But then also, it decides when to learn from the experience. And so basically, what we need to do now is increment the time step counter, which is one of our object variables here, self.tstep. We're going to increment this time step counter and reset it every 4 steps so that we can learn every 4 steps. All right? And we will learn with another method that we will call the learn method, and that we will implement later on in this agent class. So what we're going to do here is take this self.tstep object variable, and then just below, we're going to paste it because we're going to update it by first incrementing it and then resetting it every 4 steps. So first, let's start by incrementing it, meaning adding 1 to it. And the way we're going to do this is very simply paste it again and then add +1. All right, so that's the increment. We increment the time step counter. But now we also want to reset it every 4 steps, and we're going to do that in the same row. And well, the way to do that is to use modulo. I don't know if you know this. If I put some parentheses here and then add a percentage and then 4, well, all this exactly means the rest of the Euclidean division of self.tstep +1 by 4. Meaning, if self.tstep +1 is divisible by 4, then all this will be equal to 0, because the rest of the division would be 0. And therefore, that checks if we are every 4 steps. All right? So, new step done, good. And now, time for the last part of this step method, the learning, which would happen only if we have reached 4 steps, every 4 steps. And therefore, what we need to do now is an if condition that checks if we are every 4 steps. And the way we're going to do this is, of course, with if, and then self.tstep. And now, since self.tstep is actually equal to the rest of this division by 4, then the way to check if we have reached a new 4 steps is just to do this if self.tstep is equal to 0. All right? And so, if that's the case, then what are we going to do? Well, we're going to learn, because we want to learn every 4 steps. But then, remember that when we learn, we don't learn on one observation only. We actually learn on a mini batch of observations. That's why we created the mini batch variable before, which we initialized to 100. And therefore, what we must do first before learning in the step method is to check that the number of experiences in the memory is already larger than this mini batch size of 100. And therefore, we're going to continue here with another if condition, which will check if the length of our self.memory object, but more specifically, it's going to be an attribute of that memory. So first, let's paste self.memory, and then let's get a quick refresher of what we did in the replay memory class. I'll show you that it has a specific attribute, which is actually the memory, and it's actually not to be confused with the self.memory instance of that replay memory class that we just created here. So basically, simply put, this is the instance of the replay memory class, and then in order to call the memory attribute that we see here, well, we just need to add dot memory here. Okay, so this is the object, the instance of the replay memory class, and this is the attribute of this self.memory object. All right, I think it was important to clarify this, but there we go. So now we have the memory size of our memory, basically. And so if that memory size is larger than the mini batch size, which we also created and initialized before right here of 100, well, in that case, we can learn. We can learn on 100 observations instead of just one observation. In AI and reinforcement learning, we always learn on a mini batch of observations as opposed to one observation. And so then let's add a colon here. And so if that's the case, well, what do? First, we're going to get our experiences. So I'm creating a new local variable here, which will contain this mini batch of 100 experiences. And how am I going to get them? Well, I'm going to use, of course, another tool we created before, which is the sample method from the replay memory class. And so to do that, I have to take my self.memory object, the instance of the replay memory class, and then from this object, I'm going to call that sample method, right? Which will sample 100 experiences from the memory. And it will find them because we check that the size of the memory is larger than the mini batch size of 100. So there we go. Let's enter 100 here, of course. And so now we have our experiences, and therefore the last step is to learn from those experiences. And of course, we're not going to implement the learning algorithm right now. We'll do that in a separate method. But since we will call that method learn, what we can do now is actually to call this method learn, which will be implemented in 2 tutorials, and which will take as input, of course, our sampled experiences, but then another one, which is the discount factor gamma, which remember we called discount factor, or maybe you called it gamma, when we initialized the hyperparameter. And that, what we did here to call the learn method even before defining it, is totally fine, as long as, of course, we define it after in this agent class. All right? So there we go. We're done with this new step method. Now we can move on to the next method, which will be the act method, which will be, of course, the method that will select an action based on a given state in the environment. I can't wait to implement this new method with you in the next tutorial, and until then, enjoy AI. Hello my friends, and here we go with the implementation of a new method of our agent class, which will be the act method that will select an action based on a given state and a certain epsilon value for an epsilon greedy action selection policy. So here we go. Let's start by defining this new act method, which will take as arguments, well, first self for the object, but then since it will select an action based on a given state, well, it will take, of course, the state. And then also, since we're going to do an epsilon greedy action selection policy, well, it's going to take, of course, epsilon as the last argument. And we're going to give it a default value, which will be 0 point to make it a float. And here we go. Now let's define that act method. All right, so first what we have to do is start from the state, because right now at this point the state is a NumPy array, and we need to make sure it is a torch tensor so that we can work with the neural networks later on. So what we're going to do is call this function we know already from the torch library, which is of course the from NumPy function, right? And which will take the state as input, so far a NumPy array, but which will be converted into a torch tensor. Then we're going to make sure to set the data type as a float. And then we're going to do something else that we haven't done before, but which is extremely important for any deep Q-learning, deep reinforcement learning that you're doing. We need to add here an extra dimension to our state vector. Right now, we have 8 dimensions of the state, corresponding to the coordinates of the spaceship, the velocity vector, and etc. But we need to add an extra dimension which will correspond to the batch, meaning that this extra dimension will say which batch this state belongs to. All right, because we're going to work with mini batches. Instead of learning on one observation, we're going to learn on 100 observations. And so we need to know for each state in which batch it belongs. All right, and so that's exactly what we're about to do now. And the way we're going to do this is with a dot and then adding unsqueeze, then parenthesis, and then in the parenthesis, you're going to have to enter the index of which you want this dimension of the batch to be. And since we usually put the dimension of the batch at the beginning, before the other dimensions of the state, well, we're going to enter here 0. So that the first dimension of our new state vector, but now torch tensor, will be at the beginning. Okay? So then we're just going to add 2 parenthesis self dot device, just to move it to the designated device, GPU or CPU. Perfect. And so, since all this actually updates the value of the state variable, well, we're going to add here state equals all this, so that now our state is updated to be a torch tensor set as a float with this extra dimension of the batch added and sent to the designated device. So that's perfect. Now, next step. Well, because we're about to forward pass the state through the local queue network to get the action values, well, we're first going to set our local queue network to evaluation mode. And the way we're going to do that is by taking first our local queue network and then add a dot and then call the eval function. So where does this eval function come from? Well, that's because remember, local queue network was created as an instance of the network class. And remember, the network class actually inherits from the, let's go back to part 2, it inherits from the module class by the NN module. And so we can use now the tool of the module class by the NN module, and one of these tools is of course the eval method to set our local queue network in evaluation mode. So let's go back here, there we go. Now thanks to this eval method we are in evaluation mode, and now we can forward path the state through our local queue network to get the action values. And how we're going to do that? Well, first we're going to make another check to make sure we're not in training mode, but in inference mode, meaning that we're doing predictions. And so to do this, we're going to add torch to call the torch library. And then from the torch library, we're going to call the no_grad function, which will make sure that any gradient computation is disabled. All right, then you're going to add a colon, and then just below, well, there we go. We're going to do something very exciting now. We're going to finally make the predictions from our local queue network to get the action values. And how we're going to do that? Well, first, let's introduce a new variable, a new local variable, which we're going to call action values, which will be, of course, the actions predicted, with the queue values. And how we're going to get them? Well, we're going to call, of course, our local queue network while entering as input, of course, the state. And that's exactly how you forward pass the state to the output layer through our 2 fully connected layers to get the final action values. But in fact, you're getting the queue values corresponding to the actions. And then you'll see we'll use that epsilon greedy policy to select the final action. All right, so let's do this. Now, since we're done with the inference mode by, getting those action queue values prediction, well, we're going to go back into training mode. And the way we're going to do this is, of course, by first calling our local queue network. And then again, just like the eval function, since local queue network is an instance of our agent class and the agent class inherits from the module class by the NN module, well, we're going to use another tool of that NN module, which is this time the train method. And that's exactly what sets our local queue network back to training mode. So great, now we're back to training mode as opposed to inference mode, making predictions. And so now is the time to do that epsilon greedy action selection policy. And so how we're going to do that? Let me remind you how epsilon greedy action selection works. So basically we generate a random number, and then we're going to say if this random number is larger than epsilon, the epsilon we set here, then we're going to select the action with the highest Q value. And else, if our random number generated is lower than epsilon, then we're just going to select a random action. And so, since I just explained to you what is epsilon greedy action selection policy, well, try to press pause on the video and try to implement this if condition yourself to select that final action based on this epsilon greedy action selection policy. But now I'm going to do it with you. Here we go. So we're going to start with if And then let's generate first this random number by calling first the random library, from which we're going to call this time the random function, right? We have first the library and then the function. And so we're going to check that if this random number generated is larger than epsilon, then what are we going to do? Well, we're going to do, of course, we're going to select the action with the highest Q value. And so, well, directly we can return that action with the highest Q value. And how we're going to do that? We're going to use a tool from NumPy, which is the argmax function, and which will allow us to do exactly what we want, meaning select that action that has the highest Q value based on the action values we already got here. Okay, so let's do this. We call NumPy first, and then from NumPy we call this argmax function, which will take as input, of course, our action values. But then, since this selection is a simple operation, we're going to send that to the CPU. And then, because the argmax function actually expects a NumPy format of data, well, we're just going to add here .data.numpy with some parentheses. And there we go. That will exactly select this action with the highest Q value. All right, good. And now we're going to do the else, meaning if the random number generated is lower than epsilon, then what are we going to do? Well, we're going to just select a random action. And so the way to do this is very simple. We're going to return a random action by using the choice function by the random library. So here we go. I'm calling the random library first, from which I'm calling this choice function. And then the trick, to select a random action among our 4 actions, which remember are 0, 1, 2, or 3. Well, the trick to do that is just to use NumPy and then this function from NumPy called arrange. And then inside, we just have to specify the action size, meaning 4. In other words, we're going to select a random index among 0, 1, 2, and 3, because 4 is excluded. Okay, so that will exactly select a random number between 0, 1, 2, and 3. All right, so that's perfect. And we are done with this new act method that will select an action based on an epsilon greedy action selection policy. Perfect! So now we're gonna move on to the next step, implementing that new method, which will be the learn method finally, which will of course update the agent's Q values based on our sampled experiences. I can't wait to do that with you in the next tutorial, and until then, enjoy AI. Hello my friends and welcome to this new tutorial, a very exciting one because finally we're going to implement that learn method of the agent class that will update the agent's Q values based on sampled experiences. So it's quite a big method, so let's get started. We're going to define this learn method, which will take of course as argument self for the object, then our sampled experiences, and then the discount factor gamma, or if you want you can call this gamma. All right, then colon, and here we go. So let's scroll down here to give some space, and the first thing we're going to do now is unpack our sampled experiences into their respective categories, meaning states, next states, actions, rewards, and dones. So here we go. We're going to create these new local variables here, which are going to be the states, the next states, the actions, the rewards, and dones. And according to you, what are they going to be equal to? Well, of course, our experiences, because our experiences are exactly the tuples of these elements. All right, so we're just basically now separating, unpacking the experiences into the different elements: states, next states, actions, rewards, and dones. Okay, good. Now next step. The next step now is to get the maximum predicted Q values for the next states from the target network. And why is that? That's because then, remember, we're going to compute the Q targets for the current states, which include those maximum predicted Q values in the formula. So let me show you. First, let's get these maximum predicted Q values for the next states, which we're going to call next Q targets. Okay. And how we're going to compute them? Well, of course, we're going to use our target Q network, right? As opposed to the local one. Remember, we created with the constructor method in it here, we created our target Q network as an instance of the network class. So what I'm going to do now is take this and just below, I'm going to paste it here, because the first thing we're going to do now is forward propagate the next state from our target Q network. All right, good. And now what does this give us? Well, this gives us the action values of our target Q network propagating the next state. And therefore now, since we want to take the maximum of those action values, well, we're going to use the max function to get that maximum. But before, we actually have to detach the action values in the tensor in order to then get the maximum of them. So the detach function actually detaches the resulting tensor from the computation graph, meaning that we won't be tracking gradients for this tensor during the backward propagation. And then in this max function, we have to input a 1 here because we need the maximum value along dimension 1, which corresponds indeed to the action dimension in the tensor. But then it's not over. We also need to add here a square bracket 0, because actually after getting max 1 we get two tensors, a tensor of maximum values and a tensor of indices corresponding to the actions for these maximum values, and therefore we need to add this 0 in the square brackets here to select just the maximum Q values tensor. But then actually what we'll have to do next is to add a dot on squeeze of again index 1, because we'll need to add again the dimension of the batch, but this time we'll add it at position 1. Alright, and that gets us the maximum predicted Q values for the next states from the target network, not the local network. And now that we have that, the next Q targets, well, we can compute the Q targets for our current state. And so let's call them Q targets, just like that. And it's going to be, of course, the reward plus the discount factor gamma multiplied by our next Q targets multiplied by 1 minus dons. Alright, that's exactly the formula giving us the Q targets for the current state. Make sure to remember that formula. You will implement it many other times. Okay, awesome. So now, next step is to get the expected Q values from the local Q network this time. Okay, so this time we're going to forward propagate the state from our local Q network, as opposed to propagating the next states from our target Q network as we just did. So let's do this. Let's call these new expected Q values Q expected. Okay. And then, as we just said, well, we're going to forward propagate the states from our local Q network. And therefore, let's just take it here. We're going to take our self.local Q network, copy it, paste it right below, and we're going to enter the state to indeed forward propagate the states to get the expected Q values from the local Q network. Okay, but then we're just going to add here gather, because we're going to gather all the respected Q values returned by our local Q network. And so how we're going to do this? We're just going to add 1 and then actions here in this gather function. Alright, so now that we have our Q targets and our expected Q values, well, finally we can get the loss, meaning we can compute the loss between the expected Q values and the target Q values. And therefore, that's exactly going to be our next step here. We're going to create a new local variable, which we're going to call, of course, loss, and which will be exactly that loss between the expected and the target Q values. And so, how are we going to compute that loss? Well, we're going to call our functional module, which we gave the shortcut f, from which we're going to call a new function, which is the MSC loss function, computing the mean squared error loss between actual values and predicted values, here respectively Q expected and Q targets. So here we go. Let's call this function MSC underscore loss, computing the mean squared error loss between, and that's exactly what we have to input here in the argument, between first Q expected and then of course Q targets. Perfect. So now we have the loss. And so now, according to you, what are we going to do? Well, of course, we're going to back propagate this loss in order to update the model parameters to then update the new Q values, leading to a better action selection policy. Okay, so let's do this. That's going to be our next step here. But first, we're just going to initialize the optimizer by zeroing out the gradients of that optimizer. Basically, we're going to do a reset. And the way to do this is by, of course, taking another object we created in the constructor method, which is, of course, self.optimizer. So I'm taking it here and then back below, I'm going to paste it right here. And well, to reset it, I'm going to call the 0_grad method. All right, because optimizer was created as an instance of the Adam optimizer class. Therefore, it contains this 0_grad method as a tool. Okay, good. And now, finally, time for back propagation. We're going to back propagate the loss that we just computed to compute the gradient of that loss with respect to the model parameters. So let's do this. It's super easy. We're going to take our loss that we just computed here, and then we're going to add a dot and then call the backward function. And that's it. That's all we need to do to back propagate this loss. okay? And that computes at the same time the gradient of the loss with respect to the model parameters. Okay, great. Now, next step. The next step is to now perform a single optimization step to update the parameters of the model. And so how are we going to do that? Well, I think I still have it copied. We're going to take our self.optimizer, there we go, from which this time we're going to call the step method. And that is a method that exactly performs a single optimization step to update the model parameters. Okay, perfect. And now, final step. The final step is to update this time the target network's parameters with those of the local network, just like in deep Q-learning. And so how are we going to do that? Well, unfortunately, we can't do everything of it now. So what we're going to do is we're going to call the last method of this agent class, which we're going to create in the next tutorial. That will exactly do this update. And we're going to call it soft update. The soft update method, which will take as arguments our self.local Q network as the first argument. Then, of course, our self.target Q network. And then finally, can you guess? When we do the soft update, we always use the interpolation parameter, and that's exactly going to be our next and final argument here. Perfect, so I'll see you in the next tutorial to implement that soft update method, and until then, enjoy AI. Hello my friends, and here we go for the final method implementation of this agent class. We're going to define now the method that will softly update the target network's parameters, and we're going to call this method soft update. So here we go. What is going to take as parameters? Well, first self for the object, then it's going to take our local Q network, so we can call that local model, then the target Q network, which we can call target model. I'm just taking different names here so that we don't confuse with our variables created before. And of course, it's going to take as the last argument the interpolation parameter. Perfect, here we go. So colon, and then let's implement the soft update method. So first, what it's going to do is loop through the parameters of the local Q network and the target Q network. And so we're going to start with a for loop here that will loop through first the target parameters, so I'm calling this target param to keep things simple. Then it's going to loop through also the local parameters, meaning the parameters of the local model. So I'm adding here another loop variable, which I'm going to call local param. And then the trick to get those parameters at the same time is to use the zip function, which will take as arguments, of course, well, the parameters of the target model and the parameters of the local model. And how are we going to get them? Well, first, we're going to take our target model, from which we're going to call a certain attribute, because remember, of course, target model is supposed to be here, our target Q network, which we created here, target Q network. And remember, since this is created as an instance of the network class, and since the network class inherits from the module class by the NN module, well, we can use this attribute parameters, which will give us the parameters of the model. All right, so let's go back down, and that's exactly how we're going to get those parameters. So after target model dot here, I'm just going to add parameters and then some parentheses. All right, perfect. Then we're going to do the same with our local Q network, our local model. So I'm going to add a comma here and then paste it, and then just replace target here by local. All right, perfect. So let's add some colon here for the for loop, and then here we go. Let's now implement what's going to happen for each target parameter and local parameter of our two Q networks. So actually now is the time to do the soft update. And so as a reminder, the soft update consists of, well, softly update the target model parameters using the weighted average of the local and target parameters. And so first here we're going to take our target parameters, target param, and then since we want to update them, the target parameters, well, we could do an update like this, but instead we're actually going to use the copy function to update the parameters of the target Q network. And so the trick to do this is just to add here dot data and then dot copy underscore, which is actually a function. So I'm adding some parentheses here, and inside the parentheses you're going to have how you want to update those target parameters. And well, the formula of the soft update of the target parameters is as such. First, you take your interpolation parameter, which you multiply by your local parameters, local param. But actually, again, here to get them precisely, you need to add dot data. So that's the first part of the formula, and then you're going to add Well, this time 1, which I'm writing as a float, minus, again, the interpolation parameter multiplied by the target parameters, target param. And again, to exactly get those parameters, you need to add dot data here. And there you go. Double congratulations, because not only we're done implementing the soft update method, but also we're done implementing the agent class. So congratulations. We did some good work here, and mostly we have everything we need, meaning all the tools to implement the training. Now, what I'm going to do is just summarize everything we've just done here in a few words. So I'm going to zoom out a bit so that we can see everything, with a good bird's eye view. There we go. I hope it's not too small. Let me know in the comments if it's too small, and I can always update this and improve this. But there we go. Now we have a good look at the whole code we just implemented together. And so let me just summarize it again. First, we created this agent class that defines the behavior of an agent that interacts with our space environment using a deep Q network. And while it's interacting with this environment, the agent maintains 2 Q networks. First, the local Q network, and then the target Q network. The local Q network is the Q network that will select the actions, and the target Q network is the Q network that will calculate the target Q values that will be used in the training of the local Q network. So it's very important to understand both what they do separately, and also what's important to understand is how they interact with each other, meaning that this double Q network setup will stabilize the learning process that we implemented here. And at the same time, we have the soft update method that will update the target Q network parameters by blending them with those of the local Q network, with that formula we implemented here. And what's the purpose of that? Well, that's to prevent abrupt changes which could destabilize the training. And also, we implemented the ACT method that will help the agent choose an action based on its current understanding of the optimal policy. Those actions will be returned from the local Q network that will forward propagate the state to return the action values. And then following an epsilon greedy policy, it will return the final action. And that epsilon greedy strategy is used as an exploration mechanism. The fact that sometimes we can select random actions allows the agent to explore some more actions which could potentially lead to a better result at the end. And then finally, the learn method uses experiences that are sampled from the replay memory in order to update the local Q network's Q values towards the target Q values. Alright, and that's it. That's the bird's eye view of what we just implemented. Huge congratulations again. Now we're going to move on finally to the rest of this training implementation. We're first going to initialize the DQN agent, and then finally we will train it to accomplish a beautiful landing on the moon. I can't wait to implement those new steps with you, and until then, enjoy AI. Hello my friends, and welcome to this new tutorial. It's going to be a very simple one because it will just take one line of code to initialize the TQN agent. Because indeed, now that we're done building our agent class, we can finally create an instance of that class. By the way, I forgot to run this cell in the previous tutorial, so I'm doing it super quickly here. All good. We're good with our agent class, and so now we're gonna initialize the DQN agent by simply creating an instance of that class. So here we go. Let's insert a new code cell here, and we're gonna call our agent object very simply agent. Okay, and then this object will be created as an instance of the agent class. Make sure not to forget the capital A, which will take as input, of course, the state size, but then be careful not to input action size. That was the name of the argument in the agent class, but actually when we initialize our variables just a bit above, we called action size number actions, or maybe you called it action size if you're used to it, but maybe number action speaks better for itself. So we're gonna take that name here, the name of that variable we initialize while setting up the environment, and we're gonna paste it right here. And there we go. That's all we need to do to initialize the DQN agent. So now we can simply run that cell, and congratulations, you now have for real an artificial intelligence. All we've been doing before was just the architecture of it, modeling it, but now we really have it because we finally created the object. So that's super exciting. Now, in the next tutorial, we will of course train it, because so far we only built an AI with a non-trained brain. And so we need to train that brain with the tools that we implemented here. By tools, I mean the step method, the act method, the learn method, of course, the soft update method. So we will use all these tools to train the brain of our AI. And that's exactly what we'll do in this new step, training the DQN agent. So I can't wait to do this with you. And until then, enjoy AI. Alright, my friends, here we go. Let's start the training implementation. So we're going to add a new code cell here. And before we start this big for loop that will perform the training, well, of course, we need to initialize the training parameters. And which are they? Well, first, it's going to be the number of episodes, which is actually the maximum number of episodes over which we want to train our agent. But you will see that it will already get some amazing performances before that maximum number. And so we'll initialize this number to 2000, okay? But you will see if we're getting the same results as when I tested it myself, well, we should get some good reward even from a couple hundred episodes. But I don't want to tell you more now. I want to keep you surprised at the end. So here we go. Let's proceed with the next training parameter. So the next training parameter is going to be the maximum number of time steps per episode, meaning that we don't want to let our AI try too hard. For example, if it keeps staying in the air, or if it stays too long in a certain stuck state of the environment, we don't want this to happen. So we're going to set a maximum number of time steps per episode. And to make things super clear here, so you can read the code easily, I'm going to name this variable, and this is just for educational purposes. I'm going to name it maximum number time steps per episode. Of course, feel free to choose a simpler variable name, but at least we will be able to read our code exactly like we would read our native language, okay? So maximum number time steps per episode, and we're going to initialize that to 1000. In any attempt on landing on the moon, there's going to be maximum 1000 time steps. Perfect. Then, next training hyperparameter to initialize, well, it's actually going to be a series of 4 corresponding to the same thing, which are the hyperparameters related to our epsilon greedy action selection policy. Because you might have wondered, what will be this epsilon value over which we want to compare this random number generated, to either select the action with the maximum Q value or select a random action for exploration. Well, here's how we're going to do it. We're going to start with an epsilon starting value. Again, I'm taking very simple variable names so that we all understand what's happening. So epsilon starting value, which will be, of course, 1.0. All right, and that will be our first epsilon value in the epsilon greedy strategy. But then we're going to let it decay, thanks to an epsilon decay value, meaning that we're going to reduce it little by little to test other epsilon values. All right, but we're going to do that up to a certain point. And that's why then the next hyperparameter variable I'm going to initialize here is going to be the epsilon, this time ending value, which will be the last epsilon value we want to test in our epsilon greedy strategy. And this value is actually going to be 0.01. Okay, so we start at 1, we end up at 0.01, and then by which decrement we're going to go from 1.0 to 0.01, well, that's going to be with, this time, the epsilon decay value, which according to you is going to be something like what? Well, we actually want to decay our epsilon starting value and then our next epsilon values by very little, by multiplying it by very close to 1 float. And that number is going to be 0.995. All right, so for example, the epsilon starting value is going to be 1, and then the next epsilon value after the first decay is going to be 1 multiplied by 0.995, meaning 0.995, okay? And then it's going to be 0.995 times 0.995, which is a little bit lower than 0.995. And we will do that until we reach 0.01, okay? So that will allow us to get different exploration in the epsilon greedy strategy. And then, final thing, what do we have to do? Well, of course, we have to create and initialize our epsilon variable, right? Because this is just a starting value, this is the ending value, so these are fixed, this is decay value, but then we want to have the epsilon value that will vary over the different decays. And so, how are we going to initialize this epsilon variable, of course? Well, with, of course, the epsilon starting value, which I copied before. All right, perfect. And now we have one final training hyperparameter that we need to initialize, which are going to be the window of scores on 100 episodes. Okay, so again, in order to make things super clear, I'm going to call this variable scores on 100 episodes, which will contain that window of all the scores on the last 100 episodes. And how we're going to get that, how we're going to initialize this? Well, with a double-ended queue in order to keep track, of the scores of the last 100 episodes. And how can we get that double-ended queue? Well, that's with a certain function called the decay function, inside which we will only enter this argument, maxlen, which will correspond, of course, to the 100 episodes. And that's it, my friends. We are now ready with the whole initialization of the training hyperparameters. So now we can finally move on to that next big step, very important step, the step where we finally make our AI intelligent. But of course, having the specific intelligence, not the general intelligence, to be able to land properly on the moon. So let's make that for loop happen in the next tutorial, and until then, enjoy AI. Hello my friends, and here we go. Are you ready to implement that final training loop? I'm super ready and I'm super excited. Here we go. So we're going to start, of course, with for. Then, according to you, what is going to be the loop variable? Well, that's of course going to be the episode. So let's call it episode. And our episodes are going to go in the range from the first episode of index 1 up to the number of episodes variable. But remember, the upper bound of a range in Python is excluded, so we have to add here a +1. All right, and here we go. Now let's implement that for loop. All right, so now according to you, what is going to be our first step? Well, as always in a training loop, especially in reinforcement learning, the first step is to reset the environment to its initial state at the beginning of every episode. And right now, since we're dealing with one episode specifically, starting with the first episode, well, we have to reset the environment to its initial state. So how are we going to do this? Well, we're going to take our state, which here is a new local variable, and then add a comma followed by an underscore, because then we will call, of course, our environment, and then the reset function. And actually, this returns not only the initial state, but also some other information, like, for example, the initial observation, which is discarded here with this underscore. Okay, perfect. So then the next step, let me scroll down a bit. Here we go. The next step will be to, of course, initialize the score, because the most important thing we'll have to measure here is the score. When I say the score, it's of course the cumulative reward, which is why we have to initialize this to 0. So let's do this. We're going to call that score, obviously, and we're going to initialize that to 0. All right, so this over the episode will be the cumulative reward. Perfect. Then we're going to start a new for loop now. And according to you, what will it be iterating over? Well, of course, I'm sure you guessed it. It's going to be a loop over the time steps, right? The time steps over the episode. Okay, so we're going to start this new for loop. Then let's call our time steps t, very simply. And then, well, these time steps are going to be in the range from 0, but we don't have to specify it. So let's just specify the upper bound, which is, of course, we initialized it before, the maximum number of time steps per episode. Right now that we called it like that, it seems super easy to understand, right? So let's paste it here, and that's our second for loop. So here we go. Let's implement it. According to you, what is the first thing we should do in this second for loop? Well, actually the question should be, what is the first thing that the agent should do at a specific time step? At the beginning of this new for loop, looping over the time steps. Well, of course, it will be to select an action, okay? And so we're going to introduce a new local variable, which will be the action selected. And how will the agent select that action? Well, of course, that's with one of the tools we implemented before. First, we're going to call our agent, which we just created before, as an instance of our agent class. And then, well, speaking of the agent class, we can now use one of its tools, which will be, of course, here, the act method. The act method, which, remember, selects an action in a given state of the environment and following an epsilon greedy policy. Okay? So, speaking of state and epsilon greedy, well, what are the arguments here? Of course, the state. So let's implement it now. That's, of course, the state here we got in the first step. And then, of course, it's going to be epsilon. Okay? Great. So now we have the action. So now, according to you, now that we have the action, what is the natural next step? Well, since since we have the action, what does it mean? That means that the AI just played an action, it just made a move, and therefore, by making this move, it ends up in a new state of the environment. And therefore, because it played this action, we now have the next state. And of course, what do we also have? Well, we have the reward. Because each time the AI plays an action, it receives a certain reward, which, by the way, my apologies, I forgot to show to you in details. Let's have a look at what exactly this reward is. So I'm going back to the Lunar Lander environment, scrolling down to the description here. And so let's just see quickly how the rewards work. Well, after every step, a reward is granted, of course, but then this is what we're interested in. Here is the reward for each step, meaning for each time step now in our for loop. Well, the reward is increased, decreased, the closer or further the lander is to the landing pad. Okay, makes sense. Then it is increased, decreased, the slower, faster the lander is moving. Okay. It is decreased the more the lander is tilted, angled, not horizontal. It is increased by 10 points for each leg that is in contact with the ground, decreased by 0.03 points each frame a side engine is firing, and decreased by 0.3 points each frame the main engine is firing. And then finally, we have the worst punishment and the ultimate reward. We have an additional reward of minus 100 points if the AI crashes, of course, and plus 100 points if it lands safely. And I can assure you that we will get those plus 100 points. All right? So let's go back to our implementation. It was good to understand how the rewards work. And now, well, since we played this action and therefore reached the next state and got the reward, well, we're going to put those new information in new variables. So here we go, next state, then reward, and then also we'll also have done. The Boolean saying whether we are done or not with that specific episode of the environment. And actually now, since we're about to use the step function from our environment, this will also return some other information but which we won't need, so we will just discard this information with a first underscore here and another one. Alright, and so all this will be returned by the step function of the environment, so I'm calling the environment first, and then this step function will take as argument, of course, the action. Okay? Great. And now, finally, time for the most important step of this training loop. Now is the time we're going to use the step method that, remember, includes the learn method. In other words, we're going to use the tool that will perform the training. Indeed, we have everything we need to call this step method, right? We implemented it in the agent class. Remember this step method. It needs the state, the action, the reward, the next state, and done. And well, this is exactly what we just gathered. And remember, the step method includes the learn method, which of course performs the training by backpropagating the loss between the expected Q values and the target Q values with our optimizer here and on the sampled experiences. So let's do this. That's the most important step of this training loop. Here we go. Let's use the step method to perform that new step of the training. All right, so how we're going to do that? We're going to, of course, take our agent from which we're going to call the step method. And there we go. We're just going to enter its inputs that we just gathered, the state first, then the action, then the reward, then the next state, and finally done. And that's it. This step is exactly what will train our agent to land better and better on the moon. Okay, perfect. So then what is going to be the next step? Well, now that we've reached the next state, we need to update our state variable because it becomes the next state. So we're going to do that simply with a state equals next state. There we go. Then we're going to have to update the score, of course, because we got the new reward. So since the score is the cumulative reward, well, we just need to increment the score with that new reward. Perfect. And then finally, we took care of the action, we took care of the next state, we took care of the state, and we took care of the score. What is missing now? We need to take care of this. Done. And how we're going to do that? We're just going to check if at this specific time step where we are in the second for loop, well, our episode is done. And so if done, meaning if the episode is done at this specific time step, well, we'll simply do a break so that we can finish the episode. Okay, great. And so, well, if the episode is not done, we will continue this second for loop. And if it is done, well, we will, of course, exit this second for loop. And so then what happens now, when the episode is finished? Well, we're going to append the score of that finished episode to that window of the scores on 100 episodes. And so, well, we're just going to take our variable here. We're going to copy it. And outside of the second for loop, be careful, we're going to paste it and then add a dot and append, of course, the score of that last episode that was just finished. Perfect. And then finally, we're just going to, of course, decay the epsilon for the epsilon greedy policy while ensuring that it doesn't go below the ending value of 0.01. And so how can we do this efficiently? Well, we're going to take our epsilon and we're going to update it this way by taking the max of first the epsilon ending value and then, of course, the decayed epsilon, which is epsilon decay value times epsilon. And my friends, now huge congratulations because we are done with that training for loop. So now I can't wait to see you in the next tutorial where we're going to do one final print in that same for loop to visualize the training results. It's going to be a fun and exciting tutorial. I can't wait to meet you there, and until then, enjoy AI. Hello my friends, and here we are at the end of this training implementation. We just have to do one final print to print the training result, and we're not going to make a classic print, we're going to make a very exciting one because we're going to make a dynamic print, meaning that we will get the average score for each episode, but in a dynamic way, meaning that episode by episode we will see the average of the cumulative reward evolving over the episode, but we're going to make an overwriting effect, meaning that each of these lines printed will be removed to give place to the next one. And of course, we will keep the average reward over 100 episodes every 100 episodes. Okay, so it's a bit of an advanced print, but you won't be disappointed at the end by the result. All right, so here we go. First, we're going to make that first dynamic print, which will print those average scores for each episode with that overriding effect from one episode to the next. All right, so here we go. We start with print. Then we're going to start with some quotes because we're going to use the format function. So, first in the quote, you enter the string, and then outside of this quote, you're going to add dot format, which will contain the variables corresponding to the values that we're going to enter inside these quotes. Okay, so that we know that's a usual technique of printing. So first let's enter the print, and then I'll show you how to make that dynamic overriding effect. Alright, so we're going to start by printing episode, the episode number. So that is just the string, and then to add the number, we're going to add a space and then this pair of brackets, like that. Then we're going to add this \t, which is a tab character just to add some space. And then we're going to add average score, which will be, of course, the average score, meaning the average cumulative reward over the last 100 episodes up to this one, unless we still haven't reached 100 episodes, in which case it would be from 0 to this one. So then we're going to add in another pair of brackets like that. This time, since it's going to be a float, and since we have to choose the number of decimals we want to have up to the comma, we're going to enter this colon dot to f, meaning that we will want the average score to be printed as a float with 2 decimals after the comma. All right? And here we didn't have to enter anything because it's just an integer, which is the number of the episode. Okay? So all good with this. And then inside the format function now, we will have to enter 2 variables. The first one that will give us the value of this episode, and the second one that will give us the value of this average score in this particular format. All right, so let's start with the first variable, the obvious one. The variable that will give us the number of the episode is, of course, our episode loop variable. And so that's the first variable we enter here. Okay, good. That was the easy one. And now the more difficult one, how we're going to get the average score in a variable here. Well, unfortunately, we don't directly have it, so we'll have to compute it. But what we have is this, scores on 100 episodes. And so according to you, how do we get that average score thanks to this scores on 100 episodes? Well, by using, of course, the mean function by the NumPy library. So that's why here I'm calling the NumPy library, from which I'm calling the mean function, which will take as input, of course, our scores on 100 episodes variable. Alright, so note that as long as we haven't reached 100 episodes, actually the scores on 100 episodes variable will contain less than 100 episodes, and therefore we'll get the mean of less than 100 episodes, but at the end, of course, we will get to 100 episodes. Okay? And now, finally, let's create that dynamic effect with the overriding effect. So the trick to do this is simply to add at the very beginning here, inside the quote, a \r, which is called a carriage return in programming, meaning that the cursor will return to the start of the line when printing. And so when you use it in a loop, well, it will allow the newly printed line to overwrite the previous one, which is exactly the effect we want to create. You will see it's going to look very, very nice. We'll have a dynamic effect in the console. But then that's not all. We also need to add at the very end, but inside the parenthesis of the print function, of course, a final argument, which is the end argument, and which we will have to set equal to a pair of quotes. Okay, just like that. And that means that after printing this line, it won't automatically add a new line. And this is crucial to create that overriding effect caused by discourage return \r. Alright? So great, we have the dynamic printing, but then remember that we also want to keep the average score on 100 episodes every 100 episodes, and therefore we're gonna naturally make a new if condition here that will check whether we are every 100 episodes. Okay? And so how we're gonna do that? Well, you know the trick. We're going to use modulo again, you know, that percentage giving us the rest of a Euclidean division of an integer by another. And what will be that integer? Well, that's of course going to be the episode, because we're going to check if the rest of the Euclidean division of the episode by 100 is equal to 0. Alright? Because if yes, if that rest is 0, then that means that we are every 100 episode. If episode is 100, then the rest of this is 0. If episode is 200, then the rest of this is 0 as well, because 200 equals 2 times 100 plus 0. Alright? And so, if we are every 100 episodes, what are we going to do? Well, we're going to do this exact same print, but without that dynamic overriding effect. And therefore, right here, I'm going to paste that same print, and then we're going to remove at the end this end argument. We just remove it, and so then this print will stay. Perfect. And now, according to you, what else do we have to do? We have to do one final thing that is very important. I'll give you a hint. It has to do with the way the Lunar Lander environment works. Let's have another look at it in Lunar Lander Gymnasium. Let's have a look again at the rewards. If you remember, there you go. An episode is considered a solution if it scores at least 200 points. And therefore, we need to check that, because if this happens, that means we win. And so we have to say this in the print and also save the model if we win, because it would be nice to keep a winning model. That works very well. And so, back into the implementation, we're going to create below a new if condition, which this time will check if, well, the mean of our scores on Google Colab will find it. There we go. If the mean of our scores on 100 episodes is larger than 200, and we have to add 0.0 to make it a float. Well, if the average score in 100 episodes is larger than 200, well, time to say we win. And so, let's paste the previous print again, and let's change this the right way. So first we're gonna replace this by a /n to jump a new line, and then say environment solved in, and then in brackets we're gonna enter colon D, because it's gonna be a double integer. So environment solved in a certain number of episodes. So I'm going to add here episodes. Then we're good for the average score. That's fine. However, in the format function, here, do you think we have to keep episode or change it a bit? Well, actually, if this average of the scores on 100 episodes is larger than 200, that means that in fact, we actually started winning from this episode number minus 100, because this is a score over 100 episodes. So here, as you want, you could either keep just episode or subtract 100. That's up to you, okay? Let me actually zoom out a bit so that you can see better the whole code. Another one. I hope it's not too small for you. Let me know in the comment if you can still see well. I can always re-record this. Okay, then we will also remove this end argument at the end, because we don't need the dynamic overriding effect. And now we're good. And so, now what are we going to do? Well, since we have an intelligent AI that is able to land on the moon, well, time to save its model parameters. And how do we do that in PyTorch? Well, first, we call the torch library, from which we call the save function, which will take as input two arguments. Well, first, the model parameters that we want to save, and then second, a file in which we want those model parameters to be saved. So let's enter the first argument. How do we get those model parameters? Well, first we have to call our agent. Then from our agent, we're going to call our local QNetwork. There it is. And then from a local QNetwork, we're going to call a method that will return to us in a dictionary those model parameters, and that method is state underscore dict parenthesis. Okay, perfect. And then the other argument, the file that will contain those model parameters. And well, we simply have to enter a name of that file, so we can call this checkpoint.pth. Okay, perfect. And then now we have one final step, meaning one final line of code we need to do in this training for loop. According to you, what is it going to be? Well, now that we solved the environment, now that we have an AI working properly to land on the moon, well, it is time to exit the training loop, right? Because we don't need to do more training. And how we're going to exit this training? Well, with a simple break. And that's it, my friends. We are now ready to run this training for loop and observe some very exciting training results. All right, so are you ready? Let's do this. Let's do this now. But first, it's possible that because we implemented a lot of code, your session actually expired. So if that's the case, what you only have to do is click runtime here and then restart runtime. Okay? Don't do restart and run all because we still have the results visualization, which I want to show you in the next tutorial. But at least restart the runtime and then rerun the different code cells we implemented together one by one until reaching this one. Okay? And once it's done, well, now is the time to run this last cell we did. So here we go. I'm going to do it in 3, 2, 1, go. And here we go. Now the training is launched. And you can see the dynamic printing of the episode with the average score. And as you can see, at first we start with some negative average scores, which is completely normal. You know, we just need to give some time to the AI to explore, to do some exploration, to train, to learn, and to update its model parameters, to update its Q values. Basically, it will take a bit of time before we see a better score. But as you can see now, we already increased the average score. You can see it increase a bit over time with this dynamic printing. So yeah, there we go. We started at minus 146. Now we're at minus 104, which is pretty good. And now there you go. We're over minus 100, minus 95 for the 200 episodes. And now minus 91, minus 89, minus 86. So you see, it is improving over time. It is amazing. The deep Q-learning model works very, very well for this environment. And it keeps increasing over time, over the episodes. Now we are at episode 230 and the average score keeps increasing. And soon we will have a positive average score and mostly an average score over 200. So yeah, let's just continue watching and very, very soon we will see some positive average score. I can't wait to finally discover the score. Now we are at episode 263 and we have reached an average score almost close to minus 50. So as you can see, it is still exploring a bit. It is still doing a bit of exploration. It is still learning thanks to not only the deep Q-learning model we implemented, but also remember that epsilon greedy action selection strategy. And now there we go. We are over minus 50. We're at minus 45, minus 47. And we have reached almost the episode 300. We're approaching 300 now, and we have reached minus 47, which is completely normal. You know, it always takes time for the AI to learn, to update its model parameters in order to achieve the desired performance. But now we can see the average score kind of stagnating. It is still not increasing, but that's probably because, you know, sometimes it still needs to do a little bit more of exploration, and soon enough, well, it will improve. And there you go. Now we are over minus 40, minus 37. That's perfect. And we have reached episode 329. Minus 31 now. We're close to the 20s, the minus 20s. There we go. Minus 20s, minus 28, minus 27, minus 25. You see, it keeps increasing. Now it keeps improving. Oh, wow. It's going really well now. Minus 13. We're getting super close to the positive reward. Minus 10, minus 8, minus 6, minus 6. We have reached episode 349, minus 7. So still doing a bit more of exploration now maybe. Still learning, still updating its parameters, its model parameters, still updating the Q values. We're decreasing a bit, now minus 10, but then that's probably because of some more exploration. Minus 4 now, minus 2, and there we go. Congratulations, my friends. We have reached finally the positive average score. So it is really well improving. Plus 9 now, plus 11, plus 12, plus 13, plus 19. So you see how it is getting better and better over time, how it is really getting more performant, how it is learning better, how to land properly on the moon. And of course, in the next tutorial, we'll see the results in the video of that AI, you know, properly trained to land on the moon. We will see how it is able to train on the moon. But as you can see now, we have reached more than 400 episodes and the average score is still increasing. That is amazing. And so I'm very confident now that we will soon reach an average score of over 200. Now we are at 74, 76, and we have reached episode number 423 now. And we're still at 75, 78, still doing a bit more exploration, still updating its parameters, still updating Q values, still applying the epsilon greedy action selection policy while learning with deep Q learning. And the average score is now at 80. So it keeps improving. It keeps getting higher and higher. And we have reached episode 448, 449. The average score is still increasing. Now it is kind of increasing slowly, but don't worry. It will at some point, increase more, because sometimes it needs to do a bit more of exploration before, really take a big leap in improvement and in performance. But there you go. Now we are approaching an average score of 100, and we are approaching the episode 500. And remember, the total number of episodes over which we want to do this training is 2000. So we still have some time. We still have some good margin before reaching that objective, that goal of 200 average score. So now we are at 96. We're approaching the 100, and there we go. 100. Perfect. So we're getting close. We're getting close. So average score 102, 104, 104 still. So we are now past the episode 500. Good. So the average score is around 106, 107, 106 again. So yeah, it keeps improving. It keeps improving. Now it's probably doing some more exploration, on how to really take another big leap in improving the average score. But soon enough, we will see it at 110, and then 120, and then 130, and this will be exciting. There you go, 112, 113, 114. And the episode is at 546. By the way, feel free to share in the comments the average scores you get. Maybe you already won. Maybe you found an AI. Maybe you tweaked a bit the AI, the neural network architecture. I don't know. But maybe you already got the average score, the targeted average score of 200 before me. I'm at episode 569 and reaching an average score of 121. But maybe you got a better one before that. So feel free to share in the comments. Feel free to share your AIs, your architectures. And yeah, probably you will find an even better than the one we implemented together here. All right, so where are we now? We have almost reached episode 600, and the average score is at 128. So yeah, 132 now, 131, episode 600. So yeah, maybe we will get that final win, that final desired performance at episode 1000 maybe. It can change, it can vary with different experimentation. It's not deterministic at all, so let's see what we get. But now the average score is kind of stagnating. Oh no, it keeps increasing. Very good. 134, 133, okay. So very, very interesting. So there we go. Now we are at episode 650. And so the average score seems to be still increasing. Sometimes we see it decrease, but that's completely normal. That's because sometimes the AI needs to do some more exploration to explore more actions that it can do in order to achieve the desired performance. But there you go. Now we are over 140 for the average score, and we have reached almost 700 episodes, and now over 150. So we're getting close. 153, 154, 154. We have reached more than 700 episodes now. So yeah, I think this is what I said. We're gonna finally win around 1,000 episodes. So you see, we really don't need the 2,000 episodes in order to achieve that final performance of the average score around 200. We are over 165 now. We're getting close. That's great. That's great. Maybe we will actually win before 1,000 episodes. We could have actually, do this training over 1,000 episodes only instead of 2,000. But at least now we have some margin. We can feel confident that we will win before the end of the first for loop, looping over the episodes. Oh, wow. Now we are almost at 180 and sometimes decreasing a bit, but that's totally normal. That's because of the expiration. But there you go. 183, 84, 82. Oh, that's great. And we have reached 780 for the number of the episodes. So now it's stagnating around 180, but it's really increasing, it's really improving. So I feel totally confident that we will reach that targeted average score of 200 super soon. Now it decreased a bit, but that's again totally normal because of the exploration. It doesn't have to increase all the time. But there you go. I'm just betting if we're gonna reach that 200 average score before 1,000 episodes or after. Let's take a bet. I bet that we might actually reach that average score after 100, because now it's doing some more exploration. The average score is decreasing a bit, but maybe at some point it will increase again because it will realize that the direction of the exploration it took is not the right one, and it needs to go back to the previous subspace of the actions it took. All right. So 166 now, after having reached 875 for the episode. And now it is increasing again. Good. 172, 173. So it found a new, better subspace of the action space, sub-action space. 180 again. Now we're back into the 180. Now 175. Okay. So 175 for episode 916. 174. 180 again. There we go. 182. Oh, maybe I will lose my bet. Actually, maybe we'll reach that 200 reward before 1000. 186. 188. Still increasing. Amazing. We have reached 945, 947, 190. There we go. First time we are over 190. 195, 96. I will lose my bet. We will actually win before 1000 episodes. There we go. Congratulations. We solved the episode in 863 episodes with an average score of 201.64. Remember, the 863 is because of that minus 100. If you didn't use this minus 100, maybe you actually got 963. But that's an amazing result. Now I can't wait to visualize our AI landing on the moon in this part 3, which we won't re-implement because it doesn't really have to do with AI. It's more a visualization code. So we will just enjoy the results and see our spatially intelligent AI landing properly on the moon. I can't wait to meet you there. Congratulations again. And until then, enjoy AI. Hello my friends! Alright, so are you excited for this final tutorial where we visualize the results? Indeed, we're now completely done with the implementation. We don't have any more code to implement, related to the AI. So now is the time to just enjoy in our chair with a good coffee or a good tea the final results visualizing our AI landing on the moon. Remember, between those two flags, and we should see a super beautiful landing because indeed in 963 or more, specifically 863 episodes, we were able to get an average score of over 200, which is the desired performance. Alright, so now let's get into part 3, visualizing the results. As I said, we won't re-implement all this because this is more a visualization code than an AI code. However, what's interesting to note is that, as you can see, first we get the environment, then we initialize the state, we initialize done to false, the frames, but then the important thing I wanted to show you is that in this while loop that will run an episode, well, as you can notice, we only use, of course, the act method for our AI to play the different actions in order to land properly on the moon, and of course the step method of the environment, to get the next state, the reward, and whether or not we are done with the episode. But what do you notice here? What do you not see that we had before when we implemented the training loop? I think that's very important to highlight this. Well, of course, we don't see the step method from our agent because now our AI is trained, so we don't want to do any more training. We just want to be in inference mode, playing the different actions to land on the moon. I'm talking, of course, about this step method that we call from our agent, and that, remember, includes the learn method in order to do the training. All right, and as you can see, we don't see it here in this visualization code. Alright, so we only use the step function from our environment to get to the next state until the episode is done. And then at the end we save all the frames in a video, which we will have of course. And also in order to show the video in this Colab notebook, well, we use this show video function to show the video just below in the console. Alright, that's all you need to understand in this code. We don't have to re-implement it. So let's just enjoy, let's just watch our AI land on the moon. Are you ready for this? Here we go. So what we only have to do now, unless your session has stopped, in which case you need to restart it by clicking runtime here, and then this time you can do restart and run all. Well, mine is still on, so I can just run this cell and visualize the result. So are you ready to see a beautiful landing on the moon? Here we go. 3, 2, 1, go. Let's run the cell, and in a second we will have the video. Actually, not a second, but in a few seconds we'll have the video. And also here you will see, well, first you see the model's parameters saved in this checkpoint.pth file. So that's from the previous code cell that we run. But soon enough, we will see a video here, which we'll be able to download on our machine and watch anytime we want. But of course, we'll also have it here in the console. And indeed, it's going to take a little time, but not that much, because we're not in training mode, we're just in inference mode. So right now, our AI is just playing the different actions over one episode. It is not doing any training, it is not doing any deep Q learning anymore. And since this code actually gathers all the frames together, well, it takes a little time to, gather these frames and include them into a video in the MP4 format. But the code is still running. All right. Oh, we are here, as you can see. The agent is still playing the actions. It is still returning the actions. And there we go. The code is executed after the agent played the actions. It was very fast to do the rest of this implementation. Are you ready to see the final video? Let's do this. 3, 2, 1, go. Here is our AI trying to land properly on the moon. It is very in control. It is playing some great actions. And look at this beautiful landing. That's a perfect landing. Oh my goodness. This is the first time I see such a perfect landing training this AI, because sometimes, it lands a bit on the right or, touching one of the flags. Here, it's really in between those two flags. That was a great one. So congratulations if you got the same thing. You probably got something very similar if you use the same architecture of the neural network. But there it is. That's a super beautiful landing. And as you can see, the video is also here if you want to download it. I'm gonna download this one to share it with you in the course. You just click on the 3 little dots and then download, and this will appear in our machine. All right, done. Let's have a look at it. Here it is. Here is the video. Let's watch it again in full screen, even if it will be lower resolution. But let's have a look one last time at this beautiful landing of our AI landing on the moon. Here we go. Super! So congratulations again. Now we're going to do one final tutorial where we're going to play a little bit with ChatGPT, trying to re-implement this with ChatGPT. Let's see if that's going to work. I can't wait to do that final tutorial with you of this part 1. And until then, enjoy AI. Hello my friends, and welcome to the final tutorial of this module 1 on deep Q-learning. Congratulations for having reached so far by implementing together this deep Q-learning model. And speaking of which, now I want to say something very important, because in this tutorial we're going to build our deep Q-learning with ChatGPT. The really important thing that I want to say is that rest assured, all those 19 tutorials we just did together implementing ourselves deep Q-learning was completely worth it. It's very useful for you, because actually very few people can do it. Everybody can use ChatGPT to build a deep Q-learning model, but very few people can implement a deep Q-learning model as we just did. And therefore, that gives you a significant advantage as a data scientist or an AI engineer compared to people who are directly using ChatGPT to build an AI. Indeed, because we implemented the model together, you now know all the little details of the AI. You also know the foundations, the different layers of its mechanism, not only in terms of architecture, but also in terms of training. And therefore, that gives you so much more room for improvement compared to people who are directly asking ChatGPT to build an AI. So no worries at all. What we just did is extremely useful for you. It will make you one of the top AI scientists. But still, just for fun, let's build a deep Q-learning model with ChatGPT and see what we get. So let's start the chat. I'm going to say, hey, ChatGPT, can you please build a deep Q-learning model for the lunar landing environment? Okay, then I'm going to say, please implement it in PyTorch. By the way, PyTorch for deep reinforcement learning is undeniably much better than TensorFlow. Every expert will tell you that, even the experts working at Google. Today, this is a certainty. 3 years ago, I would have told you something different. But yes, today, PyTorch is the AI framework by excellence. All right. So please implement it in PyTorch, and please also include the code that generates the video of the trained agent at the end. Okay? Just like what we did, here we go. All right, so what do we have? Certainly. Below is a PyTorch implementation of a deep Q-learning model for the lunar lander environment from OpenAI's Gym. Yes, okay, so first it starts with the import, then it implements the DQN class, just like us. Okay, then it has a similar architecture to the one we use, but with different number of neurons in the fully connected layers. Then the forward function, of course, and then the DQN agent within a class. So we have the initialization of the parameter. It uses also an epsilon greedy strategy, okay? Then it initializes the Q network. Then, of course, it implements experience replay with that remember method. Then the act method, of course. Then replay, so that's for the experience replay again with the buffer memory. Then it updates the target model parameters with this update target model method. Then it initializes the environment, the state size, the action size again. You recognize the variables here. Then it creates the agent itself, and then it starts the training loop, looping over all the episodes and the time steps. And then it generates a video of the trained agent. And finally, we get that video. Okay, so at first sight, it seems pretty good, but I bet that whatever code you got, you probably got a similar code to this one. If you take this code and paste it in Google Colab, well, I'm pretty sure you will not get a performance training and mostly not that great results at the end, at least not as good as the ones we obtained, which is why I was telling you not only using ChatGPT for AI is easy, but besides, you will get much less great results than the ones we got thanks to the great understanding of AI we have while implementing our deep Q learning model. But still, this is definitely some good work by ChatGPT. We definitely have a nice architecture here, a good class of the DQ and agent integrating that epsilon greedy strategy as well as experience replay. Here is the epsilon greedy strategy. So yeah, that's not bad. And if you really want to be convinced that what we implemented is much better, well, I encourage you to try this code in a new Colab notebook, and you will see that the results will not be at that same level of quality we obtained while implementing on our Google Colab notebook our deep Q learning model. Alright, so there we go. I just wanted to finish this section with a little bit of code generation within ChatGPT and play a little bit with ChatGPT to see the kind of implementation it would return. Now I just want to say two things. First, huge congratulations again for having implemented your first advanced AI of this course, the deep Q learning model for the lunar landing environment. You did some great first work there. And now the second thing I want to say is that I really look forward to seeing you in the second part of this course to implement an even more advanced AI model, which is the deep convolutional Q learning model, which is more advanced because indeed, instead of having a one-dimensional vector of input state, you will have multi-dimensional arrays representing images. Because this time, meaning for the environment we'll work on in this part 2, our AI will be playing a game with its own eyes just like a human would play a game. And those eyes will be brought by the convolutional layers inside the neural network. It will be very exciting to implement. That's why I can't wait to see you there. And until then, enjoy AI.
Hello and welcome back to the course on artificial intelligence. In today's section, we're going to tackle deep convolutional Q learning. So we're taking deep Q learning to even a further step. So we originally started with Q learning, the simple Q learning. Then we took that to deep Q learning, and now we're taking it to deep convolutional Q learning. So let's see what we're going to discuss in terms of intuition. The intuition section is going to be quite quick. There's not much that we need to add as long as we're familiar with convolutional neural networks, and we'll touch on this towards the end of today's tutorial. So today in this section, we're going to talk about deep convolutional Q learning, the intuition behind things, and why it's so powerful, why exactly it's so important to move away from deep Q learning, and why deep Q learning is just a basic building block, where it's just a step for us on the path to deep convolutional Q learning, and what kind of avenues deep convolutional Q learning opens up to, what kind of avenues the knowledge opens up to, and where it can be applied. We'll have some examples of that. And then we'll talk about eligibility trace or end-step Q learning, a very powerful addition to the whole concept of deep Q learning, and we'll talk about the intuition behind that. It's quite a complex topic, but nevertheless, we'll break down the intuition in quite simple terms, and then I'll give you some additional references where you can read up about eligibility trace if you'd like to go into more detail. But it is important for us to get the intuition down pat, because we're going to be using that in the practical tutorials, because we're delving into much more complex topics now that we need to add these extra elements to our agents or to our Q learning algorithms so that they can actually handle these complex environments and navigate them successfully. And of course, in this section, because we're talking about convolutional neural networks, it is highly advisable that you check out Annex number 2, convolutional neural networks. Once again, if you've done the deep learning A to Z course, then you're already familiar with this information, so you can safely proceed with these tutorials on the deep convolutional Q-learning. If you haven't done the deep learning A to Z course, then it's a great idea to look at convolutional neural networks and look at those intuition tutorials there, so you understand better how images are processed by neural networks in order to look for features, and what's the whole convolutional layers are about, the pooling layers, the flattening layers, and how all of that works in order to come up with some parameters about that describe the environment or that describe that image. And therefore, we're going to be using those as inputs into our neural network instead of that vector which we're talking about. But more on that in the next tutorial. So if you haven't seen those tutorials yet, we highly advise you to check them out to get up to speed with or refresh your knowledge on convolutional neural networks. All in all, we've got an exciting section, and as you can see, quite not that many intuition tutorials, meaning that you can you'll be able to jump into the practical side of things very quickly. So on that note, I can't wait to see you in the first tutorial, and until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're starting off this section on deep convolutional Q-learning. So let's have a look at what it's all about. Previously, we talked about deep Q-learning. So we had an environment with an agent, and we had a vector describing that environment, which was fed into a neural network, and at the end we got the Q values as our outputs. And then, of course, we found out how the network is trained, the learning part. We found out how actions are decided based on those Q values. That's an action part. And we talked about the action selection policies and different things about how deep Q learning works. But here, the key concept for all of this is how do we get from the actual environment and the states to the neural network? Well, the transition is over here, the input vector. So the input layer of our neural network, and it is a vector. So what we're looking at is, okay, so we're actually not the correct, it's not the correct term. We're not looking at anything. The agent basically has this information. So the environment is passing it this information saying, okay, you, the agent, you're currently in your state is described by this vector. In this simplified example, it's described by this vector x1 of 1, x2 of 2. So your coordinates are 1, 2, and that is your whole state. In a more complex environment, the state might involve other things that the agent can be observing. But the point here is that it is passed as a vector. And the thing is that doesn't happen in real life. In real life, yeah, except for GPS systems and other things like that. But in real life, what do we use most of the time? We use our senses. We use our eyes. Even in GPS, it's not built into our brain. It's not telling us the coordinates through our brain. And so we're still using our eyes to look at the GPS and understand what's going on there. And so this is kind of cheating for AI to be able to get like information about the environment as a vector. It's too simple. It's not how it works in real life. That's not how we as humans operate. And ultimately, we want to create artificial intelligence which can operate in a similar fashion to humans, which is as can take on the same challenges as humans. And so in the human world, we don't have that. We don't have these coordinates or other types of vectors that are passed to us that explain the state we're in that environment. So we're going to have to remove that to make it more realistic. And then what can we replace it with? What do we see, or what do we do as a human to get information? Well, most of the time we see. Of course, we use all of our senses, but most of the information that we're getting about the world around us comes through our sight. And that is why we're going to change that little arrow which we had into a whole convolutional neural network. So this is from our annex number 2. We've got the convolution layer, and that's why it's important to be quite comfortable with convolutional neural networks and how they work. So if you've done our deep learning course, then you should be comfortable with that, or you can just have a look at the annex number 2. We've got some very good intuition tutorials there. So here we've got the convolution operation which happens. So we're actually going to be looking at this as an image. So this is an image of net environment, and so the agent is actually looking at the environment. So in this case, not that he's like looking from within there, he's like looking, like let's say he's playing this on a computer and he can see this environment, and therefore he can see like where this figure representing the agent is actually is. So you can see this whole environment, or whatever a human would see. If it's actual maze, then the human would see the maze from inside, and so the agent should be able to see exactly the same thing. So whatever he sees is goes through a convolution layer, then goes through a pooling layer, goes through flattening. Again, you can find out more about these different parts of the convolutional neural network in the annex. And then after it's flattened, then we have inputs which go into the neural network. And this is way more realistic because the agent has to use their sight, or has to process images which the environment is supplying to the agent, just as a human would be processing images. And the beauty of this is not just that it's more realistic and it's kind of like more as the agent's actually more as a human would be, but it allows us to process much more complex environments. For instance, this is how we can play Doom or other games like that, because instead of just getting a vector of information, which somebody would have created for us in this environment, we can just hook up our artificial intelligence to any environment, which as humans, we would have a vision of this environment. So we, as a human, when you're playing this game, you can see exactly this picture. And that's exactly what the artificial neural network or the agent would see now. So in this part of the course, when you're going to be programming the practical tutorials, the agent will actually see this exact picture. It will see the pixels. It will get this exact picture of all of the pixels, with this person, with this gun, with this face, with this percentage, with everything. Exactly what we see here. That's exactly what the agent will see. Then it will have to dissect that through convolution layer, pooling layer, flattening, and then it will go into a neural network. And needless to say that the neural network will actually be much more complex than that. So let's replace it with something like this. This is not much more complex. This is looks a little bit more complex, but in reality, the neural networks you're going to be working with and creating with Adlan are going to be quite interesting. They're going to be much more complex than this. But as you can see already here, even if we just have 5 inputs instead of 2, things become much more complex. And here you can see we have many more actions that the agent can take. So in the game of Doom, turn left, turn right, look down, look up, run, shoot, reload, or all those different actions that are possible in first-person shooter like Doom. And moreover, it doesn't have to be that. You can attach this agent to another type of game. That's the beauty of it, that it then realizes that it can now operate any kind of environment that you attach it to, because as long as there's like a visual representation of that environment, it's already got the whole infrastructure, the whole structure is ready to process that. So that's what deep convolutional Q-learning is all about. So we're taking it even to the next step. We're adding convolutions into, or the convolutional layers into our agent's brain now. And we're making it even more complex, and therefore we're rewarded with being able to solve even more complex challenges. So I hope you're very excited about this. This is going to be an epic section, and we're going to create some amazing things. And I can't wait to see you on the next tutorial. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're going to cover off quite a complex tutorial called eligibility trace, or n-step Q-learning. And this is something that we're going to implement in the practical side of things, so that's why we need to cover it off. And at the same time, it is quite a complex topic, so I've got a very interesting approach to getting us up to speed with the intuition behind it. So I have like a different approach in mind than we're used to. So let's have a look at that and see how that goes. So I'm going to give you an example to start off with. Like, I'm going to give you an example in this tutorial, and that will demonstrate the power of eligibility trace, and it'll give us the intuition behind things. And then if you like to delve further into eligibility trace, I'll give you the best place where you can read about it. I'll give you a reference to a book. But otherwise, so why this is going to be different is because we're going to first look, rather than delving into the intuition, we're going to look at an example, and the intuition will become obvious after we talk about it. And that's my hopes for this tutorial. So let's have a look. Let's see if we can do this. So here we've got 2 agents. and they're navigating the same environment. And we're going to see how these two agents work. The first one is going to work without eligibility trace. Second one is going to work with eligibility trace, and hopefully we'll see why the second one is going to be so much more powerful than the first one. So let's have a look. We're going to look at this agent first, and the way he operates is the exact way that we've discussed deep Q-learning so far. So the agent is going to take a step, or is going to take an action, move into a new state. It's going to get a certain reward. It's going to put that reward through its algorithm, update the neural network that's running this agent, or that's running in the mind of this agent. So that's basically how it's learning from the environment. Then it's going to take a new step. So from this new state, it's going to take a new action based on what its neural network is telling it to do. It's going to get a reward, it's going to update, and so on. And it's going to keep doing that. So obviously this agent is going to do quite a good job. And as we've seen previously from the previous practical tutorials, we're going to get some quite good results here. But now we're going to add a new feature. Now this agent number 2, this guy over here, he's going to navigate the same environment, but he's going to use the eligibility trace. And this is what it means. What he's going to do is he's going to take n steps. He's going to take, in this case, 4 steps. He's going to take 4 steps, and then only after taking these steps will he calculate the total reward that he got from those steps, and he will put it through his network. He will put it through his neural network that's governing the decision-making process, and then the neural network will learn from that. So which one, right away, like which one do you think is more powerful? The guy that is just taking one step at a time and kind of like poking in the blind or in the dark, and he's like, okay, so I'm going to take a step, see what happens. I'm going to take a step, see what happens. I'm going to take a step, see what happens. The guy at the top. Or the guy that takes just very courageously marches through 4 steps in a row, and then he decides whether those were good steps or not altogether. And why you can see here, or why you're probably getting a sense for why the second guy is better or is more powerful, is because the second guy actually knows what's at the end. The first guy, when he is assessing whether this step is good or not, he's only looking at the reward that he's getting. And so he's only guided by the reward the environment is giving him. Same thing here. He's only guided by the reward that this environment is giving him here. So every time, that's his only kind of compass that he has, the reward, the reward, the reward. Whereas here, he actually can assess, after taking all these steps, he can assess, oh, okay, so I did get to the finish line. So this combination of steps was good. All of them were good. Or, oh no, I ended up in the fire pit. Or, oh no, I didn't win my car didn't get to the finish line. Or I crossed the sand wall. Or I lost the game of doom, or something like that. And then he decides for himself that this whole combination of steps is bad. And therefore, for these steps that are earlier on, he has more information. He has more insights. Like in a very intuitive approach. This is a much more complex topic than we're portraying here, but in an intuitive way. For example, if we take this step only has information to update it. You only have information coming back from this reward here. And for this step, in this case, the same exact step, it has more information. It has information coming all the way from, okay, so what was the outcome after 4 steps or 5 steps or whatever? Yeah, so that is how it works. And why it's called eligibility trace is because during this process, not only does he look at the cumulative reward of this of what's going on, and then the cumulative loss, and then all of that is propagated through the network, but actually there's a trace of eligibility. That's why it's called eligibility trace. There's a trace that is kept in the algorithm, which says, okay, so if we do get let's say we get a punishment, we get a negative reward, then which of these steps is most likely to be eligible for that punishment? So not only do we know what overall this whole pattern or this combination of steps is, but we also keep a trace of eligibility. Which steps are we going to update if we get a reward? So for instance, if it's a negative reward, we might have an eligibility trace that indicates to us that this is the step that is most responsible for what we got in the end. Or if it's a positive reward, again, we might know the algorithm helps us keep track. This eligibility trace algorithm helps us keep track of what step or what action is eligible to be updated based on that reward that we get. And that's why it's called eligibility trace. And so that's the basic intuition behind eligibility trace. And hopefully these two examples of these two agents make it quite obvious or quite intuitive in why eligibility trace can be so powerful. And if, as promised, if you'd like to delve further into the topic of eligibility traces or end-step Q-learning, then a wonderful, amazing book which you can find is called Reinforcement Learning: An Introduction, is by Richard Sutton and Andrew Bartow, 1998. I think they're in the process of creating a second edition, or they've already created a second edition. But this is the most common, or the most popular, or the most referenced book on reinforcement learning. It's got a ridiculous number of citations. I think like tens of thousands, if I'm not mistaken. And also the chapter you need for this is chapter 7. So in order to look at eligibility traces, there's a whole chapter about it, chapter 7. You can read about it, and it goes into lots of detail, forward, backward eligibility traces, and also how you've got temporal difference on one hand, and on the other end of the spectrum you have Monte Carlo methods. In between you have eligibility traces. So eligibility traces are your link to go from temporal differences to Monte Carlo methods. Very interesting read, lots of pictures, which I really, really appreciated, very intuitive explanations. So there's lots of things that you can learn from this book about artificial intelligence and reinforcement learning, but specifically eligibility traces are like a very good place to go to, is this book for eligibility traces. And the second reference for today is something that Adlan's going to show you in the practical tutorials, the deep learning, or the Google DeepMind research paper on asynchronous methods for deep reinforcement learning. Yes, that's the paper. That's the one paper, that the A3C paper that we're going to be discussing further down in this course. We're getting closer and closer to it. And as you can tell, we're pretty excited about this. So this is going to be looking a little bit at how they implemented eligibility traces in this paper. So we're going to be using this more for the practical side of things. So hopefully you enjoyed today's tutorial, and now you're a bit more comfortable with eligibility traces. And I can't wait to see you next time. Until then, enjoy AI.
Hello my friends, and welcome to the practical activities of part 2 on deep convolutional Q-learning. I can't wait to start, because now we're gonna have a more challenging task of building an AI, because now instead of having just a simple vector of input state, with just one dimension, we will have images. Because indeed, with the convolutional part of the deep convolutional Q-learning model, well, we will have convolutional layers that will act as eyes for our AI. In other words, our AI will be playing the game of Pac-Man, because this is going to be our environment for Module 2. It will be playing the game of Pac-Man with its own eyes, which are exactly the convolutional layers. So this is super exciting. I can't wait to start to implement this, and therefore welcome to Gymnasium again. I'm going to introduce to you right now the environment we'll be working on for this part 2. So it's going to be in the Atari environments, of course. Then you're going to expand this to see more environments, because of course the environment we're going to play on for this Module 2 is Pac-Man. So you just have to scroll down a little bit and you will find it in the P's. Here we go, Pac-Man. Let's go inside. Alright, so let's have a look at the different important information here. First, I'm sure that you all know Pac-Man, that you played it at least once in your life. I remember playing it a lot of times when I was a kid, and I absolutely loved it. So I'm very excited to now build an AI to play it. And before we look at the action space, the observation space, I want to show you something important at the bottom of this page, which are the variants. Because now that we have a much more challenging task to do, since the input state is much more complex, well, we have to be reasonable and choose an environment that is not too complex for our AI. Because indeed, if we go, for example, with the Ali Pac-Man v5, well, we will need big resources to train our agent. And besides, you know that not every model can solve every environment, and actually the deep convolutional Q-learning model is not powerful enough to solve this particular variant of the Pac-Man environment, Ali Pac-Man v5, which is the most complex one. However, Two things to say about this. First, the A3C can solve this. That's the more advanced model we will build in part 3, even though we will build it for Kung Fu. And then the second important thing is that our deep convolutional Q-learning model we will build in this part 2 can solve some variants of this Pac-Man environment. And the one that is not too complex and therefore doesn't require too much computing resource for the training will be this one, Miss Pac-Man Deterministic V0. Now, the deterministic part in the name can be a bit misleading. Of course, it's not going to be a fully deterministic game. What they mean here by deterministic is that part of the other agent's actions will be deterministic as opposed to, intelligently stochastic. But that's only a part of it. Of course, most of the other agents' actions, the monsters, will have intelligently stochastic actions, but part of it will be deterministic so that it makes the environment less complex and therefore easier for us to train our deep convolutional Q-learning model, which is important because I want everyone in this course to be able to train our agent and not require too much compute-intensive resource, without which you wouldn't be able to get a good score at the end. Alright, so we'll choose this environment. It will be perfect to illustrate what the deep convolutional Q-learning model can do, and besides, it fits the resource we have in our Google Colab notebook. Okay, so now here we go. Let's do this. Let's take again that link I sent you just before this tutorial. So we're gonna open it in a new tab. Remember that I am in my new Gmail account just so that I can do everything with you from scratch. And so now it's just like I'm a student doing the steps with you. And well, the steps we have to do now is to go, of course, into the part 2 deep convolutional Q-learning folder. And then same, you will have the complete code with the full code and the full results, but don't look at it until we implement the whole code together and discover together the results in the end. Now, of course, what we're going to open is the partial code notebook. And then remember that this is a read-only notebook for the simple reason that everyone has access to it, and therefore no one should do any modification on this. Therefore, in order to be able to do some modifications and code on it, just like what we did in module 1, well, we're going to create a copy of this notebook by clicking File here and then Save a Copy in Drive. There we go. It is creating a copy, which we will find in our drive in the Colab Notebooks folder. If we refresh this, oh no, here it is. That's the copy that was just created, and now you own it. As you can see, the owner is now me in this particular artificial intelligence A to Z gmail.com account, as opposed to here where I was the owner from my other account. Okay, so now you are the owner. You can, if you want, rename this very simply Deep Convolutional Q-Learning for Pac-Man Partial Code. And now here we go. Let's open it and let's start coding. Let's start building our new AI, the Deep Convolutional Q-Learning Model for Pac-Man. I can't wait to start with you in the next tutorial, and until then, enjoy AI. Hello my friends, and welcome again to the implementation of our Deep Convolutional Q-Learning Model AI of Part 2, which we will be implementing for the Pac-Man environment. First of all, I hope that you made sure to create a copy of this partial code notebook you got from that link I gave you previously. And second of all, well, I hope you took the partial code so that we can implement our new AI together, just like before. This partial code notebook contains only the codes that are not essential to building an AI, not related to building an AI. So it will contain the code that installs the gymnasium library, just like before, that imports the libraries, and then that visualizes the result. And this is exactly the same code as before, only the name of the environment changes. Okay, and of course, in this new part 2, we'll implement all these cells, starting by creating the architecture of the neural network, and then we will set up the environment, initialize the hyperparameters, pre-processing the frames, implementing the DCQN class, Deep Convolutional Q Network class, initializing the DCQN agent, training the DCQN agent. Alright, so that's all we'll do in this new implementation. And the good news, actually, is that for most of the cells here, well, they will be very, very similar to the cells we implemented in our Deep Q-Learning implementation. Indeed, as you notice, this is the exact same structure, right? We start by creating the architecture of the neural network, and then in part 2, training the AI. If you look closely, well, we have the exact same series of steps here, setting up the environment, initializing the hyperparameters. However, we won't be implementing experience replay, but we will still have a memory for our AI, and we will just use an append function to store the different experiences. I'll show you how we will adapt this. but then of course we will implement the DCQN class and initialize the DCQN agent, training the DCQN agent. All right, and you will see that the codes for each of these cells, for each of these steps of this part 2, training the AI, will be extremely similar. So actually what we'll do is not re-implement all this. We will actually take from our code here and then just adapt to this new code, okay? Because you will see that even in those big codes like this one, that implements the DCQN class, or this one that implements the training for loop, well, we will only have 2 or 3 things to change. So as AI scientists, of course, we want to do this efficiently, and so that's how we'll do it. All right, so let's do this. Let's get it started. We're going to start by executing this first cell to install Gymnasium, right? Because we are in a new session, so we are in a new notebook in which Gymnasium is not installed yet. And there we go. Now it is installing, collecting Gymnasium, downloading Gymnasium. Then remember, it downloads all the dependencies like Fireman notifications and also Box2D and the other ones, Fireman notifications, Gymnasium. There we go, Gymnasium, and requirement already satisfied. That's probably because I was working on some other notebooks before in this account, but there you go, downloading AutoROM and other build dependencies. Perfect. Requirement already satisfied. Downloading another dependency here, installing collected packages, successfully installed AutoROM and build dependency. Okay, good, successfully upgraded. I can't follow. Downloading again Box2D, and there we go, build wheels for collected packages, Box2D PY. And in a few seconds now, because this is the last step, remember, in a few seconds now we will have all the Gymnasium packages and dependencies that we need to run our Pacman environment. All right, just like before. So it's going to take a couple more seconds and then we'll be good to go to build our environment and, most importantly, build our AI, our deep convolutional Q-learning model, playing just like a human the game of Pac-Man with its own eyes, represented actually by the convolutional layers in the deep convolutional neural network. All right, so this is of course much more complex and much more advanced than what we did before, but you will see that we will get good results at the end, because indeed we will be able to achieve a good score. What do we have here? Successfully built Box2D PY, installed collected packages, and all good. Successfully installed Box2D and Gymnasium and everything. We are all good to go. Now let's import the libraries before we get started with part 1, building the AI and creating the architecture of our neural network. Now a convolutional neural network, because our AI will have eyes. So there we go. Let's import those libraries. Importing Torch now, importing Optim, the Optim module, the NN module, neural network, the functional module to, use the activation functions, and the loss function, remember, for the training, and the and data loader and tensor data set. So once again, as you can see, this is the beauty of Google Colab. We didn't have to run some pip install commands in the terminal to install any of these libraries and modules. So we only had to install Gym, but this is done. This worked perfectly well. And now we're good to go to build our AI, and by that we mean, of course, creating the architecture of our convolutional neural network. All right, let's get some good energy. It's going to be a big code, of course, because we have a lot more layers than before. So get some good energy, get a good coffee, and as soon as you're ready, let's meet in the next tutorial to implement this. And until then, enjoy AI. Hello my friends, and welcome to this new step of this implementation, a very exciting step, because this is basically when we build the brain of our AI, but not only the brain this time, but also the eyes, because we're going to bring into the neural network some convolutional layers which will act as eyes in order to be able to see the input images from the game, which are nothing else than the states. All right, so we have a lot to build, we have a lot to architect, so let's do this. Let's fire away. So we're going to create a new code cell. And just like before, we're going to create a new class, which will be the network class, and which will inherit again from the module class by the NN module. So we call the NN module first, from which we call the module class. All right, and that module class is actually the base class for all neural network modules in PyTorch. Okay, here we go. Let's define the class now. And as usual, we're going to start with the constructor method, the init method. So here we go. Let's define that init method. All right, so our init method will take self as the first argument for the object. Then it will take the action size. And however, it will not take, like before, the state size, because this time the state is an image. It's not a simple one-dimensional vector. It's a multi-dimensional array representing the images, besides in 3 dimensions, with RGB. So we cannot simply enter the state size here, even though there is a state size, we will compute it afterwards. But basically, we will just need the action size for when we create an object of our network class, an instance of our network class. So action size, and then, however, just like before, we're going to set a seed with a default value of 42, just to ensure reproducibility. Okay? Alright, so now let's initialize all our object variables. But first, before we do this, remember what we have to do in order to activate the inheritance from the module class by the NN module. Remember we do this? Well, actually this time Google Colab didn't help us. I think that last time it helped us. But basically we call the super function, which takes as input first our network class and then our object self. And then there we go. Then we just add a dot and remember the init method. Alright, just like that. This is just in order to call the initializer of the base class, meaning the module class by the NN module, to correctly activate the inheritance by setting up the internal state of the class. Okay, so no need to understand more details of it, just know that we have to add this line, and then now we define our object variables. So, according to you, what is going to be the first one? Let's start with the easy one, self.seed, which remember we initialize by calling first the torch library, from which we call the manual seed function, which takes as argument, well, the argument we input here, the seed. Alright, just like what we did in our deep Q learning class. Alright, so now let's go back and next step, next object variable. So actually the next step now is where things get interesting, because this is exactly now that we start building the brain, including the eyes of our AI, the whole neural network. And according to you, what is going to be the first operation here? The first connection or convolution. I'm just giving you some hints here. Well, of course, the first operation is going to be a convolution, right? Because the eyes come first before the fully connected layers of neurons in the brain. All right, just like a human, the information, the signal comes first through the eyes and then it will go through the brain. And so here, that's exactly how we're going to build it too. We're going to start with the eyes. And so the next object variable I'm initializing here is going to be our first convolution, which I'm calling conv1. Okay, and how do we create it? Well, by of course calling the NN module, from which we are going to call the conv2D class. Okay, so conv1 will actually be an instance of that conv2D class. All right, and now very important, what are going to be the arguments of this conv2D class? Well, first, it's going to be the input channels. And since we're going to work with colored images, we're going to choose to have 3 input channels corresponding to the RGB channels of an image. So here we go. That's our first argument, 3. Then the next argument, as you see, is the number of output channels. And there is no rule of thumb right now to choose the optimal number of output channels. Just know that there has been a lot of experimentation to make this AI work on this Pac-Man environment. And well, a good number, probably not the optimal number, but a great one that leads to good results, is 32. Okay, so 32 output channels. Then the next argument, as you see, is the kernel size. And again, after a lot of experimentation, we find out that a good kernel size is 8 by 8. So I'm adding here kernel size equals 8, but that means we will use an 8 by 8 kernel. And finally, the last argument here will be, this time Google Colab doesn't highlight it, but it's going to be this one, the stride. All right. And again, after a lot of experimentation, we find that a good stride value is 4. All right. And that's our first convolution of our neural network. Congratulations, we have just built basically the first layer of the eyes of our AI. Of course, these are not the full eyes because we're going to make other convolutions, actually 3 more, with besides some batch normalization layers. But there you go, we have just architected the first layer. So congrats still. All right, now next step. So the next step, as I just said, is to define now a batch normalization layer for 2D inputs. And why do we add those? Well, that's because they will help in faster and more stable training. Okay, so that's very powerful in a convolutional neural network for training purposes. Okay, so let's add this. That's our next object variable, which we're going to call bn1 for the batch normalization operation. And again, our self.bn1 object variable will be created as an instance of a new class, which will not be the conv2D class, but of course, as you might guess, the batch norm2D class. So there we go, we call our NN module first, from which we call this batch, there you go, you have it here, batch norm2D class. And now, very simply, according to you, what will it take as input? we actually only have to input this one, the number of features. Well, just like when we do the full connections, it's basically the number of channels or feature maps in the previous layer. And well, the previous layer is a convolutional layer of 32 channels or feature maps, and therefore that's exactly what we have to input here, 32 channels. Okay, great. So now we're going to do 3 copy pastes, because we will actually create 3 more series of a convolution followed by a batch normalization operations. And so there we go. Let's get those 2 lines of code, and just below, let's copy them 3 times. Okay, and now we'll just change the parameter values, meaning the number of channels and kernel size and stride inside each new pair. So let's start with the second pair, this one corresponding to the second convolution and the second batch normalization. And so here we go, let's do this together. So here, for the number of input channels here, what do you think it's going to be? Well, of course, it's going to be what we have here, 32, okay? Then, for the number of output channels in this second convolution, what do you think it's going to be? Well, you can't really guess, but again, it's after a lot of experimentation. We find that a good number is actually 64, but again, there is not really a rule of thumb. What matters is that we gradually increase the depth, meaning the number of channels, while decreasing the spatial dimensions. So the number of channels will be increased through the different convolutional layers, while the kernel size and the stride will be decreasing. Then, what do you think is going to be the kernel size? Well, again, you can't really guess, but a good one is 4. And then what about the stride? Well, same, you can't really guess, but a good one is 2. Okay? For our particular environment with this particular AI that we're building. Okay? So, now, however you can guess it, what is going to be the number here for the second batch normalization? Well, of course, it's going to be the number of output channels in our second convolution, which is, of course, 64. So that we can guess no problem. Then let's take care of the third convolution, self-conv3, and the third batch normalization. Here we go. So you can guess the number here. What is it going to be? It is going to be, of course, the number of output channels or feature maps that we have here. Therefore, 64. Then, according to you, what is going to be the number here? Well, if we follow the logical sequence, we would be tempted to say 128, but no. There is no logical sequence here actually. It's still going to be 64. And again, this is just after some experimentation and hyperparameter tuning. Okay, so 64 again. Then for the kernel size, well, again, after some hyperparameter tuning, we get that a good kernel size here is 3. And then for the stride, same, a good one is 1. Okay, so that's for the third convolution. Now, what about the third batch normalization? What is going to be the number here? That you can guess, of course, is going to be the number of output channels in the previous convolution, meaning 64. All right, great. We're almost there. We're almost done with the eyes of the AI. Are you excited to be able to build such advanced things? I think this is very exciting. And plus, PyTorch makes it easy to build. So here we go with our final convolution, conv4, with the final batch normalization bn4. First, we can guess the number here. What is it going to be? It's going to be, of course, the number of output channels or feature maps in the previous batch normalization layer, which is therefore 64. Then, according to you, what is going to be a good or hopefully optimal number of output channels here in this fourth convolution? Well, remember, we want to gradually increase the depth, meaning the number of channels over the convolutions. And so since we didn't do it for the previous one, well, we're going to do it here, and we're going to add 128 output channels. Okay, so now what is going to be the kernel size for our final convolution, conv4? Well, same as before, a good one will be 3. And then for the stride, again, a good one will be 1. Okay? And finally, what is going to be the final number of channels here or feature maps? Well, of course, it's going to be that number here that we had in the previous convolutional layer, meaning 128. And that's it, my friends. Huge congratulations. You just built some artificial eyes for an artificial intelligence, which now, thanks to what we've done, our AI will be able to look at images, the images of the game, in order to understand what's happening in the game and therefore play the game and therefore win the game. Okay? But winning the game will be, of course, thanks to our implementation of the fully connected layers, which will be the layers that will be able to understand the logic, and besides, with the deep Q-learning algorithm that we will implement in the training for loop. Okay? So huge congrats again. That was very exciting to build this. Now we're going to take a little break, of course, and in the next tutorial, as soon as you're ready, we will build the fully connected layers of our neural network. And until then, enjoy AI. Hello my friends, welcome back to the implementation of our network class, more specifically our convolutional neural network, for which so far we have built the convolutional layers and the batch normalization layers. And now, well, of course, what follows the convolutions are, of course, the full connections, right? Just like in a human brain, first the signal comes through the eyes, so we built the eyes first here with the convolutional layers, and then the signal goes from the eyes to the brain, which will be represented here by our full connections. Alright, so here we go. Let's start with the first full connection, which we're going to call, like last time, FC1. Self.fc1, which will be created as an instance of course, the linear class, which is a class that can build a full connection to build fully connected layers. And now the big question is, what is going to be the first argument here for the number of input features? Well, it's not that direct to get that number because it's actually going to be the number of output features resulting from flattening all the previous convolutions. You know, that final flattening layer coming after the convolutions, well, that's this number that we're looking for here. How many neurons there are in this flattening layer. And well, there is a formula for that. The formula, if I remember correctly, is the input size minus the kernel size plus 2 times the padding, all that divided by the stride, and then plus 1. So you would need to apply this formula here first to get the output size of the first convolutional layer, then to apply this formula another time here to get the output size of the second convolutional layer, then another time here to get the output size of the third convolutional layer, and then finally another time here to get the output size of the fourth convolutional layer. And then by applying this formula 4 times, you would end up with the final output size of the flattening layer, which would be the input size of our full connection here. And so, well, we're just going to enter that formula without doing the whole computation. It's going to be 10 times 10 times 128. Okay, that's the output size resulting from all the convolutions we had before, which therefore is the input size of our first full connection here. All right, now, what is going to be the number of output features in this first full connection, meaning the number of artificial neurons in the first fully connected layer? Well, again, no rule of thumb, but a good architecture that works well here after some experimentation and hyperparameter tuning is actually 512 artificial neurons or output features in this first fully connected layer resulting from this first full connection. All right. Now, let's move on to the second full connection. Indeed, there's going to be another fully connected layer before the final output layer containing the action values. So let's do this. Let's build another full connection, self.fc2, which again will be created as an instance of the linear class because it's going to be another full connection leading to a new fully connected layer. Now, the number of input features is of course going to be the number of output features in the previous full connection. So therefore 512, and however now what is going to be the number of output features in this new fully connected layer resulting from this second full connection? Well, again, hard to guess, but after some experimentation and hyperparameter tuning, a good value here for the number of output features in this second fully connected layer is 256. Okay, all right, great, we're almost there. Let's copy this second full connection to create the third full connection. So I'm going to replace here FC2 by FC3, then replacing of course the 512 here by, well, it's going to be the number of output features in the previous fully connected layer resulting from the previous full connection, therefore 256. And now finally, what is going to be the final output size of our final output layer? Well, that's of course going to be the action size because it will return the action values. Alright, so we are done with our new full connections. Now we have basically the artificial neurons of our AI's brain that will be able to understand and learn the logic in the Pac-Man game, which of course will be understood with the deep Q-learning algorithm. Alright, so now what else do we have to do? Of course, we have to implement the forward method, to forward propagate the signal coming from this time the eyes and then through the artificial brain of the AI represented by the fully connected layers. So I can't wait to implement this method with you in the next tutorial. Try to practice it by yourself first, and once you're ready, let's mash this together in the next tutorial. And until then, enjoy AI. Hello my friends, and here we go. Now that we've implemented the convolutional layers and the fully connected layers of our AI's brain, well, let's define the forward method to forward propagate the signal from first the Pac-Man images to the eyes, and then from the eyes to the fully connected layers, and finally from the neurons to the body of the AI, let's say, that will be playing the actions. Alright, so let's do this. Let's start by defining this new forward method, which remember takes as input, well, first of course self for the object, and then state, which are the images. Alright, then colon, and here we go. So let's make some space, and let's implement the forward method. So what is going to be the first step here? Well, it is to forward propagate the signal from the images to the first convolutional layer of the eyes. So let's do this. Well, how do we propagate this? Very simply, we're going to call our first convolution self-conv1, which of course is going to take as input the state, which is the image of the game Pac-Man. Okay, so that basically forward propagates the signal from the state to the first convolutional layer. And now let's continue this forward propagation. Let's now forward propagate the signal from this first convolutional layer to the first batch normalization layer. And how can we do this very efficiently? Well, very simply by calling our self.bn1 object, which is our first batch normalization operation, which is going to take as input, of course, well, this signal propagated from the state to the first convolutional layer. Okay, perfect. Then let's activate this thanks to the rectify linear unit activation function, also called the rectifier activation function, also called famously ReLU. And so how do we do this? Well, we're going to call our F module, the functional module, from which we're going to call the ReLU function, which will take as input all this signal, first propagated from the state to the first convolutional layer, and then from the first convolutional layer to the first batch normalization layer. Alright, great, so now we have this signal, and so let's create a variable for this signal, which we're going to call x, and which will be equal to all this. Okay? Great. And now the hard part is done. It's going to be super easy from now because we're just going to do some copy paste, because indeed the next phases of the forward propagation will be exactly the same by calling the convolution first on the signal x, and then calling the batch normalization, and then activating the signal with the ReLU function. So we're going to take all this, we're going to copy and paste it here. And now, according to you, what do we have to do in order to forward propagate the signal from our first batch normalization layer to the second batch normalization layer? Well, very simply, we're first going to replace here state by x, and then of course conv1 here by conv2, so that we can now forward propagate the signal coming from the first forward propagation to the second convolutional layer. And now we're going to forward propagate the signal from the second convolutional layer to the second batch normalization layer. And there we go, we are done. Now this signal x is forward propagated from the second convolutional layer and then to the second batch normalization layer. And so now let's copy this again to paste it right below, because indeed now we're going to forward propagate our signal x from the second batch normalization layer to the third convolutional layer thanks to our conv3 convolution operation. And then, of course, we forward propagate the signal from the third convolutional layer to the third batch normalization layer thanks to our third batch normalization operation. And that's done. Now the signal x is forward propagated to that third batch normalization layer. And finally, let's do that one last time. Let's copy this to paste it below and replace, of course, conv3 by conv4 in order to forward propagate the signal from the third batch normalization layer to the fourth convolutional layer, and then forward propagate the signal from the fourth convolutional layer to that fourth batch normalization layer thanks to that fourth batch normalization operation. Great, perfect. So we are done with those 4 sub-steps of this forward propagation. And now we just need to do a little reshape in order to reshape the tensor, in order to, flatten it. That flattening step coming after all the convolution operations. Well, that's exactly what we have to do right now. We have to reshape x in order to get that flattening layer in order to fit into the fully connected layers that come next. Okay? All right, so let's do this. How are we going to flatten our tensor? Well, we take x first, from which we're going to call the view function, which will take as input first x dot size 0, and then for the second argument here we add -1. And what does that do? Well, that reshapes the tensor so that the first dimension corresponding to the batch remains the same and the other dimensions are flattened. Okay, so that basically flattens the tensor while keeping that first dimension of the batch. Okay, perfect. Then, now that we have the flattening layer, now that the tensor is flattened after all these convolutions and batch normalization operations, what do we have to do next? Of course, the forward propagation is not over. Now we need to forward propagate the signal from this flattening layer up to the final output layer through all the fully connected layers. And so how do we do this? Well, we know exactly how to do this. We did this in part 1 when implementing the deep Q-learning model. We're simply going to use our 3 full connections here. Alright, so let's do this. Let's take our signal X, then let's forward propagate this signal X from the final flattening layer to the first fully connected layer thanks to our first full connection self.fc1, which takes as input X, of course. And then let's activate this new signal thanks to the ReLU activation function. And this will result in a new signal X. Okay, and that's it. Now let's do some 2 more copy paste to smash this. So I'm copying this, I'm pasting the next one below. And of course, here we're going to replace FC1 by FC2 in order to forward propagate the signal from the previous fully connected layer to the second fully connected layer thanks to this second full connection. Alright, and finally, next and final step, we're going to return the signal in the final output layer containing the action values after forward propagating this signal from the second fully connected layer through the third full connection thanks to our self.fc3 full connection object, which takes as input X. And that's it, my friends. We are now done with the whole forward propagation, propagating the signal from the input images to the convolutional layers and the batch normalization layers, and then to the final output layer containing the action values through our 2 fully connected layers. So there we go. Now I guess you feel like masters of forward propagation. We did some great work here, and of course I want to say now congratulations, because we are now ready to move on to part 2, training the AI. Indeed, our AI now has some eyes and a brain, so we can train that brain into playing the game of Pac-Man. And we'll do all that in part 2, following those steps, which are almost the same steps as before, and we will use the codes we implemented before to do this efficiently. So there you go. I can't wait to see you in part 2 to train our AI, and until then, enjoy AI. Hello my friends, and welcome to this new tutorial, and mostly welcome to part 2, training the AI. Indeed, we now have an AI with a brain that besides has some eyes in order to be able to visualize some images, which will be the images of the game. And now, well, it's time to train that brain to play this game and get a good score at the end. So let's do this. We're going to start with the first same step as last time, setting up the environment. And well, since it's almost the same, well, what we're going to do is take our previous implementation, we're going to take the code that sets up this environment, and we're going to paste it back into a new code cell here to set up our new environment. And so what do we have to change here? Well, only one thing. That's of course the name of the environment. It is no longer Lunar Lander, but of course Pac-Man. And remember that we chose this variant, Miss Pac-Man Deterministic V0. Deterministic means that a small part of the actions of the other agents, meaning the monsters, will be deterministic. That will make the environment less complex. And V0 means that it's actually the initial version release. Alright, so we'll choose this. It is really the best for us to start, and mostly for us to train the deep convolutional Q-learning model, which is a powerful model but not the most powerful one, especially if we compare to A3C, which can solve here the most complex variants, including this one. So there we go, this one will be perfect, and besides we'll be able to train the model with the resources we have in our Google Colab notebook. Alright, so let's take this one. We're going to go back to our implementation, and we're going to replace Lunar Lander V2 by Miss Pac-Man Deterministic V0. And besides, just to decrease even more a little bit the complexity, we're going to enter here the full action space to be false. Alright, and that will basically ensure that the agent uses a simplified set of actions for Miss Pac-Man. And again, that will decrease a little bit the complexity of the environment, which will be better for us to train the model without having to wait too long or without having to have too much compute intensive resource. Alright, perfect. So now, well, we're done. We're done with this code cell. I told you it's almost the same as before. So let's run this cell, but first I remember that I forgot to run the previous cell, which builds a network class. So I'm gonna run it now and everything should be okay. There we go, perfect. We have the network class, and now let's run this cell to, by the way, remember, get the state shape, get the state size, and the number of actions. If you want, we can have a quick look at it. If we go back to the top here of the Pac-Man environment, well, we see that the action space is discrete 5, which makes sense, right? Pac-Man can turn left, turn right, go up, go down, and the fifth one might be do nothing, or, continue in the same direction. And this is the observation space, but I will tell you more about this when we make that preprocess frames function. All right, great. So let's go back to our implementation and, well, let's run this cell to see the state shape, the state size, and the number of actions. So what do we have? All right, so the state shape is images of dimensions 210 by 160 and by 3. So these corresponds to the RGB channels, the 3 channels of colored images. The state size is 210, but here that doesn't make that much sense. And besides, we won't use it for our implementation, so you can actually ignore this. And finally, the number of actions, well, 9. Okay, interesting. We just saw that the action space here is discrete 5, but maybe that's actually for the Pacman v5 environment, and Miss Pacman deterministic actually contains more actions. Let me know in the comments what you think those actions are. Feel absolutely free to discuss, what you're learning through the tutorials, and if you want to make a comment, for example, you might know some things more than me, and well, I'm more than happy to discuss these things with you. All right, so let's go back to the implementation, and there we go. We're done setting up the environment. So now we're going to move on to the next step, initializing the hyperparameters, and of course, we'll do that in the next tutorial. And until then, enjoy AI. Hello, my friends, and welcome to this new step of the training implementation, initializing the hyperparameters. So it's going to be a super easy and quick tutorial because actually, as we said, we want to make this efficient, and therefore we're going to take the code from our previous implementation because you will see that it's actually going to be almost the same parameters. So in a new code cell, I'm going to paste that code section. And now indeed, well, the learning rate will stay the same. We'll take that same value of the learning rate. It actually appears to be a good one too for this Pacman environment and the deep convolutional Q-learning model. But after all, it's almost the same algorithm. It's just that now our AI has eyes. Then the mini batch size, well, we will actually change that. We will reduce it a little bit to 64. It appears to be a better hyperparameter value for the Pacman environment. Then for the discount factor, well, we will keep the same value of 0.99. It also appears to be a good one. And in general, we do want to reduce by very little the epsilon variable in the epsilon greedy strategy. Then for the replay buffer size, well, actually, we won't implement again the replay memory class as we did in module 1. However, we will still implement experience replay. Only we will do this in a much more simple way, not through the replay memory class. And therefore, since the replay buffer size was actually a hyperparameter of the replay memory class, well, we won't need it for our deep convolutional Q-learning implementation. And however, the interpolation parameter, well, we will simply remove it because we won't do any soft update. And why is that? That's because, very simply, the soft update doesn't really improve the training performance, neither the final results for this particular deep convolutional Q-learning model in this particular Pacman environment. I checked, so no need to implement any soft update in our future agent class. All right, so that's it. We're now done with initializing the hyperparameters. Now we're going to move on to the next step, preprocessing the frames. I can't wait to do that with you in the next tutorial, and until then, enjoy AI. Hello my friends, and welcome to this new step of the training implementation. We just initialized the hyperparameters, and now we're about to preprocess the frame. So now, before we start, I want to highlight something very important. Remember, in the previous implementation of Deep Q-Learning, the step after initializing the hyperparameters was to implement experience replay. Although now we won't do the same for our implementation of deep convolutional Q-learning, simply because now the input states are no longer input vectors of a small size, they are now input images of a big size, because there are many more dimensions. So you can imagine that unless our AI has a super powerful memory, well, we can't store 100,000 experiences containing all these images in the memory of our AI. And therefore, that's exactly why we have to not only make a simpler implementation of experience replay, we will still have experience replay implemented in the DCQN class, but most importantly, we have to pre-process the frames so that the input images can be converted into PyTorch tensors that are accepted by the neural network of our AI, meaning first the eyes represented by the convolutional layers, and then the brain, the artificial neurons represented by the fully connected layers. So that's exactly why we're not implementing experience replay, but most importantly, we are pre-processing the frames so that they can be fed into the neural network of our AI. All right, that's what I wanted to highlight. Now, there we go. Let's do this. Let's implement this new code cell. So First of all, we're going to import a new class which is called image and which is taken from the PIL library, which is the Python imaging library, and which will allow us to load images from files and create new images. Okay? So we will basically need that for the image preprocessing. And so here we go. We start from PIL, the PIL library, from which we import the image class. Great. Then we will also need the transforms module from the Torch Vision library, and therefore I'm going to start from the Torch Vision library, from which I'm going to import this transforms module, and now there we go, we can implement this new function. So we're going to call it preprocess underscore frame, which will take as input, according to you, what exactly? Well, of course, the frame, right? The frame meaning the real frame coming from the game of Pac-Man, which then will be converted into PyTorch tensors, of course. Okay, so here we go. That's the only argument it has to take. And now let's define what this function has to do. All right, so right now we have a frame, right? The frame of the game, one frame of the Pac-Man game at a particular time. But in what form is this frame? It is in the form of a NumPy array, which represents exactly the image. And so the first step we have to do here is to convert this NumPy array, which is our frame, into a PIL image object, because we will need that for the next steps of the image preprocessing. All right, so how we're going to do this? Well, first we're going to update our frame. Right now it is a NumPy array and we want it to be a PIL image object. And so to convert this into a PIL image object, we're going to use our image class, from which we're going to call the fromArray method. All right, which will take as, of course, our frame now in the form of a NumPy array. All right, perfect. So now our frame here becomes a PIL image object, which is exactly what we need for our next step. And so now what is the next step? Well, now is the time to do the main preprocessing, the preprocessing that will lead to that PyTorch tensor that our neural network expects, you know, the neural network of our AI. And so what we're going to do now is create an object which will be a preprocessing object. Basically, it is an object that will preprocess our frames, but in the format of our PIL image object that we just got thanks to the fromArray method. And so there we go. Let's define this new preprocess object, which will be created as an instance of the compose class. And this compose class is taken from the transforms module, which we just imported from the Torch Vision library. And so there we go. From this transforms module, we're going to call the compose class, which will take as input only one argument here that we absolutely have to input, which is a list, which is why I'm entering a pair of square brackets here, a list that will contain the different transformations we're going to do through our preprocess object. Okay, so what is going to be the first transformation is going to be a resize of our frames, because indeed, remember that the frames will have this dimension. We can actually also see it, remember, in the setting up the environment code cell. This is the original dimensions of our frames, 210 by 160 by 3, corresponding to the 3 RGB channels for colored images. But there you go, these are the original dimensions, and actually, if we keep those dimensions, we will have a very difficult training. We not only need to lower the dimensions, but also make squares, which is why we're going to have, after the image preprocessing, dimensions of 128 by 128. And that's, of course, for the convolutions that we applied to our preprocessed images. Here with the first convolution, we have the 32 filters here, which filter the preprocessed frame converted into torch tensors while applying the convolutions, and therefore having dimensions of 128 by 128 will make it easier than having those dimensions. And that's exactly why here the first step of this transformation we have to input in the compose class is to indeed resize into 128 by 128. And be careful, here I included two parentheses because actually these are the dimensions entered into a pair, which is the argument of the resize class. And by the way, this resize class has to be called from the transforms module again, which we imported here from the Torch Vision library. Okay, so that's the first transformation, and now we have to enter the second one, which is of course the conversion into a PyTorch tensor. And so how are we going to do that? Well, first we're going to call our transforms module again, from which we're going to call this time the toTensor class. And this will exactly make the second part of the image preprocessing, which is to convert RPL object frames, first resized into 128 by 128 dimensions, and then converted into a PyTorch tensor. Okay? And you also have to know that this transformation will also normalize the frames, meaning that this will also scale the pixel values to the range between 0 and 1. Alright? And now, well, we just have one final step to do, which is to return the preprocessed frames. And to do so, well, we're going to call our preprocessed object, of course, which will take as input, of course, our frame.pl image objects. Perfect. And now, according to you, are we done? Well, almost. Remember this very important thing we have to do most of the time in deep reinforcement learning. Let's never forget that extra dimension of the batch. Remember that our frames always need to be in their corresponding batch, and in order to keep track of which batch each frame belongs to, well, we need to add this extra dimension of the batch, and you know how to do this. We did it many times already in the previous implementation. Of course, we're going to use the unsqueeze method, which will just take as input one argument, which is the index of that dimension of the batch, and usually we set that as the first dimension, and so we're going to enter 0 so that the dimension of the batch will be the first dimension. Alright, and we're done with the preprocessed frame function. So now we're going to integrate that function, of course, in the DCQN class, which we will be implementing in the next tutorial. So there you go. That's exactly our next step here, implementing the DCQN class while integrating experience replay and image preprocessing. Let's get some good energy to do this. And as soon as you're ready, well, join me in the next tutorial to smash our DCQN class. And until then, enjoy AI. Hello my friends, and welcome to this new step of the training implementation, that very exciting step, implementing the DCQN class. And the good news for us right now is that it's going to be almost the same as the DQN class we implemented before for our deep Q-learning model. So of course, as efficient AI scientists, we're going to select this whole code, copy it, and we're going to paste it in a new code cell of our deep convolutional Q-learning implementation. There we go. And now let's do the little changes to adapt this to our deep convolutional Q-learning model. So of course, what I'm going to do first is zoom out a bit because the code cell is huge. But of course, in the comments, feel free to let me know if it's too small. I just want us to be able to see the whole code so that we can, manage those changes more easily. So let's do it one more time. I hope it's going to be okay. Okay, I think that's enough. I'll do some scroll up and scroll down, but let me know if the zoom out is too strong, okay? So, first of all, what is the first very easy update that we have to do here for our deep convolutional Q-learning model? I'll give you a hint. This is exactly where the cursor is right now. Of course, what I'm talking about is the soft update. Indeed, as said before, we're not going to do any soft update for our deep convolutional Q-learning model for Pac-Man because indeed, I experimented this before. It doesn't really improve the training results. So let's remove this. And what is the next thing we have to do? Well, it's the same hint. It's again where my cursor is. Of course, we have to remove this row in the learn method that indeed calls the soft update method to perform the soft update. So let's remove this, and there we go. Okay, good. Good changes done. Now, what according to you is the next step? Well, maybe now is the time to check for those changes from the top. Alright, so let's do this method by method. We're gonna change the little things to adapt this to our deep convolutional Q-learning model. And let's start with the init method. Alright, so first, do we have to change anything in the arguments here? Well, yes, of course. For our new use case, training an AI to play Pac-Man, well, the state size doesn't make much sense. So we're gonna remove it. Not only it doesn't make much sense here because of the image's input, but also we won't use it. So we remove it. And also, let's not forget that, let's also remove it in the network class, because indeed, the network class no longer takes as input the state size. So I'm removing it here as well. Here we go. Done. Perfect. So good first change done in the init method. Now, what is the next obvious change we have to make? Well, this one, of course. Remember, previously in our deep Q-learning implementation, the self state size was indeed an object variable of our agent class, but not anymore for the same reason we just mentioned. So let's remove it as well. And now, what is the next obvious change? Well, of course, it has to do with the memory. But be careful, we still want to implement experience replay. So The only thing we're going to do here is just remove the replay memory class because we haven't implemented it in this new deep convolutional Q-learning implementation. So let's remove it, and instead we're going to replace it with a simple double-ended Q, which remember we get thanks to the deque function, and which takes as argument the capacity, but the name of the argument is actually max len. Okay, and so far we're going to set that to 10,000. Okay. All right, and now, is there one more or one final thing we need to change? Well, yes, but that you can't really know. It's because actually what we did here in the step method of our deep Q-learning agent previously, sampling the experiences and learning every 4 steps, well, we're no longer going to do it for our deep convolutional Q-learning agent. And that's because, we are making a simplified version of experience replay, which doesn't use this. So we're not going to use self.tstep object variable, so we're going to remove this, and now we're done with our init method. Okay, so since we just removed self.tstep, well, let's also remove it here because we won't use it. So let's do this here and here as well. Okay, so now we completely got rid of self.tstep. And now, according to you, what do we need to change in our step method? Well, it's pretty obvious again. Push here is a method of the replay memory class, but since we haven't implemented it for the deep convolutional Q-learning model, well, of course, we're not going to use it here. So I'm going to remove this line of code, and now let's see what else we have to update here in the step method. Alright, so first let me just fix the alignment here super quickly, so I just have to do it like that. Same for here and this, and all good. So now, what do we have to change here in this step method? Well, remember what we just removed. We just removed that push method that indeed appended an experience into the memory. And so what we need to do is actually replace this append through the push method by a simple append. And well, for that we have the append function. So that's exactly what we're going to do now in this step method. But before we do this, according to you, what do we have to do? Basically now we want to append this whole new experience here in the memory, just like we did before in the step method of our deep Q-learning agent. And so, well, we have everything to append to the memory, but the state and the next state are not pre-processed yet. And in fact, in the memory, they should be already pre-processed because then they will be fed into the neural network. And so the simple thing we have to do here to start with in the step method is just to pre-process the state and the next state, which so far are NumPy arrays because they're coming from the images of the game. And so we just want to pre-process them to make them ready to be first added into the AI's memory and then fed into the neural network. So let's do this. Let's first update the state. And to do this, we're going to call, of course, our preprocess frame function, which will take as input what? Well, of course, our state, but so far in the form of a NumPy array. So here it will be a NumPy array, and then it will be a PyTorch tensor that is, remember, resized and normalized. All right, so that's done for the state. Now let's do the same for the next state. And so, well, let's just add here next underscore and here next underscore, and done. The next state is now preprocessed. Perfect. So now what can we do? Well, we can append this whole new experience of the preprocessed state, action reward, preprocessed next state, and done into the memory. So let's do this. Let's call our memory object, not coming from the replay memory class, but simply created as a double-ended queue. And then, well, since it's a double-ended queue, we can call the append function, the classic append function, to append what? Well, the tuple of all this, the whole experience composed of the preprocessed state, the action, the reward, the preprocessed next state, and done. Alright, so I'm copying all this, I'm pasting that into that tuple of the experience, and now we're done adding this new experience to the memory. Alright, so now let's check the end. Are we all good here with those last 3 lines of code of our step method? Well, there is a little issue here. Can you see it? Well, I'm going to tell you it has to do with this. You notice this self.memory.memory? Remember, we had this before because previously the memory was first created as an object of the replay memory class, and this was exactly the object. But then we also had the memory attribute. But now our self.memory is not created as an instance of the replay memory class, and therefore it doesn't have a memory attribute. So we just need to remove the memory attribute here and only keep our self.memory object variable. Okay, so we're all good here. And now, according to you, do we have to change that line of code? Well, yes, of course, because again, previously we implemented this sample method, in the replay memory class of our deep Q-learning implementation, but now we no longer have the replay memory class. And so how can we replace this by a simple sample function that will sample some experiences from the memory? Well, by simply calling the sample function from the random library, which we imported before. So that's exactly what we're going to do. I'm going to actually take all this self.memory and simply replace this by random. Okay, great. So basically we're calling the sample function from the random library, which will take what as input? Not directly 100, but first it has to take our memory, self.memory, because we have to sample from the memory. And then it will also take the number of elements we want to sample, which is of course our mini batch size, which was a variable we initialized before. And therefore let's do this. Let's enter that other argument, which is k here, and which is equal to mini batch size. All right. And now finally, do we have to change anything in that last row, self.learn experiences discount factor? Well, good news, no we don't, because we'll still use that learn method to update the parameters of the model when we call the step method at each step of the training. So basically we're done. We have successfully adapted the init method and the step method for our new agent class of the deep convolutional Q-learning model. And so now we're going to do a little guessing game, but only with one question. The question I have for you is, do you think we have to change anything inside this act method? Alright, that's the question. I'll give you the answer in the next tutorial, and we'll see in the next tutorial if we have to change anything in the act method or if we can directly update and adapt the learn method for our deep convolutional Q-learning model. So think about this and we'll do what's necessary in the next tutorial. And until then, enjoy AI! Hello my friends and welcome back to the implementation of our DCQN class. In the previous tutorial we adapted the constructor init method and the step method, and by the end of it I asked you a question, which was, do you think we need to change anything in the act method in order to adapt it once again to our new DCQN agent class as opposed to the previous DQN agent class? And the answer to the question was yes, we had to make one single change, which had to do of course with the state, because indeed here previously we applied the torch.fromNumPy function to convert the state into a torch tensor, because the state was an input vector of one dimension. So this was a perfect fit. But now our input states are input images, and therefore we can no longer use this torch.fromNumPy function. And so how do we need to change this? Well, that's of course thanks to our preprocess frame function we defined before instead of experience replay. So let's do this. And besides, the good news is that in the preprocess frame function we already included the unsqueeze, to add this extra dimension of the batch. So we won't have to do it again. However, we haven't included this to send this to the proper device, and so we will keep this. Therefore, the only thing we have to do now is just take all this, torch from NumPy up to unsqueeze, and then just replace this by preprocess underscore frame function, which will take, of course, as argument, the state. And there we go. That was the only change we had to do. We just needed to preprocess the state the right way, because now the state is not an input vector, it is an input image, but of course in the form of a NumPy array. Alright? So great, that was the only change, and now let's do the final change in the learn method. So here we have a little more to do. According to you, what it is exactly that we have to do. It's very important to not forget this. Well, I'm going to tell you, remember that in these formula, computing the Q targets, the next Q targets, and the expected Q values, well, we do this on stacks of states, and stacks of actions, and stacks of next states, okay? And so, if you notice, since we haven't implemented the replay memory class, well, we don't have those stacks of states, stacks of next states, etc. And so that's exactly what we need to do here. We need to get the stacks of states, the stacks of next states, the actions, the rewards, and don'ts, so that we can compute these formulas on these stacks. Alright, so the first thing we're going to do here, because we already have the experiences, it is an input of the learn method. The first thing we need to do here is to unzip our experiences, meaning to separate the different elements of the experiences, states, next states, actions, rewards, and don'ts, separately. Okay, and how we're going to do this? Well, we're simply going to use the zip function, which will take, of course, the experiences as argument, but we're just going to add a little star here in front of the experiences. As you can see, it is what is expected for the iterables here in the zip function. So we just have to add this little star, and then this will unzip those experiences into the states, next states, actions, rewards, and done. And now we can do the stack. And so now it's going to be funny. According to you, how can we do this stack? Well, it's very important to notice that actually right now the states and next states are already PyTorch tensors, because indeed the states and next states come from the experiences, and the experiences come from the sampling from the memory. And to the memory we just appended the state, action, reward, the next state, and done. And the state and the next state here were already pre-processed with our preprocessed frame function. Therefore, they're already PyTorch tensors. So at this point, the states and the next states are actually PyTorch tensors. So a priori, we would think that we couldn't use again that vstack function we used when we implemented experience replay. Remember, here we used this vstack function to perform the stacking. But the vstack function is actually a function by the NumPy library, which therefore we would think would apply only to NumPy arrays. But here's the good news. Actually, the vstack function can actually take as input a tensor, like a PyTorch tensor, and automatically convert that into a NumPy array so that it can perform the stacking. And therefore, we can still call the vstack function here on our tensors, I'm talking about the states and the next states, to perform the stacking. And then we'll still use this torch.fromNumPy function in order to reconvert that into PyTorch tensors. Alright, so that's the easiest way to do it because we already have the code. We're going to take exactly this. The other alternative that we could have done is to use the torch.cat function by the torch library, meaning the cat function for, concatenate by the torch library. But we already have this, so let's just take this. And so here I'm just going to copy these 5 lines of code, all of them, because it's going to be exactly the same. And then back into our deep convolutional Q-learning implementation, I'm simply going to paste this. Alright, and now new guessing game. What are the very final things we have to change in this new agent class of our deep convolutional Q-learning model? These are only 2 things. Let's start with the first obvious one. It is the order here. We have to respect the order of the experience, starting with the states, then the actions, then rewards, then next states, and done. So I'm just gonna take that next states here, cut this, and then here I'm just going to paste it. Alright, so now the order is respected. That was the first change we had to do, and now what is the very final change we have to do in order to adapt this learn method to our deep convolutional Q-learning agent? Well, I'll give you a hint. The answer is in the vstack function. Well, the only thing we have to do is, of course, to replace these for loops here by simply the element. So we remove that whole for loop in a list, and here we replace that, of course, by states. Alright, and then, well, let's do the same for the other ones. We remove that whole for loop in the list here, and we replace that by actions. Alright, there we go. Then we remove that whole for loop in this other list here, and we replace that by rewards. Okay, and then 2 more to go. We replace that whole for loop in the list here, and we replace that by next state. And finally, the very final change of this learn method, we remove that whole for loop in the list here, and we replace that by done. And there you go, my friends. Double congrats, because not only we're done with our new learn method adapted to our deep convolutional Q-learning agent, but also we're done with our new agent class. There it is. We have a complete view at it. Here is our new agent class for our deep convolutional Q-learning model. So huge congrats. We did this successfully and efficiently. So now we basically have the model on how to create a deep convolutional Q-learning AI agent. But remember that we still don't have it for real. And that's exactly going to be our next step. Remember, once the class is defined, we can now initialize our DCQN agent by creating an instance of that agent class and therefore get that AI for real. So we're going to do that in the next tutorial. But first, let me just run the previous cells that I haven't run so far. I think I left things at, there we go, initializing the hyperparameters. Let me just run this cell to initialize the hyperparameters, then run this cell to preprocess the frames, and then finally run this cell to define the agent class, which will allow us to build our future deep convolutional Q-learning AI model. I can't wait to do that with you in the next tutorial, and until then, enjoy AI. Hello my friends, and welcome to the final step of this training implementation. It will be a very easy and fast one, because indeed, what if I told you that we can finish the whole training implementation and also launch the training and get the training results in this same tutorial, which won't be too long, you'll see. Well, you already know actually, I don't know yet, but this is my bet. So here we go. Indeed, we have done the biggest and the most difficult part. Now we're just going to do 2 copy-paste and you will see that we will have very few things to change. So here we go. Let's start by initializing our DCQN agent, meaning getting for real our AI. So let's go back to our deep Q-learning implementation. Let's take this line of code. Then let's go back to our deep convolutional Q-learning implementation. Let's create a new code cell. Let's paste that here. And now, according to you, what do we have to change here? Well, I'm sure you all know the answer. Of course, we have to remove the state size because now our agent class only expects one argument, which is of course the number of actions. So here we go. We are now ready to finally get our AI. So let's run this cell and let's get our agent. There we go. Now we have an AI for real that not only will be intelligent once we train it, but also has the ability to see images thanks to its eyes represented by the convolutional layers. Alright, and now let's move on to the final step, training the DCQN agent. So let's create a new code cell and now you will see that it's going to be super easy. We're going to once again go back to our deep Q-learning implementation. We're going to take the whole training code here, the training for loop. We're going to go back to our deep convolutional Q-learning implementation. We're going to paste that inside. And now according to you, what do we have to change here? Well, my friends, I have some great news for you. We literally only have to change 2 things. I'm gonna zoom out a bit so that we can see the whole training for loop. There we go. And so as I was saying, we only have 2 things to change. First is the number of time steps per episode, because indeed 1000 won't be enough to give enough training of our agent to play in the Pac-Man environment. So we're gonna increase that to 10,000 time steps. And then, according to you, what is going to be the other parameter value that we have to change here? Because indeed we have nothing else. The whole training for loop is already implemented. We only have to change one final hyperparameter value, and a priori we can't really guess because it requires to already play at least once in the Pac-Man environment. So I'm going to tell you what it is. It has to do with the average score here, that score from which we declare the environment solved. And so actually now that's for us to choose, because indeed in the Pac-Man documentation, unfortunately it doesn't say, like for Lunar Lander, from which value of the score the environment is considered to be solved. Indeed, maybe I missed it, but I don't think so. In the documentation here, we don't see a certain value of the score from which the environment is considered solved. But you have to understand that the reward here in the Pac-Man environment is of course the score that we see in the game. This score here, it starts at 10, but then it increases the more Pac-Man eats some sweets and then doesn't get killed by the monsters. There you go, you see the score here increasing. So that's the score. And so I tried several trainings and I played a bit with the Pac-Man environment, and well, I think that a good score to consider the environment solved is not 200, but we're going to increase that to 500, because if we reach 500, you will see the agent will be able to eat a good amount of sweets and not get killed too fast by the monsters. So that's the only thing we're going to change here. We're going to replace 200 by 500. And there we go, my friends. The training for loop is now ready. So you see, how efficient was that? We can basically now launch the training and enjoy the results. But now I have to tell you something very important. You understand that now we're no longer training an AI on input vectors, on simple input vectors of small dimension. Now we're training an AI on input images, therefore of a much bigger dimension. And so you can imagine that the training is going to take much more time, and besides it's going to require much more compute resource. And so now we have a choice. Either we don't mind waiting too long for the training and we stay with our tensor processing unit. By the way, let me show you the different resources we have. If you click this little arrow here and then change runtime type, well, you will see the different processing units that you have. So you have the CPU, central processing unit, that's the least powerful. Then you have TPU, tensor processing unit, that's more powerful than CPU. I think it's 3 times more powerful than CPU. Then you have T4 GPU, which is even more powerful than the TPU. That's the best one you would choose among these options that you have in the free tier of Google Colab. However, my suggestion, and of course you don't have to do it, if you want, we can get those more powerful processing units, because indeed after T4 GPU the more powerful one is A100 GPU, and then the most powerful of all is this one, V100 GPU. So now the choice is yours. Either you don't mind waiting for a few hours to train our AI and you would use the T4 GPU, or we can get access to premium GPUs. It's not that expensive, and get the V100 GPU to train our AI much faster. And as far as I'm concerned, and also for educational purposes, so that we can all enjoy a fast and performant training, well, I'm going to go for the V100 GPU. And to do so, I'm actually going to switch now to my other Google account, in which I have indeed a Colab Pro subscription. So I'm going to show you right away. I'm going to cancel this. I'm going to share this notebook just so that I can get a link and then get this Colab notebook in my other Google account with the premium access. So I'm going to change that to anyone with the link. I'm going to keep that to viewer. I'm going to copy the link. And now I'm going to go back to my other account, my other Google account with Colab Pro, and I'm going to paste that here. So here we go. This is going to take me to my Colab account, but I still have to make a copy of this notebook. So I'm just going to quickly save a copy of this notebook in my drive, but the drive of my other Google account with the Google Pro subscription. And there we go. So let's have a look at what I have. So again, I'm going to click this little arrow here and then change runtime type. And well, okay, I don't have A100 or V100, but that's because even though I'm subscribed to Pro, I consume before all my compute units because I was doing a lot of training and a lot of hyperparameter tuning on this same deep convolutional Q-learning model for Pac-Man. And so I just have to purchase additional compute units, but that's totally fine. I'm happy to do it for educational purposes. And at the same time, you will see the Colab offers. As I told you, it's not that expensive. As you can see, if you want to have now a fast and performant training, well, you just have to pay either 11 euros per month or 11 euros for 100 compute units, and you will get those units to run a performance training. So now I'm in the Colab Pro, but I consume all my compute units. I'm going to pay as I go, and so I'm going to go for this. I'm going to just order now 100 more compute units. I'm going to agree, and then I'll be able to get the V100. All right, perfect. 11 euros. I'm going to click buy. And we're now going to enjoy a fast and performant training of our deep convolutional Q-learning model trained on the Pac-Man environment. And we're going to try to reach a score of 500. All right, it's making the payment, checking out, secure checkout, and sign up successful. Let's go. All right, so now I should have my compute resource. Okay, so this is okay. We don't need it. And now let's see if I refresh, if I have my V100 GPU. I'm going to refresh this. And let's see if I can switch to the V100 GPU. So I'm going to go back to this little arrow here. By the way, you can also access it here in runtime and then change runtime type. And there we go. I have the V100. This is the most powerful one. And this is the one that will get us a much faster training. All right. And make sure to also select high RAM because, of course, you know, our AI has a memory and that memory is actually provided by the resources of Google Colab. Okay. So let's do this. Let's click save. And now, are you ready? So unfortunately, since it's a copy of the notebook, I just have to run all the cells again. So I'm going to click run all. There we go. It's going to reinstall everything. All right, so now it's installing Gymnasium and great, done. Now it's running the other cells, importing the libraries, creating the architecture, setting up the environment, initializing the hyperparameters, pre-processing the frames, implementing the DCQN class, initializing the DCQN agent, and there we go. The training has started, and of course, even if we have now a powerful GPU, you know, the V100, it's not going to be an as fast training as before, you know, with the dynamic printing. We still have the dynamic printing, but it's going to take much more time. There we go, to get the average score on one episode. So we actually start with an average score of 250 for episode 1, and then it's going to take a few more seconds to get the average score of episode 2. There we go, 255, and then the average score of episode 3, and so on. So let's hope that we will get that, you know, threshold of average score, you know, the average score of a 100 episode over 500, in which case, well, we consider to have solved the environment and we consider to have a performant agent able to play Pac-Man. So episode 4, we have reached 257. So it's a good start. It seems to be increasing a bit already. But what we're interested in, of course, is the average score on 100 episodes. 258 for episode 5. So there we go. So now it is training. Of course, I'm not going to comment the average score on all the episodes, even if I would love to do so, because it's going to still take quite much time. 256 on episode 6. Okay, good. But as I was saying, it's going to take a lot of time. So I'm just going to fast forward here video and I'll see you if, of course, we reach an average score on 100 episodes of over 500, in which case, you know, the training will break and we will have that final note environment solved in a certain number of episodes with the average score being over 500. So let's hope we get that. And I guess I'll meet you if and once we reach that score. $494 at episode 729. I feel that we're super close. I think we're gonna touch soon the 500, our threshold for considering the environment solved. We had a very good and steady increase of the average score over the hundreds of episodes, and sometimes the average score would decrease a bit in order for the agent to do a bit of exploration. But now it seems to have found a good action subspace. Oh, there you go, average score 499.70. We're super close. We're super close to our 500 threshold. I think it's imminent now. We are at episode 732. 497, still doing a bit more of exploration, but it's so close. It's so close. I've been waiting for, actually the training was 2 hours, and I've been waiting in front of my laptop to see how the average score evolves, and I can say that I'm pretty happy at the evolution. We had a steady increase, 306, 323, 394, and there we go, 633 episodes for the environment to get solved, and we reached an average score of 508.60. Congratulations, my friends. Please share in the comments what you got, in how many episodes you reached that average score of 508. But there you go, that was a beautiful training. We had a steady increase of the average score while having at the same time a bit of exploration. Indeed, from episode 500 to 600, we decreased the average score by quite a bit. But that was just in order for the agent to do a bit of exploration, in order to, explore some different action subspaces to maybe find a subspace of actions that could potentially lead to a higher average score. And probably that's what happened, because then from 600 to 700, it considerably improved the average score from 393 to 467, after which probably it found a good direction of actions leading to increase the average score, and that's what we obtained at the end with an average score of 508.60 reached at episode 733. But since we consider the lower bound of the scoring window, well, the environment was solved in 633 episodes. Again, please share in the comments what you got. I'm super curious, and congratulations for having solved the environment. Alright, so let's stop here for this tutorial. Let's take a little break, and in the next one we will enjoy the final results, visualizing our agent playing the game of Pac-Man with a good coffee or tea. I can't wait to see you in that next tutorial, and until then, enjoy AI. Hello my friends, and welcome to part 3 of this implementation, visualizing the results. We have just finished a beautiful training of our AI, the deep convolutional Q-learning model for Pac-Man. We ended up with this nice score of 508.60, which is above indeed our threshold for considering the environment solved. And now we can just sit back with a good coffee or a good tea or orange juice, whatever you prefer, and enjoy the final results. Because indeed, now it's exactly the same. The code to visualize the results is exactly the same as before in our deep learning implementation. Of course, the only thing that changes is the name of the environment, Miss Pac-Man Deterministic V0. Alright, and that's it. All the rest is the same. We have the same show video function, and then we call it to show the final video. So what I suggest we do here super quickly is that we don't look at it. We're going to enjoy the results in the full screen video. So I'm going to download it immediately. I'm going to download it to my desktop. Here we go. It is downloading. There we go, the desktop. I'm going to save it. and I'm gonna go immediately to my desktop to watch the video with you of the final result. So I'm gonna put it in full screen. Sorry for the low resolution, but we'll be able to see well enough. So my friends, are you ready to visualize our AI now playing a game with its own eyes just like a human being and trying to achieve the highest scores possible? So let's just expect what we're going to get here. Remember that we trained our AI to try to reach a score of above 500. So probably here we're going to get a score around 500. Of course, if we had trained the AI longer, maybe we would get a higher score, but it's possible that we get a high score or even a lower score. We don't know. But since we trained the AI to get an average score over 500 over 100 episodes, well, probably we'll get a good score here. Okay, so are you ready? Remember that our AI is now not only intelligent at playing Pac-Man, but also is able to see the game of Pac-Man while it's playing. So that's amazing, right? That's as if we get closer and closer to building a real artificial intelligence mimicking human intelligence. All right, just wanted you to be aware of that when I press play. So here we go. 3, 2, 1, go. And here is the game of Pac-Man starting, and there we go. It's hitting some sweets pretty well. It's hitting some sweets, trying to avoid the monsters. Ah, it got caught. Okay, so second round, it's hitting more sweets, more sweets. Yeah, very good, very good, very good. No, turn right, turn right, turn right. What is it doing? Okay, good, 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 good. Now it's going back up. Good, excellent, excellent. It's hitting a lot of sweets. As you can see, the score is really good, 700. Did you see that? And the score is going to increase now probably because it's going to eat more sweets. Miss Pac-Man is doing really, really good. 790, and that's the end of the episode. Wow, that was a great one. Miss Pac-Man did really amazing here. And remember that it was playing with its own eyes, with the convolutional layers, getting all these frames that we just saw as input and then processing them and then sending them to the neural network and then using deep Q learning to play great actions in order to catch the maximum sweets and get the maximum score. So that was a beautiful one. I'm going to save the video for you. I'm going to share it in the lecture so that you can watch it, but you're probably going to get another video that is just as good, or maybe you'll get an even higher score here with the inference mode. If that's the case, please share, or even if you did some more hyperparameter tuning during the training and you got an even better average score, well, please share in the comments. And also, if you got a lower score than the one we just got here, that's totally normal. It can happen that during the inference mode, the AI doesn't do as well as what we just saw, but here it really did very well. Alright, so that marks the end of this part 2 on deep convolutional Q learning. We're still going to end this section with a little tutorial with ChatGPT just to see what ChatGPT suggests to us when trying to solve the Pac-Man environment with a deep convolutional Q learning model. So it will be a quick tutorial just like the one we did in deep Q learning section. I look forward to seeing you there, and until then, enjoy AI. Hello my friends, alright, so let's finish this deep convolutional Q learning part 2 with a little ChatGPT tutorial just to check if we got the best architecture or if ChatGPT can provide us some ideas of how to improve the neural network we built. We never know, even though it seemed that we already got some good training results. Alright, so right now I'm in my ChatGPT Plus account, so I'm gonna select GPT-4 and then the default option selected. So here we go, I'm gonna say, hey ChatGPT, can you please implement a deep convolutional Q learning model for actually, let's get the exact name of the environment. Reconnect, yes, okay. For, here we go, Miss Pac-Man deterministic V0. So I'm copying it here. I'm gonna paste that exactly here. And there we go. For Miss Pac-Man deterministic V0 in PyTorch, very important. I remind that PyTorch is much better than TensorFlow for deep reinforcement learning. So in PyTorch, and voila. We're just going to stop here because we mostly want to see if it returns a different kind of architecture than the one we built. All the rest of our code works perfectly well, so we're mainly interested in the architecture. So here we go. Hey ChatGPT, can you please implement a deep convolutional Q learning model for Miss Pac-Man deterministic V0 in PyTorch? Here we go. Pressed enter. Certainly, deep learning with convolutional neural network is a powerful combination for training agents. Setup. Okay, so we have the pip install, all the imports. Great. First, it creates the DQN class with it seems to be a different architecture. Okay, we'll have a look again at it. And okay, so it implements the replay buffer class. We chose to integrate directly in the training for loop, but that's all right. And then it defines the train function for the main training loop. Okay, does it implement epsilon greedy? Probably. We'll have a look at it again. And what does it do also? It goes too fast. Preprocess, see, it builds also the preprocess function. And okay, so done. We'll have a look at it again. But there we go. What I mainly wanted to see is the architecture and compare it to ours. So let's have a look at the neural network at the top. Here we go. So create the DQN. Okay, so it starts with a convolutional layer of 32 filters with a kernel size of 8 and a stride of 4. Just like what we did, the kernel size and the stride are reducing over the different convolutions, and the feature maps are increasing. The filters are increasing. So that's pretty similar to what we did. We went up to 128 here. It chose to stop at 64. We could try this architecture as well. But anyway, I think it will lead us to very, very similar results. And then for the full connection, the fully connected layer, well, it also chose 512 artificial neurons here. So pretty similar. And then it made the forward method, okay, resizing the tensor for the flattening, okay, feature size. So it chose to implement separately experience replay. That's totally fine. We could have done the same thing actually. And then the main training for loop. Here it does exactly the same. It's pre-processing the state input images, unsqueezing them to add this extra dimension of the batch and sending to the proper device. Then here that's where it integrates experience replay by adding experiences to the memory. And then here that's where it gets separately the states, action, rewards, next states, and dons, and converting all that into torch tensors. Then it applies deep Q learning with the Q values, the next Q targets, and the targets. And then it computes the loss between the expected Q values and the targets. Then it uses the optimizer, first resetting it and then back propagating the loss and then using the optimizer to update the model's parameters. Then we have the preprocess function to preprocess the images, the input states, and then the main function. Okay, so anyway, what I was mostly interested in is this architecture that was suggested here by ChatGPT. Feel free to try it if you want. I'm pretty sure it won't really improve the results and at best get some very similar results. So there you go, your choice. It's always very good if you can practice a bit more, if you can do a little bit more of hyperparameter tuning. And of course, please share in the comments or the Q&A if you manage to get some much better training results and a much higher score at the end in the inference mode. And please, if you can, share the video if you get a really great one. So now it is time for me to say huge congratulations for having implemented the deep convolutional Q-learning model and having got those beautiful results at the end. Now I look forward to seeing you in part 3, where we will implement an even more powerful AI model, which is the A3C model. And just to give you a teaser of what will be improved in terms of artificial intelligence, well, in part 1 with the deep Q-learning model, we built an artificial brain containing only artificial neurons. Then in part 2 with deep convolutional Q-learning, we built not only a brain with artificial neurons, but also some artificial eyes. And now, according to you, what will be this extra feature that will get our artificial intelligence closer to human intelligence? Well, I'm going to tell you right now that is going to be a critic sense. Indeed, that's exactly what we're going to bring to our AI besides the brain and the eyes that we were already able to build. We're going to also bring to our AI a critic sense, and that's exactly what the A3C model is about. So I can't wait to see you in part 3 to implement it with you, and until then, enjoy AI.
Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're going to discuss the plan of attack for this amazing section on the most powerful algorithm in artificial intelligence, which is A3C at the moment. So let's have a look. Today we'll talk about the following things. We'll start with the 3 A's of A3C. So we'll talk about what the abbreviation stands for and how we're going to deal with the 3 A's, and also we'll look at the actual article or the actual research paper that gave birth to A3C, the Google DeepMind research paper, and we'll have a quick look at it so that you're more comfortable navigating it in your free time. Plus, we will see exactly why the A3C is the cutting edge, most advanced algorithm on the planet for artificial intelligence at the moment, and why it's so important to have this in your arsenal. Next, we're going to talk about the first A of A3C, which is actor critic. Well, A3C actually stands for Asynchronous Advantage Actor Critic algorithm. And so we're going through the A's not in order, but we're going through them in an order that makes sense for us, that will help us in our intuitive understanding. Then we'll talk about the asynchronous element in the A3C algorithm. And then we'll talk about the advantage. And that's the tutorial where we'll put everything together and all start making sense. So a quick word of caution that as you're going through these, you might notice that after the actor critic and even after the synchronous tutorial, you will still not exactly have the full picture or full understanding of how this all ties in together. And that's totally okay, because all these three elements, they indeed work together, and they require each other to function. So just power through it and get to the third tutorial. And in the third tutorial, the advantage tutorial, that's when it'll all come together. And if at that point you still don't quite understand something, then you can just revise that specific tutorial with this actor critic or asynchronous or the advantage tutorial to put all together. But basically, just don't get thrown off if after one of those two tutorials you still feel that you need some more information. That's because they all work together to come to one functioning A3C algorithm. That's in the advantage tutorial that all ties in together very nicely. And finally, we'll talk about some additions that you can add, or some additional modules and elements that you can add to the A3C algorithm. The thing is that there's different versions of the A3C algorithms, different modifications, and already through the first 4 tutorials in this section, we will see some modifications, and at the end we will add an extra one, the long short term memory, LSTM. Now here we won't go into a lot of detail on LSTMs. That's a topic for another course, but nevertheless, you will get a overview of what LSTM is and how those structures or how those layers in neural networks work, so that you have a better understanding in preparation for the practical tutorials. But very important also, this will showcase how the A3C algorithm can be modified to suit certain purposes. So there we go. That's the plan for this section. Definitely, it's going to be an exciting algorithm to look at, because it's the top algorithm at the moment in the world, and we're going to be developing an intuitive understanding. And then together with Adlan after this, you're going to be coding it, which is very, very exciting. And I can't wait to see you on the first tutorial. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're taking our first step into the world of A3C. And as a first step, we're going to find out what this abbreviation stands for. So A3C stands for Asynchronous Advantage Actor Critic Algorithm. This is an algorithm which was developed at Google DeepMind in 2016 by a group of researchers, and it's the cutting-edge algorithm for artificial intelligence to date. Now, it has multiple modifications, and we'll discuss that more in the course, especially in the practical tutorials. But nevertheless, this algorithm blows everything else, including deep convolutional Q-learning networks, out of the water, completely out of the water. And it is faster, it takes less time for training, and gets better results. So throughout this part of the course, we'll be referencing, and we have already referenced, but we'll be referencing even more, a paper, or the paper that was published that first introduced A3C. It's called Asynchronous Methods of Deep Reinforcement Learning by Vladimir Mnych and others from Google DeepMind. So I'm going to show you this paper now so that you have an introduction to it. So here is this paper. I wanted to show it to you so that you can get a feel for it and already get introduced to it a little bit. And of course, it is highly recommended to read through the paper and understand what exactly they're talking about. And you'll see that throughout the practical tutorials, Adlan will be taking you through certain parts of the paper, through certain paragraphs or sections which will be relevant to what we'll be programming at that point in time. And what I wanted to point out here is, like, as you can see, a lot of research went into this, and there's a lot of references as well. But like a part that I really like is that at the very end, they compare the different algorithms, compare the results. And this is what I wanted to point out here. So let's zoom in a little bit. So here, as you can see, even in Google DeepMind, they're training, or they're evaluating the algorithms on games, just as we're doing in this course. So exactly the same principle, because games are a simulated environment or a small environment, a confined environment with certain rules, and they want to understand how well this artificial intelligence is doing in those games. And here we've got exactly all those games which you can find. A lot of them you can find on OpenAI Gym, and the games that we've been working with. So for instance, in this section, we're working with Breakout. So it's also here. And so you can see that for Breakout, they've got in bold, they've got the best algorithm highlighted. So DQN, that's the algorithm we've been working with. Then some other algorithms. And then here you've got A3C with an LSTM, long short-term memory. So that's the one we'll be implementing in this part of the course. We'll have A3C with an LSTM, which makes it even stronger. So as you can see, Breakout is the best result is achieved by A3C with LSTM. So that's the score, 766.8 compared to the others. And also you can see that for the most of them, so if we now take like a bigger picture view, you can see that most of the bold ones are actually in this last column. So yes, indeed, there are some games where other algorithms are performing better, but as you can see, DQN is actually not performing better in any of the games. But you can see that there are other algorithms perform better sometimes, but A3C LSTM performs the best in most cases. So you can see that this is bold, this one, these ones, this one, and so on. So you can see that A3C LSTM is a really powerful algorithm. It is indeed at the forefront of artificial intelligence, and that's exactly what we'll be implementing. So very exciting section ahead. Highly encourage you to go through this paper and get a feel for what we're going to be talking about, and then throughout this section and throughout especially the practical side of the things, practical side of Stroh's, we're going to be going through this in detail. We're actually going to be working with their pseudocode here, which is available, and we're going to be, so Adlan will show you how to implement that and how we're going to be working with that. And on that note, I hope you're going to enjoy this paper, and I look forward to seeing you next time. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're talking about the first part of A3C, the actor-critic part. So here we've got asynchronous advantage actor-critic algorithm, and we're going to be talking about that underlined actor-critic part. That's where we're going to start. You could technically start anywhere, but it just makes a lot more sense to start from actor-critic, because that way we'll have like a very consecutive explanation of, or intuitive understanding of what's going on. It's going to facilitate us better if we start surprisingly at the end of this abbreviation. All right, so far in this course, we've come up with deep convolutional Q-learning, which is illustrated over here. So we've got the computer seeing the pixels, so the actual image in pixels, not just a vector. So it's not cheating. It's actually seeing exactly what a human sees. It sees the monsters, it sees the health, it sees the parameters at the bottom, it sees the corridor, it sees the gun, it sees exactly the same thing as a human would see when playing this game. Then that image is passed through a convolutional layer, then it's passed through a pooling layer, then it's flattened and goes into a neural network. And then at the output, we've got actions. As you remember, we've got those Q values. Then we apply a action selection policy to them. So for instance, we apply a softmax and we find out which action we want to take. And so there's some exploration plus exploitation going on there, a combination of the two. So that is how deep convolutional Q-learning works. But now let's see what we're going to do with this. So for simplicity's sake, just so that it's easier for us to operate with this, because we're going to be adjusting this image and moving it around, we're going to replace the circles with squares, with these rectangular boxes. And we're also going to get rid of those lines in between, just change them to arrows. So this doesn't change the essence. This is just the representation on this chart. This is still, even this representation is still deep convolutional Q-learning. It's just going to be easier for us to modify it and show exactly what A3C is. So that's just how we're going to represent things from here. And what A3C does, or this specific part, so we're starting, remember, we're starting like step by step. We're starting with the actor-critic part. So we're going to see how we go from deep convolutional Q-learning to A3C step by step. And first step, we're going to introduce this actor-critic part over here. So we're going to talk about that. So the first thing that happens is this last bit the output is actually, we're just going to redraw it like this. So it's exactly the same output, exactly the same Q values, or exactly the same actions. So if you had 8 possible actions, you still have 8 possible actions. We're just going to put them at the top so they take up less space. So nothing has changed. So far this and this are exactly the same. But now this is where the actor critic part comes in. We're going to have a second output. We're going to have, so the first one is a set of outputs, and here we're going to have a separate individual output. So technically we're going to be using our neural network. So once the image and everything, like the values go through the network from left to right. Over here, they don't just spit out one set of values, they spit up actually 2 sets. And so the top set, we already know what it is. It's the possible actions, but here we're actually going to have another extra value. So let's have a look at that. What is that value? So here we go. That's the top. So we just kind of like reduce the size of this illustration. The top output are the Q values, as we discussed previously, for the actions. So they're same thing, everything is same. But then now this bottom part, and the top part is actually called the actor. We're going to give it a name. That's the actor because that's the part where the agent chooses what it wants to do. So that it's like it's acting, it's as if it's performing on stage. And it'll make more sense once we have the second name up on the screen as well. And then the second output is just like one value, and that is V of S. So that is the value of the state. So if Q of S and A is the Q value of a certain action, and as you can see, that's why there's action 1, action 2, action 3, up to action 6, or however many actions there possibly are in that state. So in a given state S, what is the Q value of taking action A, action 2, action 1, action 2, and so on. Then here we're also using the neural network to predict what is the value of the state we're actually in. And this part is called the critic. And so that's the intuitive, or the kind of not even full intuitive. That's just like the start of the intuition behind actor critic, that there's 2 outputs now from the neural network, not just one. Before we just had that one output, which we now call the actor, but now we have 2 outputs, actor and critic. And there's going to be a dynamic between them, which we'll explore further. But for now, it's important to understand that we're predicting not just the Q values of the actions that the agent can take from this certain state, but we're also predicting the value of being in this current state using that same neural network. So that's the core of the first step into the actor critic. And now we're going to need to talk about asynchronous, which we'll do in the next tutorial, in order to understand exactly what's going on between the actor critic. And the final thing for today is that all of these Q values, as we know, that's also called policy. So in some literature, in some blogs, in some discussions you might find in the actor critic, you might find the author talking about Q values on this side of the actor. In other literature and blog posts and discussions, you will find the author talking about the policy. So, and usually it's they use a Greek letter P for representing the policy, or it might just say policy of state S. So altogether, these are the policy of state. It's because, as we remember, the policy is if you put all the actions together, the possible actions, and then it's deciding which action to take. So these are going to be like the probabilities of taking each action. So that's the policy. So don't be thrown off if you see one or the other. They basically mean the same thing. So on one hand here, you've got the policy or the Q values. On the other hand, you've got the actual value of the state, and they're being predicted from the neural network. So that's the start of the actor critic. We'll continue with this in the next tutorial when we're talking about asynchronous. And I look forward to seeing you there. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're continuing our journey into the world of A3C, and we're talking about the asynchronous side of A3C. So there we have our abbreviation, Asynchronous Advantage Actor Critic, and today we're going to find out what asynchronous here stands for, what it means. And let's go back a step. Let's look at what we started this whole course with. We started with reinforcement learning and what it's all about, that the agent is in a certain state. They observe the state, they make certain decisions, they take actions in that state, and then the state is changed, so they get into a new state, plus they get a reward. So they get a reward for taking that action, or some sort of reward, which could be a penalty as well, and they end up in a new state. And based on that, now they take another action. Again, they get a reward, and end up in a new state, and they take another action, and so on. And so that is the basis behind all of reinforcement learning, and that's what we've been using in Q-learning, in deep Q-learning, in deep convolutional Q-learning, and that has allowed our agents to beat gradually more complex and more complex environments. But now we're going to introduce a even better concept, and even further take this even to a further level. What A3C introduces through this asynchronous element is, instead of having one agent attack the environment, they have 3 agents or whatever number of agents. So several agents attacking the same environment. And the key here is that why it's called asynchronous is because they're initialized differently. So their starting points are different. So for instance, as you'll see from practical tutorials, you set a random seed and you set it differently for each of the agents. And that way, because their starting points are different, they're going to first go through environments in different ways, and then they're going to explore in different ways. And then in the next iterations, they're also going to explore in different ways. And so, for instance, if you have 3 agents, you're all of a sudden you're getting triple the amount of experience. Instead of just one agent going through and exploring the environment and trying to understand how to operate in that environment, you now have 3 or however many of them going through that, getting this experience. And so so that each one of them is learning through this bigger experience. And apart from being just giving a broader range of experience, it also reduces the chances of one agent getting stuck in a local maximum. So for instance, if one agent finds like a way to beat the environment, which is not the most optimal, because if it deviates to the left or to the right from that solution that it found, it always gets more penalized. It might get stuck in that local maximum. It might just keep doing that, thinking that that's the optimal solution where it's actually not. Well, the likelihood of several agents getting stuck in that same local maximum decreases with the number of agents. So the probability of one agent getting stuck in a certain local maximum might be high, or might be a certain value. But the probability when you have 3 of them, of all 3 of them getting stuck in that local maximum, is much lower. And as long as they share experience between each other, they can help each other out. So if one of them gets stuck, for instance, it's stuck in a local maximum, just simply think that's the best one, that's the best solution all the time, and keeps doing that. Well, as long as it interacts with the other agents, so let's say this guy gets stuck in a local maximum, as long as it interacts with the other agents through the way we build our whole algorithm, A3C algorithm, they will help him out. They will give him knowledge that actually, no, hey, you should explore this, or he will be more likely to get out of that. And also overall, the environment will know that, hey, even though this is a great maximum, these other agents have seen better options, and we should keep exploring because they looks like they're better options. So in a very short, kind of rough, intuitive understanding, those are some of the advantages of having these asynchronous agents. First of all, you have more experience to choose from and to learn from. You could get to the solution faster, and generally speaking, there's a lesser chance of getting stuck in a certain local maximum. So let's see how this all plays out in this model that we've built so far. So as you remember, this is what we've gotten so far through the actor critic. And this is like where it all ties in. This is, so far, as you remember from the previous tutorial, we did introduce this, we had this already, even in deep convolutional Q learning. So we just named it actor now. But now we've introduced critic, but so far it doesn't really make sense. What's the point of having this critic and measuring the value of the state, or predicting the value of the state using the same neural networks, this same approach? But now this is the part where it's going to start making more sense. What we're going to do is we're going to replicate this, because now we have multiple agents. So with multiple agents, this is what it would look like. So the first way of imagining it is now we have these 3 things. Well, remember what we said about them sharing the experience between each other. So this is actually right now they're all independent. You have one playing the game, another one playing the game, another one playing the game. It's like launching your agent on 3 different computers. You put 3 different computers next to each other and you launch them, and that's great. Like, indeed, you'll get more experience, you'll get like more variety, especially if they're initialized different. So we're gonna assume from here that they're always initialized different. Even though we have the same picture here, we're going to know that they're actually initialized differently. So it's not going to be like identical training, identical learning from this game. And so even if you put 3 computers side by side and you launch them, yes, you're going to have more experience because you're going to have 3 agents playing. And also you're going to have a bigger variety of possible solutions. So that's true. But the problem is that they're not sharing that experience among each other. They're not learning from each other. So they don't have that synergy. They don't have the advantage or the extra power that they would get if they were cooperating. You know, like how if you have a team of people, they work better together than each one of them separately. So like in a team, here you got 1 + 1 + 1, it's 3. But in a team, 1 + 1 + 1 is not 3, it's like 33 because they leverage each other's strengths and mitigate each other's weaknesses. And same thing here. So if you put these 3 computers side by side, yes, you'll have more experience, more variety, and possibly someone will get to a better solution than the other one. That's great. But it'll be even better if they start sharing that experience. And how do they do that? Well, it's through this V that we calculated. So this V value that's the output of our network is actually like that. So they have this same V. So every time all these agents, they're contributing to the same critic. They don't have separate critics, they have a common critic. And that's the key of how the actor critic ties in with the synchronous. So there's one critic that's watching as they get experience. So how do we calculate the V? We calculate the V through, as you remember, we calculate the V through the values that we get. So the rewards that we get through the environment. And so as the agents explore their environment, they are calculating, they're predicting the V, plus they have the V that they can calculate. This is all ties back into what we've already discussed in the previous sections of this course. So they already have a V that they can predict, like expect through the rewards that they know that exist in this maze, and that they've already explored. And as they explore them, of course, that value can change. But also they have the V this V is the output of the neural network. So as they're going through this, they're going to be adjusting their neural networks in order to better match that expected V. So basically, this is shared. The critic part is shared between the agents. And that is how they share the information between each other. That's how they are able to kind of see what's going on in the environment, shared with each other, and then use that, as we'll see further in the next part, in the advantage, use that in order to optimize how they're behaving in that environment. And the other thing to note here is, so this was A3C. This is like the core of A3C up to here. This is a version of A3C. But there's an actually even better implementation of this A3C, which you'll actually hear Adlan talk about in one of the first tutorials in the practical side of things. And what he'll be talking about is how the creator of PyTorch actually made an adjustment to one of the codes that was shared on GitHub, where he took all of these. As you can see right now, they have separate neural networks and only they share the V. That adjustment that was made was actually to take all of these neural networks and put them into one, take them and put them together. So ultimately, there's only one neural network here shared among the agents. So before each one of them had one neural network, which was shared for the actor and for the critic, one neural network shared for the actor, for the critic, one neural network shared for the actor, for the critic. Now they all have one neural network, which is shared for the actor, critic, actor, critic, actor, critic. And then the critic is here in common. So let's see. Let's move these pictures to the left over here. So make some space. And this is basically the architecture or the structure that we're going to be using in the practical tutorials. I know that like this may sound a bit overwhelming at this stage, but we've got one more A to talk about, which is the advantage, and there we'll see a bit better in action how this is going. So we'll talk about the intuition in action there. But generally speaking, this is what it is. There's one network which each of the agents use. So they share, basically what that means is that they share the weights. The weights of the network are shared between the agents. And when they update the whole network, not just their own network. And then they have outputs. They have like these actions for each agent, and then they have the critic that is shared, which is going to be monitoring. So I know all of this is kind of like there's a lot of stuff right now, but hopefully it's slowly coming together. At least the main takeaway from here is that the critic, because it's shared, that's how the agents are able to make sure that they're cooperating together in order to get to the result much faster. And then in the next tutorial, we'll see even further how all of this adds up, how all of this comes together. And for now, there's I would like to recommend, or we would like to recommend you an additional reading. So this is a blog by Jaromir Janisch. It's called Let's Make an A3C Implementation. There's actually two parts, implementation and theory. There's the link, and it's very similar to what Adlan will be implementing in the practical side of the tutorial. So it's not specifically for this tutorial, not specifically just for this tutorial, but it's for this whole section. Encouragement there, some additional information, some additional insights there. And so that's why we're bringing it up here. But nevertheless, in the next tutorial, we're going to start pulling all of this together, everything we've discussed so far. And I look forward to seeing you next time. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're talking about the final A in A3C. We're talking about advantage. So there it is. We've already spoken about actor, critic, and asynchronous previously, and slowly built our way to what we're going to be looking at today. And with advantage, we're going to put everything together. So this is what we have so far. We've got a neural network which is shared between the agents, the asynchronous agents, and then we've got the critic, which is also shared between the agents. So how does this all play out, and why is this critic shared between the agents? Let's have a look at that. Well, to understand this better, we're going to look at an example. We're going to look at this agent, for instance, and see what happens when he's in a certain state and he needs to make a decision what action to play. So this agent is in a state, he sees this image, and then what happens is this information goes into the neural network, it goes to the convolutional layer, then it goes into the pooling layer, then it goes into the flattening layer, and then from there it goes into the hidden layers of the neural network. And then as an output, he gets all of these policy values, the QU values of the policy, and also he gets the V value, the critic value. And so, as we know, neural networks, in order to operate, they need to propagate certain errors or losses back through the network, so this way, in order to update the weights. So what losses are we going to be dealing with here? Well, we've got two losses. We've got the value loss and the policy loss. So the value loss is linked to the V value, policy loss is linked to policy. And so value loss, we've already dealt with it before. We know that we have rewards, and we know that we have a discount factor. So basically, this is very similar to what we were talking about in the deep Q-learning tutorials. Basically, the network predicts a certain value V, and at the same time, we can estimate what should be, based on what we know about the environment so far, we can estimate what should the value V be in the state. And by comparing the two, we can calculate the value loss and then backpropagate the network, update the weights. So that's pretty straightforward. The new thing here is the policy loss. And so what is this policy loss and how does it work? Well, this is the part where this whole situation where the critic is shared between the actors or between the agents is going to finally emerge. So to understand policy loss, we need to introduce a value called advantage, hence the name of this part of this tutorial and this whole part of the A3C algorithm, the advantage. And the advantage is calculated as Q of S and A minus V of S. So basically, the Q value that you chose to play of the action that you chose to play in the state that you were in state S, minus the value of that state. So this is the difference between the two, and that is called advantage. And the advantage is used in the calculation of the policy loss. Now, we won't go into the formula of the policy loss calculation because it's quite complex. It uses entropy, or it can use entropy, doesn't have to. We're not going to dissect that formula, but we're going to understand this on an intuitive level. Why are we doing this? Why are we calculating this advantage, and how is it going to help us? Well, let's look at this for a second. The Q value here comes from what the neural network predicted for this agent. So it predicted in this specific action, in this specific state for the action that it can play. So it's got these actions, and it can select one of them, and it can play it. Well, whereas the V value is the value that is dictated by the critic. It is the value that we have here in this shared part. And that's the key here, that this part is shared. So the critic, because this is how the critic comes into play, because we've got a value that we choose, or the action that we choose to play for this agent in that state, but then the critic can tell us what is the known value of that state, what is overall the known value for this whole group of agents that are performing together, because they're sharing, not necessarily because they're sharing the network, but because they're sharing the critic, they're all contributing to these V values that are being calculated for a different state. So the whole A3C algorithm says, okay, so the critic knows a V value. How much better is your Q value that you're selecting compared to the known V value? That's what it's saying. So that's basically it. So that, okay, I'm going to select a Q value here based on my policy, based on whatever we use, like a softmax function or a epsilon greedy policy or something like that. And of course there'll be exploration plus exploitation combined in there. But we select a Q value, and now the question is, what is the advantage? Hence it's called advantage. What is the advantage that your selected action brings compared to the known value of that state? And that is the essence of the advantage. And basically, then that is used to calculate the policy loss, and then the policy loss is then backpropagated back through the network. So they're both backpropagated through the network, and the weights are adjusted in order for the network to better represent the value of the critic. And also, so that's this top part, but then this also part, the key here is that the weights are when this policy loss is backpropagated, the weights are adjusted in such a way so that this advantage is maximized. So like that's the intuitive side of the intuitive understanding of it, that we are backpropagating this policy loss through the network in order to help maximize this advantage. And what that means is basically that when an agent comes across bad actions, like actions where the Q value is less than the known value for the state. So basically the whole A3C algorithm knows that the value for the state is something X. And then all of a sudden you came across a very bad action, and you chose a bad action. And what that means for the A3C algorithm means that, well, why would we do something like that when it's worse than what we already know about this whole environment and what we could have done? So we shouldn't do more of that. And therefore the weights are adjusted in a way so that happens rarer, so that happens less rare. So that's a less frequent occurrence that we choose that bad action. On the other hand, if you choose a very good action where Q value is greater than V or much greater, then during this backpropagation of the policy loss through the network, the weights are going to be updated in such a way to reinforce that, to reassure that to happen again, so that the weights will be adjusted in such a way so the A3C algorithm will think, oh wow, that was really cool, the advantage was very high there, I should do more of that. And therefore it will update the weights in such a way that will be more likely to occur in the future, that action. So, and therefore that is that's how the network is slowly going to adapt and slowly going to construct itself into something that on one hand calculates the value correctly, and then on the other hand, or as correctly as possible, and on the other hand it encourages, or it has actions which have a high advantage. So there we go, that's this part. And now let's have a look at another one just to kind of reinforce what we just discussed. So let's look at the top one. So same thing here. The top agent sees a situation, a state is in a state, and then needs to decide what to do. So sends this information to the network. So this image goes into network, goes to convolutional layer, pooling layer, flattening layer, goes into the hidden layers. And then from here we get an output. We get the Q values of the policy. We get the V values. Again, the same thing. We've got two losses. We've got the value loss, which is here, policy loss, which is here. Value loss, we already know how it's calculated. We discussed this in the deep Q learning, and just discussed it just now as well. So that's how the value loss calculated. And then the policy loss, again, in order to calculate that, which we're not going to go into formula, but on an intuitive level, we're calculating the advantage, which is, okay, so we took a certain action, we chose a certain action based on our selection policy, whether it's softmax or epsilon greedy or whatever other selection policy that we're using. And then what's the action we took? Now let's compare it to the known value of the state, which comes from the shared critic. So this critic is kind of like, if you think about it, he's kind of observing all of these agents at the same time. He's looking at this one, looking at this one, this one. They're all contributing towards the critic to get the critic more up to speed with the environment, to make sure that the critic is representative of what's going on in the actual environment, so that the weights, that's where the value loss comes in, so that the weights of the actual neural network, that they reflect very well the actual situation of things in the environment, so that they can then rely on this value and then use it here. And so basically, so all of these agents, agents are contributing to this critic, but then at the same time, through this value loss, but at the same time, the critic is observing the decisions or the policies of these agents. Like, it's like looking back at the, like, I'm trying to draw like an arrow to the policy, an arrow. It's looking back at them, at the decisions that they're making. It's criticizing these decisions through the advantage. It's saying, okay, you made a decision, you chose this action, that's great. Now let's calculate the advantage. What is the advantage? The advantage is A equals, the Q value of the decision I made, or the choice I made, the action I made, chose to take, minus the known value to the critic, So calculate the difference. If it's a low difference, then when your policy loss is backpropagated through the network, the weights are going to be adjusted. It's going to encourage the weights to be adjusted in such a way that doesn't happen again. That Q value, or that Q value is going to be lower, so that because our policy selects the actions based on the Q values. The higher the Q value, the more likely it's going to be selected. So if we were using like an argmax policy, then we'd just always select the one with the highest. As you remember, we discussed this. Then we'd always select the one with the highest Q value. But we're using a probabilistic approach, whereas either using like softmax or epsilon greedy policy. And then, so we're basically selecting, we can select any one of them, but the higher the Q value, the better. So if we selected something and then the advantage was very low, then bam, the network is going to be updated in such a way that next time this Q value of that certain action is going to be less, and maybe something else will be more. So that's how that is played out. And on the other hand, if we select something where the advantage is going to be high, then this is going to go into the policy loss, and then the network is going to be updated. So that is a more commonly observed event, scenario. And so basically, this whole policy loss helps the network adapt or morph in such a way that we do more of the good stuff, good actions and good things, and do less of the bad things. And that's how these two losses come into play, and that's how they backpropagate. So hopefully that clears up in a very intuitive way. Of course, we didn't go into the formulas, into the complex mathematics behind all of this, and like into the very intricate details. But at the same time, hopefully in an intuitive way, all of this clears up why we have the actor and the critic and how they interact together. That, you have these agents synchronous. So this is the synchronous side of things. Then this is your actor and your critic, and this is your advantage, and how that all comes into play. So these asynchronous agents, they're playing this or exploring the environment and working through the environment, and they're all together contributing to a critic, which is then observing their policies, observing the actors, which is what this is called, and through the advantage, and therefore coming up with this policy loss, and then policy and value loss, they're backpropagated to adjust the network in order to, on one hand, represent the true way of things in the environment, on the other hand, to improve the actors' performances. So there we go. That's a quick recap of the intuition we discussed. And once again, hopefully this is all coming together on an intuitive level. And of course, in the practical tutorials, we'll talk more about how all of this works, and Adlan will walk you through the process of building this. But having this image in your mind, and this kind of like a roadmap of everything, how it comes together, should be, I hope it'll be very helpful for you to better navigate the practical side of things. And in terms of additional reading for today, we've got two elements. So first one is on the advantage. So here we've got high dimensional continuous controlling using generalized advantage estimation by John Schulman. And this is an image of a stick figure getting up, like standing up. And here you can find even more about advantage, and you'll find out the different types of advantages. So you've got the generalized advantage estimation, You've got advantages that you use actually in the formulas, in the calculation. So if you want to find out more about advantage and exactly how it works, the formulas behind it, and some of the top elements or formulas and know-hows in the space of this advantage that we discussed, then this is the article to go to. And one other element that or piece of work that we wanted to remind you about is the blog, a series of blog posts by Arthur Giuliani, which we've mentioned a couple of times already. This is part 8, which is specifically about A3C. So here you can get another explanation, so with a bit more mathematics about what's going on, and maybe you can pick up some additional things from here. Just 2 things to keep in mind. First of all, as always, this blog is in TensorFlow, whereas we're using PyTorch, so keep that in mind. And the second thing is that the way we structured our approach is we talked about actor-critic first, then we talked about asynchronous, and then we talked about advantage. Whereas in his blog, Arthur first talks about asynchronous, then actor-critic, then advantage. So keep that in mind. So hopefully that doesn't throw you off. But other than that, of course, it's a great piece of content, and we do highly recommend checking it out for some additional information. So there we go. Hopefully you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're going to talk about an add-on that we're going to be implementing for our A3C algorithm. It's called the long short-term memory, or the LSTM for short. So let's have a look at what we have so far, and then we'll discuss why we need the LSTM and what an LSTM is. So far we've discussed the A3C algorithm. We've talked about all 3 letter A's in the A3C, and of course we've seen that it's actually a bit more complex, much more complex than what we have on this image. We actually have 3 or more, multiple agents going through the environment, and they're communicating between each other and so on. But for simplicity's sake, for today's tutorial, we're going to just illustrate everything with this one agent. At the end, we have this actor part, the critic part. So basically, once we have a state, that state of this image goes through a convolutional layer, then it goes through a pooling layer, goes through a flattening layer, and at this point we have values or numbers which are then propagated through the network, and they go into the hidden layers, and then as the output we get the policy or the actor part, and we get the value of the state, or we get the critic part. And what we're going to do today is we're going to talk about this hidden part. So in the hidden layers, we can actually take it to the next level, and we can add a modification. And we've already seen that multiple modifications exist for the A3C algorithm. We've seen one of them. We've seen that in some cases you can have this main part of the network which is individual to every agent, or you can have this main part of the network which is shared. And that's what we saw, that in our previous intuition tutorials we had a shared part of the network. This network was shared between the agents, and as Adlan will tell you more in the practical tutorials, that really helps with the challenge of breakout. And there are lots and lots of other ways you can modify the A3C algorithm, lots of other additions that can be implemented. And one of them we're going to discuss, because we're actually going to have it in the practical side of tutorials. Here, before your hidden layers, which you can add, is an LSTM layer, a neural network layer, which allows your A3C algorithm, which allows your algorithm to have memory, which allows your algorithm to remember what happened before. And we'll talk about LSTM just now in more detail, but basically you can add an extra layer here, which is the LSTM layer, and enhance your algorithm with some additional memory, with another feature. And what you'll actually see in the practical tutorials is that we didn't even need any hidden layers after the LSTM layer. So you'll see that in Adlan's implementation, he's got the flattening layer. Right away after that, he's got the LSTM layer. So basically this box represents the LSTM layer. And then after that, right away, you've got the output. So you didn't even need any other hidden layers after that, simply because that's how much power the LSTM layer adds to the algorithm. And again, the algorithm, or the architecture of your neural network, it's a very individual thing. It's a personal preference. It's a very creative thing. So you might want to have 2 LSTM layers. You might have an LSTM layer, and then several, like 5 hidden layers after the LSTM. That's totally up to you and for you to experiment and explore. But this is what we came up with in the practical tutorials. So you'll see that we have a flattened layer, and after that, we've got an LSTM layer and then the output. So now that we've talked about the LSTM layer so much, what is this LSTM layer? Well, the LSTM layer adds memory, gives a feature like allows the neural network to have memory about what happened in the previous iterations. And it is often symbolized or shown with a symbol which looks like this. This is us just getting started into it. And I'm just putting here, I know it looks very crooked, but I'm putting it here so you can see when we further discuss this image, you can see what's going on. So the output of this layer goes into here, and that is our so this is a whole layer going in here. So it's a vector of values. X is a vector of values, goes into the LSTM, which we'll just discuss just now. And then as an output, you get another vector, which is, the concatenation of these two, or somehow it ties in with network. In our case, as an output, you get this and you get this. So let's have a look at this in more detail. So we're just going to focus on this part. In fact, we're going to, as you probably noticed by the letters being on this side, we're going to turn it to the side. So like that. And this whole jumble around was just to reiterate the fact that even though it looks like this, what is actually happening is a layer of values, a whole vector of values is going in here. Something is happening, which we'll discuss just now, and then a whole vector of values is going on here. So this is the layer. It's not just one element of the, this is the layer itself. So let's go back again, just to reiterate, layer goes into this layer, something happens, layer comes out. So that's the LSTM. It's just on its side. So it's just easier to discuss this way. And that's the common representation. All right, now that we agree why this image was on its side and how we're going to proceed with this, let's start digging into this LSTM situation a bit more. So what happens inside the LSTM layer? So this is what it looks like. And of course, this looks very complex. And we're definitely not going to go through all of this right now. Simply because there's quite a lot to discuss. These are point-wise operations, these are layer-wise operations, and there's just a lot going on, or a lot of intricate details which we're not going to go into because otherwise it would blow out this course. And this is not, the purpose is not to talk about LSTMs here, which is going to utilize LSTMs. And if you'd like to learn more about LSTMs, you can either go to over here, Christopher Ola's blog. He's got a good description of LSTMs, or we also talk about LSTMs in our Deep Learning A to Z course. You can check it out there. We've got a whole section on recurrent neural networks and LSTMs as well. So basically, this is the internal part of the LSTM, and what happens is the layer goes in. So we're going to talk about this on an intuitive level, on a very basic intuitive level, just what is going to be enough for us to understand what happens, why there's memory, and so that you can also better understand what Adlan is talking about when he's implementing this. So a layer goes in, all of this, something basically goes on here, a layer goes out. What we need to actually see is that these parts, there's actually additional inputs into this layer. So remember this, usually you have an input from a previous layer, then this layer, and then you have an output. If you think of that image we had previously, the normal network, which is not on its side, which is from left to right, not from bottom to top. But with an LSTM, you actually have more inputs. So I know it's getting even more complex. But these things, at least we can understand them. So this is your memory cell. This is the key, and this is what you'll hear Adlan talk about. So the memory cell is something that is saved in the LSTM. So these inputs and these outputs, they're actually, here what you're looking at is the time axis. So this is unraveled in time. So in one specific iteration, this happens. But then this value is taken from the past, and this value is passed into, these values are taken from the past, and these values are passed on to the future. And how they pass? Well, through the way the LSTM works. So without worrying about too much what's going on here, all we need to understand is that the layer goes in, and here we already have a value which came from the past, which is stored inside the LSTM, inside the long short-term memory. We've got this memory cell, and whatever value was here before, it just stays here. As you can see, it just goes through, it flows through freely, except for these point-wise operations where it can be either closed off or something can be added to it. But regardless of that, it's just some value that flows through freely. So it's basically it's passed on to the next point in time, So you can just think of it as like some memory that, like a flash drive or something like that this cell has. And so it just remembers the previous value that was in here. And then it can use that to either add to it or read from that value and so on. And this value is the hidden state. So hence the H. And the hidden state is basically another value that comes from the past and then is used inside the LSTM. And as you can see at the end, after all of this happens, what you get is you get a layer that comes out, and so you get this value that comes out, and it is the same value that's passed forward. So basically, the LSTM remembers two things. There's a constant value that is just like stays in the LSTM that can be changed. Like there's a flash drive for like a constant value, so the memory cell. And so you have the luxury of storing something in that space, in that memory, and it'll be passed on to the future. So whenever in the next iteration, so like the algorithm was in an environment, it saw something, did something, and so on, and then in the LSTM you can store a certain value, and then it will remember this value even when it's in the next state. And also the other value that it will remember its previous output. It automatically will remember its previous output. So the output goes here and goes here. So that's basically the very, very, very high level of what happens in an LSTM. Once again, if you'd like more details, there's lots of resources where you can find. And at this stage, we just don't need to go into that much detail on all of these things. We just need to understand, what a memory cell is, what a memory cell is, what a hidden state is, and how they facilitate memory for the LSTM. And the question is, so now that we kind of have a general overview of all of this, to reinforce or to solidify this knowledge, or kind of like give a reason for this knowledge, let's ask the question, why do we need memory? Why do we need memory in our A3C or other algorithms? Well, let's look at our example, the challenge that we're taking on in this section. So the challenge is breakout. And what happens in breakout? Well, in breakout, you've got this environment, these little blocks that you need to destroy with this little ball, and you need to make sure that this is your kind of like racket or platform that's moving around, and it must, wherever the ball is flying, it must catch the ball, and it'll bounce off the platform and go back and hit. It'll bounce off the walls as well and go back, hit a block, and come back. And so that's the essence of what you need to accomplish. But now let's look at this ball. Like, imagine you're an A3C algorithm, or an agent inside one of those agents inside A3C. You see this picture. What do you extract from here? What would your actions be here from here? So you can see the ball is flying, right? So, well, it's flying, right? So it's going somewhere, and maybe it's flying towards you, right? Could you make this conclusion? Could you like anticipate that it's coming towards you? You probably could, and maybe you're in the right spot to catch the ball. But what if the ball is actually not flying that way? What if it's flying that way? The thing is, you cannot tell from this one image which way it's flying, because you don't know where it was in the previous moment of time. So if it was here, then it's flying this way. So if you knew the previous moment in time, if you knew that it was here, then now you know here, as a human, you just draw a line from these two and you'd be like, oh, cool, so it's going this way. But if you knew it was here, you draw a line from these two and it's going this way. Moreover, look at this. It could have actually been somewhere like over here. Maybe it's going up. Maybe it's actually going that way. So maybe it was here, now it's going up way. So just from that one image is very hard. It's actually impossible. It's just like geometrically impossible to tell which way the ball is flying. And so that's why the LSTM, the memory, actually really, really helps algorithm. Without the memory, you can still do a good job. It could probably like guess or find other ways of understanding where to go. But with the LSTM, with just even that one memory, so if we go back, even with that one value, well, that was kind of like the output of the previous value, or maybe you can store it here, or based on this value, like based on the information that it gets from the previous point in time. So let's say from what happened here. So that's where your ball was before. So you can pass on information about the environment from the previous point in time through here. And then now you have it. Now you don't not only have your information from the image. If we go back even further, you'll remember that information from the image, well, this is Doom, but we're actually working with Breakout. information from the image came here, 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 turned into these flattened values. And so that's information from the image coming into the LSTM. And now all of a sudden, as you remember, coming from not from somewhere, but from the previous point in time. So that's why you can't actually demonstrate it's coming from the top or from the bottom, from left, right. It just stays in the LSTM layer. You have that information just through the architecture of the LSTM. You have the information about what happened previously. And so we go back. That information here helps you now make a decision on what to do, helps the algorithm make a decision. And now all of a sudden it knows that, okay, so the ball is actually flying in either direction. Let's say it's flying in this direction or in this direction, so I'm in the right place. So I should stick around here. The ball is coming in my direction. Or if it realizes the ball is flying there, it should start moving to the left, because if it waits a bit longer, it'll be too late and it'll miss the ball. So basically, that's how the LSTM layer really helps in this algorithm, and that's exactly what we will see when you're doing the practical tutorials with Adlan. So there we go. That's how LSTMs work. And just one additional note, as we mentioned at the start, LSTMs are not 100% necessary. They're not a complete, like they're not completely attached to the A3C algorithm. You might want to have them in the A3C algorithm. You might not want to have them depending on the situation, depending on the architecture you choose. There are lots of additions, and we've already discussed the addition or the modification where the neural network is shared between actors or is not shared between the agents or not. Now the LSTM. There's another one that you will see in the practical tutorials where we add entropy, which is calculated through a policy loss, and Adlan will walk you through that. So basically, there's lots of different modifications that can happen in an A3C algorithm. Just remember that it depends on what you want to achieve, and it's also something that we'd encourage you to explore if you're going to be implementing lots of these and trying out different algorithms. We've already discussed a couple, and maybe you can find some additional modifications that might be of interest to you. Or maybe when you're watching these tutorials, maybe by then more modifications have come out, which are very interesting. So definitely that's something that you could look into, and that could further enhance your knowledge of artificial intelligence and how to create these algorithms. And on that note, I hope you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy AI.
Hello my friends, and welcome to the practical activities of part 3 on the A3C model. I'm super excited because now we're getting even closer to mimicking human intelligence, because indeed we're adding to our AI a critic sense. In addition to, of course, first the brain that we were able to build in part 1, and then the eyes that we were able to build in part 2. And so indeed that's the human intelligence feature that we're adding into our AI for this part 3, which is a critic sense, which is brought, of course, by the critic agent in the A3C model. So you will see it will be super exciting to implement that. And so there we go. Let's not wait. Let's start right now. So remember, in part 1, we built an AI and trained it to land on the moon. In part 2, we built an AI and trained it to play a game. And now in part 3, we're going to build an AI and train it to fight Kung Fu. Alright, so let's do this. We're going to go now into the environment. We're going to go into Atari, of course. And then we're going to scroll down. We're going to click here, see more environments. And we're going to scroll down to K to find Kung Fu Master. Here we go a bit more. And here it is, Kung Fu Master. So let's have a look at the environment. That's always the first thing we should do when we build an AI, to understand the environment, to understand what is the action space, what is the observation space, and how the reward system works. So there we go. The action space is composed of 14 discrete actions. So let's have a look at them. We can find them in more details below. Actions, there you go. So these are all the actions. So the action of index 0 will be do nothing. Then action of index 1, up, which means probably jump. Action of index 2, go to the right, then go to the left, then down, meaning probably kneel down, then down right, down left. Okay, so these are all the fight moves. You see right fire, left fire, down fire, up right fire, up left fire, down right fire, and down left fire. Okay, so we have all these actions. However, these are the actions of the Kung Fu Master V5 environment. And again, you know, in order to not have a too long training that requires too much compute resource and memory, well, we're going to take a simpler environment than this one, and it's going to be, once again, one with a small part of deterministic action. So we're going to go for the Kung Fu Master deterministic V0. Indeed, it is simpler because a small part of the actions of the other agents, meaning the monsters, the enemies which we have to fight, or which our AI has to fight, will be deterministic, but that's only a small part of them, just in order to decrease the complexity of the environment and therefore offer us a faster and easier training, which is good, for educational purposes, because I really want every one of you to be able to train your AI and enjoy the results at the end. So we're going to go for this one Kung Fu Master Deterministic V0, and anyway, we will have a look at the actions again in the implementation, so we will know exactly what the action space is. And for the observations, well, of course, there are going to still be images, right? Each time we are progressing closer to mimicking human intelligence. So in the last part, our progress was to add some eyes to our AI. So of course, now we're going to keep those eyes and we're going to add a critic sense. But therefore, since we're keeping those eyes, well, the input states will still be images of these dimensions, which we will resize, of course. Okay, so we have it here. These are the dimensions of the images, 210 by 160 by 3, the 3 RGB channels. But of course, we're going to resize that again in order to decrease the complexity for the training. All right, so I think we're good here. And what about the reward? Well, the reward, just like last time with Pac-Man, the reward is going to be the score. That score that we see here, it starts at 0. And well, if we kill some, if our AI kills some enemies and avoid some bullets and progresses in the game, well, the score will increase. Right now we don't see it increasing because apparently the AI is doing nonsense actions, but there you go. You will see at the end we will get some nice results with that score increasing over an episode, and hopefully we will reach a good score. If our AI already reaches 500, well, we will see it already able to fight quite well. Maybe not like Neo in the Matrix, but still definitely better than me. Okay, so let's do this. Let's go into our implementation. So I copied before the link that was provided to you just before this tutorial, the link, of course, of the Google Drive folder containing all the codes of this course. And so there we go. Now we're going to go into part 3, A3C. And again, you will find 2 implementations, 2 notebooks, the complete code one containing the whole code and all the results and everything. But I recommend not looking at it right now so that we can practice and code everything together first. And speaking of which, well, that's what this partial code notebook gives us. Indeed, this code only contains the code cells that are not related to building an AI, and inversely, all the cells related to building an AI were removed so that we can recode them together as we should. We should practice the maximum and really know and understand how to build an AI on a practical level. So let's do this. Let's open this notebook, A3C partial code, and here it is. But remember, this notebook is in read-only mode, and therefore no one can do any modification on it, code on it. Therefore, we're going to go to File here and then click Save a Copy in Drive. And this will create a copy in your drive, which you will find in your Colab Notebooks folder. Here it is, copy of A3C Kung Fu partial code, and now you are the owner of it. Therefore, you can modify it and code on it. So perfect, we can now start. But first, let's rename that to A3C for Kung Fu partial code. I'm just going to remove the copy of here. And there we go. Now it's better. So now you have all the 3 codes, of parts 1, 2, and 3, and of course excluding the LLM code for generative AI. So again, congratulations for having reached this far in the course. So there we go. Let's open this new notebook, which now belongs to us. We are the owner of this notebook, and therefore we can code on it and implement our new, even more powerful and even closer to human intelligence model, the A3C model for Kung Fu. So let's start the implementation in the next tutorial, and until then, enjoy AI. Hello my friends, and welcome back to this implementation of A3C for Kung Fu. So before we start, I just want to show you the structure of our implementation, because it's good to have a bird's eye view of what we're about to implement before we do the implementation. So as usual, we start with the part 0, where we will be installing the required packages and importing the library. So it's always the same thing. We just need to install Gymnasium thanks to Google Colab, where indeed most of the libraries and packages are already pre-installed. So we will just install Gymnasium. Well, actually, let's run the cell right now because, it takes a little time to install indeed Gymnasium and the environment. All right, so here we go. It is now downloading Gymnasium. It's downloading the dependencies like format notifications, etc. Just like before, right? It's exactly the same. It's the exact same code cell, and we will have the same dependencies being installed, auto roam, and etc. So the cell will be running now. The dependencies will be installing. Successfully built auto roam, successfully installed auto roam, reading package list done. Everything looks good, just like before. processing triggers, downloading Box2D, building wheels for collected packages Box2D for Python, and in a few seconds we'll have our gymnasium. So that's perfect, that's exactly like before. Then the next step will be to import the libraries. And so here, well, same as before, but this time in the import, I included the gymnasium libraries and modules or classes that we will use from gymnasium. So there we go, it's included here. And so once this cell is done, meaning once gymnasium is installed, well, we will be running this cell to import the libraries that we will need in this implementation. Of course, we'll have a few more libraries to import later on, but I try to include the maximum of them. Successfully built Box2D API, perfect installing collected packages, Swig, Box2D API, and there we go, successfully installed Box2D Python. You might have a different version when you take this course, but that's fine. We will always keep the code up to date whenever something is out of date, okay? And I might even re-record some tutorials if some codes or module expire. Alright, so great, so now we have gymnasium, so we're gonna import the libraries, okay? So same, we import NumPy to work with NumPy arrays, we import the random library to generate some random variable, we also import, of course, all the torch, library and modules such as the NN neural network module to build our neural network, but also the optim module to build our optimizer and use it to update the model's parameters, meaning the weights. We also import the functional module to, not only use the activation function, but also to use the loss function, when we backpropagate that loss between the target values and expected values. And then we import some other modules such as distributions by the torch library. And there we go, gymnasium, observation wrapper, and box for the environment. So with this, we'll almost have everything we need. We'll have a few more imports later on, but that's okay. Let's start with this. Let's import the libraries. Alright, so it's importing the libraries now, and in a second we will have all the libraries imported. And once again, we didn't have to install any of those modules and packages because it is already pre-installed in Google Colab. That's the beauty of Google Colab, and that's exactly why I wanted us to work on Google Colab. This makes our life much more easy. Alright, so now let's have a look at the structure of the implementation. Just like before, we're going to start with part 1, building the AI, where of course we're going to create the architecture of the neural network. So once again, the neural network of our A3C agent, our new AI, will have fully connected layers representing the artificial brain just like before, but also convolutional layers which represent the eyes. So we will include all that, of course, and besides we'll make that forward function to forward propagate the signal from the input images up to the final output layer, passing through the convolutional layers first and then the fully connected layers. Alright, so we'll do all this, and that critic sense that we're adding to our AI, that extra feature which will make our AI closer to human intelligence, well, won't be implemented in this architecture. It will be implemented in the A3C algorithm, okay, which we will do later on in part 2. And well, speaking of part 2, well, that's of course about training the AI, because of course once we have our brain here and our eyes, well, it will be time for us to train it to fight Kung Fu, okay? So how will we do that? Just like before, we will start by setting up the environment, right? Same first step of part 2, although this time we have to use this much more advanced pre-processed Atari class, which will make our environment fully ready for our AI to be trained and fight Kung Fu. Okay, so no need to implement that at all. It's not really related to building an AI. So let's just save us some energy here to focus on the real deal, which is of course all the cells that come after, meaning initializing the hyperparameters of our AI, the A3C agent, then implementing the A3C class, then initializing the A3C agent, then evaluating our A3C agent on a single episode. We will need that in order to measure the performance of our A3C agent during the training. Then of course we'll test multiple agents on multiple environments at the same time in a function so that we can indeed implement the A3C algorithm. And finally, once we have all that, we will train our A3C agent in a nice loop. And once done, we'll get some good training results, hopefully, and we'll move on to part 3 to visualize the results. And here, that's the exact same code as before, with the show video of model function first and then show video, and then we'll get the video at the end of our AI fighting Kung Fu. Alright, so I hope you're excited. I'm super excited to start this implementation because indeed this is the most powerful model of this course. Indeed, with that critic sense added, it will really make our AI more artificially intelligent. So there you go. I can't wait to start the part 1 of this implementation, building the AI. So take a good break. Again, we'll have a big architecture of our AI's neural network to implement. So once you're ready, join me in the next tutorial and let's smash this. Hello my friends and welcome to part 1 of this implementation, Building the AI. I'm super excited to create the architecture of our neural network. We will, just like before, implement a network class which will include the whole architecture of our A3C model, which will contain of course the convolutional layers to build eyes, the fully connected layers to build neurons, and the forward method to forward propagate the signal from the input images up to the final output layer. Alright, so that's all we'll do in this new code cell, creating the architecture of neural network, and indeed the rest of the A3C algorithm will be implemented later on in the agent class. Alright, so let's do this, let's create a new code cell and let's start the implementation. Great, so as usual we're going to start with class because we're going to define once again a network class just like before, which will inherit from the nn.module, meaning the module class from the NN neural network module by PyTorch. There we go. Then let's add some colon, and here we go, defining the constructor method init method. Alright, so let's do this. Let's start with def to define it, then double underscore init, double underscore again, and it will take, just like our deep convolutional Q-learning model, first self for the object and then the action size. Remember, the network class of the deep Q-learning model took as input here the state size and the action size. Then the deep convolutional Q-learning model took only the action size because for images the state size didn't make much sense. And now, well, since we're doing the same, since we still have input images and also eyes in our AI, well, we're only taking the action size. So far, exactly like the deep convolutional Q-learning model. Alright, so let's add some colon, and then remember, we're going to activate the inheritance with the super function, which takes as input our network class, the class that will inherit from the NN module, and then comma, and then self for the object. Alright, great, then we add here a dot, and then another double underscore init, double underscore, and parenthesis, inside which we don't input anything. Super, inheritance activated. Alright, so now let's define the convolutional layers, or more specifically the convolution operation. So we're going to start with the first one, self.conv1, just like before, which will be created as, of course, an instance of the conv2d class, which we import from the NN module from the Torch library. So that's why I'm starting with Torch here, and then NN, calling the NN module, and then from which we call this conv2d class. There we go. Let's add some parentheses. And inside, well, remember, we have to input the number of input channels, the number of output channels, the kernel size, and the stride. So here we go. Let's start with the number of input channels. And so now, remember, in the deep convolutional Q-learning model, we had 3 input channels here in the first convolution. But actually now, we're going to have, guess how many? We're going to have 4. And what does this time 4 correspond to? Well, be careful, it doesn't correspond anymore to the 3 RGB channels for colored images, because here actually for our A3C model, we're going to have a stack of 4 grayscale frames from our Kung Fu environment. Alright, so that's why we have 4 here, and then, however, for the number of output channels, there it is, well, we're going to have, just like before, I think we had 32, right, in the deep convolutional Q-learning model. Let's check again. Or maybe 64, I don't remember exactly. Yeah, 32. See, we started at 32, then we increased to 64, 128, and you'll see how we will do now with our A3C class. Okay, so 32 output channels still here, and then we're gonna have a kernel size of 3 by 3, and finally a stride of 2. So once again, there's no rule of thumbs for choosing the optimal numbers here. We just have to do a lot of hyperparameter tuning, a lot of trial and error, and a lot of experimentation to end up with hyperparameter values that lead to a great score. And of course, a lot of experimentation was done on this A3C model for Kung Fu, and these hyperparameter values turn out to be quite good. Maybe not optimal, maybe you'll find better ones. If you do, please share in the comments, but these are quite good already indeed. Okay, so that's it for our first convolution, self-conv1. So now I'm going to copy it, of course. I'm going to paste it right below, and I'm going to replace self-conv1 by self-conv2. All right, self-conv2, here it is. So now what is going to be the number of input channels in the second, therefore, convolution? Well, that's of course the number of output channels in the previous convolution, meaning 32. And now, regarding the number of output channels in the second convolution, well, it's not going to be exactly like our deep convolutional Q-learning model where we increased the number of channels, however, feel absolutely free to try that, but in fact we're going to stay at 32 filters. And again, that's because it leads to pretty good results at the end. So 32 output channels, and then the same kernel size of 3 by 3 and the same stride of 2. So actually, we're all good with our second convolution. So I'm going to copy it again, and just below I'm going to paste it, and I'm going to replace selfconv2 by selfconv3. Because indeed we're having another convolution with a third convolutional layers. And well, the good news now is that we don't have to change anything in this line of code, because actually for our third convolutional layer, we still want 32 input channels and 32 output channels. So you see, it's not increasing this time. It doesn't have to increase all the time. For deep convolutional Q-learning, increasing the number of filters over the convolutions actually was better and led to a better score in the end. But here, we're having great results, but once again, maybe not the best ones with this architecture. But again, feel free to try some other architectures, and if you get a much better result at the end, well, please share that in the comments. I'm super curious to see your better architecture than in this tutorial. Okay, so that's gonna be it for our convolutions. Now we're gonna do something that we haven't done before in the deep convolutional Q-learning model, which is to create directly the flattening layer. Remember, in the deep convolutional Q-learning model, well, first we had the batch normalization layers, which we don't have anymore in our A3C model, simply because they don't really improve the results, but mostly, as you can see here, we didn't create the flattening layer. We directly moved on to the fully connected layers here. But here we're going to do something different. We're going to create that flattening layer within an object, which we're going to call self.flatten. And it's good that you know this also. You can create a flattening layer thanks to a torch class, which is actually the torch dot, of course, and n again, because this class belongs to the nn module. So torch.nn dot, and as you might guess, of course, well, flatten. The flatten class, which indeed allows us to create a flattening layer after the convolutions. And you will see, thanks to the forward function, how we forward propagate the signal from the convolutional layers to that flattening layer. All right, and actually we don't have to input anything here because the transition will happen thanks to the forward method. And so we can directly move on to our fully connected layers. Okay, so well, let's do this. The next operation that comes after the flattening is, of course, the first full connection, and which we're going to call, of course, self.fc1, right? Just like before. And remember, we create that as an instance of the linear class by the NN module from the torch library. Therefore, we call first the torch library, from which we call the NN module, from which we call the linear class. There it is, and then we add some parentheses, and inside the parentheses, remember, we have to input first the number of input features, which is actually the number of outputs in our flattening layer. And for this, well, remember that we have this very complex formula that requires to be applied in the different operations and layers we had before. So we're not going to go into the details of that. I'll just tell you that number, which is 512. Okay? If you're really interested in knowing how we get to this number, well, feel free to ask ChatGPT. You just provide this architecture to ChatGPT. You ask ChatGPT to help you decompose that whole formula through the different operations and layers, and you will get to that 512 number at the end. Okay? But let's not spend too much time on this and move on with our following full connections and fully connected layers. So 512 for the number of input features, and now for the number of output features. Again, no rule of thumb, but a good number is 128. Okay, 128, perfect. And now something very interesting is going to happen, and that is proper to the A3C model, therefore we haven't done before. What we're going to do now is actually directly move on to the final output layer, or should I say final output layers, because indeed, first, we're not going to have any second intermediary fully connected layer. We're directly going to move on to the final output layer, but mostly we're going to have two final output layers, right? Do you guess what they will correspond to? Well, the first one will correspond to the action values, which are of course going to be the Q values for each action, which is the expected return, meaning the sum of rewards starting from the current state. So that's exactly what we had in our previous models, right? The deep Q-learning and deep convolutional Q-learning model. So we're still going to have that here, but also we're going to have the state value, right? Which will be a single output of the network that will provide an estimate of the value of the current state. And that value is actually a prediction of the expected return from the current state if the agent follows the current policy. Okay, so we need both of these for the A3C model, and therefore we're going to create a first second full connection, which we're going to call FC2A for the action values. And therefore, to create that, we're going to call first the torch library, from which we're going to call the NN module, from which we're going to call the linear class, which will take as input first the number of input features, which will be, of course, the number of output features we have in the previous fully connected layer. Therefore, I'm going to enter 128 here, and then since this second full connection will return the final output layer corresponding to the action values, well, here we have to input, of course, the action size, okay, containing the number of possible actions. And therefore, the output of this second full connection FC2A will be the action values, meaning the Q values for each of the actions representing this expected return if we play that action from the current state. Okay, so that we know, but now what we also need to create is that second full connection leading to the final output layer containing the state value, and this one I'm going to call it FC2S, okay, for the state value, okay? And so for this one, what will be the number of input features here? Well, of course, that's going to be the number of output features here in the previous fully connected layer, therefore 128. This we don't change. However, what is going to be the final number of output feature here in the second full connection FC2S? Well, since we're expecting only one state value, of course, this final number is going to be 1. Okay? And that's it. That's it for the architecture of the network class for our A3C model. Now I guess it's time to take a good break. We did some good new work here to build this A3C model. So let's get some great energy, and as soon as you're ready, we'll implement together that forward method, which will forward propagate the signal from the input images up to the final two output layers. And until then, enjoy AI. Hello my friends, and welcome back to creating the architecture of the neural network. We are now at the second step of implementing this network class. We just implemented the init method to, build the different properties of the object, the future A3C eyes and brains that will be created later on. And now we're about to define the forward method to indeed forward propagate the signal from the input images up to the final two output layers of the action values and the state value. All right, so let's do this. Let's start by defining the forward method, which will take as input self first for the object, and then, of course, as always, the state. The state, which is, of course, input frames. Okay, so let's add some colon, and there we go. Let's forward propagate the signal. So we're going to start from our state, right? That's the very beginning. Then we're going to forward propagate the state to the first convolutional layer, and to do so we're going to call our self.conv1 convolution, which will take as input the state and which will return, of course, the signal in that first convolutional layer. Alright, so first step of the forward propagation done. Now we're just going to activate that signal thanks to the rectified linear unit activation function, also called rectifier activation function, also called ReLU. So here we go. You know how to do this. We first call our functional module, which has a shortcut F, from which we call, of course, the ReLU function, which takes as input, of course, X, right? That signal which we have to linearly activate. So now we're going to update X by just adding here at the beginning X equals. Okay, so now the signal is activated, and so let's continue the forward propagation. And so, well, let's do that efficiently. We're going to take that first line of code here. We're going to paste that here. And now, according to you, what do we need to change? Well, we need to change two things, of course. First, the convolution. We're now forward propagating the signal X from the first convolutional layer to the second convolutional layer, and therefore we use our second convolution conv2 to do such propagation. And of course here it's not going to take the state as input, but of course the signal X. Okay, perfect. So now the signal is propagated from the first convolutional layer to the second convolutional layer thanks to our second convolution. Alright, so now let's take this to activate once again this signal thanks to the rectified linear unit activation function. So let's paste that here. And here, of course, we have nothing to do because, again, it applies that activation function on our signal X here, which is then updated here. All right? So now let's smash that next step for propagating the signal from the second convolutional layer to the third convolutional layer thanks to the third convolution, and also while activating it. So what we're going to do now to make it efficient is take those two lines of code and then just paste them below. And of course here we're just going to replace self-conv2 by self-conv3, and voila, this is all we have to do to indeed forward propagate the signal X from the second convolutional layer to the third convolutional layer, thanks to our self-conv3 third convolution object we created here. Okay, so perfect. Now the forward propagation is done through the different convolutional layers, and so now we're gonna continue that forward propagation from that last convolutional layer to the rest of the neural network. And speaking of the rest, well, what is the next step here in our neural network? Well, that's of course the flattening layer, right? We created that flattening operation here, which gives us the flattening layer, and therefore we're going to forward propagate now the signal from the third convolutional layer to that flattening layer. And according to how we're going to do that, well, that's super simple. We'll of course use our flatten object, just like our conv object and our fc object. So let's do this. We're going to call indeed our self.flatten object, which will take as input, of course, what? Our signal x. Okay, x here, which is currently in the third convolutional layer, and which we're going to forward propagate to the flattening layer. All right, so that does the trick. And so now, well, we only have to forward propagate the signal from the flattening layer to the first and only intermediary fully connected layer, which is given by our FC1 linear full connection operation. So there we go. Let's do that next step of the forward propagation. We call our self.fc1 linear full connection operation, which will take as input, of course, our signal x, and which will return that new signal x in the first fully connected layer. And then, of course, we're going to activate that. So we're going to add that same next line here, x equals f.relu of x. Perfect. So that activates the signal just forward propagated from the flattening layer to the first fully connected layer, thanks to our first linear full connection. And so now, finally, what is the next and final step? Or should I say final steps? Because indeed now we have two final output layers, one returning the action values and one returning the state value. Well, that's exactly what we're going to do. We're going to get those final outputs in the two final output layers. All right, so let's do this. Let's start with the action values. Okay, which we're going to get by forward propagating the signal in the first fully connected layer to the final output layer, thanks to our FC2A linear full connection operation. So, well, actually, let me take this here, because that's exactly what we have to add next here, because indeed we're going to call our FC2A linear full connection operation, which will take as input, of course, our signal X. All right. And that gives us the action values, meaning the Q values for each of the different possible actions that the AI can play. Okay, just like what we did in the previous implementations of deep Q-learning and deep convolutional Q-learning. But now we're implementing the A3C, so we're also going to return the state value thanks to our other final full connection FC2S. And so I'm going to take my last object here, self.fc2s, I'm going to copy it, and here just below, I'm going to create that final variable of the state value. There is only one, right? And then I'm going to call, of course, our self.fc2s linear full connection operation, which will take as input what, of course? Well, still our signal x, right? Because we start from the same signal x in this intermediary fully connected layer, but then we call two final linear full connection operations to forward propagate the signal to different final output layers. One that will contain the action values and one other that will contain the state value. So there we go. That's exactly what we will get here. The state value in that final output layer returned by that second FC2S linear full connection operation. But here actually, in order to get the state value itself, we just want the value, not in any vector or any array. Well, we're just going to add here a pair of square brackets and then 0 inside to really access this value. Because, we will use this value in the future formulas of the A3C algorithm. Alright, and so now, according to you, what is the very final step that we have to do? Well, remember, the forward method is supposed to return those final outputs in the final output layer. And so that's exactly what we're going to do. We're going to return first the action values and then second the state value. Because, of course, we now have two final output layer, one containing the action values and one containing the state value. So congratulations, my friends. Well, actually, now it's time for me to say triple congratulations, because not only we are done with the forward method, but also we are done with the network class, and also we are done with part 1, building the AI. So let's not forget to run this cell to indeed have our model of the network class created, so that we can create anytime we want and as many as we want some brains of our future A3C models containing eyes and neurons, and that forward method as a tool to forward propagate the signal from the input images to the final two output layers containing the action values and the state value. And so now, well, let's get recharged in energy with a good coffee or tea or a good nap. And as soon as you're ready, well, join me in part 2, training the AI to train our brain we just created with the A3C intelligence integrated. Alright, so I can't wait to start this part 2 in the next tutorial, and until then, enjoy AI. Hello my friends, and welcome to part 2 on training the AI. We have now our network class, which gives us an artificial brain and some artificial eyes for our AI to be able to see and learn and understand some logic in the Kung Fu fight game. And so now it will be time to train it thanks to this part 2. And our first step here is to set up the environment. And so for this, as opposed to before, we have this preprocessed Atari class, because actually setting up the Kung Fu environment is a bit more complex, and therefore we need this preprocessed Atari class to preprocess it. But once again, since it doesn't have directly to do with building an AI, well, I chose to leave it here for us not to have to re-implement it, okay? But basically it has the init method, the constructor method, which defines the properties of the environment with the different object variables here, like the color, the observation space, of course, and the frames. Then you have the reset method to reset the environment, of course. Then the observation method to pre-process images of the environment. And then you have the update buffer method to update the buffer. The makeOnv function, so be careful, this is outside of the preprocessed Atari class in order to, well, actually create the environment variable while using the preprocessed Atari class to, well, preprocess it. And then we have the environment here, okay? Here, this is really where we get for real the Kung Fu environment. And then for the rest, well, you know this very well. We implemented that in our deep Q-learning and deep convolutional Q-learning implementation. We first get here the state shape, then the number of actions, and then we do those sprints. But here, I just added this extra sprint, which will give us the action meanings, exactly like what we saw, remember, in the description of the actions here. We will get all these in our console once we execute the code cell. So, speaking of which, let's do this now. Let's run the cell and let's see the state shape, the action size, meaning the number of actions, and of course the action name. So here's the state shape. Remember that the state is actually a stack of 4 grayscale images, so these correspond to the 4 here, and then of which dimensions? Well, 42 by 42. Therefore, the states are going to be stacks of 4 images of dimensions 42 by 42. Right? Pretty clear? And then we have our 14 actions. So we have 14 possible actions that the AI can play, and they are right here. Noop, up, right, left, down, right, down, left, left fire, exactly like what we saw here. Okay? Perfect. So now it's very clear what the input states is, what the actions are, and so, well, we can move on to the next step, which is, just like before, to initialize the hyperparameters. So let's create a new code cell, and here we actually have 3 hyperparameters to initialize, which are similar to the ones we saw before, except one, which is totally proper to the A3C model. So let's start with the ones we know. First, we have, of course, the learning rate, which we will initialize to 10 at the power of minus 4. All right, I think it's the same value as the one we used before. And of course, it's going to be the learning rate of the Adam optimizer we will use to, update the model's parameters, meaning the weights of the neural network when we backpropagate the loss into the neural network. So that's for the learning rate. Then another hyperparameter, which you know very well, which we used already twice in the deep Q-learning and deep convolutional Q-learning model, is of course the discount factor. So here the discount factor is the hyperparameter that will be used in the formula that will compute the target state value. We will see that when we implement the A3C class. And so, just like before, we're gonna initialize this discount factor to 0.99. Alright, it looks very familiar so far, right? But now, here is where things change, because now we're about to initialize a hyperparameter which we haven't created anytime before. I mean in this course. And I'm talking about a very exciting hyperparameter because it's actually the number of, can you guess what it's going to be? Not the number of actions indeed, but the number of environments. Right? This is totally proper and specific to the A3C model, because in the A3C model, we actually train multiple agents in multiple environments in parallel. And that's the super brilliant part of this algorithm. Indeed, each of these multiple environments will be typically run in their own process, and inside which an independent agent will interact in each of these environments. So that's the really cool thing, I think, about this A3C algorithm. And there we go, we are about to initialize this number of environments variable. And how many environments will we choose to, train those multiple agents in parallel? Well, we're going to choose 10 environments, and that should be enough. And by the way, this particular feature of the A3C algorithm is one that considerably improved the training performance. Thanks to this idea of training multiple agents in multiple environments at the same time in parallel, well, will significantly speed up the learning process and help the overall algorithm to converge much faster. And you will see that in the final result. You will see that we reach convergence of the score very, very fast. I can't wait to show you this. So there we go. That's all we need to initialize here. So we're gonna run this cell, and perfect. Now please get some good energy, because indeed the next step is to implement the A3C class, which will be of course in that new agent class as we did before, only this time it will contain the A3C algorithm. I can't wait to implement this. Please recharge in great energy, get some good coffee or tea or a good nap, and as soon as you're ready, join me in this next tutorial to smash this A3C agent class. And until then, enjoy AI. Hello my friends, and welcome to this next step of the training implementation, where we're going to implement the A3C class. So it will be a very exciting step. It's of course the step where we implement the agent class, just like how we did with our deep Q-learning model and deep convolutional Q-learning model. And once again, just like before, it will be a class that contains, well, the init method for sure to define the object variables, then the act method in order for our AI to play an action, and this time it won't be an epsilon degree policy just like we did before, but a softmax policy. Alright, so it's good that you know several strategies. And finally, so this is pretty interesting, because both in the deep Q-learning or the deep convolutional Q-learning implementation, remember when we implemented the agent class, well, we had a learn method at the end, right? Which is called, in fact, into the step method. But this time for the A3C model, we won't implement separately a learn method. We will directly integrate that into the step method, so that we only have to implement the step method. Therefore, the agent class that we will build now for our A3C model will only contain 3 methods: the init method, the act method, and the step method. Alright? And of course, we're going to start now with the init method. So let's create a new code cell. And here we go. Let's start by declaring our class. So of course, we're going to call it agent, just like before. Then nothing to input in the parentheses. We can add some colon, and there we go with the init method. So we start by defining it with def, then double underscore, then init, then double underscore again, and then according to you now, what will it take as input? Well, first, of course, self for the object, but then what is the other argument? Well, it's exactly the same as the deep convolutional Q-learning model. Our A3C model has artificial eyes, which allows it to see some frames, some input images, which are the states. Remember, these are stacks of 4 grayscale frames of dimension 42 by 42, and therefore there is no such thing as a state size, just like in the deep Q-learning model. And so we're going to do exactly the same as in the deep convolutional Q-learning model. We're just going to input here an action size argument, which is of course the number of actions. Alright, so let's do this. Let's just enter action size, and there we go. We're ready to implement our init method. Alright, so now we basically have to define the different object variables, and we're actually going to start with self.device, which will be the CPU or GPU to which we send the computations. And so, well, just like before, we're going to call our torch library, from which we're going to call the device function, inside which we're going to enter first in quotes CUDA colon 0, and then outside the quotes if torch dot CUDA dot, and then remember this function is underscore available. There we go, perfect. Then some parentheses, and so that means that indeed if CUDA is available, then we will use it. We will use the GPU, or if it's not available, then we're going to add here else, and we're going to enter in quotes CPU. We're going to use the CPU, okay? Just like we did before with our deep Q-learning and deep convolutional Q-learning implementation. So all good here. Now, next object variable. All right, so the next variable is going to be super simple. It's going to be the action underscore size. And how will we initialize it? Well, of course, to the argument that will be input here when we call the agent class to create an instance of that class, which will be our A3C agent itself. Okay, so let's copy this, let's paste that here, and there we go. Now we have our action size object variable. Now next object variable, well, according to you, what does our agent always need in order to be trained? Well, that's of course the brain, right? The brain that we can get from our network class, which we implemented in part 1. And so that's exactly what we're going to get now. But remember, in the previous implementations in deep Q-learning and deep convolutional Q-learning, I can show you any of them. The way we created the brain is actually through the creation of two brains, the local Q network and the target Q network. And it was the same in deep Q-learning. But now we're implementing A3C, therefore there is no question of local or target Q network. There is only one network, well, when we create one agent, and therefore we're simply going to call that self.network, okay? Or you can even call it self.brain if you want, okay? So self.network, and then, well, how do we create it? By, of course, calling our network class, which takes as input what, of course? Well, only the action size, just like in our deep convolutional Q-learning model. So action size, and this is, of course, the argument here. So all good, we can just keep that. And then finally, we're going to send this to the proper device, CPU or GPU, which is given by our self.device object variable we created here. Okay, self.device, perfect. Now we have our brain. Great. And now, what is the final thing we absolutely need in order to train our A3C agent? Well, we have the brain, that's good, it's ready to be trained, but which tool do we need exactly to train this brain? It is the tool that will, update the models parameters, meaning the weights of the brain, inside the neural network when back propagating the loss back into the neural network. Well, I'm talking, of course, about the optimizer. And there we go, that's our last object variable here, self.optimizer. And how will we create it? Well, we will create it as an instance of the Atom class, which we get from the Optim module by the Torch library. So here we go, we call the Torch library first, from which we call that Optim module, from which we call that Atom class. All right, and remember what this Atom class takes as input? Well, it takes first the parameters of the neural network of our AI, which is of course self.network, then dot parameters to return those parameters. So that's exactly what you see here with the first argument. So here we go. Let's enter that. So we call first our self.network, which we just created right here in the previous step, self.network, perfect. Then dot, and then we call this parameters method, a method of the network class, which indeed returns those models parameters, meaning the weights of the neural network we created in part 1. Okay, so that's for the first argument. And now what is the second one? Of course, whenever you use an optimizer, you always consider the learning rate, right? Just like what we did before with deep Q-learning or deep convolutional Q-learning model. Indeed, the learning rate is one of the essential parameters of the optimizer. So here we go, let's input it here, LR equals, and well, it's going to be equal, of course, to our learning rate that we have here. So we can copy it if you want and paste it right here. All right. And that's it. That's all we need to define for our agent class, in terms of object variables. So now that means we are ready to move on to the next step, which will be to implement the act method, which will allow our agent to play an action according to, this time, a softmax strategy. So it will be a very exciting step, the first time we implement softmax in this course. I look forward to seeing you in that next tutorial, and until then, enjoy AI. Hello my friends, and welcome to this new step of the agent class implementation. Alright, so right before this tutorial we implemented the constructor init method to define the object variables, and now we're about to define the act method for our agent to play an action given a certain state. And it will be very exciting because for the first time we will implement a softmax policy to play the actions. Alright, so let's do this. We're going to start with def here, and then we're going to call this function just like before, act, which will take as input first self for the object and then the state, of course. All right, because the action that the agent will play at a certain time step depends on the state in which the agent is at this particular time step. All right, then we're going to add colon, and here we go. Let's define this act method. So first, we're going to make sure that our state is in a batch. We always need that extra dimension of the batch because very simply, this is what neural networks in PyTorch expect. And so, well, it's possible that we have some lost states not within a batch. So if that happens, we're going to make sure they are in a batch. And so with an if condition here, we're going to check if the dimension of our state, which we're going to get like that, state.enddim equals 3, because remember that the state is actually a 4-frame buffer, meaning a stack of 4 grayscale frames, and therefore you have one dimension corresponding to which frame it is among these 4 frames, and then the other 2 dimensions for the size of the images, 42 by 42. So if the dimension of the state is 3, meaning if the state is not in a batch, meaning if it is a single observation, meaning a single 4 grayscale frame buffer, well, what are we going to do? We're going to add this extra dimension of the batch by very simply not calling this time the unsqueeze method, because at this point the state is not yet a torch tensor, but we're going to do this super simply the following way by updating our state like that, by including it in a pair of square brackets, all right? And inside, of course, we enter state. So now we add this extra dimension of the batch, like in an extra pair of brackets in the NumPy array, and this makes sure that the state is now in a batch, okay? So now, if indeed the dimension of the state is 3, well, with this, what we do here, well, the dimension of the state will be 4, and therefore we'll have this extra dimension of the batch, which our neural network that we created here expects, all right? Perfect. So that's a good first thing done. And now that we have this extra dimension of the batch, well, time to convert the state into a torch tensor. And so that's exactly what we're going to do. We're going to take our state first, and we're going to update it the following way by first calling the torch library, from which we're going to call, of course, the tensor function, which will exactly convert our state right now in a NumPy array into a torch tensor. Okay, and well, this tensor function takes, of course, as input, well, the state right now in a NumPy array, but then, of course, as you can see, the D type, meaning the type of the values in the NumPy array, and then the tensor. And so, well, what is the D type? That's, of course, a float, right? Which we're going to note this way, torch.float32. There it is, perfect. And now, finally, we're also going to add the device, which we got here in the very first object variable of our constructor init method. And to do so, well, we're going to enter this last argument here, device, and this will be equal, of course, to our self.device object variable that we created before. So I'm pasting that here. And there we go. Now, not only we added this extra dimension of the batch, but also our state is a torch tensor. Perfect. And so, now that we have this extra dimension of the batch and plus a torch tensor, what can we do now? Well, since we have exactly what is required by our network here, we can simply call our network on the state to get the action values. And that's exactly what we're going to do. That's exactly our next step here. And so, well, we're going to create a new local variable, which we're going to call the action values. And we're going to call the forward method from our network object to get those action values. However, remember that the forward method in our network class actually also returns the state value, right? But right now at this point, we don't need yet the state value. We will need it in the step method of the agent class. But therefore, since we're only going to use the action values, well, what we're going to do just below in this A3C class is add here a comma and then underscore, okay? So that we can disregard the state value, okay? And so now, well, time to first call our network, of course, self.network, okay? And then, as we just said, time to call the forward method. And then remember, in PyTorch, you have a choice. Either you can call the forward method, which takes as input the state from your network, or you can use the famous PyTorch shortcut by only calling the network. That's very famous. Whenever you implement the forward method in a PyTorch class, well, it knows that when you call your network like that, it's actually the forward method that you're calling. Okay, so as you want, let's keep the shortcut. And now, great, we have the action values. Perfect. So now, according to you, what is the next step? Well, by now I've mentioned the name many times. It's finally time to use softmax, right? We're going to use the softmax policy in order to select a certain action, right? Softmax is just another action selection strategy than the one we used before, epsilon greedy. So it's good that you know both techniques, and here it appears that softmax is better. So let's do this. We're going to create a new local variable which we're going to call policy, simply because we're about to use the softmax policy to select our actions. And now, well, time to use the softmax function, which we get from the functional module, which has a shortcut f, from which we indeed call the softmax function. Okay, perfect. And now, according to you, what do we need to input in this softmax function? Well, first, that's of course the action values, right? Because a softmax policy consists of converting our action values into probabilities. And then the higher probability, then the higher chance this action corresponding to this higher probability will be selected. And so there we go. We enter first here the action values, also called famously in reinforcement learning, the logits. Okay? So comma, and then we just have to add here dim, which is the dimension along which softmax will be computed, equals -1 to specify that the softmax should be applied across the last dimension, which is indeed the dimension representing the different actions. Alright? So let's do this. Let's add here dim equals -1, and there we go. Our softmax policy is ready. And so now we have one final thing to do, which is of course to return the selected action. And so we're going to add here return, and then we're going to use our softmax policy to sample the final action. And actually, right now it's important to understand that the state is actually a batch of states, but it's common practice to actually use this simplified notation, but let's not forget it's actually a batch of several states, and therefore what we're about to return now is several actions, each one corresponding to each state in the batch. And so since we're returning several actions, well, we're going to return them into a NumPy array, so I'm calling the NumPy library first, from which I'm calling the array function, and which will contain that list of actions for each state in the batch. Okay? So how are we going to do this? Well, we're going to use our policy tensor, of course, which again actually is a list of several policies for each of the states in the batch. And so what we're about to do in this pair of square brackets here is a for loop within a list, where we're going to loop over the different policies corresponding to each of the states in the batch. Okay, so let me show you. It will be easier to understand once we code it. So first, what I suggest we do is we do it for one policy, for one specific state in the batch, and then we'll do that for loop to do the same for the other states in the batch. Okay, so let's consider just one policy for now. It will be easier to visualize. And so now the question is, we're dealing with one specific state in the batch. How we're going to return that selected action? Well, we're going to use a certain function by the NumPy library, more specifically by the random module from the NumPy library. So here we go. We're going to call the NumPy library first, which has the shortcut np, from which we call the random module, from which we call this choice function. The choice function which will allow us to draw from a certain distribution of probabilities, which is exactly what we have. Thanks to the softmax function here, we were able to get a distribution of probabilities over the different actions, the different action values for each state. And so, well, since we have this distribution, now we can use the choice function to sample an action from this distribution. And so, what do we have to input in this choice function? Well, first, the number of different actions we have for each state, and that's len of p, where p will actually be one of the policies in this list of policies for each of the states in the batch, and length of p here corresponds exactly to the number of actions. And then, as the second argument here, we're going to enter, well, the policy itself. And that's our argument here, p. We are going to enter p equals p. And p, of course, here will be one of the policies corresponding to one specific state in the batch in this policy tensor. And so, now in order to finish this, we simply have to add the for loop in order to loop over the different policies we have in this policy tensor. And so, what we're going to do, we're just going to add this for loop here. So I'm adding for p in, of course, our policy tensor here of the different policies for each of the states in the batch. Okay, so I'm adding policy here, but then we're just going to detach this policy tensor from the computational graph because we won't use any gradient to perform this computation of, sampling the actions from this distribution of probabilities. And so there we go. We're just going to add here dot detach, then parenthesis. Then after that, we're going to add another dot and then CPU because we're actually going to send these sampling computations to the CPU. And then now that we detached the policy tensor from the computational graph, well, we're going to set this finally to a NumPy array, which is why I'm adding to finish the NumPy function. So that actually our policy tensor here is converted into a NumPy array. All right. So basically, let's recap. Policy here started as a tensor, a torch tensor. Then we detached it from the computational graph. then we moved the tensor back to the CPU, and then we converted that tensor into a NumPy array. All right, so that these two formats here fit together, and so that we can have the final actions in a NumPy array. Perfect. So that's it. That's it for the act method. Now we have our actions returned for each state of the batch and following a softmax strategy. And so there we go. We are ready to move on to the next step, which will be to implement the step method, which will update our A3C model's parameters in each step of the training. Let's get some good energy for this one, because it's actually going to be a long method to implement. So as soon as you're ready, join me in that next tutorial. And until then, enjoy AI. Hello my friends, and here we go. Let's implement the very important method of our agent class, the step method. Indeed, that's the method that will be called whenever the agent takes a step in the environment, and it's a method that will receive the current state, the action taken, the reward received, the next state reached, and whether the episode is done or not, and which will update, of course, the model's parameters, meaning the weight of the neural network, so that it performs over the training better and better actions that lead to a higher score. Alright, so let's do this. Let's start by defining the step method that will take, as we just said, self for the object, but of course then first the state, then the action, then the reward, then the next state, and finally done. Okay, and once again, just to simplify the notations of the code, we are reasoning at the observation level, with a single state, a single action, a single reward, a single next state, and a single done. But in fact, what this step method will really take as input is a batch of states and then the corresponding batch of actions, rewards, next states, and dones. Alright, but in order to avoid too many S's in the code, well, we're going to reason at the state level, but please keep in mind that these will actually be batches. Alright, and now here we go. Let's implement that step method. Alright, well, speaking of batches, what will be our first step here? Well, this will be to get the batch size in a variable, because of course that will be one of the parameters we will need in all the upcoming computations. So here we go. Let's define a new local variable, which we're going to call batch size. And how will we get that batch size? Well, by simply taking our state here, which remember is actually the batch of states, and using the shape attribute, which we're going to access thanks to a dot here, and then shape, and then in square brackets, you're going to enter the index 0. Because indeed, the first dimension of the state tensor represents the number of state observations in the batch. Okay? Then, second step, let me actually scroll down so that it's easier for you. By the way, I put the zoom back so that we can all better see. And so now, what according to you is the next step? Well, at this point, when we actually call the step method, well, all these, the states, actions, rewards, next states, and dones, are going to be NumPy arrays, okay? And we want them to be torch tensors. So what we're about to do now in the next 4 lines of code is to convert the state, the next state, the reward, and done into torch tensors. And then we'll take care of the action later on. All right, so here we go. Let's start with the state. And well, you know how to convert that into a torch tensor. We first call the torch library, from which we call the tensor function, which will take as input, of course, the state currently as a NumPy array. And then remember, we also have to add, just like what we did here, calling the tensor function. Well, let me remove this. Here we go. We have to specify the D type. Okay, so actually, let's be efficient because we already did it. Let's take this, let's copy this, and actually what we have to input here is, of course, exactly the same. All right, perfect. So now we're going to do the same with, well, let's do our next states now because it's going to be almost the same. Right below, let's paste that, and let's replace, of course, the state by next state, and here as well, the state by next state. Okay? Perfect. So now our states and our next states are converted into torch tensors, in their respective batch. And now let's take care of the rewards. So here we go. Let's do it efficiently again. I'm going to paste that same line of code. We're going to replace state here by reward. All right, there we go. Yes, reward, and then state here as well by reward again. All right, and then according to you, will we keep a torch.float32d type? Yes, of course, right? The reward is a float, and then we'll keep the same device, of course. So all good here with the reward. And now, finally, this is where things change a little bit. We're going to convert our NumPy array of the done booleans into a torch tensor again. So, well, let's paste that again. And here we're going to replace state by done. Okay, and then same here, state by done. Perfect. And now, what do we absolutely have to change? Well, of course, the D type, because done is not a float, it is a boolean. And so how can we get a boolean here? Well, very simply, we're going to replace torch.float32 by torch.bool. Okay, just like that. And that gives us indeed a boolean. However, now it's not over, because we will use done in the computations and everything has to be in the same type. You know, when we do operations of several elements together, well, we will still convert the done here into a float. And that's why I'm adding at the end here a dot, then 2, and then in parentheses, once again, D type equals torch float 32. So let's actually take it here. It will be more efficient. Let's copy it and let's paste that exactly inside this 2. All right, and now we're all good. We only have floats here, so we can combine everything together in order to perform the future operations that will be needed for the A3C algorithm. Perfect, so now next step, well, time to finally take care of the action values and also the state value. All right, so let's actually get those at the same time, because this is what returns exactly the forward method. So we're going to introduce new local variables here, which we're going to call action values. There we go. Then the state value. And how will we get those? Well, by calling, of course, our self.network object, which is our AI's brain, of course, which will take as input, of course, the state, which is actually a batch of states. Okay, and that's it. Next step done. And now, according to you, what do we also need to get in the same style? Well, we have the action values, we have the state value, but what do we also need for the future A3C computations we're about to implement? Well, actually, like in deep Q-learning, we also need the next state value. And so, here what we're going to do is call the network object again, but this time not on the state, but on the next state, because it will return to us the next state value. And it will also return the next action values, but we won't need them, and therefore we're going to start here with an underscore to disregard the next action values. However, we do need the next state value, and therefore I'm going to introduce a new local variable here, which I'm going to call next state underscore value. Perfect. And now, how do we get that next state value and that next action value disregarded? Well, by of course calling again our network, but this time on the next state. Perfect. So now we can move on to the next step, which is to compute the target state value by using the Bellman equation. So there we go. We're going to introduce a new variable here, which we're going to call the target state value, and which will be equal, well, we know this formula very well. It is equal to the reward plus our discount factor, or maybe you called it gamma. There it is, multiplied by, of course, our next state value we just got. Here it is, multiplied, of course, by 1 minus done. All right, the Bellman equation gets us the target state value. Perfect. And now that we have the target state value, what is the next step? Well, of course, now we're implementing the A3C model, and therefore the advantage feature comes into play. And well, that's exactly where we're about to get the advantage, because indeed the advantage is the target state value minus the state value. So here we go. Let's introduce a new local variable, which we call advantage, and which is equal to the target state value minus the state value. Perfect. So now we have the advantage. And now let's get the other parts of the A3C model, which is, of course, the critic part. And well, that's also where the critic part comes into play, because now we're about to compute the total loss that will be back propagated into the neural network. And part of that total loss is the critic loss. Okay, so we're actually about to compute two losses, the actor's loss and the critic's loss. And that's also why we just computed the advantage, because the advantage is part of the actor's loss. Alright, so here we go. Our next step now will be to first compute the actor's loss, then we'll compute the critic's loss. But in order to compute the actor's loss, we need the entropy. And in order to compute the entropy, we need the distribution of probabilities over the action values and also the log probabilities over these same action values. So that's exactly what we're about to get now. We're going to start with the probabilities, which we're going to call probs. And of course, that's the same as the policy we got here. Only here, it's better to call it probs because it will be easier for us to understand the formula. But there we go. This is exactly the same. We're going to use the softmax function from the functional module applied to our action values across the last dimension. Okay, so I'm copying this because this is exactly, again, the probabilities we need right now. And now let's do the same for the log probabilities. And well, to do so, it's super simple. We're going to take this, copy it, paste it below. We're going to replace probs here by log probs. And here, instead of using the softmax function, we're going to use the log underscore softmax function. There it is, log softmax. Great, so now we have the probability distribution over the action values and the log probability distribution over the action values. So now that we have this, we can compute the entropy. And so there we go. Let's introduce a new local variable, which we call entropy, and which will be equal to minus the sum products of these probabilities and log probabilities. And so to get this, well, we're going to call the torch library first, from which we call the sum function, and inside we're going to put that product of the probabilities by the log probabilities. All right, so that's exactly what we're going to enter here, probs multiplied by log probs. All right, so that's exactly a sum product here, log probs. And as a second argument, we just need to specify the axis dimension across which we do this sum product. And actually, this is still the last dimension. So I'm adding here axis equals -1. Perfect. So now we have the entropy. And so now we just need one final thing before we can get the actor's loss, which is actually the log probabilities of the actions that are actually selected. I'm talking about these actions here that are selected from this whole batch of states. And so how we're going to do this? Well, we're going to create an array of size, well, the batch size. And then we're going to use this array to select the log probabilities of the actions that are taken in the batch. Okay, so let's first create this array. We're going to call it batch underscore idx for index. And then to simply create this array, we're going to call numpy, which has a shortcut np. And then we're going to use the arrange function. And since the size of this array is supposed to be the same size as the batch, well, in this arrange function, we're going to enter the batch size, which is exactly why we had to get the batch size here. Okay, so batch size, perfect. And now let me actually scroll down a bit. Now that we have this array of size batch size, well, we can use it to select the log probabilities of the actions actually played in this batch here, okay? And so, well, how are we going to do this? Well, first, let's call these log probabilities of the actions log p underscore actions. And then, how we're going to get them? Well, we're going to take our log probs tensor. So I'm going to take it here, log probs. And from this tensor, we're going to access, well, the indexes of the actions that are actually taken in the batch, which are exactly given by this variable action. Okay, but of course, we're going to take all the rows in this log probs tensor in order to get all the log probabilities for each of those actions selected. And in order to get all the rows, well, we need to enter first here for the first dimension, the batch idx, which we just got before, thanks to the arrange function by numpy. So batch idx here, and then of course for the second dimension, well, it's going to be only the indexes of the actions that are selected. And so here in the second dimension, I'm entering the actions. All right, the batch of actions corresponding to all the states in the batch. All right, amazing, because now we have everything we need to compute the actor's loss, because indeed the actor's loss is going to be the negative mean of the product of the log probabilities of the actions taken and the advantages. And at the same time, we're going to encourage a bit of exploration by adding the mean of the entropy multiplied by a very small hyperparameter, which will balance the importance of the entropy. So let's write this. It will be simpler to visualize once we code it, but there we go. Let's introduce finally the actor's loss, which I'm going to call actor loss. And as we said, it is equal to the negative mean of the product of the log probabilities of the actions played and the advantages. So we're going to write this first. We take our log probabilities of the actions we just computed before. Here it is, log p actions, multiplied by the advantages. Okay, advantage. However, now we're just going to add to our advantage tensor a dot detach to prevent the gradients from flowing into the critic network during the actor's update, right? Because we won't need those gradients at this point. And then there we go. We're going to take the mean of all that. And then, as we said, we're going to add at the end an exploration feature, which will be, as we said, the mean of the entropy multiplied by a very small number, which will balance the importance of this entropy. So here we go. This very small number is going to be 0.001, which we're going to multiply by indeed the mean of the entropy. And that's it, my friend. We have the actor's loss. Okay, that's exactly the actor's loss in the A3C algorithm. And now let's get the other loss, meaning the loss of the critic in the A3C model. And that's exactly what we're going to introduce now as a new local variable, which we're calling critic loss. And so what will be that critic loss? Well, very simply, it will be the mean squared error loss between the target state value and the state value. So here we go. We know how to do this. We take first our functional module f, from which we're going to call this MSC loss function, which we know very well. There it is, between the target state value and the state value. So let's enter first the target state value for the first argument. There it is. And then the state value. There it is again. And however, we're just going to detach the target state value from the computational graph because we want to prevent again the gradients from flowing into the target computations. Alright, perfect. So now basically we get the critic loss, which is the loss between the target state value and the predicted state value. And so now, super simple, what is the next step? It is obviously to get the total loss, which is simply the sum of the actor loss and the critic loss. So there we go. Let's introduce now the total loss, which is equal to the sum of the actor loss and the critic loss. Perfect. And so now you know the next steps, right? Because since we have the total loss, well, we can back propagate it into the A3C neural network and then use our optimizer to update the weights of that neural network. But first, remember what we always have to do before back propagating this loss and using that optimizer? Well, it is to reset the optimizer. Alright, so let's do that quickly. We first take our agent, which so far is self because we haven't created the A3C agent yet. We will do that in the next step, of course. So self, then from our agent we call our optimizer, of course. And then from our optimizer, since the optimizer is actually an instance of the Atom class and the Atom class contains this zero grad method that allows to reset the optimizer by zeroing out the gradients to prevent accumulation from the previous iterations. Well, there we go. We're going to use that zero grad method to zero out the gradients. Perfect. And now you know the next step. It is, of course, the back propagation. And the back propagation of what? Of course, of the total loss. So we're going to take our total loss now, and we're going to add this simple dot and then this simple backward function, which will perform exactly that backward propagation. And then once again, you know the next step. Well, the next step is to finally update the model's parameters, meaning the neural network's weights, with our optimizer. So let's take again our agent, which so far is self because we haven't created the agent yet. Then let's take our optimizer again. And then let's take that other method of the Atom class, which is of course the step method, and which will exactly update the weights of the neural network to minimize that total loss. And now, my friends, well, it is time for me to say huge congratulations, actually double huge congrats, because let me actually zoom out now so that we can have a look at what we've just created. Because indeed, I want to say a first huge congrats for having implemented the step method, but also another huge congrats for having implemented the agent class. Indeed, we're done. We are done with the agent class. We have our 3 methods that we'll need to perform the training loop. And so there we go. Let's immediately run this cell to have this model architecture of our class so that in the next step, we can indeed initialize the A3C agent. And that's exactly what we'll do in the next tutorial. So I can't wait to meet you there. And until then, enjoy AI. Hello my friends and welcome to this new tutorial where we're gonna finally get our A3C agent for real by initializing the A3C agent, meaning by creating an instance of this class that we just made, the agent class. Alright, so after this huge tutorial implementing the step method, well, it will be time for us to breathe now because indeed this tutorial will be super short and easy, right? We just have to call the agent class in order to create our A3C agent object, which will represent the A3C agent itself, but without its brain trained. All right, but of course, in a few steps, we will be training that brain to be able to fight Kung Fu. But before, let's get our AI, and therefore let's create a new code cell. And here we go. As usual, we're going to call our agent, and it will be created as an instance of the agent class, which takes, remember, as input only one argument, which is, of course, the action size, right? If we look at our init constructor method again, indeed it takes just one argument, which is the action size, and the action size, of course, is nothing else than the number of actions variables we got here, which is indeed 14. Okay, so here we go. That's the only thing we have to do in this agent class in order to create our agent object. So let's enter our number actions parameter, and there we go, my friends. Now we have our AI. Well, actually, we have to run the cell, and there we go. Now we have our AI. Perfect. So basically, now we have some eyes, we have a brain, we have a critic sense. Well, a critic sense that will be used during the training to basically learn better how to fight Kung Fu, and that will happen in the next tutorials. And speaking of which, our next tutorial now will be to evaluate our A3C agents on a single episode, and we will do that through a function, which we'll define in that next tutorial. So as soon as you're ready, well, join me in that next tutorial to implement this function, and then we'll get soon to the training. And until then, enjoy AI. Hello my friends, and welcome to this new step of our A3C implementation. In the previous step, we finally got our agent, meaning the A3C AI for real, by creating an instance of the agent class. And now we're about to implement a new function which will evaluate our A3C agent on a certain number of episodes. Not just one episode, it will be good to have the number of episodes on which we evaluate our A3C agent as a hyperparameter. So I'm adding this into the function, and so there we go. Let's create a new code cell to define that function, which we're going to call very simply evaluate, and which will take as input 3 arguments. The first one is our agent, which will be, of course, our agent object when we call the evaluate function. Then it will be the environment. So of course, it's going to be the Kung Fu Master environment, but feel absolutely free to plug our A3C agent on another environment and see how it does, right? There are plenty of other environments that you can try, especially in the Atari section. So env, and then, of course, the third argument will be that certain number of episodes over which we want to evaluate our A3C agent. And let's call that simply n episodes, okay? And we're going to set the default value to 1, in case we don't specify that number of episodes value when we call the evaluate function. Perfect. So now colon, and here we go. Let's define what this evaluate function has to do. So good question, actually. What does it have to do exactly? What is it supposed to return? Well, it's supposed to return a list of the total rewards in each of these number of episodes, okay? Therefore, the first thing we're going to do here is introduce a new local variable, which we're going to call episodes_rewards, and which we will initialize as an empty list, okay? And it will contain the different total accumulated rewards for each of the episodes on which we evaluate our agent. Great. Now, next step. What is, according to you, the next step? Well, naturally, it's going to be to do a for loop on that certain number of episodes. And so there we go. We start with a new for loop here. And then, because we won't use the loop variable, well, we can disregard this with an underscore. And then we're going to do that for loop in the range from 0, the first episode index, up to the number of episodes. All right? So basically, it will loop over the different episodes indexes. Okay? So here we go. Now let's start this for loop. According to you, what is the first thing we need to do in this for loop? Well, right now we have to understand that we're dealing with a certain episode. Right now, the first episode of index 0. And so again, naturally, the first thing we have to do, because we're starting a new episode, is to initialize the state. And to do so, we're going to use a certain function from our environment object, which is, of course, the reset method. Okay, so let's do this. This reset method actually returns the state, which is, of course, the initialized state, but also some other elements, which we're going to disregard again with an underscore. Okay, perfect. And there we go. Now we call first our environment object, from which we call the reset method. And perfect. Now we have our initialized state. Now, next step. What, according to you, is the next step? Well, remember what we want to do. We want to get the total accumulated reward over each episode. And so now, since we're dealing with a certain episode, well, what we actually need to do is to create a new local variable that will compute that total reward. And that's exactly what we're going to do. We're going to call that new local variable of the total reward, well, total underscore reward. Okay? Which we're going to initialize, of course, as 0. Perfect. And now, again, according to you, what is the next step? Well, it is to start a new loop. But will it be a new for loop that would, for example, loop over the different time steps? Well, we have simpler actually. We can do an infinite loop thanks to a while loop, which we will break if the episode is done, because we will have that done variable thanks to our environment object, which will allow us to break that infinite while loop if the episode is done. So let's do this. Let's do this infinite while loop, which we can do very simply with a while true, then colon, and there we go. Now we start that infinite while loop. And so now what is the first thing we have to do in this new while loop? Well, right now we're dealing with a certain episode, but more specifically a certain time step. And so basically what we must think is, what is the agent supposed to do in this particular time step, this first time step? Well, of course, it is supposed to play an action, because right now it is in this certain initialized state and it needs to reach the next state, and in order to reach that next state, it needs to play the action. Alright, so let's do this. How we're gonna make our agent play that action? Well, of course, with one of its methods we implemented in the agent class, which is of course the act method. And since the act method returns the action, well, we're gonna start by introducing this new local variable, which we're gonna call action, of course, and which will be what returns that act method called from our agent. So there we go. Let's call our agent first, from which we call the act method, which takes as input, of course, the state, which right now is the initialized state, but then in the next steps of that while loop, it will be the next state and the state after that, etc. Okay, so great. Now the action is played, we reach the next state, and therefore, well, let's get that next state and also the reward that comes with that next state. So here we go. How can we get those? How can we get the next state, the reward, and also the done boolean telling us whether or not the environment is done? Well, that's of course with another function or method of the env object, which is of course the step method. All right, so let's do this. That step method actually returns the state, which is actually the next state that the agent reaches after playing that certain action. So here we go. That's the next state. Then we also get the reward, and then we get whether the environment is done or not. But then that's not over. We also get some info, some extra info, which we won't use, but let's put that in the info local variable. And then some other elements, which we can disregard with an underscore again. Perfect. And now, time to call this step method from our environment object. So there we go. We call first our environment object, from which we call that step method. The step method, which will take as input, what exactly? Well, that action that was just played by our agent. All right, but more specifically, we will have to take a certain index of that action, because action is actually a numpy array here. And assuming that we're evaluating the agent in a non-batch mode, well, we need to add this index 0, which I'm putting in a square brackets. Perfect. So now we get that next state, we get the reward, we get whether or not the episode is done. And so what is the next step? Remember what we have to do here to compute the accumulated reward. Well, since we have the reward, we can exactly do that. We can update our total reward variable by adding to it the reward we just got in this new step of the environment. So there we go. Let's do it efficiently. Let's call our total reward variable, and then let's do the classic plus equals to add the reward we just got here. Reward, great. And so now, what do you think we have to do? Let me actually scroll down a little bit. We got our total reward, we got what we wanted, so what do we need to do in order to exit that infinite while loop when we have to? Well, with a break, of course, which we can act on thanks to our done boolean. And so what we're going to do now is a simple if done to check if we're done with the episode, in which case we will, of course, break that infinite while loop. And if not, if we're not done with the episode, well, we will go back to that while loop and start a new time step, playing a new action, then reaching a new state, getting a new reward, adding that new reward to the total reward, and we do that again until the episode is done. And once the episode is done, what do? Well, we need, of course, to exit that while loop and go back into the for loop because we're done with the episode, but however, we still need to append that total reward we got here into our episode rewards list of total rewards on this certain number of episodes. Okay, and that's exactly the last thing we have to do here. We need to take our episode rewards list. So I'm copying it here, and then still inside the for loop, let's be very careful with that. We're going to paste it, and then of course we're going to use the append function to add that total reward variable. And perfect. Now finally we have the different total accumulated rewards for each of these episodes on which we're evaluating our A3C agent. Perfect. And so now, what is according to you the very final step we have to do? So first we have to exit that for loop. We're done with that for loop. Well, remember what this evaluate function is supposed to do? Well, it is supposed to return that list of different accumulated rewards on these certain number of episodes. And therefore, we're going to finish this evaluate function with a simple return, which will return, of course, I think I still have it copied, the episode, there we go, rewards variable. And perfect, we're done with this evaluate function, so let's run the cell, and there we go, my friends, we're now ready to finally implement that last feature of the A3C model. I'm talking, of course, about the asynchronous feature. Indeed, in the next tutorial, we will be testing multiple agents on multiple environments at the same time. And so please get some good energy for that. It will not be super short or super simple, if you know what I mean. So get some good energy, get a good nap or a good coffee, and as soon as you're ready, well, let's smash this in the next tutorial. And until then, enjoy AI. Hello my friends, and welcome to this very exciting new step of the A3C implementation. It's a very exciting step because indeed you know that by now we have implemented the advantage in the A3C asynchronous advantage actor critic model. We also implemented the critic part, thanks to that critic loss that is part of the total loss that is back propagated into the neural network in order to update the weight. And finally, what is left for us to do? Well, to implement the asynchronous part. So let me quickly remind what the asynchronous is about. You know that in the previous models that we implemented deep Q-learning or deep convolutional Q-learning, well, we had a single agent interacting in a single environment, and now we're about to kind of upgrade that because we're about to make a class that will allow to have multiple environments simultaneously so that multiple agents can interact with multiple environments, as opposed to before where a single agent was interacting with a single environment. Alright, so that's exactly what we're about to implement now in this new code section. So let's create a new code cell, and in fact we'll implement that in the form of a class, okay, which we're going to call env_batch, which is a class that will allow us to handle multiple environments simultaneously in the context of, parallelized reinforcement learning, which is exactly what the A3C algorithm is about. And so, thanks to this env_batch class, well, we will be able to handle simultaneously multiple environments by, for example, facilitating the simultaneous stepping and resetting of multiple environments so that we can use that asynchronous feature of the A3C algorithm much more easily. Alright, so here we go. First, of course, we're going to start with the init method, which will take as input two arguments. First, self for the object, the future batch of environments object that we will create from this env_batch class. And then, as a parameter here, we're just going to enter how many multiple environments we want to manage simultaneously. And so, we're going to add another argument here, which will be exactly this number, and which we'll call n_onvs. Okay, and we will give it a default value of 10 so that when we create an instance of the env_batch class, well, by default, we will create and manage 10 environments simultaneously. Perfect, now colon, and here we go. So actually, for this init method, we only have to define one object variable, which will be, of course, our environments, right? Which we'll put in a list, and therefore, this one and only object variable will be the list of these multiple environments. So here we go, let's call it self.onvs. Alright, these are going to be our multiple environments in the list. And well, speaking of the list, we start here with square brackets. And then, according to you, how can we create multiple environments in one shot? Well, remember with the makeOnv function, the exact same function that we used before to create our environment. If I scroll back up, here it is. That's the makeOnv function. And we call here the makeOnv function to create our Kung Fu Master Deterministic V0 environment. And now we're going to do exactly the same to create our other multiple environments. We're going to use the makeOnv function through a for loop within a list so that we can do that in one shot. Okay, so how we're going to do that? Well, let's first call the makeOnv function. And then very simply, we're going to add this for loop here with a loop variable which we can disregard with an underscore because we won't use it explicitly in that for loop. Because indeed, we're just going to say in the range from, of course, 0 to the number of environments, which by default is equal to 10. But if, for example, it is 5, well, it will go from 0 to 4. Okay? So there we go. That's the init method. That's the only object variable we have to define. And so now let's create the next method, which will be the reset method, which will allow us to reset these multiple environments at the same time in order to allow this multiple management of environments. So here we go. Let's call this method reset, which will take as input only one argument, which will be the object itself. So self, and then colon, and here we go. So now, according to you, how can we reset all our self-on's multiple environments at the same time? Well, probably by creating a new list of these initialized states that we can get from our self-on's object containing the different environments. Okay, so that's exactly what we'll do. We're going to create a new variable which we're going to call underscore state, which we will initialize as an empty list with a pair of square brackets. Okay, and now how to populate that list, how to create that list of reset or initialized states for each of the environments in self.onths. Well, naturally with a for loop, right? Which will loop over the different environments in this self.onths list of multiple environments. Okay, so here we go. Let's do this. Let's start with for. And here, of course, we will need a loop variable, which will be, of course, the environment among these multiple environments. So let's call this loop variable onth. And of course, each of these environments will be in the self.onths object variable, which we have here and which contains the multiple environments. So here we go, self-onths, colon. And now, according to you, what do we do inside this for loop? It only takes one line of code. And that is, of course, to append in that list of initialized states the different reset states in each of these environments in self.onths. Okay, so we're going to take first our list states, from which we're going to call the append function. And inside this append function, what do we have to do? How can we get the initialized state in each of these environments in self.onths, the object variable containing the multiple environments? Well, you know this method. It is, of course, the reset method. And so we're going to take our environment first, onth, from which we're going to call this reset method indeed. Here it is, we add some parentheses, and then remember that this reset method actually returns more than the state. If we look again, for example, in our evaluate function, well, as you see, we call the reset method here from our environment, which indeed returns first the state and then some other elements which we disregarded here. But therefore, here, in order to really get the state, which is what we want, right? We want the initialized state. Well, we have to add in square brackets the index 0, because that will return the state and the state only, not the other elements. All right? Perfect. And now finally, let's exit that for loop. We're done with it. We have our initialized states for each of these multiple environments in self.onths, but we actually want to return this list of initialized states, but in the form of a numpy array, and therefore we're going to finish this reset method with a return, and then we're going to call the numpy library first, from which we're going to call the array function, which will take as input that states list we just created thanks to that for loop. And there you go, my friends. We are now done with the first two methods of this onth batch class. We still have a third one to implement, but we'll do that in the next tutorial because it is a bit longer. So let's recharge a bit in energy, and once you're ready, well, join me in that next tutorial to finish that nth batch class with this final method, which will be the step method, allowing to step indeed in multiple environments simultaneously. So I'll see you in that next tutorial, and until then, enjoy AI. Hello my friends, and welcome back to the implementation of the nth batch class, which is a class that allows us to manage multiple environments simultaneously. In the previous tutorial we defined the init method that creates indeed the object variable being the multiple environments, and we also implemented the reset method that allows to reset these multiple environments at the same time. Alright, and now what we're about to do is exactly the same principle as resetting multiple environments, but this time stepping multiple environments. And therefore, we're about to make the third and final method of this mbatch class that will allow to step in multiple environments simultaneously. Alright, so here we go. Let's create that new method here, which we're going to call, of course, step. Alright, we know very well the step method, but so far we only used it in a single environment, and now we're about to make one to step in multiple environments. Alright, so first, according to you, what is this step method going to take as input? Well, first self for the object, of course, which are our multiple environments, but then what? Well, remember, when we call the step method from an agent in a single environment, well, we take as input the action, because we perform that step by playing an action. And well, here it's exactly the same. We're about to implement the step method for multiple environments, and therefore it's going to take as input the multiple actions played by the AI, by the different agents interacting with these multiple environments. Alright, great. So now colon, and here we go. Let's define what this step method has to do. Alright, so basically what we want to do now is for multiple agents to step in these multiple environments after playing these multiple actions. And therefore what we have to do is to make some kind of a similar for loop as the one we made here, but instead of calling the makeOn function, we're going to call the step function from our different instances in this self.on's multiple environments. Alright, and now remember, since the step method called from the environment actually returns, that tuple of elements, the next states, the rewards, dons, infos, and some additional information, well, we're going to start with this. We're going to start with what this step method called from multiple environments will return. And so, as I just said, it's first going to be the next states, then it's going to be the rewards, then it's going to be the dons, then it's going to be the infos, and then some additional information, which we're going to disregard here. Alright, we could even disregard this, but in case we want to use this in the future, let's keep this in that variable. Alright, and then now time to call the step method, but so far we only have the single step method, meaning the method that allows to step in a single environment. And so how can we transform this into a multiple stepping method? Well, of course, with that for loop within a list. It's not going to be the exact same range, but I'll give you a hint if you want to implement this first. Something more similar to this. Okay, well actually let's take this, because that's exactly going to be that for loop within a list. We're going to loop over the different environments in our self.on's multiple environments object. And so let's take this, let's paste that within a list, okay, and now let's implement what we have to do for each of our environments in this list of multiple environments object. Alright, so as we said, what we want to do is call the step method, as we all know, that allows to step in a single environment. Because we have the single environment separately, it is this, this env loop variable. That's a single environment, so we can call the step method on this single environment as we're used to do. Okay, so let's do this. Let's first call our environment, from which we call this indeed step method. But now, what does this step method here actually take as input? Well, remember, it takes the action as input. And where is the action? That specific action for this specific environment in that list of multiple environments. Well, it is one of the actions that we have in this actions input. But this contains all the actions. What we need is the single action that is being played in this single environment within that for loop. And so how can we get that specific action? Well, it's going to be with the double loop variable. So what we're going to do in the step method is enter a new loop variable, which we're going to call A. And here, we're going to add that other loop variable A for the action, of course, in these actions. And therefore, here, we're not going to loop only in our self.on's multiple environments object, but also in the different actions that we have here. And how can we do that? Well, that's with a zip function, which will take as input not only the self.on's multiple environments, but also the actions. You see, that's the double loop. Pretty nice, no? So now it's not done, almost done, but we just have to do something more, which is just a matter of format, because actually we want all of these to be returned as NumPy arrays. So the first thing we're going to do is do another zip here to transpose this list of tuples, and that's just in order to arrange the formatting in order to create that NumPy array we want to get, and I need to add a star here to do that transposition. Okay, so basically with this, we now have these elements of all the tuples here grouped together. The next states are grouped together, the rewards are grouped together, the dons are grouped together. And now the final thing that we have to do here is to convert all these grouped elements into NumPy arrays. A NumPy array of the next states, a NumPy array of the rewards, a NumPy array of the dons, and then infos, which are actually dictionaries. And to do this, since we have the zip function called first, to create and transpose with a star these groups of different elements here, we can't directly use NumPy array function, but what we can use is the map function called on the np.array and with this zip of grouped elements. Okay, so let's call this map function, which will take, as we just said, as input first np.array and then exactly that zip element containing the grouped element of the next state, rewards, dons, and infos. Alright, so since I just added this map function, I just need to close the parenthesis here. And there we go. Now we're done getting our group of next states, rewards, dones, infos all converted into NumPy arrays. All right, perfect. So that was the hardest part. And now I know it's very tempting to return those next states, rewards, dones, and infos because, besides stepping in these multiple environments, we also want to return these different elements. But before, we have to check something. Can you guess what we have to check? Well, we have to check if any of these multiple environments has finished. If for any of these multiple environments, the done boolean is equal to true. Because if that's the case, then we will have to reset that particular environment that has finished. And so we just need to do this final for loop before returning those elements. And so here we go. We're going to do a for. Then because we're going to need this time the loop variable, well, we're going to call it I. And then we're going to loop in the range of course, our environments. But here, actually, it's going to be the index. We have to loop from 0 to the number of environments, which we have here, but unfortunately, it's just an argument of the init method. And therefore, in order to get that number of environments, we need to call our object and call the len function on that object. So I'm going to take our object here, self.arms, the multiple environments, then call the len function, which is going to take as input, of course, self.arms. All right. And that's exactly this, and arms. Okay, perfect. So we have our loop. Now let's start it. And so what do we have to do? Let me just scroll down a little bit. So as I said, what we have to check is if any of our multiple environments is done. And well, since we're now looping through the different environments, well, we're going to check that for each of these multiple environments. And so here we go. I here corresponds to a certain environment of our multiple environments. And so what we can simply do is do an if condition like this. If checking if, well, the done booleans of our specific environment I we're dealing with right now in the loop is done, right? So basically this means if done's I, meaning if the done boolean of our environment of index I is equal to true. And so if that's the case, we add some colon. And what do we do if that's the case? Well, as we said, we're going to reset the state of that environment, which is actually given by next state of index I here. So I'm going to take next states here, but of course the one of index I, so I'm going to enter in square brackets I, there we go. So now we have the next state of our particular environment of index I we're dealing with right now in the for loop. And so now, how do we reset it? Well, first by updating it. And how can we do that? Well, very simply by calling the reset function from this particular environment of index I, which we can access thanks to our self.arms object, because self.arms contains the multiple environments, and therefore in order to get that particular environment of index I we're dealing with right now in the for loop, well, we simply need to add here in square brackets the index I. And that's our particular environment we're dealing with right now. Okay, perfect. And so now from this particular environment, we're going to call, of course, the reset function, which doesn't take anything as input, but of course, remember that it actually returns several elements, the state and some additional information, and therefore in order to get the state, we need to add in square brackets here the index 0, and that gives us the next state, which is reset. Perfect. And so now we can do the final very easy step, which is the final return, but we have to do it, of course, outside of this for loop. So we exit that for loop first, and then we call the return final element of that step method, which will return, let's do that efficiently, of course, the next states, the rewards, the dones, and the infos in case we need them. All right, so let's return this, and there we go, my friends. We are now done with the env batch class. So congratulations. We can now move on to the very exciting final step of the training, which is of course the training loop. But of course, let me not forget to run this cell to create our env batch class, which will allow to perform the asynchronous part of the A3C model. Now we have it, and so now we can start the final training loop. And until then, enjoy AI. Hello my friends, and here we are about to start the training implementation, the training of our A3C agent, which we can do indeed because we now have all the tools to perform that training. Alright, so here we go, let's smash this. So we're going to create a new code cell which will implement that whole training loop. We will do that in 2 tutorials because it's quite big, and in this first tutorial we will just import the TQDM module, which is very nice. You will see it will be used to display a progress bar for loops. So that's going to be a first, compared to what we did before. Then we're also going to, initialize the different objects, starting with, of course, our batch of environments. Now that we, implemented the env batch class in the previous tutorials where, of course, we're going to create an instance of that env batch class, which will be nothing else than the 10 environments, because we will call it with 10 here. So we will create 10 multiple environments so that we can have 10 agents being trained in 10 different environments. And you will see that it will considerably improve the training performance. Not only the training will be much faster, but also we will reach high performance very fast. So let's do this. Let's create immediately that instance of the env batch class, which will actually be 10 environment instances of Kung Fu Master. And so here we go. Let's call our object env batch, which will be created, of course, as an instance of the env batch class that we just implemented, and which takes as input, of course, the number of environments. And so, do you remember that variable we created for that? Be careful, it's not env, that's just the name of the argument. The variable we created for that was when we initialized the different hyperparameters a bit above. Here it is. Remember that third variable here, number of environments, which we initialized to 10, and that's exactly the number of multiple environments that will be running in parallel to train our multiple A3C agents. So let's take that variable, I'm going to copy it, I'm going to scroll back down to our training loop, there it is, and inside that env batch class, I'm going to enter number of environments. Perfect, and then what do we have to do before we start eventually that training loop? Well, it is to reset our batch of states, because now that we created our env batch instance of the env batch class, well, that means that we have our multiple environments, and therefore that means that we also have our batch of states, in each of these multiple environments, and therefore what we must do now is reset all the states in these multiple environments. And how are we going to do that? Well, by using, of course, one of the tools we implemented before in that env batch class, and the tool is, of course, the reset method called from our instance of the env batch class. So there we go. Let's do this now to reset basically all the states of our multiple environments. And so we're going to introduce that new variable, which will be called batch states, and which will be, of course, the batch of states in these multiple environments. And so there we go. How do we initialize them? Reset these states by calling, of course, first our env batch object, the instance of the env batch class, from which we call, of course, there it is, reset method, which takes nothing as input. Alright? Perfect. And so now we're ready to start eventually that training loop, but we'll do that in the next tutorial because it will be quite big. So make sure to have the maximum energy for it, because we will also run that training and observe and enjoy, hopefully, the results. So let's just get a good coffee or a good tea or a good nap. And as soon as you're recharged in great energy, well, join me in that next tutorial to smash that training loop. And until then, enjoy AI. Hello my friends, and here we go with the final training for loop of our A3C model. And I have to say something, it is actually the last practical tutorial where we will be coding something together, because indeed after that we will be ready to visualize the final results. Not only we will run the training, but also we will visualize the final results. And since this is the exact same cell as in the previous implementations, well, indeed, we have nothing more to implement. So let's enjoy this final tutorial implementing that final training for loop for our A3C algorithm implemented for Kung Fu. Here we go. Let's get started. And to finish in beauty, we're actually going to implement something super cool that we haven't done before, which is the progress bar. So when we run the training, you will see a growing progress bar as we progress in the training. And we're going to get that thanks to the TQDM module, but more specifically from the tRange function by the TQDM module. So there we go. We're going to start with indeed the TQDM module, from which we call that tRange function, which will contain the exact same range as the range in our training for loop, meaning the range of iterations over which we will be training our A3C agents. And so that range is actually going to be from 0 up to 3000 iterations, and therefore I'm going to enter here 3001, because the upper bound of a range in Python is excluded, and it's important that we go up to 3000 included, because we're going to print the average score over 10 episodes every 1000 iterations, so we need to include 3000, okay? So that's the range of iterations of our training, and then we're simply going to add this shortcut name that we're going to choose to be progress bar, so that when we do the for loop, well, we can do directly the for loop in the progress bar. All right, so let's add some colon here, and here we go. Let's start that for loop. All right, so as we just said, we simply need to do that for loop in the progress bar, and therefore the loop variable here is going to be I for iteration, the different training iterations going from 0 to 3000, and so for I in not a range but directly the progress bar. All right, and that's exactly the same as if we did for I in the range from 0 to 3001. Okay, so colon, and now here we go. Let's implement the for loop. And so now basically it's very simple. We just have to put ourselves in the shoes of our agent. And so let's do that. What would we do as the agent right now in this first iteration of this core training loop? Well, right now we are in a certain state. We are in this batch of states, which was reset, initialized thanks to the reset method called from our env batch object of multiple environments. Because indeed, remember that we are now not only one agent, but several agents interacting with multiple environments. And therefore, in fact, we have to put ourselves in the different shoes of these multiple agents. But what do these multiple agents have to do in each of these initialized states? Well, of course, it is to play an action, right, for each of them. And how can we do that all at the same time? For all these agents interacting in all these multiple environments. Well, by simply calling the act method from our agent object, that same object that was created as an instance of the agent class, but called on the batch of states. And so there we go. That's exactly what we're going to do. We're going to introduce a new local variable for our batch of actions that are being played. And then there we go. We call our agent object from which we call that act method, which we implemented in the agent class, which indeed takes as input a batch of states, which are the initialized states in all the multiple environments in our env batch object. Okay, so here we go. Let's take our batch of states because that's exactly what we're gonna input in our act method. All right, perfect. So now basically we play the actions in that batch of states. And so now what is the natural next step? Well, after playing the action, we reach a next state and we get a reward, and we know whether the episode is done or not. And so we're now going to get all these elements with a new local variables, which we're going to get thanks to the step method called, of course, from our env batch object. So here we go. Let's get first the batch of next states, then the batch of rewards, then the batch of dons, and then the additional information, which we're going to disregard with an underscore. All right, and so all this is going to be what exactly? It's going to be the output of the step method. But which step method? Well, of course, the step method that was just implemented in this env batch class, because now, indeed, we have just played a batch of actions from our multiple agents interacting with multiple environments, and therefore we need that multi-environment step method that allows for our agent to step in the multiple environments they interact with. And that's exactly this one, and therefore that's exactly what we're going to use now to get our batch of next states, batch of rewards, batch of done. So here we go. What do we need to call first? Well, that's of course our env batch object. All right, the multiple environments basically from which we're going to call indeed that step method. And that step method, let's have a look at it again. What does it take as input? It takes, of course, the actions, meaning the batch of actions that are played, that are selected from the multiple agents in the multiple environments simultaneously. All right, so back in the training for loop, let's enter, of course, here in the step method, our batch of actions. Perfect. So now we can move on to the next step. And what is the next step? Again, let's put ourselves in the shoes of our agents. Well, remember that we have to be trained to be more artificially intelligent at, well, fighting Kung Fu. So maybe it is the time to do the most important step of the training, which is, of course, calling the step method, but not from our env batch object, but of course from our agent, because that step method of our agent class is exactly the method that performs the step of the training, meaning that will compute the actor's loss that includes the advantage, but also the critic's loss, and then combine these two losses together to get the total loss, and then back propagating that total loss into the neural network with the Atom optimizer that will update the model's parameters, meaning the weights of the neural networks, in order to reduce that total loss and therefore returning at the next iterations better actions that lead to higher scores. And so that's exactly what we're going to do. But first, we're just going to do a little RL trick, a common practice used in reinforcement learning to stabilize the training. Because indeed, now we're dealing with actually high rewards, coming from the Kung Fu Master environment. And we need to reduce the magnitude of these rewards in order to stabilize the training. And to do so, we're just going to use a very simple trick. We're going to take our batch of rewards and we're gonna multiply this by 0.01, and that will reduce the magnitude of our batch of rewards, which are quite high, and that will stabilize the training. And we still need to optimize these same reduced rewards anyway, so that will not affect negatively the training. It will actually stabilize it and improve it eventually. All right, so that's the simple thing we had to do before that most important step of the training. And so now let's do it. Let's call the step method from our agent class in order to perform that model parameters update thanks to the Atom Optimizer. And to do so, what do we have to do? Well, of course, we have to take our agent from which we have to call here it is, it's the last one here, step method. And the step method takes what as input? Let's have a look at it again to get a little refresher. Here is the step method from our agent class, and as we can see, it takes the state, the action, the reward, the next state, and done as input. But remember, be careful, these are actually the batches. Here we kept these notations to just simplify the formulas here and to make it more readable. But of course, these are the batch of states, actions, rewards, next states, and done. So that's exactly what we're gonna input back in the step method of our agent object, and we have to input them, of course, in the same order. So we have to start with the batch of states, then the batch of actions, then the batch of rewards, then the batch of, there it is, number 4 here, batch of next states, and then finally the batch of dones. Perfect, and that performs the step of the training, updating the model's parameters. Excellent, and now what is the next step? A very important one that we must not forget. Remember that here we started from the initialized batch states, right, which were initialized here. So the agent plays its action from the batch of states, but then afterwards we reached the next state. And so at the next training iteration, well, if we don't update this batch of states, well, we will still be in that initialized batch of states. So we need to update that batch of states to be equal to what, of course? Well, the batch of next states, right? So that's exactly what we have to do now in order to move correctly to the next training iteration. And so there we go. We take our batch of states and we update it to be the batch of next states. Here we go. All right, so now at the next iteration, when the agent plays its action, it will be from the right next states. Perfect. And so now, while the training for loop is completed, we have implemented everything that needs to happen in each training iteration. And so now we can do the final print to print the average reward over a certain number of episodes. I hope that rings a bell. So let's do it. But first, we're not going to print that average reward at every training iteration. We're going to do that every 1000 iterations. Okay? So that actually we will see the progress bar growing 3 times. You will see it will be pretty nice. So let's do that if condition to check when we are at 1000 more iterations. And to do so, well, we're simply going to do a I modulo 1000, which I remind is the rest of the Euclidean division of I by 1000. And so if this is equal to 0, well then what? Well then that means that indeed we are at every 1000 iterations, and therefore we're going to print the average score. And so here we're going to do a simple print. We'll already have some nice dynamic print thanks to the progress bar. So there we go. Let's enter in double quotes the average agent reward, then some colon and a space. And then outside of the quote, we're going to add a comma, and then after the comma, the variable, which will give us indeed that average agent reward. And so what is that variable? Well, we don't have it directly. We need to use a last tool we implemented before to get that average agent reward. I'm sure you see which one it is. I'm talking, of course, about the evaluate function we implemented here, because indeed this function evaluate here allows us to evaluate, meaning return the accumulated reward over a certain number of episodes. And well, that's exactly what we need now. We need to compute the accumulated rewards over a certain number of episodes, and then what we can do is get the mean of those accumulated rewards over these episodes. And so that's exactly what we're going to do here. Back in the training loop here, for what will be printed, we're going to call our NumPy library first to get the mean function, because indeed we're going to take the mean of the output of the evaluate function over, well, let's say 10 episodes, right? This will make sense. Every 1,000 iterations, we will compute the average of the accumulated rewards of our agent over 10 episodes, okay? If you want, you can choose 5 or even 3, but I think 10 is good. So let's take our evaluate function, which remember takes 3 arguments. First, indeed, our agent, which is our agent object created as an instance of our agent class. So our agent first, then it takes the environment, the Kung Fu Master environment, of course, created from the makeOn function, and then finally, the very important number of episodes over which we want to evaluate our agent in this environment. And well, as we said, we want to choose a number of episodes equal to 10, okay? This will give us a relevant evaluation of how the agent is doing. All right, so now guess what? Well, my friends, I have to say not huge congrats, but massive congrats, because we have just implemented the very last line of code of this course. Indeed, we're completely done with any line of code we implement over all the artificial intelligences we built in this course, because indeed now we are completely done with our training loop. So huge congrats, well, massive congrats for not only implementing fully the A3C model, but also for having reached the end of the practical sections with indeed a very powerful and advanced AI model. Okay, so now, without further ado, we're gonna run the training, but first let me say that the A3C model is actually much more powerful and much less compute intensive than the previous models, so we don't have to get Colab Pro or get a GPU. We can totally do this with the CPU. Actually, right now I am with the CPU, so that's totally fine. You will see that the training will be very fast, and plus we only chose 3,000 iterations to train our model, and you will see that this will be way enough. Okay, so are you ready, my friends? Now it's time to get a good coffee or a good tea or a good OJ, sit comfortably in our chair, and there we go. Let's run the training of our A3C agent. And it is starting, and very soon we will see the progress bar starting. It will start at 0, of course, and then we will see it grow 3 times. First to reach 33%, then to reach 66%, and then finally 100%. And for each of these 33, 66, and 100, we will see the average reward computed over 10 episodes. All right, so it's going to start soon. Actually, you know what is happening right now since we did this, and right now I is equal to 0. Well, 0 divided by the rest of the Euclidean division is 0. So actually it computed the first average agent reward of 440. And now there we go. We are, growing the progress bar from 0% to 33%, because indeed we are now going from iteration 0 to iteration 1000, right? Because 33% of 3000 is 1000. All right. And so now it's growing. The agents are being trained in the multiple environments running in parallel. And at the end of this first, training window, let's say from 0 to 1000, well, we will get, there we go. Now the average agent reward is being computed over 10 episodes, but after 1000 iterations of training, well, actually 998. And in a second, we're about to get the average agent reward over 10 episodes after indeed 1000 iterations of the training. So actually, it takes a little bit of time to, compute that average reward over 10 episodes, because we actually have to run these 10 episodes. So now the 10 episodes are running, the accumulated rewards are being collected, and then the average will be computed. And there we go, we get an amazing average agent reward of 980. That's super amazing, because indeed, already 500 was a good threshold of what's good enough in this environment, just like in Pac-Man. But now I'm actually very impressed to already observe 980. And that's thanks to the, multiple environments running in parallel and training our agents. This is absolutely powerful. And now we're almost at 67%. There we go, reaching 2000 training iterations. And now the 10 episodes are running and the accumulated rewards are being computed. And then the average of these accumulated rewards over these 10 episodes will be computed to be returned in a few seconds. So now this is exactly what is happening. We're about to get the average agent reward over 10 episodes, but after 1998 training iterations. All right. So now it is being computed, and in a second, in a few seconds, we'll get the average agent reward over 10 episodes after 2,000 iterations of the training. All right, it's coming in a few seconds. It's being computed now. The agent is running on 10 episodes and then accumulating the rewards, and then the average reward is being computed. And in a second, it will be printed here. And there we go, 1,040. That's amazing. Another very great score. The average reward is increasing. That's absolutely amazing. And now finally, we are reaching the last stage. We are in the last stage of the training, from the 2,000 iterations to the last 3,000, and 90% already reached, and we will get finally the average agent reward thanks to the 3,001. It was important to keep 3,001, otherwise we wouldn't get the final average agent reward being computed over the last 10 episodes that are run to evaluate our AI. And so let's hope that we will get more than 1,000. That would be amazing, so that we can really finish this course with a good note. That would be indeed really amazing. So now remember, the 10 episodes are running. The agent is running on 10 episodes now, and then the accumulated rewards are being computed, and then we will take the average of those accumulated rewards, but this time it's actually after 3,000 iterations of the training. All right, so we're about to get the average agent reward over these 10 episodes after 3,000 training iterations. What will it be this time? Will it be higher than 1,000? And no, it is actually 940, but that's really, really good. We reached some amazing rewards here, and as you can see, it was pretty fast. So now I'm just too excited to see the final results in the video. So if you don't mind, well, actually, I would like to already execute the cell in part 3, visualizing the results, because this is actually the exact same code cell as the one we used before for our deep Q-learning and deep convolutional Q-learning models. As you can see, with the show video of model function first, and then the show video function, and then we call the show video, and we get the video of course, our new environment being Kung Fu Master. So, are you ready to do this? Let's do this now, right? Let's run the cell and let's enjoy the very final video of our AI fighting Kung Fu after indeed a very good training. All right, that's the video and it is starting. Okay, so that's number of lives and that's the score. Right now it is punching some people. It just lost 1 life, but reaching a score of 200, 400. Now punching some more people, 800, 1,000. Really, really good. 1,000 and only 1 life left. Be careful. Oh, 1,200. Punching, dodging some bullet. Very good. Jump up, fight, Kung Fu. Okay. It has more life. Okay, 1,300. 1,300. And punching more. 1,300, 1,500. Who says better? And done. Alright, so that was pretty cool, no? That was our AI fighting Kung Fu. Maybe not as good as Neo, but I'm satisfied with the result because indeed we had a very nice training before the fight, right? Remember, we reached that final score of 1,040. So that was really, really good. And that's how we could get that final reward of that single game, on that single episode of 1,000. How much did we get again? 1,600, no, or 500? 1,500. So that's really good. Massive congrats again. Now we're going to do that final ChatGPT tutorial to see if it has some recommendations for our AI or if it suggests another architecture or maybe some other tools or features or tricks to improve the model. And also I'd like to say that if you manage to tune the model or figure out some ways to improve the final score, well, please share that in the comments. I'll be actually super happy to even record a new tutorial to show the improvement. All right? So I'll see you in that next tutorial with ChatGPT, and until then, enjoy AI.
Welcome to this quick introduction to large language models. We will discuss quite a few important topics and get to know how large language models work in a bit more detail. In this video, we're going to talk about the ingredients of a large language model. So let's have a look. So a large language model consists of the following ingredients. First of all, you need lots and lots of data. It includes data from crawling the internet with specialized algorithms called crawlers that collect all this data, and it's tons and tons of different web pages and lots of data, as much as they can gather from all of the internet. It includes things like all of Wikipedia, lots of different books and the text that's contained within them, and lots more data. So we're talking huge amounts of data. Plus, you need a transformer architecture. We'll talk a bit more about this further down, but that's an integral component of a large language model. Then you need to perform pre-training, and that is when you take the model architecture and you train it on the data that you've collected, and you're specifically training it to predict the next word. You're giving it lots of different sentences, and you're asking it to predict what the next word is, and then you're checking if it predicted it correctly, and you're adjusting, you're helping it learn further and further to get better at predicting the next word. So that is done on GPUs, and you need lots of them to do this in parallel, so it's faster. You need lots of money. We're talking about tens and hundreds of millions of dollars to train your large language model, and also it takes lots of time. We're talking about weeks and even months of training required. And then once it's pre-trained, you can apply things like reinforcement learning from human feedback to help it better understand what responses humans actually expect it to give. So basically, humans will be sitting there and actually checking the responses that it's giving and showing sample responses that it should be giving. And then finally, you can also fine-tune it on domain-specific data for your specific business use case. And this is the part that's most interesting to businesses, whether you have medical data, financial data, film data, legal data, or even you have an internal knowledge base where your employees normally go to get answers from about how they should do certain things in your company. You could fine-tune a large language model on any one of those data sets for whether it's your employees or your customers to get better answers without having to look them up themselves, but just getting them through the large language model. So there we go. Those are the ingredients of a large language model, and I'm excited for us to go through some of these things together and get a better feel for LLMs. In this quick tutorial, we will find out who invented large language models. So it all started when this team of 8 researchers at Google published the paper titled "Attention is All You Need" in 2017. This is when they introduced the transformer AI model architecture for the first time. It's a groundbreaking paper and it has been cited over 100,000 times, which is a lot of citations for a research paper. Now, the transformer architecture looks like this. We won't go into detail. It's a very technical topic, but just keep in mind that it has 2 parts. It's got an encoder and a decoder, and it was originally designed for translation tasks, so machine translation from one language to another. Now, later on, some researchers at OpenAI figured out that if you take this part, which is the encoder, and you throw it out, you'll be left with a decoder-only model architecture. And this architecture is very good at language generation. And this is exactly the architecture that is used in the most powerful large language models such as ChatGPT, Llama, and Claude. So there we go. That's how large language models were created, and a great piece of technical trivia for you to impress your colleagues at work is that large language models are a decoder-only version of the transformer architecture. In this tutorial, we will find out how large language models generate text. All right, so here we've got a large language model, and we're going to input a prompt. What is the tallest mountain? Now, all of this text will go into the input of the large language model. It will do its mathematical operations, and as the output, it will produce just one most likely next word. How does a large language model know the most likely next word? Well, it's seen lots and lots of text on the internet, text from lots and lots of books, text from Wikipedia, and so on and so on. And so it's seen lots of different scenarios of how words follow each other. And even though it doesn't know this exact sentence off by heart, it does know how to predict what is likely to come next based on everything that it's seen. And the most likely next word in this case is the word "the." Just keep in mind, the most important thing here is that it only generates just one word. Next, it takes all of the input we gave it as a prompt, plus whatever is created so far, which is the word the, and all of that goes into the input of the large language model. And as the output, it again produces the most likely next word for this new sequence, including the new word it had generated. Now, we've got the word tallest. And again, it's only produced one word this time. Again, it'll take everything that we have so far, plus the new words, the tallest, and all of that will go as an input. The mathematics will be carried out, and as the output, it will produce the most likely next word, which in this case is mountain. And it will keep doing that, taking everything we have as input and producing just one word at a time, until it gets to a point where instead of producing the most likely next word, it produces what is called the end of sequence token. And it produces it the same way. It is predicting that most likely this is the part where, this is the point in time where the sequence should end. So this is a prediction telling itself that it should stop generating text. And this end of sequence token, we don't see it. We won't be shown the end of sequence token. It's in the background. It's just a signal to the large language model that based on its predictions, it should stop generating now. And that's when it'll stop. And that's where we will get this output to our prompt. What is the tallest mountain? The output will be the tallest mountain is Mount Everest. So the key takeaway here is that large language models by design are intended to predict just the next most likely word in the input sequence. And then they take everything we've input plus whatever they've outputted so far, and it goes back in and it predicts the next word. So it's a very iterative process until you get to the end of sequence token. And that's how large language models generate text. In this tutorial, we will have a look inside a large language model under the hood. Please keep in mind that this is a more advanced tutorial. It's got some technical topics, so feel free to skip it if you prefer. Now, inside a large language model, we've got our decoder-only architecture, and we're going to go through the modules one by one from bottom to top. We won't go into mathematical detail. We will just understand what they're there for, and that'll help us get a better grasp of how large language models work. So this first module, its purpose is to convert words into vectors, where a vector is just a series of numbers. It could be 3 numbers separated by commas. It could be 100 numbers separated by commas. In large language models, typically what is used is a vector size of 512 numbers separated by commas in each vector. And let's have a look at this example. An equation where we're subtracting words and adding words to each other. So imagine king minus man plus woman. What do you think this equation equals to? Well, even though we're doing arithmetic with words rather than numbers, it's quite intuitively queen. And this gives us a hint that there is something about words about meaning of words, the essence of words, that we can capture it with numbers. And then we'll be able to do mathematical operations with those numbers, and that will translate into mathematical operations with words. And that's effectively what this output embedding module does. And it's called output because all of the output from the transformer will go back into the input as we've discussed before. So it's effectively input embedding, output embedding. You can call it either or. So that's what the purpose of this module is. The next module is positional encoding, and its purpose is to add positional information. So if you look at this sentence, for example, horses ate apples, it's a completely grammatically correct sentence with which makes a lot of sense. But if you reorder the words, now we get a sentence which is also grammatically correct and has this exact same words, but has a very different meaning. And in fact, it's nonsensical. And that shows us that the order of words is very important in a sentence. And so this module helps the large language model to remember in which order the words came when they were input originally. The next module is the heart of the transformer, and it's called mask multi-head attention, and its purpose is to capture contextual information. Let's have a look at an example of this sentence. The dog didn't cross the street because it was too tired. Now, what do you think this word it refers to? Does it refer to the word dog or to the word street? Well, it's quite intuitively dog because the dog was too tired. But if we make a small adjustment to this sentence and replace the word tired with wide, we get a different sentence. We get the dog didn't cross the street because it was too wide. All of a sudden, the meaning of the word it has changed. Now it's referring to the word street. And what this shows us is that meaning of individual words in a sentence can be affected by other words in that sentence. In fact, are affected by words in the sentence, paragraph, or even text. And that is called contextual meaning. So semantic meaning is the dictionary meaning of the word, and it's important, but also equally important, contextual meaning of what that word is doing in a sentence, or what other words are, how other words are affecting it. And so this module captures contextual information and enriches the representations we have for words inside this model enriches it with contextual information. The next module is a feed-forward neural network, and basically it increases learning capacity. It's just a two-layer deep neural network with 2 layers and an activation function. Those are quite technical terms, but effectively it adds a bit of extra sprinkle of deep learning to the large language model to allow it to learn even more complex relationships that it's looking at in sentences and in words. And finally, this output module, it outputs results. What it does is it takes all of the words of the English language, 200,000 plus of them in total, and it gives each one of them a probability score. And that is based on everything that's happened before in the large language model previously to this module. It can decipher a score for each word, and the word with the highest probability, let's say in this case it's abundance, will be selected as the next word. And as we discussed previously, large language models just output one word at a time, and then they reiterate that same process. So there we go. Those are the main modules of a large language model. That's how they all work together, and that's an LLM under the hood. In this video, we will find out about large language model size. You've probably heard people say, this large language model has 1 billion parameters, or this large language model is even bigger and has 10 billion parameters, and this large language model is even bigger and has 100 billion parameters, and so on. What does that mean? What are they talking about? Well, when you look at your large language model architecture, which looks like this is a decoder only architecture from the transformer, then all of this in reality is actually, when it's coded inside a computer, it's actually a neural network. Now, this isn't exactly the correct or the specific neural network diagram for the large language model we're discussing. This is just a generic neural network diagram, but the essence is the same. It's a series of neurons all interconnected, and information flows from left to right to get from the input to the output. And then along the way, it's adjusted. And how is it adjusted? Well, it's adjusted with these weights. So each one of these connections between these neurons, a neuron is effectively a cell where a number is stored. Each one of them is connected with weights. So for example, this neuron on the right is connected with these two with weights A and weight B. And the values from left to right will be multiplied by these weights, and then they will be added together to get into this next neuron. And effectively, these are parameters. So that's all there is to it. When people say there's 1 billion parameters, what they're talking about is, for the most part, is that there's 1 billion weights in this neural network, which is the large language model. So every large language model is actually a neural network in the background, and 1 billion parameters means 1 billion connections between these neurons. 10 billion parameters, it means 10 times bigger, 10 billion interconnections between these neurons, and so on. And that's what parameters inside a large language model actually mean. In this video, we will talk about an important concept in large language models called the context window. So imagine a human is providing prompts to an LLM, and the LLM is providing responses. Human, LLM, etc. Now, the LLM has quote-unquote memory of the conversation. It has visibility of the most recent parts of the conversation. For example, all of this is too far away for the large language model to remember, whereas all of this is still close enough for the large language model to have visibility of, and that is called the context window. Everything within the context window, the large language model can still recall and use in its further responses to the human prompts. So let's have a look at this in action. We're going to ask the large language model to describe Montserrat, and it's going to tell us about the island in the Caribbean called Montserrat. Now we're going to do this similar thing on the right, but in a new window. But before we ask to describe Montserrat, we're going to ask it to describe Times New Roman, which is a font. So let's give it a chance to tell us about Times New Roman. And now we're going to ask it exactly the same prompt, describe Montserrat, and see what happens. So there we go. And in this case, as you can see, it's telling us about Montserrat, a geometric sans serif typeface. So it's telling us about the font Montserrat. So even though the prompt here was the same as the prompt here, exactly the same, the difference is that in this window, we didn't have any context previous to this. So ChatGPT just defaulted telling us about the island. But here we have previous context from the conversation, and we were talking about fonts. So ChatGPT knows that, and it assumes that we also want to know about the font Montserrat here. So there you go. That's how the context window works. Just remember, it exists and it does have a limit, even though that limit is usually very high with pages and pages of context that can be recalled. In this video, we will find out what LLM fine-tuning is. So let's say you have a pre-trained large language model, and basically that's a large language model that has been trained on lots and lots of text on the internet that has undergone that rigorous training, which is time consuming, expensive, requires lots of GPUs. So all of that is done, and this pre-trained LLM is able to understand text and is able to generate the most likely next word very well. Now, at the same time, it's not specialized in anything. It's a very good generalist across working with a language. What you might want to do is to fine tune it on your specific business data. So let's say you have lots of medical data in your business, say you're a hospital, and you need to help your practitioners better and quicker answer questions. And you want to fine tune the large language model to help them do that. Well, you would train it on all of that medical specific data about different medical terms, about different medical conditions, and then the large language model would be an expert at that. You could fine tune the large language model on financial data so it better understands the stock market, so it better understands the financial concept and helps your teams better navigate these areas. You could train it on movie data, so it better understands movies. It's better able to help you brainstorm ideas for scripts or provide critiques of movies, recall past movies in more detail and depth and specific information that's not generally available or generally known otherwise. You could fine tune it on legal data so that it can help your team to better navigate legal debates and discussions and better extract legal information faster and more accurately. You can train it on your internal company knowledge base. So if your employees usually go to look for answers on how to do certain things in your knowledge base, you could fine tune a large language model on that knowledge base so that employees can extract the information through the large language model through prompts and get that information faster. So those are just a few examples. And my favorite way of thinking about a fine-tuned LLM is your general pre-trained large language model is like an orchestra. They've spent years and years of practicing how to play their instruments or how to play together. And now they're given a symphony. Now they're specializing in this specific symphony. They're going to be playing this symphony. So this is like your pre-trained LLM. And with the symphony, it's like a fine-tuned LLM. It doesn't take as long for them to learn how to play the symphony, but it does specialize them in that specific, for that period, specializes them in that specific piece of music, and they can create something beautiful together.
Hello my friends, welcome back, and mostly welcome to that extra practical section of the course where we will be building the fifth AI of this course. And more specifically, we will be fine-tuning a pre-trained LLM, which will be actually a Llama 2 model. You know, one of the LLM, large language models by Meta. And so that's exactly why our starting point right now is Hugging Face. This is an amazing platform for AI. It indeed contains tons of models, tons of AI models for many branches. Let me show you. If we go to the models here, you will find many AI models for many different branches of artificial intelligence, the multimodal models, models for computer vision, models for NLP, then models for audio, models for tabular classification, tabular regression, and of course many reinforcement learning models, as well as robotics models. So you see, these are just the branches of AI, but inside each of these branches you find many models. And among all these models, of course, you will find many LLMs, many fine-tuned LLMs, and well, this is exactly where we'll be starting from. We will take here a pre-trained LLM, you know, one of the Llama 2 models by Meta. I will show you this in a second. And of course, along with this model, we will also take one of the many data sets of Hugging Face. Let me show this to you as well. As you can see, you have, you know, the same branches of AI here, multimodal, computer vision, NLP, audio, tabular, and reinforcement learning, but this time for the data sets. And as you can see, you have 98,146 data sets at the time I'm speaking, but of course this will considerably increase over time. And so which data set will we be taking? Well, we will be taking a data set that contains some very specific knowledge about medical terms. But first, let me show you the model. Let me show you the model that we'll be taking. It is actually the following one. It is called Abu Naji. So that's the name of the author, who published the model. And the one we'll be taking is this one, Abu Naji / Llama 2 Fine-Tune V2. All right, so that's our LLM model. And now I'm going to open the datasets in a new tab to show you which dataset we're going to be, retraining this particular model in order to do some knowledge augmentation, because actually this model, this specific model here, has a lot of general knowledge. It can chat with you about many different topics, but of course not the very specific topics like some very specific medical terms. And that's exactly what we'll be adding to this LLM, in terms of knowledge, so that this same LLM can also talk with us about these very specific medical terms, okay? So let me show you the dataset. First, I'm going to show you the source dataset, because you will understand later that in order to train an LLM, well, the dataset needs to have a certain format, and I will explain to you exactly what this format is. But first, let me show you the source dataset. You will find it by entering here medical terms. There it is. It is this one, Gamino/wiki medical terms. And as you can see, it is a dataset which contains explanations of many medical concepts. For example, paracetamol poisoning, also known as acetaminophen poisoning, is caused by excessive use of the medication paracetamol. Most people have few or non-specific symptoms in the first 24 hours following overdose. And as you can see, there is a huge explanation for each of those medical terms, right? It's almost like a full article, on the medical term itself. And if I take, for example, another one, well, you will have the same, right? A huge explanation. And you have 69 pages of medical terms. For example, again, about chest pain, and you have a huge explanation. So that's the source dataset, but actually we wouldn't be able to use this dataset to retrain and fine-tune our model in order to add this extra layer of knowledge containing all these medical terms. What we have to do is actually to process this dataset in order for it to have the right format expected by our fine-tuned Llama 2 model. But the good news is we won't have to format it, because another author in Hugging Face actually already formatted it. Indeed, if you enter again in a search here, Abu Naji, well, you will find in the dataset, there you go, the same data, but with the right format. It is called Wiki Medical Terms Llama 2 format, meaning the Wiki Medical Terms dataset that we have here, but reformatted in order to have the format expected by Llama 2. All right, so let me actually open this in a new tab so that we have both the source dataset and the formatted dataset. And there it is. That's the same dataset, but with the right format. And what is this format? Let me show you. It starts with S in between those brackets, which means start of string. Then inst in some square brackets, which means start of the instruction. Then sys. So this is actually optional. That means system prompt. And this is just some extra guidance that you give to your LLM, which is exactly this. You are a helpful, respectful, and honest assistant. Always answer as helpfully as possible while being safe. And also, please don't share false information. So that's the end of the system prompt, with the slash. But again, this is optional, with the opening system prompt and the ending system prompt is an optional element in the format. And then there you go. That's the beginning of the instruction that we see here, after the system prompt. What is paracetamol poisoning? And explain it in detail. And then end of the instruction with a /inst in square brackets. All right. And then following this, you have what we call the model answer, meaning the output of the model. All right. And at the end of the model answer, you will see the end of string token, meaning the /s in the same brackets, lower, higher sign. All right. Let me show you. It's a pretty long explanation. There you go. You see this one. That's the end of string. And that's exactly the format. So basically, the compulsory part of the format is just start of string, then start of the instruction, then end of the instruction, and then end of string with the closing string. All right? And indeed, if we look at some other entries, for example this, we will have the same system prompt, your helpful, respectful, and honest assistant, then end of the system prompt, then what is acromegaly and explain it in detail, and then the model answer. All right, and that's how this original dataset, the source dataset, was processed in order to have the right format expected by our fine-tuned Llama 2 model. Okay, so there you go. Now we have everything. We have our fine-tuned Llama 2 model, which has some general knowledge, but not the specific knowledge about medical terms. And we have the formatted dataset, which has the right format needed to retrain and fine-tune our Llama 2 model. All right, so there we go. We have everything. And also right before this tutorial, I gave you the link to the folder containing that 5th AI of the course. It is the fine-tuning LLMs Udemy folder. So I specified Udemy here because we also have, our complete course on LLMs on our SDS platform, on superdatascience.com platform, which contains indeed a much more complete and advanced implementation of this fine-tuned LLM with Hugging Face. We do a lot more of hyperparameter tuning, and we also add extra layers of knowledge with other datasets. But for this course, we prefer to do some introductory section on LLMs with a simple implementation of how to fine-tune LLMs with Hugging Face. And as usual, you have the complete code and the partial code. And of course, just like before, we're going to start from the partial code because we're going to recode, re-implement everything together. Because indeed, in the partial code notebook, I only kept actually the cells that install and import the libraries, but then nothing is implemented. So you see, we will re-implement everything together. It's an implementation in 7 steps. So we start by installing and importing the libraries, of course. Then we load the model in step 2. Then we load the tokenizer in step 3. Then step 4, we set the training argument. Step 5, we create the supervised fine-tuning trainer. Step 6, we train the model. And finally, step 7, we chat with the model, of course, about medical terms. All right, there we go. We're almost ready to start now. Of course, because this is a read-only notebook, what we have to do is to create a copy of this notebook, which will be created in our drive. Here is the copy. We're gonna remove this. And so now this notebook is not anymore in read-only mode. You can code on it. You can re-implement the code with me because indeed it is in your drive. If you go to your drive, in your Google Drive, well, then if you go to your Colab Notebooks folder, you should see, there you go, that notebook you just copied from this link I gave you. If I refresh, the copy of should be gone, and there it is. Perfect. Fine-tuning LLMs with Hugging Face partial code. We are ready to start, and our first step will be step 1, installing and importing the library. So here we go. Let's run these 3 cells here, which will, install the different libraries and packages and classes that we'll use to fine-tune our Llama 2 LLM. And so there you go. Now it is installing PEFT, bits and bytes, for the quantization, transformers, the TRL, of course, to import our SFT trainer, as you can see here, which will be the most important step probably of this implementation. So there we go. It is installing everything. It's going to take a few seconds, and then we will install Hugging Face Hub. This will be very quick, and then we will import all the different libraries. So we have the Torch library, of course, the SFT trainer class. There we go. All this is installed successfully. Now we're going to install Hugging Face Hub. This is going to take a few seconds. Requirement already satisfied for me because I installed it before. And then let's do the final import. So we have the SFT trainer class from TRL library, the LoRa config class from the PEFT library, the load dataset function from the datasets library, and then all these classes from the transformers library. And there we go. Done with all the imports. So now I'll meet you in step 2 to load the model. And until then, enjoy AI. Hello my friends, welcome back to this implementation and mostly welcome to step 2, loading the model. I'm super excited to start this implementation. Indeed, we're kind of building, an AI doctor, a chatbot doctor, which will be able to talk with us about some very advanced medical terms. So this is pretty exciting. And now our next step here is to load the model. And so how we're going to do that? Well, we're going to use, of course, a tool by the Transformers library, which we will check on Hugging Face. Hugging Face has an amazing documentation, which I highly recommend to look up in parallel while we implement this. And this is exactly what we're going to do in this tutorial and the next ones. So here we go. The first thing I'm going to do now is go to Hugging Face, but this time in the documentation. Let me show you. Let's go back to Hugging Face, the Hugging Face platform, and now let's go into docs here. That's the documentation of Hugging Face. It explains all the tools super well, for example, the Transformers tools, but also the PEFT tools, which we're going to use as well, and many, many others. And so the tool we're about to use now is a class called the Auto Model for Causal LM. All right, and as you can see, thanks to this panel here, we can find it very easily. It's, of course, the Auto Model for Causal LM class from the Transformers library, as we saw indeed when installing and importing the libraries. So here we go. Let's click this one, Auto Model for Causal LM. Here it is. It's going to load. There you go. Auto Model for Causal LM. It is indeed a class from the Transformers library, and it's of course a class that allows to load a model suitable for causal language modeling, therefore the Causal LM here, where each token is indeed predicted based on the preceding tokens. Alright, so the Auto Model for Causal LM class from the Transformers library, and it contains several methods. The from config method, which is not the one we're going to use now to load our model, but instead the next one, which is the there you go, from pre-trained method. So that's a method from the Auto Model for Causal LM class, and this is exactly the one we're going to use now to load our model. And besides, while loading our model, we can do some configuration in order to reduce the memory and optimize the future fine-tuning and training process. And how we're going to reduce that memory, how we're going to optimize all this? Well, it will be by enabling a 4-bit precision, meaning that the model weights will be loaded in a 4-bit format, all right, as opposed to an 8-bit format. Well, actually, let me show you. If we expand the 15 parameters here, here are the only two arguments we're going to enter right now. First, of course, this one, pre-trained model name or path, which will be, of course, equal to the path to the model we will load, meaning this one, abunaji/llama2 fine-tune v2. But also, we will use another argument, which is not indicated explicitly here because you will actually find it among the additional keywords arguments here. But that extra argument we're about to use in this from pre-trained method is called quantization config. And this is where we will enable the 4-bit precision so that our model weights are loaded in a 4-bit format, which will considerably reduce the model size and therefore the memory usage. Okay, so let's do this. Let's just copy it from here so that I make sure not to make any typos. So there we go. Let's take this automodel for causal LM class. So I'm copying it and then back into my implementation. Well, I'm gonna insert a new code cell. Then we have to give a name to the variable which will contain the model once it is loaded. And so we're gonna call it simply llama_model. And then there we go. We call our automodel for causal LM class, from which we call the from pre-trained method. There you go. We add some parentheses. And then inside, as we said, we're going to enter those two arguments. The first one is, well, let's actually take it again. Let's go back here. Let's go back, scroll back down to from pre-trained, and let's take it the pre-trained model name or path, which is exactly the path to the model in Hugging Face. All right. So let's go back to our implementation. Let's paste the argument here. And this is equal to, of course, the path to the model that we want to load, meaning this one exactly, abunaji/llama2 fine-tune v2. So we can copy it from here, copy it, done. Then we're going to go back to the implementation. And now be careful. We have to enter this path in quote. And then there we go. Now we can paste it. Perfect. Done. Now we can move on to the next argument, which, as we said, is called quantization_config. All right. And this is exactly where we're going to enable the 4-bit precision in order to considerably reduce the model size and speed up the inference. And so what are we going to enter here in quantization config? Well, it's actually going to be an object from another class, which is called the bits and bytes config class, in which we import indeed in step 1. And so there you go. Again, I'm going to go into the Hugging Face documentation. And let's go back to the main documentation. We can click the little arrow here. I'm going to open this in a new tab. And in the documentation, we're now going to enter bits and bytes, just like that. And there you go. According to you, which one is it among all these options? Well, I'm going to tell you, actually, the name of the class is this one, bits and bytes config. Let's have a look. And there you go. It's a class, once again, from the Transformers library. And as you can see, the first argument that we see here is this one, load in 8-bit, by default equal to false. And then what do you see indeed? The second one is this one, load in 4-bit, which by default is equal to false. But of course, we're going to set it to true, because indeed, as we said, we want to enable a 4-bit quantization by replacing the linear layers, as you can see, with not FP4, but NF4 layers. All right. And this is exactly what will considerably reduce the model size and therefore the memory usage. Let's expand the parameters a bit to see exactly what we're going to use here. So of course, the first one is to set the loading 4-bit argument to true so that we can enable 4-bit quantization. But then we're also gonna use the BNB 4-bit compute D type in order to specify the data type for computation in the 4-bit quantization. And then we're just going to use the last one, which is the next one here, BNB 4-bit quant type. And that's in order to specify that we want NF4 instead of FP4, for the quantization data type. All right, so let's do this. Again, let's make sure we don't make any typos. So I'm going to take the name of the class here, bits and bytes config, because indeed the next argument we have to enter here for quantization config is an object, is an instance of that bits and bytes config class. All right, and so there we go. Let's enter its different arguments one by one. So the first one, as we just saw, is the second one here, load in 4-bit to enable 4-bit quantization. So I'm copying it and back into the implementation, I'm pasting it here. And as we said, we're going to set this equal to true in order to indeed have the 4-bit quantization. All right, so true. Then next argument. So what did we say? We're also going to use the BNB 4-bit compute D type, this one here, in order to specify the data type for computation in a 4-bit quantization. And so there we go. Let's take it. Let's just copy it. It will be much simpler. Let's go back to the implementation and let's paste it here. And now I will probably have to zoom out a bit because now we're going to use a function called the getAttr function. There you go. Which is a function that will allow us to fetch the float16 data type from the torch module. Because indeed you will see that by loading this fine-tuned Llama 2 model, we'll actually load 2 PyTorch models, and therefore everything needs to be done with torch. And therefore, in this getAttr function, I'm first going to enter torch for the torch library, and then that data type, which is, as we said, float16. All right, and that exactly fetches the float16 data type from the torch module. And all this will give us the best data type, in order to optimize the computation. It will give us the best data type for computation in this 4-bit quantization. Okay, perfect. Then, final argument of, be careful, the bits and byte config class and not this from pre-trained method. The final argument is that BNB 4-bit quant type parameter, which is the next one here, BNB 4-bit quant type, and which will specify that we want the NF4 quantization data type in the weights of the linear layers of our LLM. Alright? So there we go, that's the last one here for the bits and bytes config class. So let's go back to our implementation. Let's paste the argument here and let's specify in quotes the NF4 quantization data type. And done! We are done entering the required arguments not only for the bits and bytes config class, but also from pre-trained method from the auto model for causal LM class. And so now we just have two final things to do, which is again to reduce the memory usage and speed up the computations. The first thing we have to do is first to take our newly created object, llama model, which contains indeed the whole llama 2 fine-tuned v2 model, and since it is an object from a class, the auto model for causal LM class, well, we can use one of its attributes, which is the config.use_cache attribute, and which we're going to set equal to false. And that means that we're not going to store in the memory, in the cache memory, the output of the previously computed layers. And that will, of course, allow to reduce the memory usage once again and also speed up the training computations. All right? And now we're going to do one final thing, which again will be used to speed up the computations of the linear layers, and that is to set another attribute called config pretraining TP equal to 1. And what will it do? Well, it will make sure that we will deactivate the more accurate computation of the linear layers. Because if we keep them activated, this will considerably slow down the linear layers computations. Alright? So again, let's take our llama model object, from which we take again the config.pretraining_TP attribute, and which, as we set equal to 1. And again, this will deactivate the more accurate computation of the linear layers, therefore speeding up those computations. Alright, and we're done. We're done with that code to load the model. So now, well, of course, let's run the cell and you will see what happens. You will see 2 PyTorch models being loaded. There we go. This is the first one, PyTorch model 00001 out of the 2, and it is 10 gigabytes. So it's going to take a while, it's going to take probably a few minutes, and then a second PyTorch model will be loaded, but this time a smaller one. It will be 3.5 gigabytes, so it will be faster, and then some checkpoint shards and some configuration will be loaded as well. And so at the end, in a couple of minutes, we'll have our fine-tuned Llama 2 model well loaded with those 2 PyTorch models and this quantization configuration, which will allow us to reduce the memory usage and speed up the computations of the linear layers. Alright, so let's wait a bit for it to load, and I'll meet you in a couple of minutes. Alright, and the second PyTorch model is almost loaded. As you can see, it is 3.5 gigabytes and done. Now it's going to load the checkpoint shards. It's going to take, 1 or 2 minutes. It's going to be pretty fast. We don't see, the bar evolving here. At some point, it's going to be 50% and then 100%. But very soon, we will have them. So there we go. Let's just wait a little bit more. And at some point, everything will be loaded. Alright, 50% for the checkpoint shard. It's gonna go to 100% in, a few seconds now. I remind that I'm using a T4 GPU, so I'm not even using the V100 GPU. There we go, 100%. And the generation config also loaded, so now everything is done. We have loaded all successfully our fine-tuned Llama 2 model. Perfect. So now we're done with the step 2, loading the model, and we're gonna move on to step 3 to this time load the tokenizer. I can't wait to do that with you in the next tutorial, and until then, enjoy AI. Hello my friends, and welcome to the step 3 of this implementation, loading the tokenizer. Indeed, we have just loaded our pre-trained model, the Llama 2 model that we got from Hugging Face, in which we loaded through the auto model for causal LM class and then from the from pre-trained method of this class. And now that we have the model, we need to load as well a tokenizer that is compatible with this Llama 2 model, while ensuring, of course, that the tokenizer uses the same special tokens as the model and the same padding. That's extremely important, and that's exactly what we'll make sure to implement in this code cell. Alright, so let's do this. We're going to use, of course, another class, which will be the auto tokenizer class, again from the transformers library in Hugging Face. So let's do this. Let's insert a new code cell, and let's first start by creating a new variable, which will be the object containing the tokenizer, and which will be created as an instance of that auto tokenizer class. Alright, so let's do this. Let's call this variable llama_tokenizer. And there we go, let's call this class. So as usual, let's work in parallel with the Hugging Face documentation. Let's look it up because everything is very well explained. So that's why I opened a new Hugging Face page. And again, we're going to go to the docs here, the documentation, and we're going to enter here auto tokenizer. All right, auto tokenizer, and according to you, which one is it? Well, actually, these are these ones. You know, the auto tokenizer class from the Transformers library. All right, so let's look it up. Auto tokenizer, here is the class. Indeed, nearly every NLP task begins with a tokenizer, and a tokenizer converts your input into a format that can be processed by the model. And again, just like the model we loaded before, well, we're going to load our tokenizer again with the from pre-trained method by this auto tokenizer class. So that's exactly what we're going to take here. I can just, copy this auto tokenizer from pre-trained, and I can just, paste it very simply in my notebook. All right, autotokenizer.from pretrained, and this time it will take very simple arguments that we have to enter. Actually, I can show you the arguments. I think if we go back here to autotokenizer, and take this instead, with the from pretrained, we should get a better description. Let's have a look. Let's try to find the autotokenizer class with the from pretrained method, with the description of all the parameters. There it is, autotokenizer, perfect, autotokenizer and from pretrained. That's exactly what I was looking for. Anyway, I gave you all the links to the tools that we're using in this implementation, so you can just take the links. They are in the same article lecture where I gave you the link to the collab notebooks, so this link will redirect you exactly to the from pretrained method from the autotokenizer class. So here is the method, and as I was just saying, well, it contains several parameters, but we're only going to use two. Let's expand them. Here is the from pretrained method, and the two parameters that we're going to enter here is this one, of course, the pre-trained model name or path, which exactly like before will be the path to the model, in Hugging Face, the abunaji/llama2 fine-tune v2. So that's our first one. I'm copying it. And the second one will very simply be this one, the trust remote code, which by default is equal to false, but which we'll set to true because we want to allow for custom models, but here our llama2 model defined on the hub, meaning here for us Hugging Face, to be trusted. All right. This option should only be set to true indeed for repositories you trust, and we trust the platform, meaning Hugging Face, where we not only load the tokenizer but also the model. And so there we go, we must make sure to set this to true. So first, let's enter the first argument here, pre-trained model name or path, which will be of course equal to the same path leading to our llama2 model, this one, abunaji/llama2 fine-tune v2. So let's copy it here again, and back into our implementation, let's paste it. All right, and now let's add the second argument, which is, as we just said, trust remote code, in order to say that we trust the source of where we are loading both the model and the tokenizer, meaning Hugging Face. So trust remote code, and then back into the implementation, I'm pasting it and I'm setting it equal to true. All right, and that's it. That's all we need to do here to load the tokenizer. It's much simpler than loading the model. We don't have this bits and bytes configuration to set. It was just when we loaded the model. However, now we just need to do two very important things, as I said in the beginning of this tutorial, which is to configure the padding. So what we're going to do is actually two things. We're going to make sure that the pad token is the same as the end of sequence token, and that we have a right padding. So that means that the padding token will be used to fill up sequences to a uniform length. That's very important in NLP. You must always have sequences of the same length, because that's indeed necessary to process batches of text data. And so what we're going to do is set the pad token to be equal to the end of sequence token, which is indeed a special token used to indicate the end of a text sequence. All right, so let's do this first. So first we're going to take our llama tokenizer object, all right, which was created as an instance of the auto tokenizer class, but using the from pretrained method. And then we're going to get that pad underscore token attribute, which is exactly the pad token that will, fill up the sequences so that they are all of a uniform length. All right. And as we said, we want this pad token to be the same as the end of sequence token. And to do so, well, we're going to very simply take this again and paste it here again, but replace the pad token here by the EOS token. All right, and now the padding token will be the same as the end of sequence token, and all the sequences will be of the same length, each one being filled up by the padding token, here the end of string token. All right, and now one final thing to do, we need to make sure that we have a right padding as opposed to a left padding. And to do this, we're going to take our llama underscore tokenizer object again. Here it is, from which we're going to access now another attribute called the padding side, meaning right or left, right? Because sometimes we can have a left padding, but here we want to make sure we have a right padding, which makes sense, because we're filling up the rest of the sequences with the end of string token. And so to make sure we have a right padding, we need to enter here equal and then in quote, right. All right, and that's it. We're done with not only loading the tokenizer, but also making sure that we have the correct padding to process our text sequences in the medical terms dataset that we'll be adding into the knowledge of our LLM. All right, so now let's run the cell. But before I run the cell, I just realized that I forgot one little thing, which are the quotes for the path leading to the model. Probably you haven't forgotten. Congratulations if that's the case. And now I think we're all good. We have our tokenizer, we have the padding, and so let's run that cell to load the tokenizer. And here we go. It's going to be super quick. As you can see, done. It took a couple of seconds. And now we have our tokenizer. We have the special tokens. We have the tokenizer configuration. We have everything. We are ready for the next step. Step 4, setting the training arguments, which will be a very simple step before the big step, creating the supervised fine-tuning trainer. I can't wait. Let's take a little break now, and I'll see you in the next tutorial to set the training arguments. And until then, enjoy AI. Hello my friends and welcome to this new tutorial. In the previous one we have just loaded the tokenizer, and now in this new step, step 4, we're going to set the training argument. So the first question is, why do we need to do this? Why do we need to set those training arguments separately? Well, that's very simply because in the next step, step 5, we're going to create the supervised fine-tuning trainer as an instance of the SFT trainer class. And this SFT trainer class will take several arguments, one of which will be the training argument, okay? And these training arguments will be created as an object of another class, which is called the training arguments class, and which allows to configure the training parameters of the future training that will happen once we retrain our Llama 2 model with the new dataset containing the medical terms. Okay, so let's do this. Let's set those training parameters, and as usual, we're going to look up the Hugging Face documentation, because indeed this training arguments class is once again from the Transformers library. And so we have an amazing documentation explaining everything, and therefore I'm going to enter here training, the name of the class, which is training arguments. All right, and there it is, the training arguments class from the Transformers library. Let's have a look at it. Let's look it up. And here it is, the training arguments class from the Transformers library. As you can see, there are tons of hyperparameters, that you can tune, but of course this is an introductory course. In our LLM A to Z course, we do use a lot more of these hyperparameters for the training, but here it will be way enough for us to only use this exact argument per device trained batch size, which is of course the batch size for the training. All right, so by default it is equal to 8, but 8 is actually too much for the memory of a Colab notebook. You can try actually to run the training with a training batch size of 8, and you will see that you will probably get an out of memory error, and therefore we're going to reduce that training batch size to 4, meaning that the model will process 4 training examples in each training iteration, and that will not be too much for the memory. All right? So that's our first parameter that we will enter as an option. It's an optional argument. Then we'll also enter this one, output dir, because it is a compulsory argument. If you don't provide a path to a certain folder in your notebook, it will raise an error because you have to provide an output directory where the model predictions and checkpoints will be written. And finally, we will also enter one last argument, which is this one, max steps. As you can see, the default value is -1, meaning that there is no maximum steps given by default. However, as you can see in the description here, but I cannot put my mouse on it, otherwise it will disappear. But as you can see, for a finite dataset, the training is reiterated through the dataset until max steps is reached. And so, for this max steps argument, we will not keep the default value of -1, of course. We will do a pretty reasonable training, and therefore we will choose 100 steps, which will limit the training to maximum 100 steps. All right, and you will see we'll have a very sensible training. So let's do this. I'm going to copy this. We don't have to copy the Transformers library because we already imported the training arguments class from the Transformers library. So here we go. We simply have to, first create a new code cell here, then give a name to our training argument variable, which will be the object created as an instance of that training arguments class. So let's call it very simply training underscore arguments, like that. And then we paste the name of the class, training arguments, inside which we enter the 3 arguments we just identified. The first one is output dir. So let's copy it. Let's paste it inside the training arguments class. And let's simply call that folder containing the training results in quotes, first dot, to start from the root directory, then slash, and then the name of that folder, which we'll call results. Okay? As simple as that, or you can call it any other name. Then, next argument, what did we say? We're also going to specify a per device trained batch size of 4. So let's copy this one. Let's go back to the implementation. Let's paste it here and let's set it equal to 4. And finally, the last argument we want to enter here is, as we said, the maximum number of steps. So let's copy it and then back into the implementation. Let's paste it and then let's set it equal to 100. Okay? And there we go. That's it for the training arguments. We don't have to enter any more parameters here. Of course, feel free to do some more tuning, but here we have all the essential ones. And so there we go. We are ready for step 5 to create a supervised fine-tuning trainer, in which indeed we will enter the training arguments as one of the parameters of the class that will create indeed this supervised fine-tuning trainer, and which is called SFT trainer. Alright, so let's not forget to run this cell to get indeed the training arguments. And now, as soon as you're ready, let's implement step 5 to create finally the supervised fine-tuning trainer. And until then, enjoy AI! Hello my friends, welcome back to this implementation, and mostly welcome to probably the most important step of this implementation. I'm talking of course about step 5, creating the supervised fine-tuning trainer. Indeed, we're now getting into the heart of the technique of augmenting the knowledge of our LLM. I remind that there are two main techniques to develop your LLM with knowledge augmentation. The first one is supervised fine-tuning, which is a transfer learning technique in which the weights of a pre-trained model are trained on new data, which is here the data containing all these advanced medical terms. And the second technique is RLHF, reinforcement learning from human feedback, which is a much longer process and which requires, of course, human feedback, through reinforcement learning. So, of course, in this implementation, we're doing the first technique, supervised fine-tuning. And for this, we have to create a trainer, which is exactly what we're going to do in this new step. And the way we're going to build that trainer is by creating an instance of an amazing tool, which is the SFT trainer class from the TRL library. And in order to create this trainer object, well, we will need to enter several arguments in the class. And well, the good news is that we already gathered all these elements. Indeed, the first element will be the model we loaded in step 2, right here, loading the model. We will enter this as the first argument. Then, of course, we'll need to enter the dataset through which we're doing this knowledge augmentation, and that's exactly this one. The formatted dataset, of course, with that format I explained to you in the first tutorial. Then, of course, another element we'll need to enter is the tokenizer, which we got in step 3. And then, of course, as you can guess, the training arguments. So you see, we have everything we need to create that trainer, so let's do it. And as usual, we will do this while at the same time looking up the Hugging Face documentation because it is super well explained. And so here we go. Let's go first to the docs, and in the documentation search, let's enter SFT trainer. That's exactly the name of the class. Here it is, the SFT trainer class from indeed the TRL library. So let's access it, and here it is, the SFT trainer class from the TRL library. So as you can see, there are many parameters, but of course we're going to enter the compulsory ones and the essential ones. Let me expand all of them. There are 22 parameters in total, and so here we go. Let's see which ones we have to enter. Of course, the first one is the model, but the one we loaded, not directly the model from Hugging Face. Then args here are going to be, of course, the training arguments, as you can see, and that's the second element we'll enter. Then the train dataset, of course, will be the formatted dataset of Hugging Face, but we will not enter this directly as the argument, by copying this. For this, we will use another function called the load dataset function, in which we will enter indeed this path, leading, of course, to that dataset. All right? Then let's go back to the documentation. What is the next parameter we will enter? That's, of course, the tokenizer, which we loaded 2 steps before. So perfect. But then there's also one very important thing we need to do, and that's related again to, optimizing the memory usage of our Collab notebook, which is limited. Since we're using a T4 GPU, or maybe, some of you are using the V100, which would be even better, but I want to make a code that works for everyone. So I'm assuming we're going to use the T4 GPU. Well, the T4 GPU only has 12.7 gigabytes of RAM, and that's not enough to store the weight of our pre-trained Llama 2 model. And therefore, we need to do what is called parameter efficient fine-tuning, which is a technique that will reduce the amount of parameters that are going to be fine-tuned as opposed to, fully tuning all the parameters of the model, which here would be impossible for Google Colab Notebook. So we need to do this parameter efficient fine-tuning technique, like for example, LoRa or Clora. And here, we're going to do LoRa, low rank adaptation, and we can do it directly while creating our supervised fine-tuning trainer, thanks to another parameter here, which is exactly this one, the PEFT config, which is the PEFT-config object to use to initialize the PEFT model. More specifically, this means that we're going to set up a configuration for parameter-efficient fine-tuning using LoRa low-rank adaptation, which is a technique used to adapt large models with minimal trainable parameters. Okay, so we're just going to reduce the amount of parameters that will be trained to a minimal amount of trainable parameters. All right, so PEFT-config as well, and then one last one, which is the next one after that, the final one, dataset text field, where we will just have to specify that the input in the training will be, of course, text. So we will just enter dataset text field equals text. Okay, so that's all we need to do. Let's do it, starting with, of course, well, first I'm going to copy the name of the class, SFT trainer class, and then back into my implementation, I'm going to create a new code cell. Then I'm going to introduce here a new variable, which will be exactly our supervised fine-tuning trainer, and which we're going to call llama underscore SFT underscore trainer. And this will be created, of course, as an instance of the SFT trainer class. All right. And now let's enter all the arguments, starting with, of course, the model. As you can see, this is the first one here, the model, which is, of course, not directly the Llama 2 fine-tune V2 model from Hugging Face, but the model variable we loaded in step 2, right? So here we go. Let's enter model here, and this will be, of course, equal to our variable we created in step 2, meaning this one, llama model. All right, so I'm copying it, and then back in step 5, I'm going to paste it here, and that's our first parameter. Now, the next one is, as we can see here, the args, the training argument. So back into our implementation, let's enter args here, and this will be, of course, the training arguments we got in step 4, meaning these ones. So I'm copying them, and that's exactly our second argument. Perfect. Now, the next one is data collator we won't use, but the next one we're going to use, of course, is the train dataset, which is, of course, our data, but remember, not directly the path to that formatted dataset here, but that path entered in the load dataset function, which we also imported in step 1. All right, so let's enter the next parameter here, train dataset. And as we said, we're going to take our load underscore dataset function, which will take 2 arguments. The first one is the path, which is, of course, the path to that formatted dataset from Hugging Face. So let's copy it. That's exactly abunaji/wiki medical terms llama2 format. So back into our implementation, let's enter in quote the path to that dataset, to that formatted dataset, and then we're just going to enter another argument, besides that path, which is split, and that's to specify that we are loading here the training data. And to specify this, we need to enter here in quote simply train. All right, so that's it for the load dataset function. Now I'm getting out of that function and then adding a comma here to enter the next parameter of the SFT trainer class, which is, let's have a look again at the documentation. As we said, the next argument is tokenizer, which we also loaded 2 steps before, just before the training argument. So here we go. Let's paste it here. That's our next SFT trainer parameter, and that's, of course, going to be equal to our llama tokenizer we loaded in step 3. All right, so let's paste it here, and there we go. We have just entered the tokenizer. And now, very important, as we said, we can't retrain all the weight of our huge pre-trained Llama 2 model, so we're going to do a minimal fine-tuning of the parameters, the efficient one, therefore the name parameter efficient fine-tuning, the PEFT library. So here we go. Well, speaking of the PEFT library, what I'm going to do now is open a new page in the documentation where this time I'm going to enter the LoRa config class from the PEFT library. As you can see, parameter efficient fine-tuning methods for large models. That's exactly what we're going to use right now, and the name of the class is LoRa config. Here it is. That's exactly the class, the LoRa config class from the PEFT library. So let's have a look. And here is the class, the LoRa config class from PEFT. And here are the different parameters. 16 in total. That gives us a lot of room for hyperparameter tuning. But again, here we're only going to use the essential ones that we need to indeed reduce that amount of weight that will be trained to the efficient parameters. And these parameters are going to be first R, of course, which is the rank of the low rank matrices of parameters that will be trained, once we get to that minimal amount of parameters, meaning the number basically of trainable efficient parameters. Then we're also going to use LoRa alpha, which is the alpha parameter for LoRa scaling, and which we'll choose to be 16. So why 16? Well, that's, based on experimentation and some tuning over a trial and error process, and eventually we find that an optimized value is indeed 16. Then we're going to use the LoRa dropout as well, the dropout rate in the lower layers. Again, this will reduce, the parameters that will be trained, because dropout consists of deactivating some of the parameters, some of the weights during the training, so that they're not updated all the time. And plus, it's a regularization technique that will prevent overfitting. So this is very important, and we're going to set that to 0.1. And that's it. Then there are many other parameters like the bias. We're going to leave that to none. But again, the rank, the LoRa alpha, and the dropout will be way enough to do this minimization of the trainable parameters during the fine-tuning process. All right, so here we go. Let's enter first, our LoRa config class in this new argument of the supervised fine-tuning trainer class, which is, remember, PEFT config. So let's enter this argument first, PEFT underscore config, equal to an instance of that LoRa config class, which will take as argument first the rank of the low rank matrices of minimal parameters, which we choose to be 64. Again, that's after a lot of experimentation, trial and error, and hyperparameter tuning. Then, as we said, the LoRa underscore alpha parameters, which we set to 16. And finally, the LoRa underscore dropout, which we set to 0.1. And also in the same LoRa config class, we will just enter one last parameter, but which I'm not sure I've seen among the parameters here, but I can see it in the class here. It is exactly the task type. We'll just have to specify that it is causal LM, for causal language modeling. Remember when we loaded the model, we used the auto model for causal LM class. Okay, so here we have to specify again that the task type is causal LM. Okay, so let's do this. That's our final parameter here, which comes either before the rank. So I'm going to enter actually just before the rank here, task underscore type equals in quote causal underscore LM. All right, comma. And now here we go. We have all the parameters for the LoRa config class. Okay, perfect. And now remember one last parameter for the SFT trainer class, which remember is the dataset text field here. So I'm copying it. That's our last parameter of the SFT trainer class. So let's paste it. And as we said, we need to enter in quote here, text. And voila, we are done with creating the supervised fine-tuning trainer class with all the essential parameters that we need to not only create that trainer, but also integrate LoRa configuration for parameter-efficient fine-tuning in order to indeed retrain the essential weights of our LLM. Okay, so here we go. Let's now run this cell, and this will create the supervised fine-tuning trainer. It's going to take a couple of minutes, because it requires first to download our data, then generating some train split, as you can see on many examples, 20,726 examples. So it's going to take a while. Therefore, I'm going to, wait here a couple of minutes. There you go. The mapping is starting. It is going to take a few minutes. So I'm just going to fast forward here, and I'll meet you at the end of the mapping. All right, the mapping is almost done, 87%. It is going to take a few more tens of seconds now, but we should be done very soon. 6,000 out of 6,861 and done. The mapping is done, and we have our supervised fine-tuning trainer. So there we go. Now finally we are ready to augment the knowledge of our LLM in step 6, training the model. And until then, enjoy AI. Hello my friends, welcome back to this implementation. We have just done the most important step of this implementation, which was step 5, creating the supervised fine-tuning trainer, because indeed this is our main tool to retrain, and fine-tune our Llama 2 model with augmented knowledge, about medical terms. So we have the tool, and therefore we are ready to proceed to the training in step 6. All right, so let's do this. And as you will see, it is super easy, because what we simply have to do is just take, our SFT trainer, Llama SFT trainer, the object of course created from the SFT trainer class, and then from this object we will call one of its method, which according to you is which method? Well, of course, very simply, the train method. And the good news is that we don't have to input anything inside this train method, because basically all the arguments, all the elements we gathered before were already input inside the SFT trainer class. So we already have everything. We have the training arguments, we have the dataset, we have the tokenizer, we have the LoRa config, parameter efficient fine-tuning configuration. So basically we have everything, and we can train our model. All right, so are you ready? Let's do this. We simply have to click the run button to run the cell and start the training. And there we go. The training is now initiating, and then it will soon be starting. And there it is, step training loss, step 2 out of 100. Remember that we chose a maximum number of steps of 100, and now we're already at step number 3. Okay, so it's going to take some time, but now, of course, the fine-tuning process is happening. You know, the weights of our pre-trained Llama 2 model are being retrained on our new data about medical terms. And while this training happens, well, quantization is enabled, you know, with a 4-bit quantization, and also some parameter-efficient fine-tuning is happening, you know, with the LoRa technique, so that not all the model's weights are being retrained, but only the efficient ones, you know, with the minimal tuning thanks to the low-rank adaptive matrices from the LoRa technique. And also we have our tokenizer that is doing the right padding, you know, so that all the sequences have the same length, because indeed our tokenizer is filling up the rest of each sequence with the end of sequence token, you know, the EOS token. Alright, so all this is happening now. Our pre-trained models' weights are being retrained on this new data about medical terms, but not all of them, of course, because we're not doing full tuning, but only a minimal but efficient subset of them. And so there we go. Now let's just wait for this training to finish. I'll put my little music that I used to put in my other courses. I hope you like it, and I'll see you at the end of the training. Alright, the training is almost done. We have just reached step 95 out of 100. And before it finishes, I just want to show you something. Thanks to the quantization and the LoRa method we applied on our model and trainer, well, as you can see, the memory will be fine. If I open this, as you can see, the total system RAM, as I told you in the previous tutorial, is 12.7 gigabytes. And as we can see, it is not reaching its total capacity, you know, 5.0 out of 12.7. This is all good. The GPU RAM is also fine, and the disk is fine. So that's the purpose of, you know, applying quantization and LoRa on our trainer. Without this, we wouldn't be able to, you know, retrain all the weights of our pre-trained Llama 2 model. So that is super important. I just wanted to show you this before the training ends. Step 98 out of 100, almost done. And in a couple of seconds, we will have a newly retrained Llama 2 model with this extra knowledge about the medical terms. In other words, the knowledge augmentation will be done. Okay, step 99 out of 100, almost done, and the training is almost done. Okay, let's wait for this to finish. 100 out of 100. Okay. And done. So what did we get? Yes, global step 100. So 100 training steps. We ended up with a training loss of 1.65. It ran for 1,537 seconds for me. Train samples for seconds 0.26, okay, and training loss 1.65. Okay, so that's pretty good. And if you're curious to see what happens if, you know, we don't set a maximum number of steps, you know, when we set the training arguments, remember we chose max steps equals 100, and I chose to do this once again for all of us to be able to train the model without waiting too long. But if you're curious to see what happens if you train the model with no maximum number of steps, meaning on the whole data set, and of course using the V100, because now for this training that just happened, I used of course the T4 GPU, but of course without the maximum number of steps, you would need indeed a V100 to fine-tune the model. And well, I did this. If you're curious, here is what happened. The training loss was well reduced over the steps. As you can see, well, now I'm disconnected, but I did the training with a V100, and after 500 steps, we ended up with a training loss of 1.30. Then after 1,000 steps, we ended up with a training loss of 1.21, then 1.20, 1.19, and 1.20 again. And that was after 2,500 steps, but check this out. After 3,000 steps of the training, we ended up with a loss of 1.18. So as you can see, the training loss was well reduced over the steps. And of course, with this training, we have some even bigger knowledge augmentation. Alright, just wanted to show you this, but with this you will see that it's completely fine. We have indeed a model that is well retrained with some good knowledge augmentation, and actually that's exactly what we'll test in step 7, chatting with the model. We will ask our model about some pretty advanced medical terms, you know, that are not obvious. For example, we won't ask about chest pain, but about something that most people don't know about. We will choose an advanced medical term together. So there you go. I can't wait to do that with you in the next tutorial, and until then, enjoy AI. Hello my friends, and here we go. Welcome to the final tutorial of this extra practical section on LLMs. We have just trained our LLM in order to do some knowledge augmentation so that indeed we can add an extra layer of knowledge about medical terms to our pre-trained LLM who had before this training already some general knowledge about many different topics, but not the very advanced ones. And that's why we have just fine-tuned it to do this knowledge augmentation so that now it can be able to chat with us about medical terms. And that's exactly what we will be testing in step 7, chatting with the model, the last step of this implementation. And well, we just have to write some little code, to implement the prompt, the user prompt, and create that text generation pipeline so that then we can print the model answer. And so there we go. Let's implement that final step. Okay, so what do we start with? We're going to start with the user underscore prompt. Okay, and that's exactly what we will be saying to our model, the question we'll ask or anything you want. And so for now, we'll just enter some quotes. And once we're done with this code cell, we will just choose together what we'll ask to our model. Okay, so let's just leave it for now. And then after the user prompt, the next step is to create the text generation pipeline. Okay, so I'm going to create a new variable with an obvious name so that we all know what this is about. This is the text generation pipeline indeed. Text generation pipeline. And how will we create that pipeline? Well, that's thanks to another function that we imported also from the transformers library in step 1. It is this one, the pipeline function from the transformers library, and that's exactly the one we'll use right now to create that pipeline. So here we go. Let's call this function. It is called pipeline. There it is. And inside we're going to enter a couple of arguments. The first one is task, and that's of course the text dash generation task. All right, text generation. Then next argument will be the model, that will answer to our user prompt, or that will generate the output. And the name of the argument for that is, as we can see here, model. So there it is. And of course, what will be our model? Very simply, the model will load it, but into that variable with quantization applied. And remember, we called it llama underscore model. Okay, here we go. Then next argument, config. So we don't have to enter the config here because anyway, the config was input before when we created our previous object. However, we're going to enter the tokenizer again because the model always works hand in hand with the tokenizer. So let's do this. Let's add this extra argument, tokenizer, and that's of course going to be equal to our tokenizer, which we also loaded in a variable in which we called llama underscore tokenizer. All right, llama tokenizer, there it is, perfect. And now we need to input one last argument, which is the maximum length of the sequence that will be generated, and we will limit that to 300 tokens. And so there we go. Let's enter this last argument, max underscore length, which we set equal to 300. Perfect. So that creates the text generation pipeline, but it is not yet the output of the model, because indeed the output of the model is exactly what we'll get now in this new line of code. And so we will create a new variable, which we will call model underscore answer. Okay, model answer, that's exactly what is supposed to be after, the user prompt in that format I explained to you in the first tutorial. Remember, it starts with the start of string token, then beginning of the instruction, then this extra guidance with the system prompt, end of the system prompt, end of the instruction, and then we have the model answer. And now what we're about to get in that new variable is exactly this, the model answer. And so how will we get this? Well, of course, we'll use our text generation pipeline that we just created in the previous line of code. So let's call it, then we're going to add some parentheses. And now, according to you, what do we input in this text generation pipeline? Well, that's simply the formatted user prompt, meaning that exact format of the user prompt up to, well, the end of the instruction, okay? And so, since in the first variable user prompt here, there will just be the text, we also need to add that format in some F quotes, okay? So that's just for the format, and inside this quote, we will enter that exact format, with start of string, inst, and end of inst. All right, up to the model answer, basically. So let's do this. First, we start with, as we just said, the start of string in those brackets. So I'm closing them as well. All right, so that's the first part of the format. Then, second part of the format, the beginning of the instructions with some pair of square brackets and inside inst. So that's the beginning of the instruction. Then, in those new brackets, we're going to enter not the system prompt, but directly the user prompt, because we won't write this extra guidance to our LLM, to say that you are a respectful and honest assistant. We don't really need this. We will enter a very simple user prompt, but we have to input them in those brackets. Okay, and then what do you think is the final part of the format? Well, the end of the instruction, of course, which we have to enter again in square brackets, and then remember the slash inst. Okay, just like that. And that's exactly the format that we have up to the model answer. It has to stop here up to the model answer, which is why we're not including the end of string token. So basically, this is all good now for the input of that text generation pipeline. And so there we go. Now we can just end this code cell with a final print, which will print indeed the model answer. And so what do? Well, first we take our model answer variable. But then, because this is a specific structure, with several elements of multiple index, well, we need to locate exactly the model answer, the generated text inside this model answer variable. And well, the way to access it is by taking the first index and therefore in some square brackets and therefore the index 0. But then that's not all. In some other pair of square brackets, we need to enter in quote generated underscore text. And my friends, we are done. We have now implemented the whole implementation of this fine-tuned LLM. So congratulations. Now we will run the cell to the final step, but before, of course, we have to choose a user prompt together, meaning what we'll ask exactly to our model and of course about medical terms. So what I suggest we do is go back to the source data set, because it's easier to go through and ask our LLM about something super advanced, that most people don't know about. So let's go back to the first page and let's just choose, some advanced terms. So let me just reload the page first. And there it is. So paracetamol poisoning. So that's pretty obvious. What do we have here? Anthrax. Ascariasis. Ascariasis is caused by the parasitic roundworm Ascaris lumbricoides. This seems pretty advanced, right? We could, for example, test this one, or for example, babesiosis. As you want, I'm gonna try Ascariasis. Feel free to test any other advanced medical knowledge. And so what I'm simply going to do is, in the user prompt here, I'm gonna ask, please tell me about Ascariasis. All right? And that will be our user prompt. And now we will test what will be the model answer generated by our retrained and fine-tuned LLM. So here we go. Let's run this cell and let's see what happens. Okay, so the text generation is going to take a bit of time. It's completely normal. It's now looking into its new knowledge, that was just augmented with our data about the medical terms. It's going to take a couple seconds, but very soon we will have the model answer. I'm curious to see which medical term you tested yourself. Let me know in the comments. Feel free to share the results that you're getting and let me know if you think the test is successful, right? I'm very curious to see what you got. Okay, so now the generation is still ongoing. As we can see, the little arrow is at this line of code, model answer, which is exactly the text generation happening right now. So that's why it's taking a little bit of time. But of course, in a couple of seconds, we will get a model answer. And there we go. Let's see what we get. So that's the beginning of the model answer. Remember, after the end of the instruction part of the format. And now begins the model answer. Ascariasis is a parasitic infection caused by the Ascaris lumbricoides roundworm. That I'm not sure what it means. Between Ascaris sum and Ascaris lumbricoides is difficult, and the two species are often considered to be the same. The infection is caused by the ingestion of infective larvae, which then migrate through the body and cause a range of symptoms, including abdominal pain, diarrhea, vomiting, weight loss, fatigue, anemia, malnutrition. Let's check if it's true. Let's check if it's indeed what is explained here about Ascariasis. Wow, the text is huge, but yes, it is indeed a disease caused by the parasitic roundworm Ascaris lumbricoides. So that's correct. We had this in the model answer indeed. And then let's see what it says about the symptoms. These may be followed by symptoms of abdominal swelling, abdominal pain, and diarrhea. So that's all correct. We had a pretty good model answer by our model. And so that's a successful test. We have built an AI doctor who's able to chat with us about some very advanced medical terms. But feel free to share your results as well, your test results. I'm curious to see how it did with you. And again, it was a great pleasure to do this extra practical activity with you about this very hot topic of the LLMs. Feel free to ask me any questions you want in the Q&A. I'm always very happy to answer. And also, I really look forward to seeing you in another course or, in another lab or practical section. I remind that we have a complete course on LLM, which is called LLM A to Z on our superdatascience.com platform, in which we do a lot more of hyperparameter tuning, and we even do some extra knowledge augmentation by adding other data sets into our LLM so that it can chat with us about many other specific topics. So if you like this course, it would be absolutely great to see you in this other course or in our platform, which also contains many more labs and many other ways to practice. All right, so I look forward to seeing you in another course, another lab, or hopefully at a conference in the world one day. And until then, enjoy AI.